Welcome to this CUDA programming course, where you will learn to leverage GPUs for high-performance computing. The course starts with an overview of the deep learning ecosystem and guides you through setting up CUDA and reviewing essential C and C++ concepts. You'll explore GPU architecture and write your first CUDA kernels. Advanced topics include optimizing matrix multiplication and extending PyTorch, with practical applications like implementing a multi-layer perception for the MNIST dataset. Elliot Ulrich created this course.
So what is CUDA, or Compute Unified Device Architecture by Nvidia? My name is Elliot, and I'm an instructor on freeCodeCamp, as well as a student studying for my computer science degree. So in this course, I bring to you CUDA for deep learning. But don't let that repel you if you're not in deep learning, because there's still a lot that we're going to be able to cover in many other fields of parallel programming. So this is more oriented for deep learning, but not specifically aimed at it. There's going to be a lot covered here, so I'll show what the final project is first, so you can get a feel for it and see kind of what we're going to end up building by the end, and then we'll just kind of go from there. So before we get started with anything crazy, I should include a disclaimer. This course may not be fully up to date by the time you're watching this. If you're watching this 10 years down the line from when I've released it, it might not all be the same. There might be things that are updated. The new compute capabilities might be, way better. There might be a bunch of different stuff happening. So I'm not too sure where the ecosystem will be at in 10 years, but as of 2024, this is pretty much the best you're going to get. So just trying to include that, and I thought I'd try to make everything not entirely centered around time, so you can go back into this version or certain CUDA versions and reproduce all the same stuff. It just might be a little bit different down the line if you're watching this later on. So why did I create this course exactly? Well, a lot of these performance and kernel engineering jobs require a lot of knowledge. They require a lot of experience in the industry, and it's just really hard to get up to that point where you're able to compete with the top and the best of the best performance engineers. So these are the people that are writing the training runs for like GPT-4, GPT-5, all of this. You need a lot of skill to actually optimize a massive neural network training run and inference on a large data center or compute cluster. So this aims to prevent some of that manual weaving on your part, still encouraging you to do so on your own, but prevent some of that hardcore labor of going through and really figuring things out on your own from scratch. That's one of the reasons why I created this. Another one is, like, generally speaking, the point of writing GPU kernels or playing with code at all on the GPU is to run something faster. So if you have a nested loop, it's like 4i in range, 4j in range, 4k in range, whatever, however many you want to put. Essentially what parallel programming and CUDA allow us to do is unroll those. So if you take, like, for example, 4i in range, you could take each little thing in that and run that instruction on a different CUDA core. So if you have 10,000 CUDA cores and you have 10,000 different iterations in your loop, then you can effectively do each iteration in a single instruction or a single thread on the GPU. So this is some of the things it allows us to do. You're going to use your job of you're going to use your knowledge of GPU architecture, kernel launch configurations, and a bunch of other cool stuff we end up learning in this course to make that code run as fast as possible. And then the last one is, really, there's so much data nowadays. They say we have way too much data, but very little cleaned data. I've taken everything from all the other video courses, everything on the internet and YouTube, and I put them in a single course. So I filtered out a bunch of the nonsense, a lot of the old stuff, a lot of the new stuff that maybe isn't covered as well, and kind of just projected into this one masterpiece. So this includes topics covered by paid courses as well. I haven't actually paid for them, but I kind of just looked at, what are the chapters that they cover, and then include some of those important concepts in this course. I do have links for YouTube videos and all of these resources, which I've gone through, only the high quality ones, but I've gone through a lot of these videos and resources, and these are all going to be put in links inside of the GitHub link in the description. So everything you need is going to be there, and I put all of those links in that link. So what are some use cases for CUDA parallel GPU programming? What are some of the use cases for this? Well, you have graphics and ray tracing. So the computer graphics that you're seeing in video games, user interfaces, all of this. You have fluid simulation for like physics and modeling, engine dynamics. You have video editing. So the video that I'm editing for this right now is using parallel computing to render. Crypto mining, which a lot of you might be doing already, that's going to be using your GPU hardware and some of the advantages of that to like mine through the crypto mining problems. And then you have 3D modeling and software like Blender. So when you have a bunch of different points going on and you have to render things, it's essentially the same as video editing, but just 3D instead of 2D. So the last one, which you probably guessed it already, is deep learning. So the number one use case for CUDA right now is primarily what I'll be covering in this course, which is deep learning. So we're not going to go as deep into like say convolutions, but to kind of understand how to optimize an algorithm like matrix multiplication, we're going to go quite in depth with that. So now you might ask, Elliot, what are the requirements or the prerequisites for this course? So there are some that are more intellectual and academic, and there are some that aren't. So this is strictly for NVIDIA GPUs, in case you didn't catch on to that earlier. If you don't have one, you can always consider renting the cheapest ones in the cloud. I advise you to look into the pricing before giving a definite no on the pricing for some of these cloud GPUs. At first, I was actually surprised how low the cost was for some cloud instances, especially the non-compute demanding ones. So if you have like only a CPU or like a RAM intensive machine, it might actually cost significantly less than one with GPUs on it. The GPUs one are still very cheap. You can use things like Vast AI, which I'll cover a little bit more. You can use this for actually getting really cheap consumer grade hardware that you can SSH into in the cloud, and then just do all of your experiments and go through the course on that. You can continue running with any NVIDIA GTX, RTX, or data center level GPUs. So all of the NVIDIA cards are pretty much supported for this. Maybe like the lower ones that are like 15 years old, those might not work. But generally, if you have like a GTX like 1660 or something like that, it's going to be fine. As for course prerequisites, Python programming will help in understanding while we're implementing in lower languages. So just understanding the whole programming concepts is really what's going to be needed here. Again, all these different languages is just like a change in syntax, right? So, we're going to use basic differentiation and vector calculus. That'll make learning easier if you know it already. It's really only required for intuition behind backpropagation and some of the stuff we're going to use to build neural networks from scratch. Linear algebra will definitely make your life easier by not having to learn fundamental algorithms from scratch. So like if you're not really intuitively, into matrix multiplication yet, if you haven't really, gone into that extensively, it might be a little hard for you to catch up. But matrix multiplication is very easy. It's quite trivial in retrospect. It's very easy to understand. But just the intuition there and optimizing it might be a little hard if you haven't worked with it a lot already. Then if you really care, I would recommend just reviewing, matrix transpose, matrix multiplication, chain rule from calculus, and then difference between gradients and derivatives. There's maybe a few more that I missed, but those are like the general ideas that you're going to need for going into this. And then just a heads up, if you are on a Windows machine, this might be a little harder for you. So I do have a little setup guide on Windows hardware. But I do everything here on Ubuntu Linux. So this is what I'm running just on my local machine here. And this is what we're going to go through the course with. You can always use WSL on Windows to simulate a Linux system, or you can use Docker. So Docker is an awesome tool that'll allow you to essentially fire up a little simulated Linux machine just in your terminal on Windows, and you can just do everything through that. I think it supports NVIDIA GPUs directly through Windows. I'm not entirely sure yet. I haven't tested that, but if you're on a Windows machine, I would recommend WSL or Docker. If you do run into errors or issues throughout this, I do suggest you check GitHub, Stack Overflow, NVIDIA developer forums, PyTorch docs, if your issue is related to any of this course material. So, you have a lot of resources at your disposal if you need to resolve an error that doesn't come up in the course material. You also have really powerful language models to use. There's a lot of language models that have been released recently that are really, really good at solving and addressing coding problems. So I do suggest you try those out if all goes wrong, right? All the code and notes for this are kept in the GitHub repo in the description. The ecosystem is going to change all the time, so in case this video isn't up to date, the GitHub repo will be, because I'm able to push that and actually make changes. So if something is a little off in here, you might want to go check in the repo and see like what it actually looks like, so that you can actually write it properly, and maybe there's a more optimized version. Things will change, but you get the point. I do suggest following the repo for maintaining a structured learning approach. I include Excalidraw diagrams, so this is going to help illustrate like high-level ideas, how we're going to approach things, as well as how to do things on the level of kernel optimization. So all the way top down, all of it. Excalidraw is awesome for illustrating things, and it's completely free. So all the diagrams there will be included in the GitHub repo and in the course too. You can always reach out to me through my Discord server, which will also be in the GitHub repo. And you can reach out to me through there and talk with the community. There's going to be a lot of other students learning. There's going to be a dedicated set of channels for this. So in case you get stuck or wanted to discuss something or just have a cool chat in the server, you can totally join that. I do want to note early on that this course isn't on CUDA only. So there's a few things that I cover outside of it, including PyTorch referencing, going into like Triton and C and C++, with like externally, not including CUDA, just to help illustrate things on how the naive version of an algorithm works. But so there's the code side, and then there's also I'm going to provide some prerequisites, or not even prerequisites, but rather just a good understanding about the whole deep learning ecosystem. So this is actually what one of the next chapters is going to be about, is how does the whole ecosystem work and where can I apply CUDA? It would be a little silly of me to say, here's how you optimize a kernel and make it run really, really fast on your hardware, but not actually give you some solid use cases for that. So you might already know what the use case is, but in case you're just trying to learn CUDA and you might look at some ways that you can apply it, I provide that resource as well. So spoiler alert, but some takeaways you might get from this course is that through experimentation and research, you'll learn that the main GPU performance bottleneck is memory bandwidth. So in deep learning, we have these giant inscrutable matrices that cannot fit into the on-chip memory at once. So think about if you have like a giant cluster of GPUs, and each of them have really, really fast tensor cores. These are like super optimized for doing, tensor operations in deep learning. But if you're doing these across many GPUs, you really have to exchange and mix and manage information between them. So you end up sending electrons, from this node to this node to this node to the right. And there's a lot of this communication that's going on. So you really get a ton of speed from the compute inside of the chips. But when it comes to communicating, there's actually a pretty big bottleneck there. And that's, one thing that you might take away from this. There's also on-chip constraints too. So you have like GPU VRAM, which is going to be, actually comparatively slow to what the on-chip stuff is. So VRAM is like off the actual, cores and all this, and then it has to communicate with the cores and all of the shared memory on chip and all of the registers, and that ends up being a bottleneck too. So it's not just the massive matrices communicating across a lot of GPUs. It's actually a lot of the on-chip communication too. So there's multiple bottlenecks that arise. But these are just things that you'll end up coming across and being able to address later on through optimizations. Another key takeaway would be to take an existing implementation and make it faster. So a lot of the times you'll see a new research paper come out and you'll see a really cool algorithm, but you might not know exactly how it works. And so, or you maybe you know how it works and you just want to make it fast and you want to integrate it into PyTorch, for example. So this is something we're actually going to do in this course. We're going to build up an algorithm and we're going to optimize it. And then we're going to actually port it into a PyTorch extension so that you can call it in Python, which is super cool. But just learning how to integrate your own research into things to make them faster, to have it operate at production scale, these are some really important things that you'll have to do when you start working, very deeply with CUDA. Another thing is Karpathy's LLM.c. A lot of you have probably heard of this. If you go search up LLM.c, LLM.c not on YouTube, on Google, you'll come across a guy named Andrej Karpathy, and he pretty much built up a giant GPT-2 training run in C from scratch. So it uses C and CUDA and all of it, and there's a ton of stuff in it. And I really felt like it's hard to understand that at first. As someone who's not like super enriched and having done CUDA for like 20 years, it's kind of hard to understand that at first. So having a really nice basis like this, where you can actually understand how to use CUDA and where the real benefits are from it and how to use it, that will allow you to read and approach Karpathy's LLM.c a little better. So that was one of the reasons why I actually made this, is to make it easier for people to go into LLM.c and understand what's going on. So in the GitHub link and the Notion document inside of my GitHub repo, you will see this in the intro section. So just a bunch of cool videos on how CUDA works, how transformers work, a bunch of just really cool, fun videos to, really get you motivated and upbeat on all of this. So we've got some technical stuff, we've got some fun videos by Fireship, but generally speaking, these are just some cool resources you can check out. CUDA programming. CUDA mode is a really good server, actually. I highly recommend you join this. It's just a Discord community of a bunch of people who are really into CUDA. So I believe Andrej Karpathy is in here, a bunch of really cool coders, a bunch of engineers are in here just discussing how to get certain kernels working and generally just CUDA stuff. Hence why it's called CUDA mode, right? So really cool server. I highly recommend you join that, as well as my server, which is also in the GitHub repo, but that's that. So now we're going to go into a little bit about the deep learning ecosystem right now. So obviously this is not going to be up to date in 5 years. So just, take this with a grain of salt. This is not everything. This is just what I found interesting to look at and focus on and to be aware of in the ecosystem and how you can sort of interconnect things and understand what's going on. So this doesn't actually go over anything highly technical with CUDA, but I thought it's better to show you the ecosystem rather than just entering technical details blindly. Like if we just dump straight into CUDA kernels, you won't know how to connect the dots later on. So when we're actually building out good algorithms, it's like, okay, now you have the skills to do this. Where do you apply that? So this is what that aims to give you. It's just a bit of background. Understanding the ecosystem will help you map out everything properly, and it provides that initial motivation to learn. So some parts are going to get really hard, and when you have that higher level motivation to see like, okay, this is what I can actually build once I learn how to do this, instead of just let's learn CUDA blindly. That seems a little naive. So going into it with like understanding what to do later on or what you can do, I think is really important. Again, don't feel free. Don't feel binded to just watch me talk about a subject for 20 hours. You may limit your learning if you just force yourself to sit down and just watch and listen to what I'm saying. I do encourage you to go down rabbit holes. So if you find something that interests you in this section or other ones, just go down there. That's where you learn a ton, right? But anyways, I've organized this into several sections. So research, production, low level, inference for edge computing, ease of use, compilers, and miscellaneous. So we start up at the top here was the easy ones. We have PyTorch, we have TensorFlow, we have JAX, and Fireship has videos on all of these. These are very well documented. I'll let you, you can kind of just like read through these. I'm not going to go over every single bullet point because it's already here. But yeah, you have MLX developed by Apple for Apple Silicon, open source for Apple devices. PyTorch Lightning is like PyTorch, but reduces boilerplate code. So there's a Reddit post here, which was interesting. When you set like your TF32 precision to do tensor core computations in PyTorch, like that's boilerplate code. So PyTorch Lightning is actually going to reduce that, and it's going to remove that boilerplate, so you don't have to worry about like including all those little optimizations and hacks. So when it comes to production, there's typically two things that fall in here. So you have training and inference, and some of these will support two of them together. Some of them will just support one or the other. So in here we have VLM, which is quite interesting. Search up VLM on GitHub. Actually go down and we can see, where did it go? Yeah, LLM inference and serving. And then, where'd it go? Performance, yeah. So performance benchmark against TensorRT LLM, which is the next one that we'll actually talk about here. But they implement a bunch of like essentially hardware GPU optimizations that we may talk about later on. But VLM is great. TensorRT is pretty much tensor runtime by Nvidia. And they have a TensorRT LLM, so it's for like inferencing language models with all of these, all these different optimizations, specifically for LLM inference. Now, Triton is something we're actually going to cover a bit more. Triton was developed by OpenAI. We go here, you can see this. It tells you about like what the heck Triton is, like what the motivation was, where it came from. But if we look at this paper from Harvard, this is actually where Triton originated from. So Triton, intermediate language and compiler for tiled neural net computations. Tiled neural net computations is the key here. This is where a lot of the performance comes from. And you'll see this later on when we build fast algorithms. Tiling is where you have like a giant problem where you have to do linear algebra operations, like on tensors, and you have to do them fast on parallel processors like GPUs. And so what you can do is you can tile the matrix into a bunch of little like squares, like subsquares, and you can multiply them together. So this way you don't have to do like an entire thing at once and then reserve it and worry about all that stuff. You can literally just select blocks, and the parallel processors in CUDA are extremely good at processing those blocks because of the CUDA architecture, which we will talk about later. But Triton is interesting. This is a whole paper, which I'm not going to dig into in this course, but a lot of interesting both compiler and speed ups that you get from approaching things with a tiled philosophy. Now, just some other optimizations we'll get in performance is torch.compile. So you do torch.compile and then open bracket model close bracket, and this will literally just increase performance 30% out of the box. It'll take that dynamic graph that PyTorch builds and it'll snap it into a static representation for production, because we're using it for production. And it'll just apply optimizations all around, which we will dig more into this course. Like an example would be like kernel fusion, where instead of doing a separate function for each step, you're like combining 2 or 3 operations into one single function, and that like reduces some overhead computation that you have to do there. So just a bunch of these little optimizations that torch.compile does. Extremely recommend for production. TorchScript is a little older, but there's an article here on TorchScript. So TorchScript, I haven't actually used, but there are some more discussions here that you can follow. I know it's a little older, so I typically just resort to torch.compile for most things, but it's here in case you want that. And then Onyx runtime is also interesting. I probably should have put Onyx before Onyx runtime, but it is what it is. Onyx runtime is pretty much on top of Onyx. So you have this thing called Onyx, which exports a model from either PyTorch or TensorFlow or whatever you want down to this Onyx format that's intercompatible. So I don't have to just export like some tensors from PyTorch and then like I can't use them in TensorFlow, right? Because it's like a different file type. The serialization might be different. And so Onyx is like this universally optimized, supported, it's like a .onyx file extension that you use for storing neural net weights and tensors. So Onyx runtime essentially takes that and allows you to just run it faster. So that was built by Microsoft. And then a cool little project I came across and that ChatGPT recommended I put into this course was Detectron 2. So it's interesting. You might find it useful, but developed by Facebook, and it's essentially a computer vision library that uses image detection and segmentation algorithms. So just a bunch of like really cool computer vision stuff that it has, a bunch of different neural net architectures and hacks that it employs, and it's just one of those fun things that you might want to mess around with. Then we go to low level, which is what this course is based on. in case you haven't read the title, it's on CUDA. CUDA is Compute Unified Device Architecture, programming language, programming platform rather for Nvidia GPUs. And there's a bunch of stuff which we'll dig into later. ROCm, CUDA equivalent for AMD GPUs, and then you have OpenCL. So this is more general, built for CPUs, GPUs, DSPs, other types of hardware. So just like a general purpose computing language, open source. And then we have edge computing and embed systems. So what the heck does edge computing mean, Elliot? What is edge computing? Think of the Tesla fleet that Tesla has. So there's a bunch of cars that are maybe running into accidents occasionally. And so they want to report this back to the Tesla data center to train on and improve the models. So you'll have a bunch of essentially this fleet, and the purpose of edge computing is to have them each of them doing their own local computation. And then whenever you do an update, you're just going to send that back, and you're able to have like this centralized entity that, I guess the centralized data center is our entity here. And it's just going to do some training on all of those, on all that new data. And that's pretty much what it is. It's just like a decentralized computing, if you will. So, you have like TensorFlow Lite, which is like a light version, a lightweight version of TensorFlow, and then PyTorch Mobile is the same thing. There's always optimizations you can do in CUDA and like just plain PyTorch that'll just make stuff run fast either way, but there is PyTorch Mobile for that. And then you have Core ML, which is for Apple products. So like the macOS, Watch, TV, all of this. Then you have ease of use, which isn't like entirely CUDA related, but I thought I'd still mention this because some of these are really awesome. So you have Fast AI, which I'm not going to talk about a lot, but you can look into this maybe separately. So they have their own thing here, but yeah, I'm not gonna go over Fast AI, but they have some interesting stuff. ONNX, which we talked about before, stands for Open Neural Network Exchange. So the X is capital, and that's where the X comes from. Literally, you just do torch.onnx.export model, and then dummy input, and then just whatever the file name is. So you can look more into the Torch docs and ONNX as to how to do this on both PyTorch and TensorFlow and whatever else you want. But this is how you would export an ONNX format. And then this is the TensorFlow equivalent. So this is essentially this like nice little image that I got where like it kind of binds with everything. So PyTorch, TensorFlow, Keras, Cafe, which was initially what PyTorch was using. Cafe was one of those original parts in the PyTorch ecosystem from a while back. So that just kind of shows how they can interconnect together. So you like export in one of these, and then you can import back into any one of these, plus ONNX runtime, which runs faster. And then you have weights and biases. So I got a little snippet from the internet as to like what this looks like, but pretty much allows you to track your training runs and a bunch of different charts and statistics about how your models are performing. So when I want to train like a clothing recognition model, I can literally have all of these different ones. So accuracy on sandals, shirts, trousers, pullovers, boots, right? Boots is like kind of chaotic, and pullovers just kind of worked fast. And then this one too. So you can kind of just track a bunch of things and understand how your models are performing, and then show that to like maybe your employer, or whatever, or whoever's maybe your manager, and just kind of get things done that way and document things easily without having to use same matplotlib. It's all just kind of tracked and imported and taken care of for you. And then cloud providers, these are actually quite important to know, not necessarily on the low level part of like CUDA, but these are still good to know because they play a major role in the ecosystem. You have AWS. So AWS is a major one. I personally use AWS's products and prefer them. I'm not endorsing, not sponsoring them, but not sponsored by them, but I do use AWS products. And the two main things here for ML stuff is EC2 instances. So these are like used universally. You just fire up a remote machine, and you can SSH into it and then do whatever you want. And you can use all the specs. Like it's literally command line access, and you get to do whatever you want. And then you have SageMaker. So it's a little bit easier and more ML focused, but you can run Jupyter notebooks on a cluster. So instead of worrying about a command line and having to fire things up in like in VS Code, like VS Code SSH, you just run a Jupyter notebook literally like in the browser, or you can just SSH into the SageMaker notebook, I believe. And then you have the data labeling part, which is very big in the world today. So where does all the data come from that we're training models on? Well, this is exactly where it is. If you go AWS SageMaker and then you find like the labeling part, or Mechanical Turk, I believe is what it's called. That's where all of the labeling on AWS takes place. So, big stuff there. Typically costs like a decent amount of money for people to label your stuff, but that's where you find it. And then model training and deployment, that's also supported by SageMaker. So you want to like deploy your own Llama 3 variant. It's like, oh, there you go, SageMaker. And then Google Cloud, I don't use as much. They have Vertex AI and their VM machines, which are like EC2 equivalents. And then you have Microsoft Azure, which I haven't actually used that much. So it's just like another top three, like these are the top three players in the ecosystem. And then you kind of break down to OpenAI, FastAI, and Lambda Labs. So OpenAI provides their own like fine tuning services, and you can, everyone knows OpenAI. You can literally go on the website and just navigate around there and figure out what you want to do with models. FastAI. So I haven't entirely gotten a picture here yet, but if I go to fast.ai, I can go to the console. Hopefully it doesn't expose anything bad. But like, yeah, I can select any of these. It's just like a bunch of rigs that I can rent for an hourly rate. It gives all the specs on them, everything. And it's great. So, I set RTX 3070s, which is like my graphics card, and mine costs about, 1 cent per hour, which is embarrassingly cheap. But yeah, this one is more expensive. But yeah, so FastAI is awesome. You can use these like in any GPU. You can pretty much select it and just use it on the fly, and it's like hosted by someone else in the world that you SSH into and do stuff from. Then you have Lambda Labs, which if I search that up, actually find Lambda here, Lambda Cloud. Yep. So data center, DGX systems, like literally you have the Blackwell GPUs, you have the H100s, yeah, just pretty much GPU infrastructure specifically, and it's like, I believe a bit cheaper than the big three providers like AWS, Google, and Microsoft. So Lambda Labs is commonly used, but you would rent things in a cluster. So you're paying like multiple hundreds or thousands or tens of thousands of dollars per hour for these. So if you're in a company and you're trying to get like cheap GPUs that are data center quality, you might want to look at Lambda. And then compilers. So I'm not like a compiler expert, but mainly you're going to have things like XLA. So this is what is powering JAX. You're going to have LLVM, which I'm not an expert. I haven't built compilers. So I'll let you look into that. There's a ton of resources on LLVM. It stands for low level virtual machine, I believe. Go to LLVM project. A toolkit for the construction of highly optimized compilers, optimizers, and runtime environments. Multiple components. Component compiles C, C++, Objective-C, and Objective-C++ code into LLVM bitcode, and then into object files. So it's essentially used for developing stuff in C, C++, and compilers in general. And then you have MLIR, which is, what is MLIR? Look at this again. Multi-level intermediate representation. So this was MLIR and LLVM were mainly developed by Chris Latner, which I also have a course on the programming language that his company built called Modular. The programming language is called Mojo. You can search that up on freeCodeCamp and go learn Mojo too. But it's like pretty much just an AI programming language for doing like fast tensor operations. So this was moved as part of the LLVM project, and there's some interesting stuff there. It's somewhat newer, so there's interesting changes. It's not like super ancient, but the main ones that I'll be able to talk about are like NVCC. So that's like the CUDA compiler, Nvidia CUDA compiler. And there's an architecture here, which I haven't like fully memorized yet, but the Nvidia CUDA compiler is what we're going to be using to essentially compile our CUDA scripts and kernels and have them, into binaries so that we can run them fast. So, these are interesting compiler infrastructure. I'll probably add to this with some better descriptions on like what these are, but this is like the general overview. And then for miscellaneous, I could not leave out Hugging Face. So last but not least, it's like Hugging Face, right? You probably already know what it is, but I'll look it up just in case. So on Hugging Face, you have a bunch of things. You have models, data sets, and then spaces. And that's like pretty much all you need to know. So if you go to models, you can, maybe it'll take a second to load. Here, we have multimodal, computer vision, NLP, audio, tabular, reinforcement learning, and then graph machine learning. So there's a bunch of cool stuff you can do here, but most of it is language models right now. I know like Flux recently released some of their, I believe it's like image, maybe video generation stuff. I can't remember specifically, but this is where you'll see all of like the new open source models that you can just pretty much download and run in PyTorch like that. You just need enough hardware. You just need good enough hardware to run these, and it'll just work. And then you have the actual data sets for these models that you train them on. So, you can go like 3D data sets, which is interesting. A lot of it is just going to be text. So, if I remove that, yeah, vision data, awesome. Auto math text. So just all these data sets are here that the models are trained on. And then you have spaces, which is where you can actually use models. This is where people will like host things or get sponsors with custom hardware setups. And they'll be able to just essentially host these models, and you can try them out and use them. So Hugging Face is awesome. It's a major player in the whole ecosystem, and I could not leave it out. But yeah, that's pretty much it for the deep learning ecosystem. I'll see you in the next part. So doing the setup on Windows, we just need to open up our terminal and run as administrator. I'm starting with Windows. We just enable permissions, ensure that it's the system32 directory. You're going to navigate over to the turn Windows features on and off. We're going to scroll up and look for Hyper-V. Ensure that box is checked off. And then we're going to look for virtual machine platform, ensure that is checked off, and then, or checked on rather. And then you have Windows subsystem for Linux, make sure that's also checked on. In order to get this working, you will need to enable virtualization on your machine. So, once the Windows subsystem is on, you can do wsl.exe, and you'll see, a bunch of options. So install, distribution, and we see an example there, WSL install, distribution, Ubuntu. We can go ahead and enter, enable, and we'll just wait for that to complete. I've sped this up a little bit because it takes some time. Realistically, it takes more than, a few seconds to do this. So I'll speed some of these things up. Ubuntu has been installed. Awesome. Changes will not be effective until system is rebooted. Yeah, so we run it again. We have this command that it's asking us to run. So wsl.exe install no distribution. That installs correctly. And we get the same thing again. So we just do a system restart. Now, after we've restarted, you might be greeted with this terminal, Ubuntu, and then the other command prompt. So when you're greeted with that, if you're just greeted with the command prompt, you do WSL, and you can get it here and just enter a username and a password that you're going to use. Now you should be logged into your little simulated Linux environment. So once we're in here, there's a few commands we need to run. So we're going to update and we're going to upgrade everything. So just type in the commands as you see them. There's some that we're going to be able to copy and paste in. So just enter that password you set earlier. I've time-lapsed this, or not time-lapsed, but I've sped this one up again. So that was just a bunch of things updating. If we go ahead and install some other packages that we'll need later, like wget, curl, and git, we'll see that those are also installed as a part of the update and upgrade commands. And then we just installed Python 3 pip. This is just going to be Python essentially for our machine. And that also runs too. So that does not come by default, apparently. So we just need to install that manually. But that's okay. We navigate over to Chrome and we search up CUDA Toolkit. This is what we're looking for. CUDA Toolkit download. So you just navigate to the latest one. It might be 12.5, it might be 12.6, whatever it is for you. Go to Linux, pick your architecture. You can use WSL Ubuntu. Remember, we're using WSL. And then just do the run file. It's the easiest one, least amount of instructions you have to do. So I'm going to do the first one. So wget, you can just right click in the terminal if normal pasting doesn't work. Let's maybe highlight the whole thing. Awesome. So that's going to take some time to upgrade, and I'll see you guys on the other side. Okay. So now we're in the little accept part. So just only check off the CUDA toolkit there, and then you should be good to install. Now we've done the run sh file, which was the second part of the command. And it tells us in the summary that we need to add some things to our path. So I've just pulled up this here, but this wasn't really working too much. So I went off and generated some other, more up-to-date commands with ChatGPT and figured out the proper ones. So you'll see those in a second here once I pull them up. But this is just a reference. So this is one of the things we have to do. So we could just vim into our bash RC file, and then I'll just pretty much type along with me here, and then we'll save this file. So feel free to use Nano or Vim, whatever you feel comfortable with. I'm using Vim here, but Nano isn't too hard either. So I'm going to set a CUDA home, user local /CUDA, and then we're going to export another one called path, and as a part of that path, we're just essentially going to include CUDA home and then the binary for that. And then last but not least, we're just going to export the LD library, like it also said in the summary. And then lib64 to end it off. Awesome. So now we can just Control-C, Control-W, and Control-Q. Or :W, :Q. We exit that, and then we can, I noticed we missed something. So CUDA 12.5 instead of just CUDA. So we can go ahead and go back into this, and then just find that part and add. And just right click and paste that back in, and then just delete the last CUDA part. Awesome. CUDA 12.5, sweet. Now we can just exit that again. And source. Then we just do nvcc -- version, which is the Nvidia CUDA compiler. So that's working. And then Nvidia SMI, so we can actually track our GPU stats. As long as these are both working, we've done the job correctly. So if you're getting errors with nvcc or Nvidia SMI, that's not good. You need to figure that out. I don't, of course, cover all the errors, but that aside, we're going to go ahead and set up a little CUDA test just to make sure that everything's working properly and that we can execute a .cu or CUDA script. So I just made a directory called CUDA setup test, and we're going to just vim into that directory, and we're going to edit and we're going to make a new main.cu file. And inside of here, I'm just going to go ahead and paste some functions. So we include the CUDA runtime header. We include the IO stream, which is a part of C++ that allows us to use things like cout. We declare the namespace std for standard, and then we cout hello world in our int main function. So if we do nvcc out main binary and then main.cu, we should be able to run this binary and get hello world. Awesome. So if this works first try for you, that's awesome. If it didn't, that's not so awesome, but you should be able to figure it out just by navigating forums. So like GitHub, the stuff I recommended before, just navigate around and figure out how to install the CUDA toolkit for Windows. It pretty much applies the same to Ubuntu. I'm going to go over some brief instructions here, but I'm going to switch over to Ubuntu because that's what my whole thing is based on. That's where I do all of my stuff and where everything is set up and optimized for. So I'll see you on the other side. So we can go ahead and open a Chrome tab here and just type in CUDA toolkit download. So we go to this one on Ubuntu, same thing. We go Linux, x64 is mine, might be different for you. Ubuntu, this one, run file local. You can do this. You can also do network or local. So for me, I did network, but that was a little while back, and having to uninstall it and then reinstall it again just gives me a bunch of weird graphics errors. So I'm not going to do that and mess with my operating system too much, but you should be able to just plug this directly into terminal. So you should be able to just pop into here and plug these in. Get the Debian file, and then just the rest of this and install the CUDA toolkit, and then just get the legacy CUDA drivers. I just did this legacy CUDA drivers. If that doesn't work, do this one. And then you would of course want to just do NBCC version and then Nvidia SMI, and you should see some useful stuff pop up here. So if these don't work for you right away, you might want to just restart your computer. That's usually the best option, and then try something again. If you do already have these installed, you don't even have to worry about it. So I would probably check these first. Probably should have said that first, but yeah, ensure the CUDA compiler works, and then Nvidia SMI. So now we can finally get into some coding. In order to really understand how to use CUDA, you need to first cover C and C++. So this course isn't actually about C and C++, so I'm just going to provide some resources for you guys to learn this stuff. And then I'll jump into some more advanced topics just to touch over and review the subjects. So for those of you who are new to this stuff, for those of you who are new to low-level C, C++, CUDA programming, I have some resources for you, some good articles, some good things to manage through. And if you are already experienced, just pretty much skip this part, or even still look at it to maybe touch up on the basics, and I'll cover some more advanced topics right after this. So learning C and C++ is hard. And so you really have to define what the best resources are and how to actually learn things properly. What is the best use of your time, right? This is a common dilemma that we have. So I came across a Reddit article on best resources to learn C++, and it pretty much said learnc++.com plus a bunch of other links that you might like. So learnc++.com is good. I've never used this before, so I don't know how comparatively good it is. So that's an option, of course. And then there's best way to learn C. So looking through this, I pretty much found that everyone likes the modern C, this one, C Programming: A Modern Approach. So it's a newer book, but that's how people found best way to learn C. If you are just trying to learn this for free and try to just go through the syntax and understand it as quickly as possible, there are some resources I would recommend and have looked through a little bit. So freeCodeCamp has some good stuff on this. C programming, just a bunch of blogs essentially on how to just pretty much just learning the language. And then you have C++, just maybe some more advanced things, libraries, a bunch of modern C++ stuff. So freeCodeCamp is a great resource. And then the one that I've personally stuck with for a long time and continue to use is W3 Schools. So it's pretty much like a nice, easy to read, easy on the eyes documentation or just an intro rather, on how to use C and C++. So I have both here. I'd recommend, if you're new to this, just look over each of these and do a bunch of practice questions on every single one of these. All these are super important. There's some of them we might not actually use explicitly in the course, but it's still good to know it regardless, just for having that low level brain so that you can dissect problems on CUDA applications that we may not cover in this course. So I'd recommend just like looking through all of these, go down all the way to like these examples, like everything. And then same with C++ as well. So all your basics, your functions, your classes, and then down to examples as well. So that's pretty much all I have for the basics of C and C++. Now we're going to go ahead and touch on pointers. So we're going to start off with pointers. If you go to github.com/infotoshi/CUDA course, and then pop over to, well, you're not going to pop over to dev. This is going to be all pushed up and ready once you're seeing this. But essentially, you're just going to git clone this into a directory of your choice, and then we can go and get started with the C and C++ review. So I have this all in my VS Code here, and it's all zoomed in and nice for you to see. But we'll start off with a simple pointer example. So we initialize an integer x to 10. This is the data part of x. And then we initialize a pointer type. So this asterisk, that means we're doing a pointer to an integer. And we're setting the name equal to pointer. And then this ampersand is saying we're going to get the memory address of x. So we have x here, which is 10. And the ampersand says we're going to get the memory address of x, which is going to be the pointer to 10. And then we can just print this out. So if I go GCC and we do 0, 0, 1, and then run that, you'll see that we get an address. So I have the pointer type here. There's an index where you can find these. If I pull up a tab here and go printf like int, for example. So you have all these different things here on C++.com that you can use. And these are just like the formats and stuff. So we have a pointer. It's this value that we're returning. We get a memory address to the value 10. And to get 10, we're passing in pointer, and then we do the asterisk to dereference it. So dereference means we have this data thing, which is 10. We have the memory address to 10, which is the level above, and dereference is just going to go downwards. It's just going to go back to that. So we have this memory address, just dereference and go back to 10. The next example here is a little bit tricky, but it's fine. It's relatively intuitive, so I don't expect it to be that hard. But essentially what we're doing is we initialize a value to 42, and then we make a pointer, an integer pointer type called pointer1, and we set that equal to the memory address of value. So it's ampersand memory address of value. So it's going to be like 42, and then we create pointer1, which is a memory address, or a pointer to 42. And then we do the same thing. So we make a pointer to a pointer, which is what the double asterisk is for. And then we do, again, ampersand of pointer1, so memory address of this pointer. So then you have 42, and then you have memory address, which is you have the pointer to 42. Then you have another one above that, which is pointer to a pointer to a value. And then we just do that another time. So it's pointer to a pointer to a pointer to a value. This logic checks out. And when we print this out, we're going to return the integer type, so D. And then we're just going to triple dereference it. So we have these multiple different layers. So we're going up a pointer like level 1, pointer level 2, pointer level 3, and dereferencing is just like going down a level. So we go down 1, 2, 3 levels and back to that value of 42, which is an integer, and we can safely return that. So if I just go GCC and then compile 02, we can go ahead and run that, and we get a safe output value 42. Awesome. So now I pop over to number 3, which is where things start to get a little bit weird. And initially this was kind of a funky topic for me as well, but this is void pointers. So void pointers are a little funny, and they actually allow us to do a lot of tricks that allow for things like polymorphism and stuff. but we're not going to go over that a ton. That's like other, that's not covered in this review. So we initialize an integer called num to 10. We initialize a float called fnum equal to 3.14. And then we have this void pointer. So what this means is, like, if you had an integer and then an asterisk, that would mean it's a pointer to an integer. But void is no type. So it's like a pointer to no type. And that means we can actually change which type it is pointed to, which is a cool little feature that you can do in C. So we say void pointer is going to equal the memory address of num, which is this, right? And then what we can do here in this print part, we essentially we take this, we cast it to an int pointer type. That's what this part is for, these brackets, and then inside the int, and then after the asterisk, the pointer cast, and then we dereference that. So we have a void pointer, which we cast to an integer. We cast to an integer type. It's originally holding the memory address of int. And then we dereference that after it's casted. So it's going to go up to this memory address, and then it's going to go back to 10, which is the value of num. And then we essentially just do the same thing for this fnum here. I have nice little descriptions here that you can read on your own. And then a fun little fact. So malloc actually returns a void pointer, but we see it point to a specific data type after the cast. So when you typically see malloc as like these opening brackets, this brackets, and then you have the actual cast inside of it. So what we did over here is what you see in malloc. So it's actually returning a void pointer, and then you cast that to a specific like integer or a floating point pointer, and then you can use that for something like an array. So if we go ahead and just GCC compile this, and then run, we get our integer, which is integer type, of course, and then we get our float 3.14, which is a float type. So void pointers, or not void pointers, sorry, null pointers are really interesting, and you probably found void pointers interesting as well. But these are a little bit different. So null pointers can actually make our code more robust through if statements. I'm going to remove those binary files for now to clean some space up. But we initialize a pointer to null. If we try to print this out, it's going to essentially return like there's nothing, right? There's like no space actually here. There's nothing there. You can't use that pointer for anything because it's null. That's the whole idea here. So what we can do is we can check if the pointer is equal to null. And then we just essentially just report that. Maybe we throw an error message, or we put a warning up, cannot dereference this, right? If the pointer doesn't have anything, you can't dereference nothing to something. You can't do that. So we actually change that up, and we allocate memory to pointer, so to this pointer, so that we can use it safely later on. So I'm just going to actually compile this so you can see what it's doing. Initial pointer value is nil, so we have the pointer type. We cast to a void pointer, which is going to be null, of course. So nil, that checks out. Pointer is null, cannot dereference. Good. So this was true. After allocation, so this is where we get into this part. Malloc is going to return a void pointer the size of int. So that means there is actually something there now. There is something there. It doesn't have an explicit data type, but we have something there. That's like int, I think 32 bits, so 4 bytes. And then we check if pointer is equal to null again, and it doesn't print memory allocation failed, so that's good. And then we get to number 4 after allocation, pointer value is this. So we cast this to a void pointer, and we can actually see this memory address. We can actually see that it works. And then we can, we know that this exists now, so we can use it for something. So we essentially check it for null. It's safe to use now. And then we have this dereference pointer. So you dereference that memory address back to the data part, and we set that equal to 42. So now you have this safe to use. You have this safe to use memory address and the data associated with that memory address. And then we can free that pointer, set to null after freeing, and then we see that it's null again. So yeah, if pointer is null, so we know that it is null. Safely avoided use after free. Awesome. So the whole point here is that we can use null pointers to do little tricks, and we can make our code more robust. By checking if it is null, we can avoid running into unexpected errors like seg faults and other weird things that are hard to trace back, right? Sometimes you don't want to have to go through all of that just to figure out an error, so it's better to just write more robust code in the first place and ensure that it works properly. So in this example, there's quite a few things going on here, but I'll try to explain this as best as possible. So we have an array. We just declare an integer array, 5 numbers, and then we have an integer pointer equal to array. So in C, because we're just leaving it as array alone, it's going to point to the first element, because that's how memory is lined out, right? It's going to point to essentially where does this thing start, and that's going to be 12, of course. But we know that an array is a pointer on its own. If we don't dereference, or if we don't index that array, it's just going to be a pointer alone, right? So if I print f, and then we'll just go array. Sure, I'll let GitHub Copilot complete that. Not correct. Yeah. We'll see that this array, if we don't dereference it, just on its own, it is a memory address. It's a pointer to this array. So we set let me just delete that. We set an integer pointer equal to that. So that's a memory address that we have. Awesome. Now we look at our position 1, which I printed out. That's going to be 12. So we have that start of the array in memory, and then we just dereference that number. So it goes back to 12. That's what this asterisk is for. And we print as the integer type. Awesome. Now we have a for loop going on here. So what the heck is this doing? We have I starts at 0. We want to stop it. Whenever it equals 5, we stop it, and then we increment by 1 each time. So inside of here, we have an integer type, and that's going to be the dereferenced pointer. So whatever pointer is, we're going to dereference that back to the original value that it was. And then in here, we're going to do the pointer type of the actual pointer itself. So this is the memory address that we're seeing. And then we're just going to increment this each time. Each time this for loop goes, we're going to iterate it once, and we're going to increase pointer, which is the memory address. We're going to increment that. So I had a little example here that I wrote out. These obviously won't be like the same examples every time. They're going to be different, but notice how this pointer is incremented by 4 bytes, right? So this is not in bits, this is in bytes. So if we do 8 bits in a byte times 4 bytes, we get 32 bits, which is the integer 32 type, the classical integer 32. So hopefully it makes a little bit more sense now about how memory is laid out, at least on the CPU. So yeah, we just have these essentially skipped by 4 bytes every time. 4 bytes times 8 bits per byte is 32 bits, and we get our int32 from that. I also make a point that, well, right now pointers are not in 32 bits in size, but we'll see why having them as int32 right now can be a major issue. So if you actually do, we go Python and we do 2 to the 32, we'll get this number. So look how big this is. This is 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's about 4.2. That's about 4 gigabytes. In powers of 2, of course. That's 4 gigabytes. So if you have, say, 8 gigabytes of memory, which isn't actually that much, on this machine, I actually have 64. So if I have 64 gigabytes of memory taken up by like a single array, I mean, that obviously wouldn't happen. That's a really large array. But let's just say I have like one that's like, 64 gigabytes long. Well, we're actually going to get overflow when we try to index that way. So you're going to see later on that it's more useful to use a certain type for these pointers. So if we do 2 to the 64, so a double precision integer, so N64, you'll see that this is like extremely massive. This is like, I don't know, somewhere in the exabytes. It's like ridiculously high. Yeah, just we're going to deal with this later, but right now, this is the general intuition for how these pointers are printed out. So if I scroll up a little bit, you'll just see we print out the dereferenced pointer at that. We essentially take that memory address and then we dereference it based on the index that it currently is. So we just bump up the index 1, we jump ahead 32 bits or 4 bytes, and then we print that value out each time, and you see that vertically here. I just maybe run that again after it's cleared. You'll see that it's just like vertically just skips ahead as we'd expect. And then this pointer, which is just that memory address, and then I just put this out for testing sake. You don't need to worry about that. But yeah, this is the general intuition on how these things are laid out in memory. So number 6 is an interesting one. It kind of goes back to example number 2, where we have this value and then pointer just stacks up. That's essentially what 6 is. So we have these two arrays, array 1 and 2, and they're essentially just these vectors, or these arrays 1, 2, 3, 4, and then we have an array 2, 5, 6, 7, 8, and then we just have an integer pointer to those arrays, and then we store another, you could say, array. I just name it matrix to differentiate, and we store those pointers essentially on top of each other. So what it looks like is we have this matrix, so it's pointer 1 and pointer 2. Pointer 1 is it's the pointer to that array, the array 1, and then pointer 2 is the memory address for array 2. So essentially what we have is if we look at this array of like this matrix, it has pointer 1, pointer 2. If we flip it, so instead of like this and this, we stack them on top of each other, so it's pointer 1 then pointer 2, it actually looks like a matrix. So you'll have your array 1, which is 1, 2, 3, 4, and then the one underneath, which is 5, 6, 7, 8. And so it actually is like it's like a grid, right? And if we iterate through this, you'll actually see we just essentially iterate through these. So we do J and 4, and we print out the dereference matrix at position I. So that position I is going to give a memory address for it's going to be number 2, which is going to be these two arrays. And then we're going to dereference that, which is going to give us our actual values. And then we're going to iterate this each time, of course, as the for loop goes on. And then we just do a next line so that it looks nice. So that's pretty much all I have for pointers. We're going to jump into custom types now, which is more what I was talking about for these weird pointer sizes. We're going to dive into this. So now I'm going to show you pretty much the equivalent of the torch.long type. So you might have seen this before. If you're I assume you have some knowledge of Python and PyTorch, so I figured that's the best way to illustrate this. We have this size t, this size underscore t. This is typically how you write these out in C, is you'll have whatever the type is, and then you'll have underscore t to say that this is like a custom type that you made. T is for type. And this is specifically for like big numbers, right? So the idea here is this is going to be an unsigned long. So uint long. So int, it's going to be a uint 64. That's what it's going to be. If we do this in Torch, you'll see IPython import torch, and then we can make x this, just an array of integers. And then we go x.dtype. We'll see a torch.in64. So it's just like that 64 bit precision that we want to store really big matrices, right? So especially in CUDA, when you have like really big tensors that are occupying like multiple gigabytes. Like on my GPU, I have 8 gigabytes of storage. So if we're using int32, that you might get some overflow errors. Or you might get just some unexpected bad behavior that is going to like mess with things. So you don't necessarily want that. And that's the whole point of this size type. I kind of wanted to show you that this isn't so bad after all. So, just to step through this, we have the same array that we went over last time. We do this size t type. We use size and then size of array divided by the size of an individual integer. So it's like the total size of this entire thing divided by the size of each individual thing in it. So you get the total length of the array. And so if we go 0, 1, I already compiled this, you'll see we get that 5, right? So there's 5 elements in here. We print this size out. I'll go over this ZU part in a second here. But we get that output 5, and then this 8, we print out the size of this. So that's in bytes, by the way. When we do like size of int, if we do like, let's see, printf, we'll just say int size, and then we'll go sure in bytes, and we'll do that. If I just compile this again, we'll see int size in bytes. So this is an int32. This is just an int32, and it's 4 bytes or 32 bits. So when we have this, that means it's 64 bits, just to put that in perspective there. So when we go to this size t, we'll see it's an unsigned type def. So we do a type definition, unsigned, so it's only going to be positive because we're storing like you can't have like negative size. That's the logic. And then we have this long, which means it's going to be, it's going to literally tell the operating system where we want 64 bits, not 32. We want it to be long, and then just the size t type. So we can actually go into this and we can see, oh, type def, size type, and then we declare this thing. Where does this come from? Oh, right here, long unsigned integer. Boom, just like that. Super easy, right? I guess to sort of clarify like what the whole deal is here, we could just pop back to this link. If I just open it on my second screen here and pop it over, we can search for the, I'll make this a bit bigger. I don't know, can I make it bigger? There we go. So if I go up, we'll see that we have this Z, and then we have the U. So Z is just going to be, I can't remember exactly what this is for, but then we have this U, which is essentially just the unsigned int, right? So it's the U is unsigned, and then we have this size t type, which is what the Z is for, and then we just map that out. So if we had just a regular integer, it would still be size t because you can have, it's still an integer. You can do stuff with it. But when we have a uint, then it's just kind of explicitly you're gonna have this size t type. So that's kind of how we map things there, and we can use the Z followed by the U to properly print that out, to print out the type of that. So you have all these other ones too, like pointer diff type. But that's generally the intuition there. And then next up, I just wanted to cover declaring your own custom types. So we saw one in the standard C library, the standard IO C library, the standard definition library, whatever you want to call it, the headers. And It's also important that we can declare our own, because we might need to use these, and we actually will use these later on in the course. So typically how it goes is you do this thing called a type def, which is a type definition. And let's just say we're going to make a point, for example. It has an x and a y and their floating point values. So we do this struct, which is going to have some elements inside of it. It's going to have some of these, I guess, objects, you could say, these items. And it's going to have a float x and a float y. And then we say this is going to be a type point. We do type definition. It's going to be a struct, and we're going to make that a point type, essentially. And then inside of our int main here, since this is already declared, we can say a point type, like, you would do an int p or something. We're just replacing int or whatever that type is with point, and we're making that variable named p, and then we're populating it with some values here. So this is going to be our float x and our float y. And then if we go, size of point here, if I just compile this and then run, you'll see size of point is 8. So 8 bytes is 4 bytes plus 4 more bytes. So each of these is a float 32 number that occupies 4 bytes in memory. So when you add these together, it occupies a total of 8 bytes. So this point type is going to cover 8 bytes or 64 bits in memory. And then just this other C++ script is literally identical to this. So you can declare things the exact same way in C++, except you might just want to use like the IO stream instead of maybe in C++ you would comment this out and you would go include IO stream, and then you would use using namespace std, and then you would see out that. Oh, identifier cout is undefined. Okay, I guess not. I don't know why that's not working. But you get the point. So very minimal changes. So now if we pop over to type casting, I have 2 files in here. So just a single C file and then a README. So inside of here, I have static cast, dynamic casts, constant casts, and reinterpret casts. So we're only going to be covering these static casts because these are the safe ones, and these are mainly what you're going to end up using, if any. So in here, it's very simple. You have just say a floating point number, 69.69, and then we just declare an int, and all we do is just have this f, and then we do brackets int. We just literally put this right in front of it, and that'll statically typecast the float 69.69 to an int. And what this will do is it'll just truncate that last part. So in memory, essentially in binary, in bits, it'll be laid out as it'll have that first part, so the first integer piece, and then it'll have the decimal, and then it'll have the decimal bits afterwards. So it'll be like that, decimal, and then after. So what it'll do is when it's typecasting, it'll just truncate this part and then give us more precision for these essentially int32 bits. So that's essentially all it's going to look like. It's just going to be 69. It's not going to have any decimal places. It's going to effectively round down, you could say. So if I just pop into typecasting and run this, you'll see we get this integer format, so just truncated. And then when we do a character, this is actually going to convert to ASCII. So if you remember your ASCII tables, I'll go ahead and bring this up on the side here. ASCII table. Oh, it's literally right there. Okay, ASCIItable.com. We can see that this one right here is an uppercase E, right? So uppercase E, uppercase E. Look at that. How easy was that, right? It's not crazy doing an integer to a character conversion. So that's all typecasting is. I'm not going to go over this extensively because it isn't like a crazy piece we end up using in CUDA, but just to throw it out there and remind you guys of how simple this type of thing is. Another topic I thought was briefly worth touching on was macros and global variables. So we essentially have these basic ones like if defined, if not defined, elif, else, and then end if. So it's we're essentially going to use these later on to declare hyperparameters and just different global things that we'll need access to that we don't want to just pass in as an extra, bloated function argument. When you have like 20 arguments in a function, you might want to reduce that and just declare some of those locally so you can use them wherever you want. As long as they're not changing or you're not doing anything weird with them, you're okay, right? So like in this example, I do pi, like uppercase pi, and then we set that equal to a double, right? So we can do these functions too. So it's kind of like a lambda function, if you will, a lambda function in Python. We do this area, and then we pass whatever we want in. So r is our radius, and then we do essentially the radius is pi r squared. So we just do pi times r, and we get that. So it's just a little lambda function you can do as a macro. And then we have if not defined radius. So radius isn't defined here. If end def, if not defined. Define radius, and we set that value to 7. So it's going to be an integer 7. We end the if, we end this whole block, and radius is now a declared macro equal to 7. And then we have some if logic down here. So if radius, is bigger than 10, which is not, we define this. So this is like grayed out. It's not smaller than 5, also grayed out, and then else. So it's just going to stay at 7, and then it's going to end if. So we can do if logic in here as well. And then if I just go ahead and pop out of this to macros, and we go GCC like this, we're going to double. We'll do perfect. So area of circle with radius 7 is going to be this much, and that's a floating point number, which we have here. So this radius, I was not careful there. This radius is actually an integer type, so we just set that back to d, and then it works flawlessly. So that's how you do macros. Pretty easy. This part is where my understanding gets a little bit fuzzy. I haven't worked with compilers extensively, but I have found some really good resources on the C and C++ compilers. So I've just provided some links here for you to go learn. GCC is the most popular C compiler. So that's GNU C compiler. And then G++ is the same thing, but for C++. So, I have different articles on here from freeCodeCamp that you can go and look at. So there's this one, and then we have the other one as well. What is a compiler? Explained for beginners. So like an analogy, essentially just converting your machine code down to assembly, and you have all these representations in between that the computer will work with to help understand things better, and then it'll convert that assembly code down to essentially the CPU instructions in bits and bytes, so binary ones and zeros. And that'll get sent through as essentially electrons and charges through your circuitry in the computer, and that is what actually executes this stuff. And then just the C++ compiler is a little bit might be a little bit higher level. I know C++ is a higher level language than C, but these are just like really good explanations that I can't really top myself without messing up. So I provided these links here. Hopefully this all makes sense, but we won't really need to understand too much about compilers downstream. It's good to know what they're doing, but in order to debug code, you just need to know kind of the architecture of what the compiler is, what it's doing, like where it's putting stuff, not necessarily like all the math and representations happening. It's good to know, of course, but it's not needed to write functioning code. So we'll see that later on. Like we're just going to essentially type in these compiler flags and all of this, and that's what the next section on actually is. It's on makefiles. So makefiles are really useful. They're going to help you be more efficient about developing C, C++, and CUDA code. So instead of going into here and just typing, GCC every single time, and maybe you have autocomplete like me, but either way, you just want this to be a faster process and you want to be able to automate and have more control over what happens and just manage things better. Makefiles is what you want. So inside of makefiles, it looks really complicated and it's like learning this new language, but it's really not. It's not that bad. You can define variables. So like GCC equals GCC. And in order to use these, I can just do $, and then brackets, and then put that variable inside, the variable name inside, and it'll just pretty much reference this when it's called. This is a command, by the way. So we'll see this in a second. I'm going to do a little experiment with the CUDA script here, but we just have this NVCC maps to the Nvidia CUDA compiler, and then we have CUDA flags. So this is just a little thing that's like my GPU architecture. We're going to see this later. You don't have to worry about this now, but this is just like my GPU architecture is a 8.6 compute capability or compute compatibility. I think it's capability. Either way, this is just we could just have flags and we can just have more variables that we plug into this stuff. But if I go back to the README for this, we have these targets, prerequisites, and then our commands nested inside of that. So how does this work exactly? Well, I'm going to show you this just by pretty much example. So if I can actually delete this line. If I just go make 01, see how it makes a binary here? And then I can run this binary and it'll say boo. This printf, it just prints boo, like it works just from make 01. So what we're doing is we have this make command, which is for makefiles, kind of maps there. And then we have the 01 part, which is the target. So this is the target, this is left side of the colon, and then after is their prerequisites. So notice how I removed that other part, the 01.c. So this essentially means we're going to either confirm that this already existed or has been done, and if it hasn't, we're going to do it. So you'll see that in these examples down here, but just to fill in the rest. So we have a bunch of things happening. We have this variable GCC, which is just saying, it's essentially just going, GCC. It's just doing that. And then we put this @ sign in front of it, which means don't print this out in the terminal. So if I just remove this and go and just remove the @ and go real clean, or I'll just remove this for so that it makes the most sense. And then I go make 01, you'll see that it actually shows us this in the terminal. But if I put an @ there, then it doesn't, right? So that just removes it. That just makes things more clean and just, it's like a best practice, just easy to see things. You want to maybe like look at the ones that might do weird things and you just want to like ensure that all your variables are correct. But this is a very simple, you don't need to print this out. And then just jumping down to like number 2 here. So number 2 is essentially the same thing. So I'm not even going to execute that. We don't even need to run this. And then 03 is just the CUDA compiler. So we do NVCC and then the CUDA flags. So it's essentially what it's going to look like. It's going to go NVCC -arch. Get rid of that. And then it's going to pass in O 03 CU. That's the binary we want it to be. and then that. That's going to run, and we should be able to go 03 CU, and it's going to say boo from here, right? So just the same thing. We just include like CUDA runtime and all of this just to be fancy, but it just outputs the boo command. Yeah, this is a very simple example. So it's essentially just converting. It's converting these variable names and not printing anything out. We just go make 03 and it'll do the exact same thing. See, it takes a little while. Same exact thing. We have this clean command, which is going to actually remove all these binaries. So when we want to clean up everything and just make it nice and presentable, like we haven't done work, like what I'm doing with you guys is I'm deleting these binaries before doing the lessons because it looks ugly when I have more files. So I can just go make clean, gone, right? So that's just like a very, very simple example. And it's just like make and then whatever the target is. Going back up to these ones, these are a little interesting. So 01 underscore obj, which is for object. This is going to GCC, it's going to take in this C code and it's going to output this O, or this object file. So it's going to essentially this, but it's just going to do object file instead of a binary. And then this 01 obj, so this object execute run, that's going to take in this previous one as a prerequisite. So that means this one has to already be complete. And if it's not complete, we're going to run it and make sure it's complete in order for this to work. So we're going to compile this object file into a binary. So you have this C representation, and then the object file, which we do here. And then this one takes that new object file and converts that into a binary. And then we execute that binary on this line. So if I go make and then 01 obj execute run, and we don't have any of these files in here, it's literally going to ensure that this is called first because it hasn't yet. So it's gonna convert this C file into object, and then it's going to convert that object into a binary, and it's going to execute that binary. So this is just, I probably over-explained things a little bit, but this is pretty much the idea on how you can automate just C compilation, C++ compilation. We're going to use this more for CUDA scripts down the road, but that's the general idea. And then this phony part at the top might look a little weird, but this essentially means we're not going to. It's just like a way to make things easier to use, make it so you don't run into errors. I had a decent explanation here. So say we had a make file with a target named clean. So in this cleanup command that makes everything nice again. Suppose we have a directory named clean in the same directory as the make file. So here, if we had something named clean, if we run make clean, make will not run the command. It will not run the command in the target clean because clean already exists. Instead, it will see that the directory clean already exists and it'll not run it. So in short, we essentially take a bunch of mappings from target names to commands. That's where this phony thing comes from. So it's like a phony, if you will. I don't know what the philosophy was behind that naming, but that's how it works. And then we have some other stuff in here. So I already went over the @ symbol, and then there's this one too. So the colon equals. I don't think we use this in here, but equals is used for defining variables, or it's called a recursive assignment. So both used for defining variables, both of these are. This one is a recursive assignment. So value of the variable is reevaluated each time it's used. And then this one is a simple assignment or immediate one. It's evaluated only once at the point of definition. So this is like typically the safer option you want to go down. If you get really complicated make files, you might end up running into weird things with these recursive assignments. So Generally, it's safe to use these ones, but it looks a little funny, so I didn't include it in this example. We will use it down the road though. So last but not least, we have debuggers. So debuggers are awesome for just an alternative to just adding print lines. Just print this, print that. Did we make it here? Yeah, we made it. We failed, whatever. Just adding those just bloats your code up. So having debuggers makes that a lot easier on you. You can actually go down to literal assembly and see where the electrons are in your code, like in your script, like what is happening on the hardware. So debuggers are super useful. And in particular, we're going to be talking about the GDB debugger for C and C++. So you use them for both. I'm not going to like explain these super intensely. I don't feel comfortable in my own explanation for these because there's just a lot happening. But there are some commands that you generally want to be familiar with. It's mostly just commands and knowing what to look for in your script. So I have these in the README file, just with some explanations, but a really good overview is here. So this is done from Low Level Learning. It has an advertisement here, but essentially it's just a really good overview on GDB. Just going into assembly and doing a bunch of cool tricks and debugging C code that way. So I do recommend you watch that video. Okay, we can finally take a breather now. That was a lot, but I really hope that this is gonna sort of just ease that. This is designed to be a more passive part where you can kind of just sit around and listen and watch and just kind of enjoy it. There's no coding involved here at all. So I thought I'd provide some context on different types of hardware, what the whole purpose of GPUs are. I mean, you probably already know what they are, but I just want to provide that background just so that we're on the same page entirely. And just to provide some kind of internal, I guess, preparation for the next part. It's good to have these breaks just to, slow your mind a little bit and give yourself some time. But first off, we have these CPUs, okay? You already know what a CPU is. It's general purpose, high clock speed per core, very few number of cores. The on-chip memory is very large. So maybe you didn't know that. The caches on the chip are actually quite large compared to the GPU. This is because, the memory bandwidth from the CPU to the RAM slots on your computer, those are going to be, like that transfer speed is going to be very slow. You have to move the electrons all the way from this part of the motherboard to this one. And that takes time, right? You're just constantly waiting for data to arrive. And that's like what takes up most of your time, right? So you have these big caches for purposely like preloading things on so that they're ready to use. You have lower latency. So the whole idea of a CPU is to just complete this task as quickly as possible and just return the value. Just complete it fast. And then they have low throughput as well. So low throughput means it can't do as much comparatively. It can't do as much operations per second as a GPU can if you're talking about simple instructions. If they're more complex ones, like managing and loading data and doing like file reads and writes, like that'll be faster. But if you're talking like math and matrix multiplication, it is going to be significantly slower. Throughput is more talked about as like operations per second. So if I have a bunch of cores running at, say, 2 billion clocks per second, and I have 6,000 of them, versus 6 cores that are running at 5 billion clocks per second, do the math, right? How many operations are you going to do on this one versus that one? That's the whole point of a GPU. Way more cores, a little bit lower clock speed, but way more cores. It just completely outnumbers CPU, and that's why it's faster. And then on GPUs, we have the 5090 hasn't been released yet, but I thought it was funny to put it there. GPUs are very specialized, so they can accomplish simpler instructions, easier to handle ones, hence why they have smaller controllers on them, which you'll see in a second. They have a lower clock speed, like I said, way more cores, and a lower cache. So because you have that on-chip memory, because you actually have this VRAM that you can access that is on the GPU, and that all of the Nvidia hardware engineers has essentially optimized for accessing that, you're able to get a lot higher memory bandwidth that way, up in the like a high 100 gigabyte per second range. So it's in the hundreds for sure. And you have higher latency on this. Remember, it's not for, minimize the amount of time it takes to complete this task and then just done, right? It's more optimized for throughput. So we already talked about this. But then you have these TPUs, which came across recently, and these are for modern deep learning applications. So TPUs are for literally just processing tensors. Like you do fast matrix multiplication, fast linear algebra. That's what it is. Tensor is linear. Tensor operations is linear algebra. And it's just specialized for doing that. So TPUs are faster, but way more expensive and specialized and typically not consumer grade hardware. So that's why we learn how to, build on top of infrastructure with GPUs, because it's, you can actually afford it. You can have one at your house and for fairly low cost. And then you have these FPGAs, which I don't expect you know what these are, but these field programmable gate arrays are very specialized pieces of hardware that essentially say, instead of having to write or build a custom hardware configuration, like for a certain task for making something that you need to run really, really fast, you can just program these. You can just program the actual chips to do something more fine grained on what you want. So there's more control over it. Very expensive, very low latency, very high throughput, high power consumption. All of this, right? These are more expensive, but they allow for modularity, if you will. And then just for some background on GPU history. So, back in 1993, when Jensen started Nvidia, they had the GeForce cards, all of these. I wasn't alive during this time, but you have then you start getting into after the GeForce 7, you start getting into these better ones. So like the Tesla cards, the Fermi, the Kepler, Maxwell, Pascal, and then Volta is when things really started taking off, the Pascal and the Volta cards. And then you have Turing, and then Ampere, which is what my card is based on. And then you have Hopper, which, in case you didn't know, Hopper cards are really, really fast, like the H100s and the H200s, and even the recently released Nvidia Blackwell chips. Yeah, those are ridiculous. This is a little bit outdated, of course. So there are actually like chips on here. I just got like an outdated screenshot, but you get the idea. This is how it progressed. And then you have like the relative clock speed per core on here. So, some of these were like really, really high, but didn't have very many cores. And then NVIDIA kind of figured out like, okay, we should just put more and more cores on these things, right? And then you get the overall, I think floating point performance is what this is. So, once you get to Volta, it's starting to get really high. So I think this is double precision gigaflops. So, essentially 6 teraflops of compute on the Volta architecture, which is pretty good. And then it gets better and better from there. On mine, I think I have right now, it runs at a high of around 23 teraflops on cuBLAS. So cuBLAS is the fast linear algebra library that multiplies matrices really quickly. And I'm about to get pretty much like 20 gigaflops of single precision compute. So that's quite good. What makes these things so fast for deep learning? I didn't actually cover this. On the CPU, you have very little cores. You have these big control units that are taking up a ton of space. You have all these caches everywhere that are flooding the thing. And like you're not giving that much leverage to the cores, right? Like the cores can do advanced complex instructions, but there aren't that many of them. So you can only do so much. Whereas if you have this other architecture where you have simpler instructions, simpler controllers, simpler registers, smaller ones, but a ton of cores, like see how most of this is taken up by cores and then just caches and RAM. That's ideal for GPUs. So on here, you're able to essentially, the idea here is you're trying to put together a puzzle. You're trying to put together a jigsaw puzzle, and the point is it doesn't matter which order you do it in. So you don't have to do like this row and then, or this column, this column, this column. Like, it doesn't matter. You do this piece here, this piece there, do like a block, like a chunk there. It doesn't matter. As long as it's all assembled together properly in the end, that's what you care about. And that's what the GPU is really good at. So typically you'll do things as like, multiple puzzle pieces at a time, or multiple blocks of puzzle pieces at a time. So you'll have like a 2x2 or like a 4x4 thing of jigsaw pieces that you'll maybe do at a time. That's the intuition behind CUDA, and how now you program GPUs to run fast and solve these problems quickly. On the CPU, you might be able to only do there's only 4 cores here. So you might be able to only do 4 given pieces of that puzzle at once. Whereas GPU, let's say you have like 6,000 cores, right? If this puzzle has like, I don't know, say like 12,000, if it has 12,000 pieces, well, you can effectively do that in 2 operations, because you're able to do the first 6,000 in one, and then the other 6,000 in the second. So it's effectively 2 operations that you do it in. But if you divide 12,000 by 4 meaning number of CPU cores, you actually get 3,000 operations. So you can see how that can be drastically sped up. That's why GPUs are so fast, because you can do that. Now there are some common terms that we refer to these things through. So CPU is the host. You're going to see this in CUDA once we start writing kernels. The CPU is called the host, which is pretty obvious, and then it just kind of makes sense for that to be named that way. And then the GPU is the device. So you have the host, CPU, and then GPU, which is the device. The CPU is going to, mainly the performance there is going to be latency in seconds. So you're looking at latency, how quick can I do a given task? And the GPU is throughput in tasks per second. So for example, if you're doing a rendering task, it's like, how many pixels can I render per second? Or how many, I don't know, how many pixels can I, yeah, sure, render per second. That's fine. In a typical CUDA program, you're going to allocate some memory on CPU memory. So it's going to be a classical like C malloc. That's what you're going to do. And then once it's allocated on CPU or host, you're going to copy from host to device, or CPU to GPU. And then once it's on the GPU, you can actually launch a kernel, which is what these parallel functions are essentially. So on a CPU, you have a function, then a GPU, you have a kernel, which is the GPU function that can be parallelized. And that's the main intuition there, is you start off with CPU, move everything, do everything really fast on GPU, and then once you're done with the results, you move them back and then do whatever you want with them from there. You might even continue to just feed it more into more and more kernels until the whole thing is done, right? But that's the ideal workflow, is you have CPU, and then this GPU thing is like an intermediary, which you have to convert back to CPU to do something useful with. The kernel looks like a serial program. So we're going to look at these in a second here when we jump into actually writing these, but it's going to be a very simple function, and it's going to have very few lines. It's gonna look like this basic serial script, except it's gonna have some key terms in it. These are mainly threads, blocks, and grids. Don't even worry about those terms right now. We're gonna get into those. I'm gonna explain the philosophy behind them. I'm going to explain pretty much the whole CUDA architecture for you, and just help you understand what the heck these things are for. Now, some common terms to remember before we actually start jumping into this stuff are, well, first of all, kernels. So kernels is like a weird term. You might have thought like popcorn kernels, like this is what I thought. I was like, what, popcorn kernels? Why are we using those on computers? That doesn't make sense. And then I jumped over to convolution kernels, which is like when you do like a convolution operation. You might have seen this in like CNNs if you've done a lot of stuff in like maybe PyTorch and you've like looked through the intuition on that. It's like a sliding kernel that does like an image processing thing on just images. That filter that slides and does calculations, that's called a kernel. So I was like, is it that? No, it's not. It's not a convolution kernel. It's also not a Linux kernel either. Funny enough. So there's lots of different kernels we have. There's actually 4 kernels: popcorn kernels, convolution kernels, Linux kernels. But the best one is GPU kernels. So that's the ones we're going to be working with. There's actually a little keyword that you highlight. You go underscore underscore global underscore underscore, and that defines a kernel on the GPU. So there's actually a way we can explicitly say that. And yeah, not Linux kernels, don't worry. I thought the same thing too. It's like, which one is it? But yeah, so we're going to go into threads, blocks, and grids. That's going to be one of the main things in the next chapter. And then two more, like sort of just lingo terms, are GEM, so GEMM. This stands for General Matrix Multiplication. So what this generally means is you have, it's not just multiplying like A times B equals C. It's not a matmul entirely. You actually do a matmul, and then you have this alpha. You have this alpha parameter, which you scale the result of that by, and then you add it to this beta scalar times the matrix C, which is the shape of the output matrix. So that's like a lot of linear algebra, which I'm not going to cover right now. But in case that makes sense to you, it's essentially this alpha times matmul of A and B, and then you add that to a scalar B times C, which is the shape of the output matrix. That's what a gem is. So it's a matmul, but with more. And then you have SGEM, so that's just general matmul, but with single precision. So it's explicitly single precision. You can do a half matmul, so like an FP16. You can do a double matmul. You typically don't, though. It's like FP64. But yeah, so generally speaking, GEM, SGEM, those are important. Then you have the CPU, which is also called the host, which runs functions, versus the GPU, which is called the device, and it runs kernels. And that's pretty much it. I hope that wasn't too hard. We're gonna dig into some kernels now. This part's gonna be a little bit. It's going to be a little bit intensive. You'll need to pay attention a little bit, but it's going to be fun. And I promise by the end, you're going to be really enlightened. You're going to, like, the first part of CUDA isn't actually that hard. We're just going to cover very, very basic kernels like vector addition. It's not going to be that bad at all. But just to introduce you to the philosophy and the whole design principles of like basic CUDA C programming. Okay. So now things are going to get a little bit more technical, but I figured we would kind of enter smoothly by just doing a fun and useful activity. So I pulled up a bunch of Wikipedia articles on various GPU architectures. Then we're going to dive into what does your GPU actually look like? Like what are the stats of that? So just like looking at these in general, let's, we're just looking for things that are like useful to know. Maybe some little history, kind of like the intro to GPU section that we previously did. So like Pascal was an older one that we used to have. There's a bunch of cool stuff about this. So like the 1080 and the 1070 were both based off Pascal. You have a bunch of information about where it's from, all of this. But what's really cool is if we scroll down, and you have all the technical details on these things. It's crazy how much Wikipedia has. But yeah, like we have these tables that will essentially tell us like which generations had what. So like, texture cache per SM, which we'll go into later. Dedicated shared memory per SM or streaming multiprocessor, L2 cache per chip, right? So you have all of these statistics and you can sort of compare these over time. So if we jump up to Ampere, which is actually what my GPU, my RTX 3070 is based off of, you scroll down and you get this same thing, right? So like L2 cache, and then L2 cache. So like 512 kilobytes, and then this one is 40 megabytes, right? So you get some interesting comparisons here, but yeah, this is just kind of the stuff you want to be looking at when it comes to like GPU specs, especially if you don't have one, right? You're going to find a lot of useful information here. Going to Ampere, like you have these A100s that have been used to train very big models, and it's Ampere 100, right? That's what it's called. So bunch of cool statistics. Which different precisions and data types do they support? So like the, like for example, Volta. Volta doesn't support BrainFloat 16, but A100 does support BrainFloat 16. So interesting stuff like that, which you can sort of just do a side comparison of. Ada Lovelace, this microarchitecture is what is used in the 40 series cards. So Ampere is like the 30 series. I believe if we actually go to Volta architecture, Volta microarchitecture, I believe this is used in the 20 series cards. The 20, it's going to be somewhere. Okay, maybe not. Anyways, you can find a bunch of cool statistics on these. Ada Lovelace is the 40 series cards. You get a bunch of info on that, like the L2 cache. It's again bigger. Instead of 40 megabytes from Ampere, it's 96, which is great. L1 cache is actually what matters more. So, you know, like 18 megabytes and so forth. And then Hopper, which is actually what the state-of-the-art GPUs right now, or close to state-of-the-art is. Well, the state-of-the-art is actually the Blackwell microarchitecture, but the Hopper is like also very like the second most recent one. And these are what the H100s are based on. These are used to train models like GPT-4, etc. So you find a bunch of statistics on those without actually going and using one. But if we actually want to print some stuff about our GPU, I'm just going to open a new terminal tab here. I'm going to drag this to the side. If we pop over to CUDA samples GitHub, this is going to print some stuff about your GPU. So if we take this and we just git clone it, it's going to take a second to do that, but we can scroll down in the meantime and we can see if you're on Linux, you would essentially cd into your whatever directory you desire and then make to actually make the binaries for running stuff with it. So if we print this out here, let me actually make this a bit bigger. We can cd into CUDA samples, and then inside of here we have samples. So we go into our sample directory as seen there. So cd into samples, and then we have a bunch of different ones. So there's things you can experiment with here. I don't know how easy these are to use. I haven't played with them yet, but we're going to cd into utilities, and notice how we have this device query thing here. So this is actually going to turn into a, we can't execute that yet, but if we make, then we actually can, and we can see a bunch of details about our GPU. So I recommend you to do this on your own system, but one CUDA capable device. So there's one GPU plugged into my motherboard. That GPU is the GeForce RTX 3070. The CUDA driver version is 12.5, as well as the runtime version, CUDA capability. So this is actually very important. This 8.6 here, it might be different. You might have the same GPU, you might not, but this 8.6 is actually very critical in how we know like what is supported on our GPU. So there might be some operations that work, and there might be some that aren't. So if I just drag this over to the side here, we don't need to worry about the rest of this as of right now. Maybe some of this later, but I'll just give you that information. So if we go to the CUDA capability, compute capability, what's it called? Sure, GeForce products. See, 8.6, just like that. I have to go back to the CUDA docs to actually get useful stuff about this. CUDA docs. So if we go to the CUDA C, we'll do CUDA C++. No, we're not going to do CUDA C++. We're going to go down to CUDA C. Let me just search this up. CUDA C programming guide. And inside of the CUDA C programming guide, yes, capability. So like this, for example, this is what I'm looking for. So thread block clusters in 2, and then you go to 2.2.1 is thread block clusters. You only get these if you have a compute capability 9.0 or higher. So the higher the compute capability, the better. So I cannot actually use thread block clusters on mine because the architecture doesn't support it. So these are critical things you're going to watch out for. And as you might actually be able to take advantage of some features that someone else can't. Like if you have an A100 and someone else has a V100, you can actually do things that they can't, and you can do things faster and more efficiently because of things that the architecture actually supports. So these are things you're going to watch out for. But anyways, with that being said, we can actually jump into some stuff about just essentially how does the CUDA architecture work? How do we write code, and how does that whole thing fit together? So now we can actually get really into what CUDA is doing and the whole hierarchy of that. So inside of here, I've pulled up chapter 5, writing your own kernels, and then CUDA basics, and then just the README and the IDXing or indexing file. So if you do, I believe, Control-Shift-V on this, or Control, I don't know what keybind it is, Control-Alt-V, Control-Shift-V, there we go, okay. And then we pull up this one on the side here, just for reference. Let's go through this sort of hand in hand. So I'm going to zoom in. We just printed this out. We just printed out device query, so we don't need to really cover that. But when it comes to sort of the more easy stuff to get a grasp on, I mean, we already went over this. So you have the host, which is the CPU and uses those RAM sticks on your motherboard. And then the device or the GPU uses the on-chip VRAM or video memory for desktop PCs. The surface level runtime typically goes, you define some input on the host or the CPU, which you then later want to run on the GPU, but first you have to actually define it on the whole system memory, and then you would copy that over to GPU memory. And then you would execute using that on GPU memory. You would launch a CUDA kernel, and that CUDA kernel would use that GPU memory and do stuff with it, and maybe do some useful computation. And then once that's done, you would ensure everything is all synchronized up, like nothing is still waiting. You would synchronize everything, and then you would transfer it back to CPU or the host so that you can print it out or do something useful with it. This is typically how the runtime goes, and you'll see this in our later chapters. The naming scheme, like how we actually what we actually name our pieces of data, is quite critical. So typically what you'll do is you go host or H and then underscore whatever the variable name is. So if it's like matrix A, you do H underscore matrix A. That means it's defined on the host. So you're going to do your malloc, your C malloc with this, and then you're going to do a CUDA mem copy, which we will see later in a second. And that's where you take this host and you essentially transfer it over to this other variable device. So device A, that's the GPU version of that. So it just exists on two different pieces of memory. And this is just for the set variable name A. Now we have this global, which you might have seen already. This is visible globally, and this is very broad. This is typically what a kernel is going to look like, unless you are calling, say, a separate kernel inside of another one. You would use, say, device. But in this example, we'll just stick with global. You can read a little bit more into this if you want, but we're going to use global for the most part. Device, we might see that later in the course. And then host is only going to run on CPU. So don't really worry about that. It's kind of just telling CUDA that you're going to run on the CPU, but you may not actually need to, because you're just going to use like the void instead of global void, right? Now this CUDA malloc term, memory allocation on the GPU VRAM. So that's the global memory on the GPU itself. So in this example, you do define a bunch of essentially arrays. So a pointer to a device, a float array, which is a pointer on the device, and it's for A. And then the same thing for B and C. Now you do CUDA malloc, meaning you allocate it on the GPU. So you do the memory address for that. So you put in the memory address for this thing. And then you go essentially whatever the, let's just say you have a size defined above, right? Like it's like a matrix, for example, and its size, it's like a square matrix size n by n, and all you're going to do is say, we want to allocate this much memory, this memory address, and that's just going to be a square matrix of, let's say, 128 times 128 times the size of whatever a float is. So in that case, I think it'll be 4, because a float is 4 bytes, where each byte is 8 bits. You have a floating point 32 number, do the math, and then you end up with the total amount of bytes that you will need to allocate for this device A matrix, and so on through B and C as well. Now, CUDA memcopy can copy from both device to host, host to device, or device to device for edge cases. So, you would slide a little term in here, CUDA memcopy host to device, or CUDA memcopy device to host, and that's how that would go. We're actually going to see usage of this in a second here, but understanding CUDA memcopy is just going to copy things around, and then CUDA free is obviously just going to free memory up on the device. So when you're done with something, or you don't need it anymore, just free that up. If it's just like an integer or whatever, like just a float, like a float a equals 1 or something, it's like you don't need to free that. But if it's a big array like this, you're going to need to free that. Now, the NVCC compiler is something we'll dig into maybe a little more in the future, but this is all you really need to know. So the host code is essentially these NVCC will compile all of this down into something that the GPU can actually execute, but the CPU is going to run it. So CPU is going to interpret what that is saying, and it's going to launch things and tell the GPU to do things. It's not just going to compile directly down to GPU, right? So when it needs to run on GPU, when it actually needs those instructions as to what to do, it's going to get compiled down to PTX, which is parallel thread execution instruction. So that's like the GPU equivalent of x86 or assembly, as it is for CPU or host. And then it's further going to compile that down to shader assembly, which we're not going to worry about. And this is stable across all of the different NVIDIA GPUs, so you don't need to worry about that. And then just in time is just a type of compilation. So CUDA hierarchy, yes, this is where things start to get a little bit intuitive. So imagine you have this giant 3D, like a cubic volume, and inside this volume is called a grid, right? Inside of this grid, you're going to have a bunch of these smaller cubic volumes. Those are called blocks, and those blocks are organized. You can make them whatever size you want. It's just like essentially, you can think of it like a prism or something. And you have a bunch of these organized in this giant 3D volume, which is the grid. And those individual blocks have things inside of them called threads. And those threads are going to do your math operations for you. So there's a lot to unpack here, but the individual threads can communicate inside of these blocks. And that's an important part to remember for later when we're optimizing stuff. But essentially, the reason why we have all these different pieces inside of this massive grid is so that we can get the parallelism of GPUs. So when you have this block doing this, doing this piece of the puzzle, and then this doing another piece of the puzzle, and they all kind of do their part. And at the end, if they all do their part successfully and they're all like synchronized and you make sure that everything works correctly, it's better than having a single CPU thread going through each individual thing in that problem and doing it one by one. Whereas you have like a bunch of these blocks or these threads inside of blocks, which are doing little independent operations. It's doing a smaller number of operations and they have a lower clock speed, but it's going to solve the problem much quicker because it's in parallel. So that's the whole idea here. Is you have this 3D volume called a grid. Inside of it, you have these other 3D sort of cubes or rectangles, whatever. And inside of those, you have threads, and those threads are going to also do things. So I need to breathe, but we'll go into some more technical terms in a second here. So going to these technical terms, we can see this grid dim exists here in our kernel, in our global kernel. We have a block IDX, which is these three, and block dim exists here and here and here and here and here, right? You have all of these. And then thread IDX. So this grid dim is the number of blocks in the grid at, say like grid dim dot x is going to be in this volumetric grid. What is the x dimension of that? So like, what is the length? And then grid dim dot y is going to be like, what is the height? And then maybe grid dim dot z is going to be the depth of that, right? And then the block IDX is going to, it's not actually about the block itself, but like, where is it? Where is the block within the grid? So the grid dim is like, how long is it? What is like the size of the grid itself that is run on the GPU? And then the block IDX is where each individual block is. So a block will have a block IDX in both the maybe X, Y, and Z dimension. And that'll be essentially its coordinates within that grid. And then the block dim is how big that block is. So grid fits a bunch of blocks into it. A block fits a bunch of threads into it. So the block dim is like, how big is this like smaller cube or this rectangular prism? And then the thread IDX is like, which thread is it within that block? So you can see how this like spatial hierarchy goes down. You have this 3D in the grid and then this 3D in the block. So it's like kind of 6D if you think about it that way. I don't want that to be intimidating though, like 6-dimensional. I don't want that to be intimidating. It's just kind of how it's an efficient way of running things in parallel and a way of visualizing it as like a software abstraction, right? That's the idea there. And then threads, like, I mean, I assume that this spatial idea sort of makes sense now. So now we can go into like why this works, and sort of like the more nitty-gritty of that. So each thread itself has local memory on it, so registers, which are very fast, and is private to that individual thread. So for example, if you wanted to add A and B, where it's like 1, 2, 3, and then all the way up to N, which is like length, and then 2, 4, 6, so like counting by ones, and then B is counting by twos. Each thread would do a single add. So like thread at index, say 0, would be like A at the thread index, right? And so the thread index itself tells you how to index into data. And then you can use that element that it gets like from its own index, from the thread index in that whole space, and you can actually do operations with that. So it's like a little hack of essentially both getting the right elements of data and adding and doing math operations on them at the same time. So we end up doing 1 plus 2, right, with a single thread, and it's accessing this index, the index, the data based on the thread's index, and it's adding them together. And then same thing for maybe thread 2, right? So that's just like kind of how the whole that's how the whole like indexing thing pans out. That's why it's so cool. And And then warps, and it's kind of interesting. If you look at this Wikipedia article, it's like warps, warps and weft, right? So you have these warps that are going through. So like these warps that are going through it, like up and down, and then the weft is like what the warps are weaving through. So they're like interlocked like this. And so you could sort of think of the warps as the as like what is going forward. So you could say like a warp is a group of threads. Warp and weft. The vertical warp yarns, plural, are held in stationary, and the horizontal weft is drawn through them. So you essentially have all these warps, like a bunch of threads. Essentially, it's a bunch of threads that are going in and out, and you can think of these threads as like doing their own math operations, and you have a bunch of them grouped together in a warp, right? That's the whole idea there. So, like I said in the Wikipedia article, warp is a set of yarns, or other things stretched in place on a loom where the weft is introduced during the weaving process, is regarded as the longitudinal shed in a finished fabric with two or more sets of elements. I don't expect you to understand that. It's just like the idea of threads are grouped into warps, and then the weft kind of like is that other perpendicular part. So warps are inside of blocks. So remember, we have the grids, and then blocks, and then threads. Inside of blocks, you have warps which take care of threads. So the blocks themselves aren't entirely handling the threads. It's actually the warps that are doing a lot of that work. So you typically organize a warp as like a group of threads. Like I believe the maximum is 32 threads. So a warp will handle 32 threads at once within a block. There is no way of getting around using warps. The warp scheduler makes the warps run. So you could think of like maybe the warp scheduler as as like the weft, right? So it's sort of like going through and making sure they don't get like disentangled and all of this, and ensuring that everything like works out properly. You can use whatever analogy works, but the warp scheduler ensures that the warps, which are a group of threads, run. And then you would have typically 4 warp schedulers per SM, and SM is like the smaller, like the streaming multiprocessor on chip. That's what those are. And you can have 4 warp schedulers per SM. So, do the math. That's 128 threads per SM. Then we have blocks. So blocks are interesting. Each block has shared memory, visible to all threads within that thread block. So all of these, like, thread 1 can see the same stuff that thread 32 can. They can, or even thread, like, I don't know, like 500 for that matter. They can all see the same data. So like within a warp, they can kind of see they can communicate faster, but within a block, they can still communicate very fast through this shared memory, which we call the L1 cache. And I'll dig into that in a second here when we go into the next section. But the L1 cache is very important for speed and optimizing kernels. So yeah, essentially just the same thing what I said. Shared memory is more efficient. It's faster. I think the maximum memory bandwidth you get with shared memory is like on the order of like 15 terabytes per second, and then global VRAM. So like when I do Nvidia SMI like this, you can see that I get like this. This is my this is actually going at like maybe 600 or 700 gigabytes a second. Shared memory is like 15 terabytes, so it's like really fast. And blocks use shared memory, which is on an individual SM, so the SM will handle that. And then grids. During a kernel execution, the threads within the blocks within the grid can access global memory. So that's just like universally applied. You can make things more advanced if you want to use threads, but it's going to default to using the GPU VRAM, that 8,192 megabytes that you just saw. It's going to contain a bunch of blocks. And the whole idea here is that with grids and blocks and threads is that you just have to worry like conceptually, what is it doing? You don't have to worry about how things are handled on the hardware, because this whole CUDA hierarchy is a software abstraction, right? So the hardware doesn't actually look like grids and blocks and threads. Like, it doesn't objectively look like that. It looks different and is compiled down to shader assembly, which doesn't actually look close to what this is right now, and that is actually run on the hardware, right? So there's various different levels here that is hard to sort of navigate through, but this is kind of why I'm showing you this stuff, is to give you a better grasp on that. So let's dig into what this IDXing script is actually doing. Now going into the actual CUDA indexing scheme like we saw with threads, except we're going on the level of grids, blocks, and threads, so everything. This script in particular is designed to print things, useful things out for us. So as we can see, ID, all these different block IDX, all of these, and I'm going to go into these in a second here, but essentially, like you have the if we go down, we have all these terms that we define, right? So block X, block Y, block Z, right? So B and then T is for threads. So what I particularly mean here is this is the block dim. So inside of the grid, you're going to have X, like the length of the X dimension is going to be 2, and then the height dimension is 3, and then the depth dimension Z is 4, right? So you're going to have this grid volume, and it's going to be of that shape. And then in each individual block inside of that grid, you're going to have these thread dims, which this is essentially the block dimension. This is the grid dimension, and this is the block dimension. So you're inside of each block, you're going to have essentially 4 long, 4 high, and 4 deep, right? So it's going to be this perfect cube essentially. And so we go down, we can calculate the total number of blocks per grid. So just essentially base times width times height, your classical formula, and same for threads per block. And we can get the total number in each of these, and then we can go ahead and print them out, right? So blocks per grid, threads per block, and then total number of threads. So we have a certain number of threads per block, and then if we times that by the number of blocks, we get the total number of threads. Now we have this other type down here called dim3, which is specific to CUDA, but this is essentially just the same thing as we saw before. So blocks per grid. So we have these grid dimensions, X, Y, and Z, and then same thing for threads within a block. So the block dimensions, meaning X, Y, and Z. And so we plug these into our kernel, which is called Who Am I? We have this global header, and we do these three symbols. I can't remember what these are called. It's like the less than or greater than symbol, and then you put the total number of blocks per grid, or the grid dimensions as the first parameter, and then the threads per block as the second. And then there's some other ones which you can do after, and you'll see those in a second. But these are all you have to worry about right now. So the grid dimensions and then the block dimensions. And then we CUDA device synchronize to ensure that everything is caught up and we can continue with whatever else we need to do. That would be used like practically. So now when we actually go up to here, this is where things get a little bit spatially intuitive, okay? I'm not gonna lie, this part might be like one of the hardest to grasp, but I'm gonna try my best to explain. So this block ID, what is this? Well, this is essentially, you can think of a bunch of apartments in an apartment complex, a bunch of floors within each apartment, and then a room on that floor, right? And so we're trying to find where we are within that apartment complex, right? So you can think of it as, your apartment is like a pane, right? It's like a singular pane in this volume. And so you, in this one, you in the apartment complex, you essentially do griddim.x, so this length part, and then the y component, and then times whatever z is. So the block idx.z is wherever the block position is. It's not like how big something is, it's the actual index or the position. So you have this pane, which is x times y, and then a depth, which is z. So it's like however big the pane is, and then go that deep. So it's like these panes that are like layered on top, going depth-wise, right? It's going deep. And so you have these panes that are like going that way. And then you have the block idx.y times griddim.x. So you can think of this as like the griddim is like this, like a floor, right? A floor within that apartment building, and the block idx.y is like which floor is it? So you have to go up that number of floors to get there. So it's like you essentially start from the bottom, you go like this many, and then this many, and then this many. It's like each of those is like a bunch of rooms that you go through to get to the next floor, right? And you eventually wrap up to this one, and then once you get to the actual x position, which is like the x is the length, you actually stop there. So it's like you've went through like a number of panes, like panes deep, rows high, which is the number of floors, and then you end up with like this final part, which is like, okay, well, what is the offset at this floor which my apartment is? And that's like right here. It's like depth, and then goes up, depth goes up, number of floors, and then like this is where I am, and that's how you find your block ID. Like which apartment complex or which apartment building are you in with that entire city or the apartment complex, right? In a 3D scenario. This block offset is essentially the number of, you take the total threads per block, so the block dimensions, how many threads is in each, this many threads in X, this many threads in Y, and then this many threads Z. You multiply all those together, you get the total threads per block, or say people per apartment, and then times our apartment number. So it's like the total number of threads up to your, like, essentially which thread index does your, like, how many threads are before your apartment, how many people are before your apartment, or apartment number. That's what we're saying here. So we calculated this block ID from before, and then we just find like that, but on the level of threads instead. And that's the block offset for calculating which thread we're at. And then we can continue that and use the same analogy that we used in block ID, except for thread offset. So it's like thread idx.x, block idx.x. It's like these are just like mapped essentially, except it's like a lower level in the hierarchy. It's down to threads instead of blocks, right? And so you can calculate which person you are within that individual apartment. Like if it's like a big apartment with like multiple floors and there's like multiple layers in it, you could use that, but you get the point. It's a 3D analogy, and we can find which person we are within that, or which thread essentially in that block it is. And so when you add the block offset, so the total number of threads leading up to your apartment plus which one you are within that apartment number, then you can actually find which thread you are in the entire grid, and then you can do stuff with that, right? And that's what we assign the global ID to, so global person ID in the entire apartment complex. And that's that. So there's a lot to unpack there. Feel free to rewatch some of this, or even try to visualize some of this on your own, maybe write it out. But when we actually go into our terminal here, and go into 5, and then CUDA basics, if we go nvcc-o, we go 0, 1, and then 0, 1 like this. It'll compile this binary, which we see here. We can just go ahead and execute that, and it'll show us precisely all of this that we just unpacked. So I mean, I cannot put all of this on the screen, but like for example, if we look at like how it counts upward, right? So you have all of your different dimensions here, and you can at the very end, I believe, it outputs the particular thread offset. So we notice that it's like 63 and then it jumps to 32, right? So it's like 32 and then it goes for 32 numbers. So if we go 30, I mean, it's technically like -1. But the best analogy you can use here is this is 32 threads, right? That is a warp. So when we talked about 32 threads in a warp, this is exactly what it looks like. So go back to here as well. You'll see it stops at exactly 32, and you'll go up from there. So it'll be like 0 to 31. So it's like 0, 1, 2, 3, 4. So it's like 1 to 31. It's 31 elements. And then you'll have the additional 0, which makes it 32. That's just the indexing scheme, right? And then when you go from 32 to 63, it's the same idea because you go from 0 to 63 instead of 1 to 64. So you do actually have 32 elements, 32 threads per warp in there. And then you can just see the global thread ID in the entire grid. So when we actually multiply these up, we have, in the grid, we have 2 times 3, which is 6, and then that times 4 is 24. 24 times 4 times 4, so that is 16, and then 16 times 4 is 64. So you can see 1536 in this entire thing, right? And so if we scroll like backwards, we can see 1535, it ends right there, and that is the final one. So like for example, block, this has 2 elements, so it's going to be 0 and 1. And then this is going to have 3 elements, so it's going to be 0, 1, 2. And then this is 4 elements, so it's going to be 0, 1, 2, 3. It's 4, right? And then the threads, because those each go up to 4, it's going to be 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3. And then you end up with essentially whatever that number is in the end. So you can see how this kind of all adds up and how this indexing scheme works and how we can use these to index pieces of data using like the actual thread and block indexes, and then do really fast parallel math with that. That's the whole idea here. Let's go ahead and jump into kernels now. Okay, so now we're going to do a little bit more math, and we're actually going to see what these kernels are actually doing and seeing how they work under the hood. So it's actually very simple. This is the most simple it gets, but essentially we're just going to do some vector addition as a practice. So adding these two together element wise, 1 plus 6, 2 plus 7, 3 plus 8, etc. And we get all this. Very, very simple and easy to understand. We have a CPU example here, which is obvious and easy to look at. We have a GPU example, which is actually a little weird. It's different than this because here we have a for loop, and here we have this I term, which is block IDX times block dim plus thread IDX. And I'm going to explain this in a second here, but this doesn't have a for loop. And essentially what this is doing, like I talked about before, is it's just unrolling this loop. So, CPU is going to like do this iteration and this one, and then this one, and then this one. The GPU is going to take all these individual iterations and distribute it across a bunch of blocks or CUDA cores, you could say. And it's going to parallelize that operation and make it really, really fast. So instead of doing separately like 10 million different operations, like in order, it's going to take roughly 10,000 time units. Say you had, 10,000 CUDA cores to split this across. It's like, well, that's actually a lot less now. That's only about 1,000 time steps you have to do. So that it's sped up an insane amount just by distributing it across. And that's theoretical, of course. But we initialize vectors. This should be very intuitive if you've written like any random stuff in random gens in C before. It's going to essentially take a random integer between 0 and rand max. So rand max is this. Very easy to understand. It's going to be a floating point number. And then a timing function just to measure execution time. Again, in this script, we are benchmarking. So perform warm-up runs, get things fired up, and then benchmark CPU to GPU and see how well it does. But this isn't really the important part here. What I wanted to mostly expand on is what things specifically here apply to CUDA, and what do you really need to understand? So we have this CUDA malloc, which is the same as malloc, except it's on GPU. So it's going to do that. It's going to allocate memory on the global DRAM or the VRAM on the GPU. And all this really has is a device pointer and a size. So we have this device A vector or array is declared here, which is a pointer. And then we set the size for that, right? And this is just the memory address of that. So we allocate device memory with CUDA malloc. And then when we actually want to move the stuff that we've created on the host, because remember, we initialize these vectors on a global or just a regular void CPU function. So we actually have to copy these over now. And how we do that is we just literally look at this. Destination, source, how big it is, and what kind of copy do we want to do. So destination is device, hence the D. The source is host. It's size big, like we declared here. And then CUDA mem copy host to device. So CPU is going to move to the GPU, and that's it. Very simple. We define this num blocks, which is a little bit different than what we did in this indexing thing, because it's not actually this dim3 type as we saw before. It still works though. The whole idea with this is that if instead of having like 2, 3, 4, if we just wanted it to be like length of, what is this? This is 24, 2 times 3 times 4 is 24. So you could essentially set this to 24 and then set these to 1. And just having a num blocks and then putting this in the kernel launch actually just converts the integer to like dim3, and then it's like num blocks and then 1 and 1. So it's just length only, and it still looks like volumetric, but it's just laid out linearly, so it ends up looking like a line, and CUDA interprets it as a line in hardware. Then you might ask, okay, well, how exactly do we calculate num blocks? Well, this is very interesting. So we have a bunch of things going on here, and this seems a little funny. So we have n plus block size minus 1. And I'm going to illustrate this out here. Now, just to clear up what the heck is this num blocks things means, I actually laid out some calculations for this. So block size is the number of threads inside of a block. It's the size of the block itself, which threads are going to fit into, right? So if we have, let's just say, instead of 10 million elements like we have up here, let's say we have 1024 elements, right? If we're trying to fit 1024 elements across 256 threads per block, that means we're probably going to want 4 blocks, right? It'll split it evenly because 256 times 4 is 1024. And so we have to actually calculate this manually. But we have to keep in mind that we are doing there are more things we have to keep track of in case, say, this number ends up being like 1025, right? So I actually wrote out a script that does this math perfectly for us. So let's first look at this. So you have this 1024 plus 2056. That's the length of the array plus the block size, right? Number of threads per block. Then you're going to do minus 1, and whatever that is, divide that by the block size, and then the compiler is automatically going to floor this answer. It's going to truncate those decimal places off. So if you get like 4.99 or whatever, it's going to take that 0.99 and just truncate it off. So you're going to end up with 4. So if we were to do, for example, like 1024 plus 256, well, what's that? 1000 plus 200 is 1200, and then 56 plus 24 is 80. So we get 1280. And if we divide this by 256, we end up getting around, what's the answer? Divided by 256, we get this number. But remember we have the 1 here, which I actually forgot for a second there. We have the 1, so it technically is 79. So you end up with this 0.99 part, and it ends up just being 4 because you truncate that off. However, if you end up having this as like 1025, then this number is actually going to end up as 1280 because you're just adding 1 back to, 1279, and you end up with 5. So in case you end up adding an extra element, you want to allocate space and resources for that, or else you will not get the answer that you want. So that's all this is doing up here. And we make sure, and this is just like a careful calculation to make sure that everything goes as we want. And so this is just a little script that I wrote up to test this, but I don't need that anymore. So going further, we essentially, in this kernel here, let me slide up. So in this kernel, we have just this X dimension laid out, right? So what you're doing is you have this block IDX, which is which block it is in that line of a grid, and then you're multiplying that by the size of the block. So how many threads are there per block times the number of blocks, and then plus whatever thread we're at, right? So this gives us the thread in that like line of a grid, right? And so we end up with whatever place we're at, and we use that thread index to then access elements in A and B and C, and then we just do an add operation. So whichever, it might be, in some cases, this might be like, 2.5 million, and in some cases it might be like 3, in which case they're going to be the same number, and then they're going to add, and we're going to get the answer that we expect. It just might not happen in the order that like a loop might, right? So instead of doing like the first index and the second index and the third, it's going to like scatter and distribute these, and it's just going to be fast, right? So that's what the whole idea is there. And if we go ahead and actually run this script, go 0, 0, and then we could just go 0, 0 vector add, and then enter. We'll just run this file. Performing one-up runs, benchmark in CPU, benchmark in GPU. So the CPU average time is about 0.14 milliseconds, which is really fast. However, the GPU average time is significantly less than that, about 143x speed up, almost 144. And the results match up when we compare them index-wise or element-wise. So we just verify the results here. We ensure that the absolute value of the difference between those two is greater than 1 times 10 to the negative 5, which is just a common verification thing. So you'll see that when we're comparing things, more like as we go more into CUDA, it's going to be this idea of you benchmark, you get like an average time across all the runs, and then you make sure that you're getting the correct results by having this tolerance factor. So sometimes this might be like super low, or it might be like super high, but that's typically how we'll do it. Then we have the second example of vector addition, which is very much the same. However, instead of just having this one-dimensional like x-axis thing where we have 1, 2, 3, 4 lines, we have a lot more. So going back to that example from indexing where we had 3 dimensions, if we actually apply this to vector addition, we get a noticeable slowdown. So the first thing you'll notice is that this has way more lines, but you're like, Elliot, certainly this is going to be faster, right? It uses up the whole space instead of just a little bit, right? Well, the issue with this is that CUDA is not really going to struggle with scheduling things and making them run fast and compiling down to something that's going to like really work at speed. It's more so like, what are the calculations that you're actually doing in a single thread, right? So this is what's going to happen in a thread. Notice how we do 1, 2, 3, 4, 5, 6 operations. So 3 adds, 3 multiplies, and 3 stores. So equal sign as well. And then this one, it's like you have a bunch of these comparisons, and it's just like a bunch of math. It's just like hard to read, right? And the point is, this does 1 one multiply, one store, or one multiply, two stores, and two adds, significantly less than this one. So the point is, only use the 3D aspect when you absolutely need to, when it is like dependent on your algorithm, and you don't need to, when you actually have something that's like spatially 3D, then you can use something like this because it might actually work a bit easier and you won't have to do all these calculations to end up laying out this 3D space into like this one-dimensional thing. And you have to worry about like things wrapping around and strides and all of this. So that's mainly the bottleneck there. And I just really did a comparison between the 3D and the 1D vector addition kernel. So we can go ahead and actually compile this here. So we notice that they're both a lot faster. However, the speed up CPU versus GPU 1D, like the GPU 1D is 106 times faster, but the 3D is only 102 times faster. So this is actually faster than the GPU 3D. Not by a crazy amount, but you know, by like 3-4% maybe. And if you scale up your numbers, it might grow, but you get the point. There's a lot of unnecessary calculations there, and it's just kind of simpler to go down this route with the 1D kernel. Now we dive into something a little bit more intuitive, algorithmically, called matrix multiplication. You might have already done this, in which case, you know, this might just be some simple review. Maybe you might want to skip ahead. It's up to you really, but I'm going to go over this because no matter what, because some people may not know, and sometimes it's good to get a little refresher on that. So we're essentially going to write the naive version of the matrix multiplication CUDA kernel, which is the slowest one, but it's the most basic and intuitive to understand. So a matrix looks like this. You have rows and you have columns, right? Let me actually zoom in a little more here. So rows and columns, for example, A is a 3x2 because it has 3 rows and 2 columns, right? So it's like 3 high and 2 long. It's like width by height, you could say, or height by width. And then we have B, which is a 2x4, so it's 2 rows and 4 columns, right? And the idea is that as long as these two inner numbers are the same, then it actually works. We're allowed to do that matrix multiplication. And you'll see why in a second here. And then these outer dimensions, these 3 and 4, would end up being the new size of the new output matrix C. So we have, 1, 2, 3, 4, 5, 6, and 7, 8, 9, 10, 11, 12, 13, 14. And what we do here is it's very simple. You essentially go 7 and 11. You take this, you have this this B, it's like this, and then A is like this. And so you take the 7 and 11 in B, and you rotate it, and you do a dot product with 1 and 2. So you take this 7 and the 11, you flip it over, and so the 7 is going to multiply with the 1, and then the 11 is going to multiply with the 2, right? So you're just like, it's like sideways. And then when you multiply 1 with the 7, you get 7, and 2 with 11 gets 22, and then you would add those together to get 29. And we can see that right here as the first element. So notice how it's like the first column and the first row aligned together, and so it's like they're like pointing at one spot. It's like the first row up here instead of down here. First row, and then the first column, and they meet together, and you get this top left corner thing. And that's where we end up with this 29 value. And then you essentially just do this for the rest of them. So you go 8 and 12, and then you flip that sideways, and it'll multiply with the 1 and the 2. And then you put that here. You have the second column and the first row. So it's going to meet in the second column and the first row, right? And then you just continue doing this for the rest of them until you end up with your final answer. So you're essentially just like flipping a column of B onto a row of A, and you're doing a dot product operation where each of like the element wise you're going to multiply, and then you reduce and you add all of them together and you squash it. and then you end up with this final matrix, which is of shape 3 by 4, so three rows, three rows high by 4 columns wide, and that's how you do a matmul. So when we go into typically when you're writing out, hard to understand algorithms like this, when you're trying to fit this all in your head, ideally you want to write it on the CPU first. If you just jump straight into the GPU and try to optimize, you're probably going to mess up. You're probably not going to get the answers you're looking for, and things are going to be weird. So you write out maybe even go back to Python and write this out in Python first so you can visualize it. And make sure that yours matches like PyTorch or NumPy or something. And then you write this out in C and you say, okay, well, how do we do a matmul on the CPU here? So you have your A and your B and your C matrix, and then your shapes M, K, N. So M is this how high A is. So M in this case would be 3, K would be 2, so 2 and 2, and then N would be 4, right? So you end up doing this like M, yeah, just like this, autocomplete. M times K, and then you multiply that with a K by N matrix, and you get an M by N matrix. I'll just space this out so it's easier to look at. And that's that. So when we look at our nested for loops here, we can see that we iterate over M, so that's that is the height of A, right? That's the number of rows we have. And then we're going to I++ that each time. And keep in mind, when this is laid out in memory, it's not actually going to be a matrix. It's going to be an array. So you're going to have like 1, 2, 3, 4, 5, 6 instead of 1, 2, like as an array, and then another array below it, and then another. It's not like that. It's just laid out at once. So you have to actually manually consider like the wrapping over. So you have to actually keep that in mind when you're writing these, and that's a tricky part too. So then you have J, which is going to iterate over N, which is N is the number of columns here. And then we plus that, like each iteration, we make this accumulation sum. So we're going to accumulate into the sum, right? Because you're essentially accumulating things as you're, like when we do the add operation and we have all these multiplies and we fuse and add them together, that's what this accumulation sum is for. And so when we iterate through K, which is K is the X dimension, you could say in A, or the number of columns, and then K in B is going to be the height or the number of rows, right? And so you iterate through that, and when you do your sum, you essentially add it, and you do essentially, this is where the dot product comes in, right? You do A, so that's I, whatever I is. Let's say I is like I is 0, right? So I is going to be whatever this is, right? It's going to be the first one times whatever K is, and K in this case is going to be, well, 2. So when you have 0, the 0th, when I is 0 and K is whatever number, it's still going to end up equaling 0. And so you have L afterwards, and that's going to be whichever spot at it, wherever it is through K, that's where it's going to end up at. So like the offset through the row. And it's going to multiply the same thing. It's going to do L. So L is where it's at through K, which is going to be the going up and down instead of left, right. It's going to be up and down. And then you have this N term, which we could say is maybe also 0 if you're just doing the first one here, like the top left corner. And then say J in this case is 0, so it's just going to end up hitting hitting the same value. So you end up just getting the first points, and then you multiply them together, and then you add that. You multiply them. You multiply the 1 and the 7 together in the first one, and then you end up hitting the second one, which is the 2 and the 11, and that gets summed up together. And you're doing this every single time this for loop, this second for loop triggers, right? So every time this goes through an iteration, you're hitting n, and n is just whichever value is essentially coming next, right? And so you're just getting this one, and then this one, and then this one, and then this one, and so on and so forth until the end. And then you end up just writing this out. So you essentially assign the value c to whatever that sum is so that you can compute the next dot product. So this is like very visual. I encourage you to, I mean, if this doesn't completely make sense, if you haven't like taken an introductory linear algebra course, I completely get it. You might want to just pass this through, language models, or look at some intuitive videos on the internet and just sort of understand what's going on here. Try to understand how things are wrapping around when they do like a stride or something. That's very important to pay attention to. Like this, like the k, when the k is wrapping, for example, k is here, and k is essentially this length. So it's going to be like whichever row you want to wrap around that entire row. So you want to go to the length of it and wrap, and then your offset is going to be that. And then same idea here, except instead of rows, it's going to be like column offset, right? And that's the whole idea there. And then we go into the GPU implementation, which is a little bit different, but we're essentially using, instead of just an I or an ID, a single IDX term, we use rows and columns. So in this grid, we have the block IDX.y times block dim.y. Block IDX is where the block is at in essentially where the block is vertically, and we're just getting essentially the vertical thread, like which thread do we want within considering like this vertical grid and all the blocks that we have, right? Going back to what I said before, and we do the same thing with X. So we have the thread in the vertical and the horizontal direction. And then we want to, this is actually very this is required. You need this if statement here, because if things go off track, or if you have like too many threads, then they might go and compute values that you don't want. Like it might go access other parts in memory. It's not restrained, right? So it's not going to stop when you think it should stop. You actually need to put careful restraints on it and say, okay, well, we want to stop it once the row gets to m, because there's no other values outside of that. And then same for column as well, right? So like when we go up here, we have m by n, right? So m is the m is this part, which is the where'd it go? Yes. M is rows, so rows is y, right? This y, this height part, and then n is that the width, the horizontal part, x, and so that's columns, which maps to x, right? And so you have to. This is just the kind of thing that you have to be careful with. CUDA handles this very well, but you just have to include this if statement, and then you essentially for each thread, because this is itself in the thread, you're going to just do essentially a dot product between elements, and you're going to do like essentially a row of A and a column of B, and this is going to be done per thread. So each different thread is going to have maybe a different row and a different column of B to compute. So you have this K term, which is from here, and you're cycling through that, and you just essentially apply the same wrapping, but instead of worrying about all of these nested for loops, you worry instead about the rows and columns. So these are your actual these are the way we index with threads, as I was talking about before. But yeah, this is I'm going to dig more into sort of the intuition behind this later in the course when we end up optimizing matrix multiplication. This is called a naive kernel. It's very limited. It doesn't have a ton of optimizations. It's not like it's not fast. it is like, it's like 100th the speed of what state of the art is. It's actually quite slow comparatively. And we're going to optimize this later on. And this is going to be the most intuitive thing you will probably learn in this entire course, is matrix multiplication in CUDA. So don't worry if this doesn't entirely click right now. Just kind of worry about where these threads are, how we're getting the row and column values, and then this wrapping that we have here, and then the offset part, right? Wrapping and offset. And yeah, that's pretty much all you have to worry about for now. And then we just do, the same route, perform warm-up runs, benchmark it across 20 benchmarks or across 20 runs, benchmark CPU versus GPU, and then return the average time in microseconds. So if I just open up a terminal here and go nvcc out to 2, and we go ahead and run that, performing warm-up runs. Okay, this is I'm actually made very large matrices. Maybe we should shrink these a little bit. We can go, let's see, maybe 256, 512, 256. Yeah, the CPU is not going to like that one. And so it's benchmarking CPU, and so that takes 89,000 microseconds, and this takes 88 microseconds. So we get, just like out of the box with these small matrices, we get a 1000x speed up with using CUDA. And that's that. So this is kind of how we test stuff. But yeah, now we're gonna go ahead and jump into like, how do you profile these? I know we haven't gone extensively into like how CUDA actually works under the hood completely. There's still more to do, but in a little bit we're going to hit up profiling. I would like to cover actually some more stuff before we do that. Let me close this out. We pop into the README here. Just close this and close this. I'm going to zoom out a little bit. Sure. So again, we have these dim 3 types, which I was talking about before. These should make sense already. These should not be like too hard to grasp. This is what it normally looks like, right? You put this in, like I said before, it's going to simplify to a dim 3. So this is going to look like a 16 by 1 by 1 tensor, you could say, and it's going to add that to the kernel launch configuration. This is the kernel launch configuration. There's more stuff we can add to it. Already covered this stuff already. And then you have more stuff you can add to it. So we have the grid dims in 1 to 3D, block dim in 1 to 3D, and then this NS. So this is the number of bytes in shared memory that is allocated per block for this call. So you're going to explicitly allocate memory for a block in shared memory, which is really fast. So typically you would omit this. However, if you have a specific production, like you're trying to deploy a CUDA kernel in production to run something really, really fast, you might actually want to capitalize off of this because it'll give you more explicit control over what happens, and you can measure performance a bit better, and you'll maybe get some little performance gains out of that. And then there's this S term, which is the stream it's in. And I'm going to cover streams actually in number 5, so don't worry about this too much, but streams are pretty cool. They let you do some interesting stuff. And then this, I didn't talk about this entirely too much. CUDA device synchronize and sync threads. So CUDA device synchronize ensures all the kernels or all of the threads for one problem are all of the different parallel computations for a problem are done before you begin the next. So when you launch a kernel, it's going to have a bunch of blocks in parallel and a bunch of threads in parallel run this massive problem, and they might not all finish at the same time. Like some of them, just like due to physics, they might like not finish at the exact same time, And so you have to explicitly synchronize them. You have to add this little barrier, essentially preventing a race condition. So if you have a bunch of threads, like for example, in this one, when you're bit shifting, when you're like moving this one over here and then this one over here and then this one over here, it's like, well, ideally you'd want to do this in a certain order and not like store something before it's not supposed to be stored. Like if, for example, if I do this one, and then this one is supposed to happen after, but it ends up doing this one first because we didn't synchronize properly, you'll end up with the wrong answer, right? So you have to purposely synchronize the thread so that all of them, regardless of like this one might be like way ahead, you have to wait for all the other ones to catch up in order for them to hit the same spot. So you say, okay, this one's done, but these ones aren't. We're going to wait for all of these to synchronize up together, and then we can continue the next step, right? That's what CUDA device synchronize will do. After you typically put this after launching a kernel, and then sync threads is put within a kernel for thread execution inside of it. So one is like out, like when you're trying to synchronize the whole grid, and then one is like synchronize all the threads within a warp. So as you might have been able to tell, I was a little bit unsure about that last answer, so I decided to look it up. And sync threads is actually on the level of thread blocks instead of warps. So you can do sync warps instead of sync threads. So I actually pop back to here and we go sync threads. You can actually do, if you want to do warps, you can do sync warps to sync all of the threads within a warp. And then this one will do that. It'll be the same thing, but a thread block instead. Threads within a warp. And then this is for an entire thread block. So just a piece of clarification there. One other cool thing I came across when studying CUDA is how you can actually add in explicit flags, and you can actually convert something like a log to logf using compiler flags. And I know that there's a little bit to unpack there, but if I just go back to this compilation here, actually no, we don't even use any of those math functions. But if I were to say do like log inside of a kernel, that would go slower than if I were to use logf. So logf is like a device operation, and log is a host operation, so designed to run on CPU cores, right? So we can actually do use fast math as a part of the compiler flags. So I can go use fast math like this. And of course we won't really see any difference, but yeah, like same 106x, same thing. But this will actually convert this to this in case you haven't done that yet on your own. This actually comes from the CUDA Math API reference manual. So if we look at, say, like some of the single precision intrinsics. Yeah, so single precision intrinsic functions that are supported only in device code, right? Notice how it has like cosf, exponentiate with base 10, f, exp, f, and then like, f add, round towards 0, right? All of these are designed to execute on device, and they have f at the end. But if you were to just do just cos, for example, from the math.h library in C, that wouldn't run as fast. So this is another little thing you could add to your kernels if you're trying to, say, do like softmax or something in a kernel, or if you're trying to maybe do like some digital signal processing, right? You can add these and get some benefits and performance-wise out of those. And same thing here, like if you wanted to do a fuse multiply add, this will like tell the actual, this will actually like pour this into the instructions where instead of doing like separate multiply and add operations, you're fusing them together. So you can do little tricks like this and just speed things up performance-wise. But yeah, now we can actually dive into profiling. So I actually forgot to do the tiled matrix multiplication by hand, so I figured I'll just squeeze this in now and let your mind sit on this for a little bit before we actually start using it and applying it. But before we had this idea of a matrix multiplication, which was you have like a matrix A, and can you see that? Maybe not. I'm going to move this down. Let me switch markers here actually. A matrix A. Yeah, with some numbers in it maybe. And a matrix B. And the whole idea here is we dot product this with this, this with this, this with this. We do the same thing and we bring it down here. Do, right? All the way till the end. That is one way to do matrix multiplication. However, you can actually make this more efficient by using something called tiling. So I'll provide some examples on this later in the course, but this is the idea here. You have these two matrices A and B. So I'm just gonna. You have to look at this a little bit differently, but this is what it looks like. So we have, say, let's just say this is A and this is B, right? And then you have this C matrix. And how do you compute like the first element, right? Well, you would typically take this row and then this column, and then you would put that there because that's where they intersect, right? But what you can do is you can actually take a chunk. You can take a chunk, like an actual square or rectangle of A. So like maybe this, I'll just put this into like separate pieces. Say this is like maybe a 9 by 9 matrix, right? And this is also a 9 by 9. So technically each of these is technically like a 3 by 3 tile or a matrix on its own, right? And so we're just splitting this up into tiles. And so what you can do here is you can, as I've lined out here, you can go 1 times, you could do a matrix here times the matrix there, like A and B respectively, like you do A times B, and then you add that to the matrix multiply of 2 and 2, A and B respectively, and then 3 and 3. You start with these, and then you add to these, and then you add to these. So it's like A1 times B1. You multiply those, and then you add it to A2 times B2, and then add that to A3 times B3, and then you end up with this C1 here, and that's the output. And this is exactly what I've written out in this sort of cube format. It's like you've laid out some matrix A right here, which is like a row, and then you've laid out some matrix B here, and you're doing this times this, and then add to this times this, and then add to this times this, and then you just end up with C1. And so what you can do with like the reason why this is so effective is because you can actually put these tiles and you can pop them over to a faster memory, like shared memory, and then they'll end up running like ridiculously fast, and you can end up doing these computations like way faster. So if you split it into little tiles and let each little like streaming multiprocessor on the chip actually take care of an individual tile or multiple tiles, then you can actually get a lot more useful. You get a lot higher compute throughput, you could say. But don't worry about this too extensively. This is just the intuition behind tiling, like the difference between this and the normal version we were doing, where we like take a whole row and then we take a whole column and then we dot product them together. This is different than that. So I just wanted to put that in your head for later so that it's not a complete surprise when we try to make this faster. Now we dig into how can we actually profile the performance metrics of our own kernels. So how do we optimize these, right? And we're going to use Nvidia Nsight Compute for this. If you're on Windows, you might not have this. It might look a bit different. I haven't tried it on Windows yet, but this is what we're going to use on Linux here. So this is kind of what it looks like at the end. You can see a bunch of details about things. It's very, very interesting. But we're going to dig into this in a second here. I'm just going to close these off, and we'll go ahead and get started. So let me close these here. We'll see in this number 5 kernels chapter in profiling, we have a bunch of files. So we're going to start off with this one, the NVTX matmul. So what the heck is NVTX? You guys already know what matrix multiplication is. I'm not going to go over that. NVTX is like the custom profiler for CUDA kernels, right? And what this allows you to do is it's actually quite straightforward. If you look at what's happening here, like it actually makes a lot of sense what's happening. So we're able to push this into a range, like essentially the timeline, push matrix multiplication, push memory allocation, right? So we're doing the this is the whole matrix multiplication thing from start to finish. We push things into a range, so memory allocation, and then we pop that out. We copy, pop that out, so it's like start and finish, and then we do our dim3s. We start kernel execution, and then it's going to stop that once we've launched the kernel, run it, and then synchronize all of our everything in our grid, and then copy back to host, right? So this is like very straightforward, literally all you need. So, I mean, keep in mind, like when we start this one, we have another one afterwards. So this one is only going to target the recent one that was put up, right? So it's not going to jump back to the first one that was ever pushed in. It's going to be like kind of like brackets, right? So you have the one layer of brackets on the outside and then one on the inside. It's like it kind of that's kind of the structure of this NVTX tool. So when we go ahead and NVCC this, we want to pass in the link NV tools extension. That's what NVTX stands for. So NVIDIA tools extension. We're going to compile that. We can go ahead and run this. It'll run as expected. Good. And then we can actually, if we pop back to this README file, we can do nsys profile stats equals true on the it's not mammal, it's 0, 0. But if we go ahead and run this, we will notice that there's a bunch of cool stats that pop up. Now, if you're running from a remote machine, you could use this. You could just look at this directly from the terminal. However, the Nvidia Nsight Compute app itself is actually a bit more informative than this. So what we can do is type your Windows key and go Windows and then type NCU and then press enter, and it should bring up Nsight Compute, and it popped up on my second monitor. I just brought it over here, but this is what it should look like. And what you can do from here is I'm just going to put this on the second one and then drag the report nsys rep file. So not the SQLite. SQLite is for a different thing, but we drag this into the sidebar here. Now it's in. We can see it at the top. And now there's a bunch of interesting things in here that we can look at. So this text might be a little small if you're on a phone, but just bear with me here. So we have a bunch of stuff on threads. NVTX, what's happening sequentially here. We can actually zoom in and see, the memory copy, kernel execution takes about 2 milliseconds, and we can see everything, right? So all these are actually pushed into the range, and we can see what's happening. And then of course the memory allocation takes a while, and then the matrix multiplication from start to finish, like we highlighted in the code. So that's what NVTX does. You can push things into a range, and you can see how long it actually takes. You can see like when it's happening on the timeline, and you can look more in more detail as to like what's happening there, right? So, anyways, if we go to the CUDA hardware at the top here, we can see it consists of kernels and memory. So there's like copying, so CUDA mem copy, and then there's the matrix mul kernel that we can see here. And if we click on this, we go show in events view. We can click on this down here, zoom to selected on timeline. We can right click, we can go profile kernel. And there's a bunch of interesting things here. And this might be a little overwhelming at first, but there's common, filter, metrics, PM sampling, warp sampling, other. So we're just going to use PM sampling right now. PM sampling is performance metric sampling. So it's going to give us very detailed metrics about things, and we'll be able to optimize from that. So it's going to use this binary 00 file that we made before during compilation. And it's going to bring up this new menu here, which is different than the timeline one. So this is timeline view, and then this is different. So in here, we can see all of our kernels at the top. So in case we were like maybe profiling two different matrix multiplication kernels, they might both show up here, like the runtime, the lifetime of our program. That's what would pop up here, and all the kernels inside of that. So if we go to say summary, there's some interesting stuff here. Maybe we don't care about this too much. There's details. So you have throughput. So overview of throughput for compute and memory resources. PM sampling. So performance metrics. We can bring this down, and we can see things like SM throughput, pipe throughput, a bunch of metrics I don't even understand yet. But we have things like cache hit rate, which is really useful. But if we go to like speed of light throughput, for example, this is for the memory resources. We have the compute throughput as a percent, so that's at about 97%, and then memory is also at about 97%. So, we get to see cool things like this, and it'll make more sense in a second here. We go down to memory workload analysis. We can see memory throughput in it, like very detailed memory, memory metrics. So gigabytes per second, how much are we able to transfer back and forth, right? Bytes, DRAM bytes per second. So that GPU VRAM, how fast are we accessing that? And that speed is about 41 gigabytes per second, which is not super high. And then we have like L1 hit rates, L2 hit rates, all this, and we can see a memory chart here. There's just like a whole bunch of metrics that we get access to. And so if we can pay attention to like this number 41. We'll keep this number in our head for now. There's also a source too. So you can look at the actual assembly instructions and see how many registers is it taken up, a bunch of very low level stuff, which I'm not going to dig into right now. But yeah, there's so many settings to dig through. Anyways, we're going to keep this number 41 in our head. Now we close this out. We'll just put on the side for now. We have some other scripts as well. So I have a naive mammal. So this is the one that we wrote previously. This is the exact same, just a direct copy and paste. And then we have a tiled mammal, which I'm going to cover a little bit later. It's a bit more advanced, but we're going to compare the performance metrics of the naive versus the tiled mammal. So if we go ahead and pop into here, we go NVCC 01 and then 01, and we link NV pools. Run successfully, and we can go nsys profile and then put in 01 right there. And I'm going to go ahead and drag this, so we pop up another one. I'm going to go drag this into Nsight compute. And if we check out our CUDA hardware, go to kernels, matrix multiply. This is the naive version, remember. Show in events view, zoom to selected, profile. We run the PM sampling again. It's going to run that, and then we take a look at our new stats. This is the exact same thing without NVTX, but just for context, details, memory workload. So we get 30, 37. It's pretty close to what we had before, right? Maybe a little bit lower. But when we compile the tiled matmul, it works as expected and says profile. We're going to get a number 3 here. I'm going to go ahead and drag this into Nsight Compute. We open this up, pop over to our kernels, matrix multiply optimized, show in events, zoom to selected on timeline so we can see the length of this. By the way, this is how long it takes. It's going to go from 430 milliseconds, 430.24 milliseconds, all the way to 431.57 milliseconds. So that's actually how long it takes, and you can sort of see the length of the timeline there. Profile, PM sampling, and give it a second. We open this up in details, and we can see in memory workload analysis, this is significantly higher than it was before. So these are the types of things you want to look out for. When you see your memory throughput drop after you change something, it's like, ugh, maybe we shouldn't do that. From here it went from the naive, it was at 37, and here it's at 60, right? So that's making a better use of memory. And we'll see more optimizations later on, especially in this faster matmul chapter, as to how we can seriously get this number up. But yeah, this is how you profile. There's a bunch of cool things you want to look out for here. It really depends on which algorithm you're working with. With matrix multiplication, there's some more fine-grained optimizations that are just proven to work. So we can just run those and kind of compare the difference. But you have all the resources at your hand here. There's tons of things that you can use and learn from. So yeah, this is how you profile CUDA kernels using Nvidia Nsight Compute. We have a README file here with just pretty much everything we went over. So the nsys profile command. You can profile Python as well. So nsys profile, and then you can, if you have an MLP script in Python, you can profile that. Funny enough. And it'll just use the whatever NVIDIA libraries that Python file is using. Then we have you can do some stuff over the command line like this. So NCU kernel name, and you can do stuff over the command line. But yeah, there's a bunch of useful tools here. So this might be updated later on. It's not in the best format yet, so this might look a bit different when you see it. But these are kind of the main ideas. And then just to I guess leave it off on an end note, CUPTI, or CUDA Profiling Tools Interface, the PTI at the end. This is for creating your own custom profiling and tracing tools that target specific CUDA applications. So you can design your own profiling tools with this. If that's something that catches your interest, you might want to look more into it. So I'll leave this here, but that's how you profile CUDA kernels. Next up, we have this thing called an atomic operation. And atomic operations are used in very specific cases, so I'm going to try to cover these as best I can. By atomic, we mean the indivisibility concept in physics, where a thing cannot be broken down further, right? So you have an atom, it's like, oh, I mean, technically there are quarks and stuff, but you don't worry about those. It's just like the indivisibility concept of this thing, you cannot cut it in half, right? There are parts maybe inside of it that make it up, but you cannot cut it in half. And that's what this atomic operation is, and it operates as a software abstraction for us. So the hardware and the CUDA compiler take care of all of this for us. Essentially, an atomic operation ensures that a particular operation on a memory location is completed entirely by one thread before another thread can access or modify the same memory location. This prevents race conditions. So remember before when we were talking about how there are like multiple threads that like one might end up being faster and hit the goal before this one, and they sort of need to like not modify each other's. They need to like not mess with each other's things. So that's what this idea is referring to. So cannot access or modify the same memory location of another thread. It's a very key point, right? And we're going to see a very crystal clear example of this in a second. We might lose some speed. So if we limit the amount of work done on a single piece of memory per unit time throughput an atomic operation, we're going to lose some speed from that, right? If we're locking things down and limiting how fast the program can finish by just having everything like not wait for everything else, then it just finishes faster, right? So when we use atomics, things will slow down, but it is guaranteed to be memory safe. And that's ultimately what you might care about in some cases. It might be better to get the memory safe aspect instead of the performance gain. So there's a bunch of different atomic operations that we have. I'm just going to make this a bit easier to see. You have atomic add. So essentially what this is, you have an int, a pointer to an int, some memory address, and you have a value. And all you do is adds value to the value at address. So when we pass in, like, for example, say the number 4, and then we get the memory address to that, which is some hex code. We put that hex code in here, and then we put a val, let's say like 2. And so what that'll do is it'll say, okay, well, we have memory address. Let's get the value for that memory address, which is 4, and then we're going to add the value to that. So it's just like this memory address stays the same. There's nothing new being created. It's just you're taking this value and you're adding it on top. And that's kind of the whole philosophy of everything in here. So substitution, exchange, and the return value will always be the old value. So when we do like atomic add, and then we say like put int equals atomic add or of whatever's in here, it's going to return the old value of whatever this was. So it's going to essentially return the value at address, right? So we can sort of compare and contrast. It lets us do that. Or you could just not like return anything. That's fine. You could just, if you just want to add val to that, to the value, then to the address value, then you can just do that. But these are all the operations that come with atomic. These are all the atomic operations. There's also floating point atomic operations. So you can think of atomics as like a very fast hardware mutual exclusion operation. And I'll dig into mutexes in a second here, but essentially how this goes is you lock down a memory location, you set the old value, the returned value equal to like dereferencing that memory location. So like the hex code, and then you get the value for that. You set this old value that you're going to return equal to that, that dereference value. And then we set the dereferenced memory location, so that value that goes with that hex code, to the old value plus the increment, which is val, right? This is int val. And then we unlock memory location, we return it. So it's just like during this part where we're incrementing and we're storing the old value, we're going to lock it down. So nothing else can interfere with that. It's just this has to complete, this is priority. And that priority will exist through however many cores threads we have, right? So that way they can't interfere with each other. So one has to finish before another one accesses it. And then we just return that, right? So in terms of mutual exclusion, there's a nice YouTube link on here that I found, which was very good. Mutual is like a shared relationship between entities. So all of us threads, we're going to, the act of keeping something out or preventing access. So we're going to exclude everyone else from accessing each other's thing. We're going to let each other finish, right? That's mutual exclusion. And this applies to atomics, right? So you don't have multiple threads accessing the same thing at once. And there's like an intuitive example here of like what this might look at a lower level, what this is actually doing. So if we go over to our atomic add over here, if I MVCC compile this, we'll see, like, first of all, we import whatever we need to, the CUDA runtime.h. We have a number of threads, so 1,000 threads per block, and then 1,000 blocks in the grid. These are macros that we define. So if there are 1,000 blocks with each 1,000 threads inside of them, then we're going to have a total of 1,000,000 threads, right? And then we have two kernels here. So one is going to increment a counter non-atomically. So it's going to take in a counter. It's going to store that old value as the dereferenced counter, because this is a pointer, right? We're going to set the new value to whatever this is, whatever that actual integer value is, plus 1. We're just going to increment by 1. And then we're going to update counter, right? And then there's an atomic version of this, which does the same thing, except it locks instead. So this part here, this is actually like you're essentially adding not locked, and this is not unlocked, right? So we're supposed to lock here and then unlock there and return whatever that is. So I think that's correct. Yes. So we go down and everything here is fairly intuitive. We have our num blocks and our num threads, and the idea is we're gonna have 1,000,000 threads that are each trying to update this same counter, because we pass this counter. This is a single variable or a single pointer that we pass in, and all of these threads have to modify the same thing, right? So when we actually run this, you're gonna see non-atomic counter value is 41. So this means that all of these threads are attacking the same memory address, and they're all performing modifications on it at the same time. But atomic, it's going to take a little while longer. It might take 1,000,000 operations instead of 41, but it's going to ensure that we get through this properly. So it's going to say, okay, well, this thread wants to access it, so we need to lock down only this thread can access this value. And then all the other threads, instead of racing to it, they're going to just wait, because it's an atomic operation, right? And so this one gets to complete first, and then maybe this guy, and then this guy, and then this guy, and they all sort of complete. And then you end up with the actual true answer, which is 1,000,000, right? Because it increments from 0. So that's pretty much atomics. They're pretty cool. Maybe you can think of a way that you could use them right now. I don't know. But that's just something that's super important to cover, because that's one of the risks with kernels, is that you have a bunch of different threads accessing the same thing and making changes that maybe you don't want to it, and not like getting any errors or warnings about it, right? That's a danger that you have. So atomics help secure that and lock that down. So now we go into CUDA streams. And CUDA streams are one of the most useful things for performance optimization and maybe even large systems, right? So this especially works in large systems, and you're going to see why in a second here. So you can think of the intuition here. So you can think of streams as river streams, where the direction of operations flows only forward in time. So you have this timeline, and the idea is normally you would copy some data over from host to device, and then you would do something with that data, like a kernel launch, and then you would copy that back from device to host to do something useful with it. And what you have here is you have these little dependencies where it's like you have to wait for the data to come in before you actually start the kernel launch. But wouldn't you always want to be running kernels, and wouldn't you always want to be doing computation? Well, streams actually solves that issue for us. Instead of just having one little timeline, you can have an extra layer underneath it too, and even more. You can have as many layers as you want. And the whole idea is you can copy something over, do a kernel launch, and then during that kernel launch, like when that stuff gets copied over, you can start copying the next stuff over in a separate stream. right? So you'll be doing some computation while you're copying stuff over, and then when this stuff is copied over, you can do the next kernel. So it'll look like sort of a staircase. And I have an example of this in the NVIDIA documentation here, the NVIDIA streams and concurrency slides. And it essentially looks like this. So you have this thing called CUDA memcopy async, which is asynchronous. And normally, if you're doing a serial program, which is what we've worked with so far, you'd be going in this fashion, where you're not always doing. You'd be like copy something over, do something with it, copy it back, copy something over, do something with it back, and then in this example, you'd like copy a bunch of stuff over, host to device, and then you do maybe it's better illustrated in this example is like you copy some stuff over, you do like say like 3 kernels in a row, and then whilst a kernel is running, you're always copying new stuff over. So you're always doing work across all the streams, right? And this is super useful, especially when you have something like when you have things like training a massive language model, right? When you have this data loader that is like constantly loading big chunks of text in, you don't want to be waiting for that. You don't want to just do your training forward and backward pass and then wait for it again. You want it to be loaded in while you're doing your forward and backward pass. Like you want it to be ready for you. So that way you can just do it again. So it's like nonstop forward, backward, right? Never want to stop doing that. And that will greatly increase performance. And so this is where CUDA streams come in, right? So this whole idea that I'm talking about with like fetching data before you actually need it, like it's literally called prefetching, a software abstraction called prefetching. So you move data around before it is needed, and this hides the latency of moving data around, like CUDA memcopy, right? So we have this kernel launch configuration. You've seen this before. We have a grid size, we have a block size, right? And then there were 2 other things that I talked about, which are here. Now this is the number of bytes in shared memory, right? So you're doing stuff with shared memory, which don't even worry about that right now. And then there's this other one, S, which is the associated stream, right? So you can actually put a specific kernel on a stream as we showed in here, right? You can have, these are all the different streams, stream 1, stream 2, stream 3, stream 4. So you have, you launch this one on stream 1 and etc., right? So that's the whole idea there. And this is just a super easy way to interface with the streams when we do our kernel launches. So there's multiple things that come in here when we're dealing with streams. So you get this thing of priorities. So create streams with different priorities. And if we go into, I don't know if it's in this one, maybe this script, if we look at the get priority range here, we can see this takes in a pointer to a least priority int, just a variable, and then a greatest priority int. And so it's like, this is the least priority. We're gonna plug this in here. And then we have a greatest priority, which we plug in here, right? And that's our range. And so we can feed these in so that CUDA will actually manage which ones get more priority over others. So if you want to load in a bunch of data first, and that's your initial priority, you want to like get that part done as fast as possible, you can actually prioritize that with like least and greatest priority, right? And then we go a little bit further down, and we have some examples here. So let me just touch on the basics here. So there's some stuff that you may have not seen before, which I've probably used earlier, but I did mention it. These are macros. These are the error checking macros that we have to essentially make sure that operations go through successfully. So when we do like a CUDA malloc, we want to make sure that went successfully, right? And this will return a CUDA error type, meaning either success or error, like fail, right? Just indicating whether that went through or not. So that's what that is. And then if we scroll down a little bit more and see where the actual streams are happening, keep in mind up here, we use this CUDA stream type, right? So it's a CUDA stream type, and we define two streams with that, stream 1 and 2. We create the stream, so we actually have to have custom handlers for this to say like, okay, you made this, you defined it. It's like now you have to actually create the thing. It's a weird context thing Nvidia has, but it ensures everything is safe and handled properly by the compiler. So we get this other term, CUDA mem copy async, and this essentially just allows us to have like these asynchronous copies. I mean, when you have these ordered, like if you go CUDA mem copy async on stream 1, and then later on you have like a kernel launch like right underneath it, it'll actually go in that order. So it won't try to do like the kernel launch before because it's asynchronous. It'll just be asynchronous, meaning in the context of streams. So you can have things sort of happening, I guess, concurrently. But it'll still follow that sequential order within that stream as long as you assign them to the same one. So then we have our threads per block and blocks per grid configuration. We launch this on stream 1, and we have this B array on stream 2, and we can do stuff with that as well. So, and then notice how we have the comment copy inputs to the device asynchronously. So this is just a little cheat where instead of copying A from hosted device, then copying B from hosted device sequentially, you do them at the same time. So A gets copied and B gets copied at the same time, and then you don't have this extra barrier here where like no work is being done. You can just get right to kernel computation, right? So we see that here. We have a stream 1 and stream 2, and this is all done on stream 1. So all this memory is going to be shared, and we go down further to this. We copy C back asynchronously, but there's only one, so it doesn't really matter which stream that's on. We just do async because why not? And then the stream synchronize. So we're going to ensure that all of the streams are then caught up, and then we can do something with that, right? So we're going to free the device A, B, C, and then destroy both of the streams, and then it's done. So if I go ahead and actually compile and run this, test passed, and we got everything correctly, and we did this vector addition. So it's just kind of all we really did here was just this is where the magic happens. Instead of loading A and then B, we load A and B at the same time, and then we go into what's it called? Advanced. So I'm gonna lower this a little bit so you can see. So when we go into advanced streams, things get a little weirder, but it's not too crazy. So there's a few things that I want to introduce here. We have pinned memory. So it's essentially saying on the CPU global DRAM, it's gonna preserve this piece of memory. We're gonna pin it using CUDA malloc host. Instead of just saying, this is a part of CUDA, it's reserved for the GPU to use later. So we're not going to modify that. We're not going to let the operating system or anything play with this. We're just going to pin it. Nothing can touch it. And then we're going to drag that over somewhere else for later. And we're just going to reserve that, right? So we're going to use this. We're going to need this for later, so don't play with it, is a good way to think about this. Events are a critical part of using streams. So we can measure kernel execution time, given this example here. So we have an event type, start and stop. So these don't actually time anything, but they're part of the input to these event record functions. So we go ahead and create these with the memory addresses of start and stop, and then we can plug in whatever stream, for example, just stream or stream 1 or stream 2. We do an event record. We launch our kernel on this stream, and then we do another event record in this stream, and we can take these values, start and stop, and they might carry some metadata. I don't know exactly how CUDA handles this, but for start and stop, we can synchronize everything, and then we can plug it into CUDA event elapsed time, which takes this milliseconds float which is going to be in milliseconds, and then you have your start and stop. And that's going to tell you how long your kernel took to run, right? So instead of launching it instead of going into an NCU profiler, you can just do this instead if you want to. And this will not have any computational overhead, or it's very minimal. So this can be run in like production environments. It's not really going to cost you anything. And then you have the synchronization between streams. So essentially, these events will synchronize, they will be placed in individual streams. So instead of the whole device or across all the streams, it's just one specific stream, right? That's the whole idea with these. And then, of course, you can overlap computation, data transfer with the prefetching idea, which we talked about before, which I believe, prefetching, yes. So events are great for that. And then we have callbacks, which are used slightly differently. You can essentially set up a pipeline where the completion of one operation on the GPU triggers the start of another on the CPU. So this is going to have some more overhead, but if you want to log when something happens, on your GPU, then you can use a callback. So in this context, we have a kernel, and then we have say some stream like stream 1, and then we place this callback right after the kernel. So in the timeline, it's going to show up as kernel and CUDA stream add callback, just as the way they are from like top to bottom in the code. And if they're in the same stream, and we put this callback in, and that's essentially going to say when this finishes, we're going to call this function, and it's just going to print GPU operation completed, right? So that's like one use case of callbacks. You might not use them all the time. You're probably going to use events more if you're really trying to get those optimizations out. But let's go ahead and look at the advanced section here. So we have kernel 1, which is going to multiply by 2, and we have kernel 2, which is going to add 1. All right, very simple operations. We have our callback here. Stream callback operation completed. Just print out when something happened, right? And then just sort of like flowing from top to bottom here, we do our CUDA stream types. We just declare some streams. We have our CUDA event type. We're just going to initialize an event. We can print out whatever that event is. I was testing earlier, so that's why this is still here. We do our CUDA malloc host for that pinned memory. We CUDA malloc our device data. We do our greatest and least priorities, like I was talking about before. We actually create the event itself using this previous event type that we initialized here. And then we do our, CUDA memcopy async. We launch a kernel, and then this is where things start to get a little tricky, and I'll do my best to explain. So when we do CUDA event record, that's going to place a little marker, like a little tick right in that stream. So we have the stream 1 here. This is on stream 1, this is on stream 1, this is on stream 1. So you're going to do your copy from host to device, and then you're going to do the kernel, and then you're going to put a little tick mark right here. And what that says is we might want to do something when this gets reached. So notice how this is right below our kernel. So when the kernel is finished, when it is done, this is going to trigger, right? And then we have this stream wait event as a little dependency. So it's essentially going to wait for everything up to stream 1 to finish, and then it's going to begin on stream 2. So stream 2 has to actually wait for this to happen. Notice how we pass in a stream, which is stream 2. So stream 2 will start doing its things like kernel execution and the callback. But we have to wait for, where did it go? We have to wait for this event to trigger first. And that's essentially all this is it just waits for it, and then it begins on stream 2 when all of these previous ones are completed, right? Or at least everything else in stream 1, so these two. So then stream 2 comes along after this is done, after we've actually done our kernel execution, and then stream 2 is going to run this second kernel. So it's just kind of ordered in that way. So you have the async CUDA memcopy, kernel 1, and then it's going to wait for that to finish and then drop down in stream 2. It's going to start the second kernel execution. And then when this is done, so once we complete this point, this is like another marker in the timeline. It's going to wait for all that to complete, and then it's going to say, okay, awesome, we can now do a callback. And then it's going to go up to this function here, and it's going to run that. So that's just kind of like stepping through one by one what is happening there. And then we'll just copy back to host with CUDA memcopy async. And then to finalize, we always want to synchronize our streams. So we have all these streams that are happening. We've just added another layer of complexity. We need to synchronize those up too, right? So there's the whole device synchronize, which is like you synchronize all the threads in the device. And then there's this one, which is on the level of stream. So you have like maybe stream 1, 2, 3, 4, and you like wait for all of them to like finish before you continue, right? You wait for all of them to catch up by adding a little barrier blocking. And that's what's happening here. And then we just destroy all of these. We just essentially remove all these contexts and then we're good to go. So that's how stream work. That's how this advanced thing works under the hood. If I go ahead and run this, so we notice how when we are printing out, where did it go? When we're printing out the event is just a pointer. So it's just like a memory address thing. And then we got our operation completed. So that's when we do this callback, and then we end up with the test passed afterwards. So, just referencing back to that NVIDIA diagram with all the different streams like that, that's essentially what you care about, right? So I hope the last part wasn't too conceptually hard for you. That's typically where people will sort of break down and question a lot of things. It was probably hard, but anyways, I'm glad you made it through. Feel free to rewatch some parts. That is one of the most challenging parts of the course. There's a lot to unpack. It's very spatially intuitive, but this part is supposed to not be very spatially intuitive. It is supposed to be just like textbook examples. This is how you navigate things. It's not supposed to be very hard mathematically, spatially, anything. So this chapter is on the CUDA API. So this is chapter 6, CUDA APIs. We have a few to go through, cuBLAS, cuDNN, etc. But I want you to navigate over to docs.nvidia.com/CUDA. So here we have a lot of resources. We have a lot of cool things to look at. And I just kind of want to point this out, not that it's specific to the CUDA API section, but because there's a lot of useful things here. So you have your installation guides for like Windows and Linux, right? Like this is just like everything you need to get started. Programming guide, best practices, all the different, Maxwell, Pascal, Volta, Turing, Ampere, Hopper, Ada, Maxwell, all these different compatibility guides and tuning guides for different architectures. And then you have like your PTX, which is the assembly instructions for CUDA. That's what it compiles down to. And then just like API references, miscellaneous stuff, and tools like NBCC, GDB for CUDA. So when we covered GDB earlier in the C++ review section, this is the equivalent for CUDA. So when you're debugging CUDA programs, you'd use that. And then there's like Insight Compute, which we used earlier. And that's, just a lot of very informative tools here. What we mostly care about is the CUDA API references. So in here, we have Runtime API, Driver API, Math API. You can go through those if you want. But mainly what I'm going to cover is cuBLAS and cuDNN, which is over here. If you go to docs.nvidia.com/deeplearning/cuDNN, you can find this. And these are the main ones which I expect to cover in this section. So you can think of these like cuBLAS and cuDNN as you're not writing things out manually. You're not writing out your own kernels. It's the whole idea here is you have like this black box function that you call, or like it's binding to a shared object file, like an SO, and it's opaque. So they use this word called an opaque struct type. And what that is you're just calling something that is compiled down to run on the hardware. You do not get to see it because it's, encoded in some binary format that you can't really read as a human. And so you have to refer to these opaque struct types to be able to call those. These are highly optimized. So like the state-of-the-art algorithms in the world for running, deep learning algorithms. These are the fastest ones. Sometimes you might get something faster depending on the use case, but we'll generally assume that the CUDA API provides the fastest functions, generally speaking. So when you're trying to figure out how to get the fastest possible inference to work on your GPU cluster, you might want to, use something like CUDA API, and then going through, just going through and researching and figuring out how to get it done by going to like Google search, Perplexity, ChatGPT, and maybe Anthropic models, and then keyword searching in the Nvidia docs, like just a control F like that. But the CUDA API is going to give you the fastest stuff, right? You may have seen this before, how we did these like error checks. And these essentially just say like when you call a function and say like kublas, you're going to check if that returned an error or not. And if it does, you're going to print the error and the line it was at, right? So these are just custom ways of printing out errors and when things don't go according to plan. So I have these both for kublas and cuDNN. So it just checks the function, make sure it went through properly. Now, kublas is short for CUDA. So the CU is for CUDA Basic Linear Algebra Subroutines or Subsystems. I can't remember which one, but it's for linear algebra stuff like matrix multiplication, right? And SGEM, which is short for Single Precision General Matrix Multiplication. And that's like pretty much what this whole like README file is about. I'm kind of like reciting it as we go down, but there are resources on this like proper error checking, library samples. If we were to go to this, there's like a library samples where you can test out each of these. But the whole idea with kublas and how it's important to deep learning is in something like the transformer or an MLP in the transformer itself. You're going to use this algorithm called matrix multiplication. And when you want the MLP to run really fast, or you want this language model to have really, really fast inference time, you want the algorithms to not really have bottlenecks, right? You want them to run as fast as possible on the hardware. And so using the subroutines in kublas, you can actually get that. There are other ways where you can like combine and mix things together, but that's more advanced. For now, we're just assume that the fastest algorithms exist in kublas and cuDNN for deep learning purposes. So we're going to go ahead and start here with kublas. Now, basic linear algebra subprograms for accelerating AI, high performance applications, like I said before, industry standard BLAS APIs and GEM APIs, so general matrix multiplication with support for fusions highly optimized for NVIDIA GPUs. I'll dig into fusions in a second here, don't worry about that. But what I've essentially done with each of these is I've laid them out into testing. So before I go into actually like printing out what the results are and how well these work, and what the differences are, it's important to cover what they actually do. What is the difference between these? So kublas itself is just the super high, it's essentially the easiest one to use and get working. It's just like the standard that you typically start with. And it's going to support your basic, single precision, so FP32, and FP16 matrix multiplication, right? kublas LT is a lightweight extension of kublas that provides a more flexible API, primarily aimed at improving performance for specific workloads. Except this is more oriented around larger matrices. So kublas LT is optimized a little differently, and it can be faster than just regular kublas in cases. So when you have something that's a lightweight, ideally it's going to be lower precision, right? You can think of the L as like lightweight or lower precision, whatever you want. And essentially what this means is it's the same as kublas, except when you use lower precision like FP16, FP8, and 8, They're going to run way faster, and that's what LT is designed for. So same idea, just lower precision, bigger matrices, different kind of workloads. And then you have XT, which is, I don't actually recommend this because it's ridiculously slow. But you can interconnect multiple GPUs and CPUs together to solve a problem. So if you have a massive matrix, you have a giant matrix multiplication to do, you can actually split this across the CPU and GPU, and they will talk to each other and get things done. However, the memory bandwidth bottlenecks really limit the compute because you don't just have this super fast, like this high memory bandwidth on the GPU that you can just go back and forth. Like the memory bandwidth between the CPU and GPU is really low. That's why it takes so long to copy things over. So when you have to worry about that, your solving speed actually gets slowed down a lot. And this is one of the holdbacks with XT. But you can run multiple GPUs. It's designed to be thread safe, ideal for large scale computations from in distributed workloads, large scale linear algebra that exceeds GPU memory. So if you have if you have giant matrices that it's like 16,384 by 16,384 and you multiply that by itself, that might not all fit on like an 8 GB card. If I go to Python and I do 16,384 squared, that's what? 8 that's like 268. That's like 268 million numbers. That's a lot of numbers. And if you have 3 of these, if you have an A, B, and a C all allocated, then that's like 700. That's like 800 million numbers. And then if you kick this up to like FP32, you multiply by the number of you multiply by 4. That's the size of a float, so 4 bytes, and you get ridiculous numbers like 3.2 gigabytes of space. So if you have a 2 GB card, or it's like an embedded system, it's not going to fit all that. Or if you were to bump this up to like say 100,000, that's not going to fit, right? Like these type of numbers are so massive that you just need to use external CPU DRAM in order to actually store them, right? So there's obviously other ways of optimizing that, but XT allows you to do this. So I did a run of these where the size was 16,384, and this all actually fit on my card because I have 8 GB of GPU VRAM, which is low but high in some cases. cuBLOS versus cuBLOS XT. So I did 5 runs each. It's about 0.59 seconds on average. And then this took about 3.5 seconds on average. So the results ended up matching. So they were like pretty much identical. And then, yeah, it's just like insane how much of a speed up that gets when you just stick with using the GPU, right? And so that's like one of the examples why you want to be careful when you use things like cuBLOS XT. cuBLOS DX is, we're not going to be doing that. We're not going to be using that in this course. But you can look more into it here with this documentation. Now Cutlass is something I'll cover in the extra section a little bit more, but cuBLOS and its variants run on the host. Whatever comes with cuBLOS DX isn't well super documented or optimized. And when we're trying to do things like matrix multiplication in a transformer, we may not want to rely on something where the operations are scheduled from the host. When we want to call like a cuBLOS operation, the CPU tells it to do that, right? Whereas on GPU, it's just like a kernel that's launched and all the operations are done there. So they're a little bit different in that regard. When we do like matrix multiplication, along with like a ReLU activation and then another matrix multiplication and then another ReLU and then like a convolutional layer, it's like you typically don't have that in a single operation. You fuse those together, and that's this idea of fusion, which we talked about before. And when you have something like Cutlass, which is a template library that is able to fuse things together, you can get a lot higher performance. So, for example, like flash attention. It doesn't actually use Cutlass, but it's an example of what fused CUDA kernels look like. So flash attention was a paper that came out, I think 2-3 years ago, something. If we just pull this up, it's, it's essentially for the attention mechanism in transformers, and it has a whole thing. And the idea is, you have this attention layer in the GPT. It's like matmul, dropout, softmax, mask, and another matmul. And if you fuse these together with custom, handwritten, highly optimized kernels, you can make this really, really fast. And you can speed this up by like 5 to 10x on certain hardware. And that's the idea of fusion. So Cutlass will allow you to develop, faster matrix multiplication algorithms. And then you would take something like fusion and you would combine what you've maybe written in Cutlass, and you would just combine everything so that you don't have to rely on whatever Nvidia provides, and you can just do your own thing, right? That's kind of the reason why we do things like fusion and we use Cutlass. So template linear algebra subroutines. But don't worry too much about Cutlass. We're not going to go over Cutlass in this course. There's a lot to cover there. But anyways, that's like the whole idea of cuBLAS. Now, we dig into these. I'm going to sort of go through this as best I can to illustrate what's happening. So we need to import this cuBLAS v2, right? So this is a new thing we're going to add. We're going to add FP16 inclusions, and then just some matrix sizes, right, as macros. And then we're going to include these macros that check for errors. So we wrap those around, like for example here, when we do a CUDA malloc, it's running on CUDA, so we have to make sure that doesn't return an error. We just do this consistently for everything to make sure that nothing just breaks. Everything goes according to plan, right? And so in this example, I'm actually going to go back to a section. There was a point I missed. As we saw in this script, I make these arrays, and notice how these are small, right? There's a few other things like this that you want to watch out for when you're comparing things. Because what we're doing here is we're essentially comparing the speeds and how similar things are together. We want to compare like the FP32 with the FP16, see how they perform, make sure they match up in the end. And so there's a lot of things you have to watch out for. So doing warm-up runs is good because CUDA might incur some additional overhead when you do like the first few runs. So you want to get those done with and then continue with the benchmark runs. So make sure that the overhead like just gets like removed. You want it to like just sort that out on its own for like a few runs, and then you do like 100 benchmark runs and you take the average time of those. And that's where you get an accurate measurement of how long it takes to execute a function or a kernel, right? Without doing any warm-up runs, you might see like the first thing take like 50 milliseconds and then the next one take 2 milliseconds. And it's like, whoa, what happened there? Well, that was the overhead that you needed, that cuBLAS actually took over and required. So that's why you do the warm-up runs. So warm-up and benchmark runs, you want to verify all of your results. So in here, where was it? Maybe we didn't compare results in here, but we do somewhere else. You want to verify everything so that it all matches up. And then the last one is when you're testing things from scratch, instead of like randomly initializing massive matrices, instead of having like 1,000 by 1,000 and just like random distribution, you want to populate it with values that you can actually calculate on your own, like something that you could take to your whiteboard or do it in your head, right? So when you have something that's laid out like this, you can go ahead and write out, okay, well, why did it not work, right? Then it's more easy to break down the problem and understand what went wrong there, as opposed to taking apart a non-reproducible 1,000 by 1,000 matrix. You just can't do that. But anyways, going back to the point here, we initialize some matrices. So 3 by 4, and then a 4 by 2. So this should have 12 elements, right? We scroll back up. This goes up to 12, and then this goes up to 8. It's the 2 by 4. We initialize these on the CPU. So C on the CPU, the single precision cuBLAS output on the CPU. and then the C CUDA output for the half precision. And then we do a CPU matmul just to test the results, just to populate, because again, the CPU might be the easiest one to actually write out for us. If we're transferring this from Python or NumPy, we just write out the CPU. Everything will be super easy to compare back to it. So we just do that first. We have this cuBLOS handle thing, which I'm going to go into in a second here. How like all of these are how all of these work together. But you have this cuBLOS handle, which it just gives like a cuBLOS context on like what you're doing. You just have to initialize this for safety. We create that with a separate function. We do all of our mallocs, and then we have this new function here, which you haven't seen before. This is called sgem. So single precision general with the GE matrix multiplication. And inside of here, if I control click on this in VS Code, we can see where this comes from. And I can right click on this and see where the root of this actually is, right? So we look at in order what all these are. So we have the handle, the operation, these operations. I'm actually going to pull these up in a second so this makes more sense. We have the shape, so M and K, the alpha term, which will make sense in a second. We have A, the leading dimension of A, so in this case it would be M. B, the leading dimension of B, which in this case would be N, because it's an Mn times N by K. And so the first one's going to have leading M, and then the second one's going to have leading K. Leading K. The B is going to have a leading K. The leading dimension is going to be a K. And then we have this beta and a C, which we element-wise multiply by, and then leading dimension of C. So there's a lot of things you have to add to this, and it gets quite bloated fast. So I guess to just sort of illustrate what all of those mean, there's a lot to unpack here. If we scroll down to sgem, cuBLOS sgem, awesome. So this is a super important part. This is exactly what we just saw. And look at this. So this is what the matrix multiplication looks like. So we have a C, and we do alpha times an whatever operation, which is going to be like maybe a transpose on A. Matrix multiply that with some operation on B, which might be a transpose, and then plus the beta term, which beta is a beta is just going to be a constant float number. So like in this case, you might want to have A as 1.0 and B as 0.0, just so that you're only doing A times B equals C, right? But it does provide this abstraction for you so that you can do more with it if you want to like add something on later, like maybe a bias, right? And then we have all these other operations. So cuBLOS op N, cuBLOS op T, and cuBLOS op C. So we want to worry about the N and the T here. So the N is like no operations. The T is a transpose. And then you have this column major format. So column major throws a lot of this off. So to illustrate this difference of column versus row major, as we saw here, so matrices are stored in column major format with these dimensions m by k, and then k by n, and c m by n. Column major versus row major is very important. So it's actually a little harder because it's column major, but we'll make do anyways. Column major matrix. We'll just have A. Well, actually, we'll make it row major first. That's a good idea. Row major A equals and then call major A. And then the memory layout. So notice the difference here. So we have a 2x4 matrix, right? It goes 1, 2, 3, 4, 5, 6, 7, 8. And then here we have 1, 5, 2, 6, 3, 7, 4, 8, right? So the whole idea here is we essentially transposed it. The way this row goes from left to right, it is now going from top to bottom. And now we have to deal with this. So if we have something that's like, I mean, typically when you're going to feed a matrix into a matrix multiplication, you expect it to be in row major. And cuBLAS SGEM expects it to be in column major. So there's a way to get around this. And notice how this, by the way, notice how this is laid out in memory. This is like a very simple way of looking at it. And then this is like, okay, that's, I guess so, but a little interesting because of, you know, it's just like 1, 5, 2, 6, 1, 5, 2, 6 in that order. But there's an interesting article I found on how to deal with this. So this is why you see our dimensions are a little messed up. But on this, pay attention to your shaping from Stack Overflow. I found an answer to this and how to make it actually work to your favor. So, where is it? This guy pretty much said, cuBLAS interprets matrices as column ordered. So when you execute this, you are correctly transposing, because you're doing an opt-T, which is going to transpose A, and then an opt-T is going to transpose B. You're correctly transposing each input, but cuBLAS dumps the result in column major order. So you want it to come back in row major order so that you can use it for something else. So what you end up having to do to avoid this whole column major mess is trick cuBLAS into computing differently. And so the way that you call this is you say handle op-n, then you go nmk instead of mkn, and then you go alpha, and then your B matrix instead of A, because normally you would do A here, but instead you do B. And then you do your leading A dimension. So remember n is the leading A dimension now. And then you have your A, and the leading dimension for that is going to be it's going to be K. I know it's confusing, but just bear with me. And then you have the beta, which is just like that number you're going to multiply C by, and then the leading dimension for C is going to be n. So there's a lot of weird changes there, but essentially that's gonna avoid the column major issue. So when we do this in VS Code, you can see that I call cuBLAS SGEM with that same idea. So n, and then I go nmk. We put device B matrix, we put n, device A matrix, K, beta, device C matrix, then n again. So just exactly like copy and paste from that. And this works. So this concept applies to HGEM as well, which is what we have below. So I've done a single precision and a half precision as well. And there's like a little casting operation that you do here. It's like a float2 half function, which we initialize these as half precision matrices, and then we do a float to half conversion and store the result in those based on their index. CUDA mem copy, half precision data to the device. So the host, right? This is a host, or sorry, a half. And then we just copy back. We do the HGEM, which is the half precision version of this. And then we copy back, and then we can just print out the results just to make sure everything matches up. So when I go NBCC, and we have to add this little L, like link, this is for link, and then we put cuBLAS at the end of it. That's what that means, because cuBLAS doesn't come just right out of the box. You have to actually manually link it, because it has to do that part separately. we just go ahead and run this, we can see our matrices. So when we go up, this is row major, right? 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And the same idea with this one. It's, it's a 4 by 2, so it's going to be 4 high and then 2 wide. So the two width is 1, 2, and then 1, 2, 3, 4, 5, 6, 7, 8, right? Everything is lined up as we want it to. And when we do a row major matrix multiplication on the CPU, we end up with what we're supposed to get. So these inner dimensions cancel out, and we end up with the 3 and 2, like we were practicing before, right? And we end up with the 3 and 2 here. These results, these are our verification results: 50, 60, 114, 140, etc. We do the cuBLAS SGEM result, we get the same shape, same numbers. And then the HGEM result, after we cast back to single precision, 3 by 2, boom, 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 right? So that is just a very clear, concise example on how, on like the differences between cuBLAS SGEM and HGEM. They're all the differences is just single versus half precision, and the key point of changing how you set this up. This is the most important part of this entire script, is just what it is, what it does, and then everything in between that we need to pay attention to in order to keep everything in row major. So now we move on to cuBLAS LT. So if we just pop over to right here, cuBLAS LT. So cuBLAS LT is the lightweight version, and it's designed to hold much bigger matrices. And so I figured a little something to do with that out the hard way when I was playing around. You cannot have matrices without multiples of 4. So if you have like a 3 by 4, like 3 is not a multiple of 4, or a 2 by 4, both of them aren't multiples of 4. That does not work. That will not return successfully. But if you do have like a 4 by 4 or 4 by 8 or like a 12 by 16 or something, like that'll work fine. So if we like right click on this, just like I found this in the cuBLAS documentation. Where did it go? Let's search this up. Oh, maybe I should copy this part. But yeah, so if you plug that string into here, you'll see in the cuBLAS LT matmul, it's going to be, scroll down, data ordering. So 4 byte align, leading dimensions must be multiples of 4. Dimensions M and K must be multiples of 4, right? So it's just universally a good idea. When you're working with big matrices, don't do like 4091, do 4096. It's just kind of like makes logical sense to do that. So that's all I kind of wanted to say for that, is to watch out there. But let's go ahead and just dive into like what the actual LT matmul code is doing. So we have this new include header or this new include that we have to do. So cuBLAS lt.h, and then we have the regular macros for checking CUDA and checking cuBLAS for errors. We have the CPU implementation to compare against. We have the print matrix, so that's just going to like conveniently print things for us so that we can look at them and make sure everything lines up. And then notice how I make the sizes 4, 4, and 4, right? So nothing less than that, just square matrices. I do also make sure to make these like different elements. So if these were a clone, if this was like 1 to 16 and then 1 to 16, like you might not get the results you want. So you want to make them a little bit unique so that you don't run into like any weird cases where you think you have the right answer, but you don't. So I changed this 3 right here to a 4. So it's 4 and then 4. And then instead of 13 to 16, I did 17 to 20, just to mix it up a bit. Now, the actual magic, I mean, we have a lot of stuff happening here where we essentially make like a FP32 matrix. We CUDA malloc and we populate those, and we also have a half. So this is just the half of a float. So it's FP16 is what this is. And then we just populate those with we we populate these. Where are we populating it? I think that's, oh no, we already populated them up here. I'm being silly. But we go down after we've like CUDA mem copied everything. This is all on the device now. We have this kublos LT handle. So this is just the handle that we need to create the context. We go and create that. And then we have this new term called a kublos LT matrix layout type. So this is just, there's a few types we need to ensure that this goes properly. And this is one of them. So essentially just the shapes and the data type that we're going to use. So CUDA data type. And then this kind of follows the same idea as the whole column major thing. So if we, I don't know where exactly this was in the docs, but if we go to kublos, what was it? It was the matrix kublos LT matrix layout create. If we just enter this in, we see it's down here. And if we take a look at the rows and columns, number and rows or columns in the matrix, and then leading dimension of the matrix in column major layout. So this is the same idea. And I'm going to show you how to like get through that. It's a little bit easier intuitively to sort of see how that pans out. But yes, we do need to abide by that column major rule there. So popping back here, for FP32, we just use real and then 32F. So if we actually look at this specific type, like where does this come from? The CUDA data type, you can actually see a list of these. So we have anywhere from like real numbers. So R is real, C is complex, and then this number is the precision. So 16 is half, and then 32 is single, and then 64 is full, and then you have like the other, smaller types that you can use. And then like just normal F is essentially what that difference is like normal FP16 will have it'll have a sign bit, so that's either positive or negative, and then it'll have a certain number of exponent bits. So how big is like the integer half, like before the decimal place, and then the mantissa bits, which is how precise can it be in the decimal places, right? So FP16 is going to be more precise in decimals, and then BF16 or BrainFloat 16. The reason it's called BrainFloat is because it came from Google Brain. That is going to have less mantissa and more exponent bits. So that's how that kind of naming scheme goes. But all we need to worry about in this case is the real 32-bit floating point and then the real 16-bit floating point. So we can see that we use those here. Just for the 32-bit, we use that. And then when we're ordering this, we want to do, so the first matrix A is going to be of shape M by K. So we want to flip that. So it's going to be K by M. And then because we've flipped it, we need to put the leading dimension here, right? So leading dimension is at the end. And that's that. So matrix B, same idea. It's normally K by N. So we flip that and then put that new N as the leading dimension. And then same idea here as well. Then we go to the FP16, which literally just uses real, but we replace the 32 with 16, and we do the same exact thing with shapes. And then we go down to the mapmul description type, which we just have to create. We just have to create that, and essentially we pass in this type that we define, the memory address to that, the compute type that we're doing, and then the data type. So we look at this. It's going to be the mapmul description with the kublos LT mapmul description type like we had here, and then the kublos compute type, which I'll show you in a second here, and then the data type, which we were doing before, which is just going to be FP32. So we go to this compute type. We actually see there's a few of these. You just do like control click to look at those. But there's a few here. So we have like kublos compute 16F, which is what we're going to want for the next one, but we're using this one right now. You can do like fast. So it'll like change. I can't remember exactly how it changes those inside, but it's something in the realm of like accumulating and this and that. But yeah, so these can be, it kind of just depends on like what you're doing. If you're sticking with BrainFloat 16, then you could pick that type. You could do like fast, up to you. But yeah, that's the whole idea there. So if we pop back to this one, you notice we're just using the compute 16 float and then the data type of 16-bit float as well. And then we're going to set an attribute, and the parts of this attribute that we're going to need are the matmul description type, which we defined earlier. We're going to need a description attribute, which is, if you can literally go to these, and these are essentially just the, I can't remember exactly what this is, but it's probably like some transpose A and then transpose B or whatever that is. That's what I'd assume this is. I haven't looked into this in depth, but and then this one is just going to be the cuBLAS operation. So yeah, so essentially just like transposing or not, and then the size of this cuBLAS operation type. So that's just like this essentially. So we're taking this transpose operations, and that we're just setting what that op is. So when it does like op and then in brackets A, like that's what this is. And then we go ahead and do the cuBLAS LT matmul, which itself, takes in a handle, the matmul description type, and alpha, A, matrix layout, B, matrix layout for B, beta, C, C matrix layout, D, and etc. Right? You can pretty much just directly paste these. Like there's a lot of these that we don't actually need that we can just set to null and aren't really required. So don't worry too much about that. You just kind of want things to be in the right order. And so similar to how we did for regular cuBLAS, you're going to do the B matrix first, and then you're going to do the A matrix after, right? So that's kind of how that goes. And then we just do the check cuBLAS to make sure everything goes properly. And then there's an important part that I kind of like messed up here, and it was a little silly, but I was trying to do this 16-bit floating point cuBLAS LT matmul with the regular alpha types. So notice how this is like this is void. It doesn't specifically say float. So I looked at that and I was like, maybe like we shouldn't use a 32-bit number and multiply that by a 16-bit floating point number. Maybe that's not how it goes. So I was like, okay. And at the time I was getting a bunch of 0 outputs, so I figured this might be a good fix, and it ended up working. So you pretty much just have to typecast this, so float to half, and then you just set, your alpha is going to be 1, your beta is going to be 0. You just want to do a matmul. That's all you care about. So that's how you're going to set them, and then just have alpha half and beta half, and just set these accordingly, and everything will work according to plan. So that's how it goes. Once we're done those, we copy the results back to host. We're not doing any like benchmarks here. We don't worry about that. We just want to make sure we have the correct results for both the cuBLAS LT single and the half precision. And so we essentially copy these back. We do a CPU matmul to essentially get a verification outputs that we can compare it to. And then we do the actual comparison itself. So we use a standard library, absolute value. We go this minus that. It's going to give us some value that's like, hopefully less than 1 times 10 to the power of -5. And if that's false, or sorry, if this is bigger than that number, if it's bigger than what it tolerates, then it says they don't match, and we end up returning they don't match. So if I go ahead and actually run this, we have to do link cuBLAS and link cuBLAS LT, because remember at the top here we did cuBLAS LT.h, so we have to include that. And then if we just run this, we can see that we get a matrix A, so row major, matrix B, 4, 4, and then 17 through 20 as we wanted, and then we get a C output, so 106, 664, 106, 664, 106, 664 for all of these different precisions. And we can see that these match within tolerance. Awesome. So that's just like comparing them and making sure that they work the way we want them to, so we can like carry that and port it to something else. But Then for actually comparing it, for measuring performance, we have a different script here. So I essentially did the same thing. Don't like worry about a bunch of what's happening in here. This is just a benchmarking script that I wrote for comparing very large matrices. So we do a 4096 by 1024 times a 1024 by 496. So the inner dimensions cancel out, the k's cancel out, and then we end up with a 4096 by 4096 matrix. And so I pretty much do a naive matrix multiply because these are very big. The CPU will take forever to do these. So I wrote a naive matrix multiply that still gives, a verifiably true answer in row major order. And then, we have our normal distribution random number generator here that, ensures everything is kind of just goes as we want. Such some essentially like when you do torch.randn, it's going to just do that. It's going to make it like rand n is for normally randomly normally distributed. That's what this is doing. And then verify results, same idea. Does the relative error match with intolerance? We do a timing, so with our previous streams. So we don't actually like put the stream in, but we just want to record the time and do this elapsed time thing, and then just return that to measure it on the actual device itself. And then we benchmark, and we just have a bunch of other stuff filled in between here, the same as what you saw in the previous script. And then we just end up printing out the average time afterwards. So it'll also return the max error we get as well. Consider there is some error with FP16, so we should know about that too. But if I just print this out here to compare, we print this out, notice, so cuBLAS results match the naive kernel with intolerance, results match, and results match. Awesome, so everything is lined up. I did give it some additional tolerance here just because of some of the error, but here we notice that this error is not super significant. It's not, this is the maximum error. So most of it is going to be very insignificant compared to this. This is just like a side edge case, which might pop up a few times, very like not often at all. So when we actually look at the times, we can see normal cuBLAS gives us FP32 average time of 2.5 milliseconds. cuBLAS LT gives us an average of about 2.8 milliseconds, which isn't amazing. And then cuBLAS LT FP16 gives us 0.63 milliseconds, and then LT gives us about 0.46 milliseconds, which is really fast compared to this naive kernel that we've written before. So this took 28 milliseconds to write. This is about the time that it takes me to ping the Google servers, about 28 milliseconds to run the complete naive kernel. And the LT took about 0.5 milliseconds. That is insanely fast. Like look at the number. If you just look back at how we were doing a matrix multiplication of like taking the column and dot producting it with a row, like you have it's like size 1024, and it does that, and it does for every single combination. And it does all of that in half a millisecond. So that's about 5/10,000ths of a second. But yeah, anyways, that is cuBLAS LT. So at this point, you might be a little upset or frustrated about why I'm just showing you code and then reviewing it and not like writing it from scratch, like starting from the very top, like let's define these and then write this and then write this. The point is, like all of this, it is a lot. It is a lot of lines. I'm not going to type this all manually. The course is long enough already as it is. I'm not going to make it 10 times longer by writing everything by hand. But yeah, you kind of get the point. I identify the main material that you need to learn, the most important stuff, and I highlight it. But I don't need to highlight everything. Like writing check cuBLAS is just redundant. Writing, I don't know, like writing this stuff, it's just redundant. Like you already know what that is. So that's kind of why I'm sticking away from that side and just trying to make like fast progress here. We might write out some things later on just to kind of help you understand it when it gets more intuitive and you're actually like building stuff. But right now, this is not very conceptually hard, so we're just kind of flying through it. But this next part is on cuBLAS XT. So it's essentially the same thing as what we've just done, except it's a bit different. We still do the handle, we still create it. We do this new thing called device select, which remember when I talked about how you can have multiple GPUs and do a computation across multiple GPUs in the host. That's what this is. So we essentially just do this little hack, and we just device select whatever the main GPU device is, and that's how we do things across. So this is just a little hack when you have one GPU, so that you do this. And then we do this XT SGEM, which is the same exact thing as we've been doing before, except you have these things that are on the host and then they're managed by this SGEM function. So you don't have to actually move anything to device. I don't have a single CUDA mem copy in here. You just pass in your matrices on the host and it'll manage all of that memory back and forth, but at some performance cost. So you'll see that in a second when I compile this. We don't actually need to link LT, but that's fine. And so you can see maximum difference between CPU and GPU results, right? And then if we go to, say, and then we just link cuBLAS. We'll give that a second here. I did the exact same thing as our cuBLAS LT, but for XT instead, and made very big matrices. So 16384. You notice the cuBLAS run does about, like I think I highlighted this before, but 0.59 seconds or 0.6 seconds on average, and then the cuBLAS LT is going to be way longer than that. So we'll just give this a second here to finish, but. Yeah, you get my point. It takes a while. You don't want to run this. Maybe you don't want to run this in production. So we get the average time. Everything matches with some tolerance, and we're good. But yeah, that's cuBLAS XT for you. Go ahead and delete these. I hope you enjoyed that section on cuBLAS, or CUDA Basic Linear Algebra subprograms. That was quite a bit. Hey, we got a second part on cuDNN. So when you do for example, like pip install torch like this, and you see like where is it, cuBLAS cuDNN, right? This is where it's kind of coming from, right? And you have all the other things like cuFFT and curandom number generators and cuSolver and cuSparse and collective communications across multiple nodes, profilers, Triton, which we'll go into later, right? I mean, this is why I'm covering this stuff, so that you can kind of work with it and you understand how PyTorch works under the hood, right? That's one of the main reasons I'm putting this out. So when we go into cuDNN, there's actually a lot more to unpack here as compared to cuBLAS, but it's not conceptually hard. Some of it is a little bit intuitive, but not really. So cuDNN is not entirely for matrix multiplication. It does matrix multiplication in some operations to really speed things up, but it's not a performance bottleneck. You don't actually explicitly do matrix multiplication in cuDNN. That's not a thing. That's what cuBLAS handles, right? So in cuDNN, you're going to deal with things like convolutions, pooling layers, softmax, dropout, right? Batch normalization, tensor transformations like reshaping and concatenation, layer norm, all this, right? So all these other deep learning operations other than matrix multiplication is what cuDNN is going to cover a lot of. A lot of the most commonly used ones. So this is kind of why I'm bringing you to the docs here, is because this is a super direct interface with everything. So they actually have their own thing, docs.nvidia/deep learning/cuDNN, and you go there and it brings you to this page. So there's multiple things here. We have like a getting started or installation guide, which we don't care about. And then the other ones, the important ones, which is backend API and developer guide. So we're going to be looking at these two today and doing some examples of cuDNN operations and comparing them. So if we go to like backend API overview, we can see it's like CUDA, so it supports the CUDA streams that we were talking about before. It has multiple things that it's kind of like linked to. So there's like, I wouldn't pay attention to that entirely, but you essentially have these three parts. So you have CUDA and graph, CUDA and ops, CUDA and CNN, and adversarial. So graph is going to, it doesn't support like graph operations where you're like dealing with graphs. It's more so how do you combine operations together in the form of a graph. So when you're doing like a convolution layer and then you're adding a bias and then you're doing a max pool after it, like that's going to look like a graph, right? You're going to have these nodes essentially where it's like a node is an operation and an edge is a tensor, right? Or a matrix. And so it'd be like convolution 2D, and then there's going to be an edge, which is the data flowing from the output of here to the input of the next node, and that next node might be like the bias that it adds, right? And then it's going to flow out of the bias into like a max pool layer or an average pool layer, and then it's going to go from there. And so instead of doing these separately, where you do a separate function call for convolution bias, you do like a manual bias kernel and then a manual max pool kernel, you just fuse these all into one, and you keep track of all of your data in between, and it does that for you. So CUDA, that's what the whole CUDA and graph thing is. It supports both forward and backward pass. So when you're going through calculating the predictions, and when you're modifying all the gradients and back propagating through, it supports both of those, right? So it's designed for kind of just putting something in place instead of having to write all the kernels from scratch. It just kind of makes your life easier that way. So there are multiple things within CUDA and graph. So we have these pre-compiled engines, runtime compiled engines. I have this pulled up on my second monitor here, which I'll probably just bring over. Where did it go? Yes. So the precompiled single operation engines, I'm going to make this more readable. The precompiled single operation engines, precompiled and optimized for a single specific operation, like a convolution. Because they're precompiled, they offer very efficient execution and are inflexible in terms of the operations they can perform, right? They're compiled down to machine code. They only do one specific function on something, but it goes very fast because of all the optimizations in binary that it has, right? So like, for example, matrix multiplication engine that is precompiled and optimized specifically for that operation, right? Like similar to convolutions. And then there's generic runtime fusion engines designed to dynamically fuse multiple operations at runtime. So offer more flexibility compared to precompiled because they're generic and they can adapt, right? These are things that would happen during the compilation. Might not be as highly performance optimized, but they are generic and they act as like a generic fuser of operations together. So you will get those performance benefits, but they're not going to be as high. So you still get them, but they're not going to be they're not going to be as high as something customly written for that algorithm. And then you have a specialized runtime fusion engine, similar to generic runtime fusion engines, but they're typically specifically optimized for certain patterns or combinations of operations, right? So offering runtime flexibility and leveraging optimizations for particular use cases or operation sequences. And then, for example, an engine optimized for fusing convolution layers, followed by activation functions in neural networks, like similar to how I was talking about before. You have like convolution and then a bias, and then convolution bias, and then a max pool layer. Similar to that, right? It'll recognize your code architecture, and it'll find the fuse patterns where you would get a speed up. So it's going to be smart, right? It's going to try to be smart when it's compiled those down and seeing where you could actually get a speed up from. And then you have the specialized precompiled. So precompiled for specific sequences, they offer the same high performance as precompiled single operations. So these ones that were really fast, but can handle sequences of operations rather than just single ones. So these are actually These are actually amazing. If you are trying to do a lot of layers, like if you have a whole, like say a transformer block in a neural network, and you want to do that entire attention block, this is an example of what that would be. So you have a lot of different operations that you're doing in there, but if you just have this wrapper that says multi-head attention, you call that, you get everything, you put everything in that you need, and you get everything out that's useful, and then you can continue on. And it's going to be highly optimized, pre-compiled into binary specifically for that, right? So this is kind of how cuDNN is structured. And these are the things you're going to want to pay attention to when you're trying to optimize, when you're looking out for how you can take advantage of underlying cuDNN features. There's an example of like runtime fusion right here. And then if we go back to the graph API, if we go back, I know it's bright, you'll be fine. We pop over to this graph API. I think that's where it was. Yeah, graph API with operation fusion. So convolution forward, pointwise bias, pointwise ReLU, right? That's kind of the whole idea. And if you wanted to fuse these together, you would do like you'd have like essentially some organization. You have 3 tensors that you input, and that would be like their variable names, and then like these 2 would go through here, like your X, and then your W, your weight kernel, the convolution filter itself is your W, and that would output something with this arrow, and then this bias would come in, and it would essentially add to the output of that convolution, and then you would do a pointwise ReLU, which is it literally just goes one by one through each element, and then you get your output. So that's the whole idea of a graph, is like you have these, which is your data flow. The edges is your actual data and where it's flowing to, and then the points, the nodes themselves, are the operations. So continuing to go through this, inputs, convolution backwards, so alpha, beta, dy, w, and dx, and then you would end up getting, you kind of get the point. You put whatever in is required for an operation, and you get whatever out is useful, right? Especially important you pay attention to that in the backward pass of things, because there's going to be more data you'll have to take care of. But yeah, these kind of work the same way all around. Normalization, you have like your mean, epsilon, and variance, then your scale. Continuing to go forward, same ideas, generic runtime fusion engines. You can kind of just scroll through this and get the idea about how everything is architected. There's quite a bit here. I don't expect that you'll read all of this, but yeah, that's pretty much how the whole fusion engine thing works. I know it's a kind of a silly term, but it is, you're effectively fusing operations together, and you could say that acts as like an engine, right? So if we go back to this VS Code here that I've opened, the README file, you can actually find these in here. So just, a bunch of stuff about like the graph API, very important. Matmul, convolution forward, backward data, pointwise. Yeah, just like pretty much some of the images copy and pasted. And then this one was actually support. This one is support for the different compute capabilities, right? So if you have, like, for example, if I did, can't remember what it was like device query. Remember that when we printed out the compute capability, and mine was 8.6. So I would actually not get the convolution backward filter fusions. I would not get this because it's only supported on 9.0 and up, right? So pay attention to things like that when you're trying to fuse things together for like research production purposes. You want to pay attention to what is supported on your hardware or whatever hardware you're working on, so that you don't like try to do something and have it not work and waste time. So it's good to just like double check with this stuff and see. This is all in the cuDNN docs, but there's still a few more sections we have to cover, so I'm going to dig into those. We have the ops API, which I'll dig into next, is very simple. If we just go to here, go to ops, essentially you have these same opaque struct types as you did with cuBLOS. except they do different operations. So you can do like you can like create tensors, pooling, filter, dropout, loss, activation, all of this. So the actual functions here might be hard to read. It's very bright. But activation backward, activation forward, you just have like a massive list of stuff. I'm not going to go through these one by one, but you get the point. These are all the operations that are supported with cuDNN, and we're going to test some of them out. So, you get a bunch of like descriptions about what each of these do. So it, in case you're wondering about something or you're not getting an output as you'd expect, you would generally refer to these docs. So you could, whatever type you're working with or whatever function you're trying to call, like let's say you're, working with this, or maybe you're doing, let's see, maybe something simple like an activation backward, right? So you have this, you copy it, F, and you can find these all across. So you have the cuDNN activation backward, and it has all the different types in here that you would use. And then you have this original one that we highlighted before. So that's how you navigate these. You just search for whatever's wrong, and then kind of just like look at that and see any of the notes on it and see if you miss something. That's kind of how you're supposed to approach these. And then going into CNN API. So this is where stuff might get a little bit interesting. It's not like any graph fusion stuff you're doing. It's just like raw algorithms. So you'll have, convolution, backward bias, like all the different convolution stuff. There is fused ops. So that's where like some of this would come in, but yeah, this is where all the convolution stuff is going to be for like image processing and you name it, right? So we're going to actually use convolutions in a second here. So I'm going to save this, but it's you approach it the similar way as you would with operations. And then you have the adversarial API, which is same idea, but other functions. So like RNNs, CTC loss, multi-head attention. We'll do multi-head attention weight. So if I go multi-head attention forward. Awesome. How do we use this? Right? There's multi-head attention forward. There's 22 of these in here. 21 now. So you kind of get the point. We can scroll through these. There's a lot. Jeez. So this is how you would do a multi-head attention block forward in the forward pass. There's a lot of stuff in here, but that's kind of how this goes, right? Just the adversarial, like extra, the other section, miscellaneous, whatever you want to call it. But now we can actually go into some of the comparisons to understand how to actually use cuDNN in a CUDA script. Now we can actually go into some of the code and examples behind cuDNN and how it works under the hood. Well, not how it works under the hood, but how we can use things like PyTorch under the hood to make operations really fast. So in this example, we do the CUDA runtime and the cuDNN.h. I'm just going to do the 10h function, for example. And in case you haven't seen the 10h function yet, we go to Google Images. It literally just looks like this, 10h. Or like this. Maybe this is a better one. It's like between -1 and 1. It's just a little activation function that you do. It's like a nice smooth S-curve. And yeah, so that's all we're really doing here. We don't actually need to like do the type in the formula. It's already done for us. I've actually written out the 10h kernel here, and the operation is literally just 10hf for 10h function on device. So very, very simple. We want to have a tensor with the shape, what's it called? N by C by height by width. That's the format we want to use. So it's going to be like N is batch size, channels is C is channels, height, and then width, right? So the whole idea of like channels is if you have like an image, for example, like the image video you're watching me on right now. This is going to have 3 channels. It's going to have RGB, right? So this is if say you've done some convolutions and now your channel dimension is very big. So instead of 3, you've got like 32 elements per pixel that you have to keep track of and do operations on, right? So we're making a big tensor here, big tensor. If I actually go into Python and do 256, I'm going to go, well, 4 times, because 4 is the number of bytes it's going to occupy. 4 times 256 times 32 times 2 times 224 squared, we end up getting this number. And if we divide this number by 1 million, it's about 1.6 gigabytes. That's how big this tensor is. And then we're going to do a 10H on that. So CUDA DNN is going to handle this, and we're going to compare that to the naive kernel. And yeah, so just stepping through this, same CUDA malloc, initialize data, CUDA mem copy. We're going to create some events so that we can time stuff on the GPU. We're going to do our warm-up and benchmark runs. We're going to do some warm-up runs for the naive kernel. We're going to do benchmarks for it. We're going to set up cuDNN, and this is where we're actually going to learn a little bit. And then like benchmarks for cuDNN, of course. This is where it mainly takes place. So we have this cuDNN handle type. We create that. We have this tensor descriptor type. So you actually need to, it's like when you did a matrix A descriptor or matrix B descriptor, like it's the same idea, but we do that for tensors because it's more in the deep learning context. There's more deep learning operations in cuDNN since it's deep neural network, deep neural net, right? So we have create tensor descriptor, which is going to just take the memory address of this and actually create the tensor descriptor based on the type. We're going to set the tensor descriptor, so it's going to be this type, which we did already, the tensor format, the data type, and then each of those NCHW format, right? So we do this format, and you can look this up, and there's it's right here, tensor format. So we can do NCHW, we can do NWC or NHWC, and etc. Right? So that's we just pick this one. And then this data float, we look at this. We can have like a bunch of different ones. Fast float for FP8. FP8, so we'd have 1 sign bit and then 5 exponent bits and then 2 mantissa bits, right? So it's 8 total, right? And then FP8, more mantissa bits, and then Boolean. We have all these different types, but we want the float. There's no like float 32 here. We just want a normal float. No half, no BF16, none of that. Just something basic to use. And then we create not only the tensor descriptor, because we have the tensor itself, and then we have the activation descriptor, which is about what the activation is going to do. And we have a custom type for that. And you can go here, and there's a bunch of different, I think it's, I don't know where exactly this is, but I just like to right click on things to learn. Yeah. Good luck. We create the activation descriptor with its memory address. And here we have the activation descriptor type as before. We have the cuDNN, or we have the activation type, mode type. So the activation mode is going to be 10H. And then the propagation type is just nan. We're not doing that. And then the coefficient is going to be 0. So there's not going to, I don't know what is coef. I don't know what that is. But anyways, this is just like the template layout we're having. And I don't expect you to like go through this and understand every single character that's happening here. This is just kind of a more template example to show you like how we're comparing these, how we're running and testing, and you can like take these out and put them into other pieces of code. So don't like feel bad at all if you don't understand this. It is there is a lot. But if we go to like this, for example, we have like sigmoid value, 10H, clip value, swish, all this, right? So we just want the 10H function. Now we go to the activation forward, as we saw just like a few minutes ago. We have this cuDNN handle, which we defined before, activation descriptor, which we just covered, the alpha parameter, the tensor descriptor, which we covered up here. We have this we have this void x, so that's just the input, a beta term, which we don't need, and then tensor descriptor type for y. So, and the output itself is just a it's nothing particularly special. It's just a void, so we don't need any like special types for it. It's just like a raw data, like array output essentially. Going to be a bunch of floats, right? So that's that, and it's going to be on device. That's why we have the D there. We're going to synchronize everything and then do our benchmarks run. Benchmarks runs, we're going to find the average time. We're going to verify against the CPU. Like a CPU 10H, for example, it's not going to take long since it's like a point-wise operation. It's just going to go one by one through it. It's like linear time. So when we actually compile this, 10H, CUDA, see it knows. We run this, we're actually going to be surprised by something. So give this a second to run. My machine might be lagging a little bit, I'm not sure, but we're going to let that run for a second here. Our matrix sizes are quite big, remember, we have these. So, tensor size as we wanted. The naive CUDA kernel time, notice how this is actually faster than the CUDA activation time. They're both correct. We just compare the results, point-wise. And this is faster. Why? That really made me angry when I saw this. I was like, what is the point of having a CUDA activation? Like, what is the point of this? And the point of that is just to give yourself things like alpha and beta, right? So when you have alpha and beta, these are extra numbers that you have to consider in the operation. And when it's so simple, when it's as simple as just a like exponentiation or like a multiplication, and it's like a very simple, like for example, ReLU takes almost no time to complete. 10H is like a very simple operation, just on a single number. You just output that to the same index. It's very computationally simple. But when you add in little things like alpha and beta, I suspect these are what actually cause the performance difference. It might be mostly these or some CUDA overhead. I mean, again, we don't even know what this is doing under the hood. It's a complete black box, opaque struct. We don't know what's happening. So it's hard to actually know why this happens. There's not very many resources on why custom kernels might be faster than CUDA. I haven't really found any of that. So we're just going to hold the assumption that there's this big opaque struct black box thing that we don't know. And then you also have just the alpha and beta as well that you're timesing and adding things by, right? So that's going to add some extra compute overhead. But these are not very big differences at all, right? So you have like 8.523 and then 8.6. It's like, this is like nothing. This won't actually matter in production. It's like if you take the difference, if you see how much faster the naive CUDA kernel is, it's like literally 1.3% faster, which you're not ever going to notice in a real environment like that. It's just unnoticeable. So it doesn't actually matter that much. If you care like totally, just like go ahead, go and write your own kernels. But that's the general idea. It doesn't really matter that much. For convolutions, it will matter though. Then going down to this, I wrote a PyTorch script to just kind of illustrate things out manually. So like how PyTorch handles the custom 10H, like when you write it from scratch on your own, versus when you just use the built-in torch.10h. Where did it go? Yes, torch.10h. So just kind of comparing those side by side and seeing how they perform. So if we write these out, it's taking some time to do this. Yeah. So custom 10H, that's going to take 21 milliseconds. Remember how CUDA beforehand was taking about I don't know what it was, like it was a very small number. The custom like built-in 10H is still very fast. So if we go back and we just NVCC compile this and then run, and let's just like look at what the shapes of our numbers are real quick. If I do batch size by say, or if I do 256 by 32 by 224 by 224, rand n, and then we wrap these in brackets here. We can check this one real quick and see how fast this runs. And then we will compare the Python script to that directly without like deleting the output so we can't see it. Just so we understand like how much performance could be gained from, say, using like a custom written CUDA kernel or custom written CUDA function. So if we go Python torch compare, it's going to take a second. Oh, yeah, it ran out of memory. Awesome. So rand. Yeah, no, that doesn't work. I bumped this down to like 128. It might work. It's not very fast. Yeah, so like custom 10H is super slow, and then the built-in one 4.3, let's say 4.4 milliseconds, right? And then we go up and we can see that, you know, this is actually this is about double that, right? So if we do about 4.4 times 2, 8.8, right? So we go back up and it's like, this is less than that. So if we write a naive CUDA kernel, like this is just naive. If you were to optimize this and implement something like loop unrolling, which we'll go into later, and you optimize this, even just something as simple as an activation function, you can get this surprisingly faster than PyTorch. And just like write everything manually, you can actually get considerable speed ups. So that's just to provide some context there. But yeah, activation functions, don't worry about that too much. It's not really going to affect you. And then we go to like convolutions, right? This is an example of where we're actually using convolutions. So, you know, we have a lot more things to pay attention to. I'm gonna dive into this right now. Now we can jump into convolutions a little bit. I've been hacking around with some of these, and let's just kind of show you how these work. So we're going to start off with a visualization first. I'm going to bring over a convolutions visualized. Just pop over to here, and this is just what it looks like. So we can like, you have these input sizes, kernel size, padding, dilation, and stride. Input size is this. I can change the input image, the kernel size, the actual weight itself, the weight term, the padding, so how much black pixels are put around the input, the dilation of it, right? And then stride as well. So I can make it stride by 1 each time or stride by 2. And that's pretty much just that you can mess around with that in your own time. But I've written 2 scripts. So one for PyTorch. So the PyTorch and this one use the exact same values in the exact same order, the exact same parameters here. They're all the same. And I'm just doing a side-by-side comparison of them so that we can get our desired output. So it's essentially like a 4x4. The input is like a 4x4 image. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And then the kernel itself is 1, 2, 3, 4, 5, 6, 7, 8, 9. And it's just going to, right? It's going to do that. And we put a padding over it so that this is going to end up flooring to 1. So kernel size is 3, and then divide that floor by 2. So if we go Python, go 3, 2, we get 1. And that's just going to be our padding. And then Torch is going to do that with this functional library here. And we get the output, right? So this should be very self-explanatory, very easy. We're just reshaping it and then reshaping it here as well. But when we look at this part, this is actually where the fun kicks in. So we do our CUDA at the top. I've written a naive CUDA kernel for this, for doing 2D convolutions. Takes in an input, a kernel, the output, the width, height, in channels, out channels, kernel size, and batch size. So don't worry about how this works internally. Just let it be there as some like template code that's going to do what we want. It's modular, so and then we have all the same settings as we do in our PyTorch script up at the top here. So we define like how big our inputs, outputs, and kernel elements are going to be. We print this out. We do our classic just mallocs. We have our values organized, more CUDA mem copy stuff, and then we create the cuDNN handle. So this is all very similar to what we were doing with cuDNN in our 10H function. We create an input and output tensor, filter descriptor for the kernel itself, convolution descriptor for the convolution operation. We create all of these. We create the convolution descriptor with that memory address. We're going to use the 4D descriptor because it's going to be shape batch size by channel, by height, by width. And then if we look at these, so we have the tensor descriptor, the format, so what it was like the shape of it, and then the data type, which is just a float 32 as we have here. And then we have the N by C by H by W, right? So batch size by channels, by height, by width. And we do the same thing for all of these. The output is going to be out channels because it's not inch, it's going to be how many out channels do we get in the end. And then the filter descriptor is going to have a different, it's going to be organized a different way. It's going to be out channels by in channels by height by width. So out channels, in channels, height by width, right? For the kernel itself. For the convolution filter, I'm going to use those interchangeably. Convolution kernel and convolution filter, same thing. And then the actual descriptor itself, this is a 2D descriptor, so it's going to be a 2D convolution. And we just dump all of these in. So the padding H, padding W, U and V, and dilations, we're not even using dilations. Convolution mode, so it's going to be cross correlation, and then data type is just float. So I don't expect you to know what all like the convolution laws are and everything. We're just comparing to PyTorch and making sure that everything lines up. And then in terms of the algorithm itself, we have a little thing that searches through stuff here. I might change this later. It's not very beautiful to look at. But what you can do is actually just like literally this, where is it? This algo here, when you give cuDNN like a workspace size to do the operation in, there's this cuDNN convolution forward algo type, which is right here, forward algo type, and there's a bunch of them in here. So by default, what that's supposed to do is cycle through them and find which one is the best. But I find that it might be a little bit better to just cycle through these one by one on your own. So try out implicit gem, try out pre-comp gem, try out gem, try out direct, FFT tiling, winograt, non-fused, count, right? So try all of these out and see how they work, which I have in this comparison script we're going to do later on. But yeah, don't worry too much about those. You can kind of just run this script as is. But we're just trying to find the best convolution algorithm for our problem at hand, right? So when you have a smaller kernel and a small image, a certain maybe an implicit gem might be faster than say an FFT tiling because of the overhead, right? So you have to just consider things like that, your problem size, all that stuff. The workspace size is just how big you actually return the minimum size of the workspace to be passed to the convolution given an algorithm, right? So you're essentially just saying how much do you get to work with here, and this is defined by a bunch of things that it just decides this, right? So we give it a bunch of descriptions, and it's going to use that context to decide what the workspace size should be. Now we can do our benchmark, warm up and benchmark runs. So we have this, just skipping the alpha and beta. We have this convolution forward function, which I'll show you in the NVIDIA docs in a second here. This consists of the handle, alpha, tensor descriptor for the input itself, which is just a void pointer, right? And then the filter descriptor, the kernel, convolution kernel, so a pointer to an array, the convolution descriptor, so the actual operation algorithm itself, the algorithm, the workspace, which we defined in workspace size in bytes. The workspace size in bytes, we pass in this, we do this size t, which is like a size type for like storing large values, and we put this into here, and then this value changes based on these settings, right? So when we put this back in here, it's going to decide when it's actually running this, how much do we need and what are the resources requirements? It's pre-decided, right? And then we do we just enter the output description and then the output device array, right? And then we do the same thing, but with our conv2d, except it's less complex to filter through. And then we synchronize all of our threads and blocks in the GPU with CUDA device synchronize. Very simple. And we do the same thing for benchmarks runs, except we just add a time and an event recording as well, right? So fairly simple concepts happening here, just timing and benchmarking and mainly just filtering through what the heck a function takes in and what are all these types doing, right? That's really the mess you have to dig through. Now if we go down, we actually print out the CUDA output and the naive kernel output. So and then the flattened one as well, so that we can compare back to PyTorch element by element. We just destroy all the context afterwards. Same thing with the tan-h. Same thing with the tan-h CUDA script. Go ahead and run this. So out 0, 1, just like that. Link CUDA. We run this. All of these are as expected, and so it's going to just it's going to select an algorithm. These are all messed up. I might change these later, but we notice that CUDA is slower than the naive kernel, and that's because it's just really small, right? It's very small. CUDA probably has more to organize. It's got these alpha beta terms everywhere that's got to take care of, and there might just be some extra overhead there. So it is indeed like 3-4 times slower than this, just because it's smaller and it's not a big problem size. So if we look at the output here, we see 111, 178, 217, and then the end is like 274, 275, 175. Now, if I go and run torch compare, it's going to do the exact same thing. Notice how we get 111, 178, 217, and then 295, 274, 299, 295, 175. So go back here, 274, 295, 175. Perfect. So everything, we can look through these all line up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 elements. And this one has 16 elements as we print out at the bottom here, just the length of that. So I try to be like fairly quick with that. It's very, kind of just a bunch of boilerplate code that we run through. But now that we know that this works and it's outputting what we want it to, we can actually go take a look at the comparison script. So the comparison script, actually real quick, before I go to this comparison script, I'm going to bring up the CUDA docs here just to kind of show you the, go to CNN. So we're doing this convolution, CUDA convolution forward, right? So we look at this, and there's a bunch of things in it. So like this descriptor type, handle, alpha, beta. So it just describes everything that we need to know, right? So if something I said didn't make sense, maybe just like look at here and it might make better sense to you that way. But if we want to say look at something like the forward algo type, we go here, click on it, and there's a bunch of values. So implicit gem expresses as a matrix product without actually explicitly forming the matrix that holds the input tensor data. So there's a bunch of descriptions here about like different algorithms you can use, and just like when you might want to use it. There's also other articles on like which ones are good for different cases. Convolutions are very, very well covered in the whole deep learning space, so it shouldn't be too hard to navigate. But these are going to be your forward pass algorithms. Now, if we go back to this comparison script, I'm essentially doing the exact same thing, except I set the algorithms used to implicit gem. So that's this one right here. So I just set that manually, and yeah, that's pretty much it. Now we set this to algo, and then we just plug an algo in there. So that's like the main difference. And then the other one is just how we initialize our data. Everything else is the same as this initial, like just the convolution compare like between PyTorch. So we, where is it? Yes. So we initialize on the CPU with just a bunch of random values. And then we just do an operation with those. So I make the elements a lot, I make this whole thing a lot bigger. So it's 224 by 224 by 11 by 32 by 11, 11, 32, 64. It's not times all of these, but the input is going to be of size width by height. It's going to be width by height by in channels by batch size. So NCHW as we did before. It's going to take up a lot of space, but we're just going to benchmark this and see how it goes. So we go ahead and run this, get a batch size of 4, and we notice CUDA average time is 14.8 milliseconds, and the naive kernel average time is about 82 milliseconds. So if we do that division there, we notice that we get a 5.5x speed up by using CUDA. How awesome is that, right? I mean, if you optimized this naive kernel up here and made it like more specific to your specific use case rather than calculating a bunch of stuff, it would be faster. But this is kind of just like for demonstration purposes. CUDA is still wildly fast, and it would take a while to get something that is actually more performant than this, like significantly more performant. It would take a lot to do that. But that's the idea, right? This is why you use things like CUDA and PyTorch, is because they're just like super fast. It just did a massive convolution operation of like an image with 32 channels of batch size 4 and a kernel size with just like 11 by 11. It's just like insane the amount of operations it does in such a little amount of time. So that's what we're working with. That's CUDA for you. Now, when you're working with big, massive data centers and GPU clusters, even if it's your own local rig that's just on the side and you have 8 4090s or 3090s connected to it, this part might come in a little bit handy, right? So larger rigs or data centers, let me just change that, how that looks. So you have cuBLOS MP versus NCCL versus MIG. Now these are all different. I'm going to start with MIG because it's the easiest one to explain. Essentially think of it as your Amazon, your AWS, and you have a giant GPU inside of your facility, your data center. And so typically with this type of GPU, most people aren't going to use the entirety of it, just like a small chunk. They just want the parallel processing aspect for like some whatever signal processing, I don't know. And so what you can do is you can actually split that node, split that node into a bunch of smaller GPUs. What's multi-instance GPU. You can have multiple instances connected to the same card, and you can split workloads evenly and securely across those. And so that's what MIG does. It's used in data center environments, use cases, right? And then you have NCCL. So NCCL is actually really, really important for distributed cluster computing. So this is essentially going to it's exactly how it sounds, right? It's not going to do operations across, but it's going to help manage and communicate different things across a cluster. So used for distributing information, collecting it, acting as a general cluster level communicator, whereas cuBLOS MP up here is going to be doing the grunt work of doing, like, say, giant matrix multiplications across like a node of 8 H100s. And then NCCL is going to like run this in batches. So remember, collective communications, the operations within that, and there's more resources on this, would be like all reduce, broadcast, gather, scatter across, right? So not like there's no like multiply or like fused operations in here. It's doing it across a cluster and communicating data, right? So just for reference, in PyTorch, you would use distributed data parallel for this distributed cluster level computing. So distributed data parallel data parallelism at the module level, which can run across multiple machines. So module would be like, say, a function in PyTorch, right? Which can run across multiple machines, should spawn multiple processes and create a single data distributed parallel instance per process. And there's a bunch of more stuff you can read about this. This is used a lot actually in PyTorch. It's very simple to set up, but this is like kind of all of that simplified into one usable thing. Now going back, I do have more resources on this too. I'm not going to cover all of this since I don't actually have a cluster in my house to experiment it on, but there are some links and resources that you could find yourself going down a rabbit hole with these, which is what might be quite fun. But cuBLAS MP is actually it's literally designed to do distributed basic dense linear algebra. So if you're doing like a multi-GPU tensor operation, this cuBLAS MP would handle that. So if we go back here and we go to cuBLAS MP, high performance CUDA library for distributed dense linear algebra. Getting started, for example, like code samples, right? You have these giant like grids and stuff that you handle, how to use it. Yeah, maybe like how to use it, for example, C API. And there's a bunch of interesting resources on here as to how you would do things. Maybe there's like an operation. I don't know. This is up for you to navigate. It's optional. You don't actually have to know cuBLAS MP because PyTorch does a lot of that for you if you're just working with those workloads. But if you're going to be working on like data center infrastructure, this is something you want to learn, like cuBLAS MP and NCCL. So hopefully that helps to provide some context on like larger setups. Give yourself a pat on the back if you made it this far. This has been a lot so far, and we've covered actually an insane amount. And now we're going to cover one of the more technical parts of the course called matrix multiplication and how we optimize it. So this is going to be one of the most technical parts, mainly because we're looking at like low-level optimizations. How do we actually speed this up on the hardware? And so it's no longer just like the general idea of how it works. We're actually using our knowledge and additional knowledge that I'm going to share with you on how we can make the fundamental matrix multiplication or the matmul algorithm really, really fast. So this algorithm is proprietary in deep learning. It is everywhere. And so I figured the best way to teach you how to optimize kernels would be to use this as an example. And luckily, we have a repo by Simon Bohem. I think that's how you pronounce it. This guy's a performance or kernel engineer at Anthropic, so he probably knows what he's doing. And he made this really cool repo called SGEM CUDA, as well as a blog post to go along with it. So I'm just going to be following this. And I was kind of lazy and not going to like write all of this from scratch on my own. So I kind of just went along with this, and I want to explain to you the steps of going through this and how we progress through these different steps, getting up to pretty close to cuBLAS performance in gigaflops, or perhaps even surpassing it depending on which hardware you have. But this is going to be the goal. So you might have come across this article already, but in case you haven't, or in case you have, maybe this was too hard, I'm just going to go over this, and we're going to go super low level. Things are going to be super clear after you finish this part. You're going to understand how to optimize CUDA kernels. So let's get started. We're not actually going to occupy the CUDA course repo with this. I'm going to link it in the README file so that you can follow along in case you're just going through this course repo. But I'm actually going to take some steps back here, and I'm going to clone it into my main CUDA directory here. So I'm just going to delete the old version. And we're going to git clone the other repo in. So it's just that, literally just pop in here, copy paste this in, go ahead and git clone that. And then we're going to go ahead and open this up and open this in VS Code. So I'm going to drag that to my side monitor here. I'm going to close this and open this one up again. Now, inside of here, we're going to look at the README first for setup. So we can see that it in the build instructions we have to do make directory build cd into it. And then we're going to cmake. It's going to take a second there, and then we go -- build period, and it's going to build everything for us. Now, the idea here is to build everything, show all the different benchmarks after we actually go through each optimization. So we're going to essentially print out the cuBLOS performance, and then we're going to print out naive, and then we're going to print out the next optimization, and then we're going to print the next one, until we get to the end. Then we're going to compare all of them and see which one is the fastest. So we can go ahead and start off with just going into here. So a bunch of different kernels. We have naive, we have a global memory coalesce. So if we actually go back to the blog post, which is what I kind of expect you guys to follow, there's not too much here. It's mainly just the code. So if we go back to the blog post, we're essentially just going in this order, and he does it in this order too. So the naive implementation, I mean, we've already done this, right? I can actually go back, and if I make this full screen and I go out of this, and I go into the CUDA course, writing your first kernels, and then matmul, notice I'm going to copy this for a second. And then we're just going to paste it inside of here, just for reference. So we have these two kernels, and I just want to make sure that we're all caught up here. The one I taught you before is the exact same one that we're showing here. So this takes in A, B, and C. This one takes an A, B, and C. It takes an alpha and a beta as well. I mean, it's doing it's slightly different operation. So it's not exactly matrix multiplication, but it's essentially doing this essentially the cuBLOS matmul that I showed you before, where it does the alpha term times every single element in the matrix that we calculate in the actual matmul output, and then it adds beta plus a C matrix, and then assigns C to that new one. So it's a slightly different operation that we do, but we're mainly going to worry about the matrix multiplication mechanics that get us to this temp variable. So when we look at this, we have M, K, and N. So it's a matrix of shape. So A is shape M, so it's M vertical. That's the batch size, you could say, and then it's K as the length, the number of columns, right? And then the B matrix is going to be K vertically and N long, right? So we essentially pass it in the same way, and we index them the same way, but in this example, in Simon's example, we just pass these in differently. So it's M and N as the edges, and then K is the middle one that we want to pay attention to. So we save that for the third one, I guess. Maybe that's the thought process there. But anyways, we have X and Y, so row and column. The Y is the same as the row here. So which Y index is it at? Because a row, row is vertical. It can be this row, this. It's a vertical scale, right? And then the X is columns. So which column is it at? This is horizontal. And so we make sure it's not out of bounds, and then we continue with what's inside of that little chunk of memory, and we proceed, right? So we have this accumulator sum, and then we have this L term. We could say that's the length, and then we have this K, which is the length of A, and then the height of the height of B, right? So when you're dot producting, you're taking the row, a row of A and a column of B. So you're iterating over K and A, and you're iterating over K and B, right? So that's where that comes from, that K stuff. And so you're just iterating in a row, you're going through A like this, you're going through each piece, like each number. And then in B, you're going through each number vertically, right? And then we just plus each time. And then this sum output, this accumulator, is just going to be essentially so A, we're looking to multiply the first element here by the first element here, and then advance, and then advance, and then advance, and then advance, right? That's what we're trying to do. You could also think of it as like a nice way I like to visualize this is like a 2x2 tile. So you have like a 2x2 tile. I'm gonna try to visualize this from your perspective. You have like A up here, and then you have B down here, and it's like, is that correct? Maybe it's it's A here and then B here. And so when A has like a row, that row is gonna like point to like the y coordinate in C, and B is going to point to the x coordinate in C. So when they intersect, it's going to find the index in C that you're going to calculate that dot product result from. That's a cool way I like to visualize it for. But anyways, getting back to the point. So we have this row times k. So like, which row are we at? The length of the row, right? Or sorry, which row are you at? So which row relative to, the CUDA architecture itself, and then k, which is the length of it. So you're going down, you're essentially like wrapping, you're striding around, and you're doing this as many times as you want to, like depending on which row you're at. And then you add the k offset to it. So you might not be all the way through the length of it, and so you stop, and that's where that plus comes from. And then same thing for here. We have this L term, which is k. So how, essentially, which column are you at, right? So here we have rows, and then here we have columns. So it's L, which is essentially the length of that vertical, the length of a column, and then you iterate over n times, right? So n is the length there, and so you essentially advance as many times you need to the I guess you could say to the right, and then you offset at whichever column index it is. So same idea. We're just advancing, instead of going rows, we're going columns, right? And then we just essentially assign whichever. In C, we index it like we go row times n. So it's an m by n. So it's going to be like m is here and n is here. So it's going to go row number times n. So it's going to stride n every time it wraps. And then it's going to do plus the column index, which is that x component, right? And that's how you do the naive again. Just to give you a little refresher there. That was a while back we did it. And then the same idea here. So you have m and n. You have the accumulator. We have this I term that we're iterating through, and we have k. And then we have this temp term, and we go x. So x is the same as row. So notice how row is assigned to y, and x is well, I actually got a little bit stuck there. I was looking at the block and thread indexing scheme here, and it was kind of misleading. So like, notice here how we have rows, and those are by the y index. So whichever y position it's at, that's like the row that it's going to pluck out, or the column, it's like x. So it's going to pluck out a row, or sorry, a column. In this example, we do like x. So that refers to like right here. Is picking out, like, it kind of makes sense, right? Like x matches up with x and y matches up with y. But when we look in here, like in comparison to this, it's like the row times the stride of k. So we're going to stride the k length over, and then come back to the next one, and then offset with L. In this one, we have x, which is like a column index, right? So it's like, why would you do that? We want a row index. But this actually works, and we don't have to worry too much, because this is a square matrix. So because these values are actually the same, because the grid and the thread index in both the x and y dimensions are equal, we don't actually have to worry about that. So this is something you'd want to pay attention to in rectangular matrices, but we don't have to worry about this right now. So just kind of assume that we can kind of just say that this is like y and treat it that way. But I'm not going to edit this because we might have to deal with this later on in future kernels. So you kind of get the idea though. This is very similar to what we were doing before. Don't pretty much just don't worry about the indexing scheme. It's going to be fine. And then literally the only change here is that we write out using alpha, beta, and C, right? So that's really the only difference there. So let's go ahead and actually run this now. So we pop into sgem CUDA, and then we go into build. Now we can go sgem, and then we go number 1. So this is the naive kernel that we run. And we can see that we're going to do a max size. So dimensions m equals n equals k, right? So these are, okay, I might have lagged there for a second, but yeah, I mean, as we can see, dimensions m equals n equals k, right? So these are all the same. It's just like 128 essentially, and then 256, 512, 1024, all the way up to 4096. And we can actually see the throughput in gigaflops per second. So what this means is how many billion giga, right? Giga is 1 times 10 to the 9, so billion. And then flops is floating point operations per second. And this is on a given size, right? So on size 128, we get on average 46.2 billion floating point operations per second. And on 4096, we get about 166 billion floating point operations per second, which sounds like a lot. That sounds like a lot of operations, right? 166 billion per second? Wow, that's really high. But the answer is, that's actually not that high. It's going to get a lot higher than this. So high, actually, that it's going to seem like this is minuscule. This is going to seem very, very small and actually slow. So notice how this took, about 0.83 seconds to do 50 runs, right? So very, very slow, or no, per run, sorry. So not for 50 runs, but for each run that it did, which there were 50 of, it took about 0.83 seconds to do that on 4096 with a naive kernel. So a few other points before we actually jump into this. I want to first look at the blog post here. So when we're calculating the output in the naive implementation, I mean, like even just like looking at this, it's like really intuitive. I love this example, but anyways, when we actually look at the simple naive kernel, essentially we're trying to find a certain part inside of, we are trying to find a certain index inside of C that is going to be the output. So we're saying we want to do the fastest possible calculation to get, say, this number, this index calculated in the C output, right, in C. And so right now, the way to do that is to load in a row and a column and then just calculate that. That's what we found out naively so far, and it takes very few lines of code to do that. And so we just kind of iterate through, like I was saying before, how you put A on the side here and you let them sort of act as coordinates. That's what I was referring to there. But anyways, that's kind of one of the goals we want to keep in mind is how do we calculate the output index. It'll help provide some context on how we actually get there, because when we deal with more complex kernels, you'll actually see there's a lot of steps to actually get to a certain place. And so it helps when you're able to keep in a consistent frame of thought where it's like, okay, how are we actually ending up at this result? And then you can sort of backtrack through and see what's happening. So instead of just like going and like reading like a novel from the start of the kernel to the end and just seeing like, oh, I guess like we'll see where we stumble into. It's like you actually want to see what you're trying to calculate in the end, and that helps. And this blog post provides a lot of context on that. So another little note I wanted to add is like, don't worry about 3D structures too much. So when we have the dim3 type and we have the y, x, and z dimensions all populated with numbers greater than 1, like 4, 2, and 3, it's like, don't worry about that. We're not going to be dealing with 3D stuff. It's not going to be that complicated. It's going to be more so like, how do you transform one-dimensional and two-dimensional dimensions and index efficiently. So don't worry about 3D stuff. We're not going to do any of that. And then the actual indexing scheme here is giving us coalesced memory access. So I'll jump into this in the next kernel a little bit more in depth, but essentially what's happening is when we're doing this like row calculation, for example, when it goes through each row, essentially what's happening is we have this like X term from here, and when we put this X term in, all of the like in CUDA, when you have adjacent, meaning like in the X dimension, in like the length part, horizontal, when they are next to each other, you actually get coalesced memory accesses. So when you're accessing A, you can actually in assembly, it's actually going to group multiple of those together into one. So when you have like when you have a block, inside of that you have a warp, and inside of the warps you have 32 threads per warp, right? And so we can, like inside of the actual warp itself, it's going to coalesce memory access if possible. And when things are adjacent, it actually makes that possible. So that's kind of why we're seeing the weird indexing scheme here. Again, doesn't work for rectangular matrices, but in this case, it's kind of an efficiency improvement for indexing the A matrix. So before we pop over to the global memory coalesce kernel, I thought I should probably highlight something. So this is important to know for all kernels and even the previous ones too, but this is just kind of like how memory is laid out, right? So when we have a 2x2 matrix, 1, 2, 3, 4, in memory, this is going to be laid out as literally just a vector 1, 2, 3, 4. So when we want to, like, for example, in A, when we want to go to the next, essentially the next row, and then do an offset, what we're doing is we're going current row times K, which is this dimension here, the horizontal one. So we're doing, let's just say we want to get to the number 4 here, right? So if we want to get to number 4, it's going to be current row. Well, the current row is going to be 0 and 1, right? So current row is going to be 1, and then K is too long. So it's going to be 1 times 2, which is going to give us this index. So like the array at index 2 is this, is like 0, 1, and 2. And then the offset from that is going to be the column index. So that's going to be 1. So it's going to be 2 plus 1, and it's going to give us array at index 3. So that's just kind of what I mean by strides. It's like how you go and you like jump across the whole row. That's kind of what I mean there. But going into this global memory coalesce kernel, roll down, and I'm kind of gonna like skip this part and just lay it out for you. But the whole idea here, and this is the critical concept. So the matrix memory layout, as I just highlighted, it's gonna be consecutive in memory like this. So it's gonna be it's gonna be laid out like that. And this is not gonna be consecutive memory, right? So when we do dot product of this and this, it's going to go to the third row, and this is going to go to the third column, and we get this value, right? This is consecutive, this is not. In the naive kernel, we jump through these and we iterate through A. So we start off with this like B column, and then we go, and then we go to the next one, right? We index in that fashion, and we advance through the arrays in that fashion. And what we end up with in the output is we get this stack of blocks, right? And this is what it looks like when we write to the output. It's going to be a stack of blocks because we write vertically as the rows advance in A. That's what we prioritize. However, if we instead coalesce the memory accesses, we can get these laid out in this fashion. So essentially what we're doing is we're changing the indexing scheme here. All of this essentially remains the same, except we change the way that this is indexed, and we ensure that we're using thread IDX, right? So remember when we did, when I was previously talking about how all of the X, like the thread IDX.X component, those are grouped together in a warp. So if you have, like, for example, block size 32, there's going to be 32 threads in a warp. That's the maximum. And so in like blocks, if you have this like this square block, it's like 32 by 32, and you get the X dimension, you're going to get the maximum number of threads in a single warp if each element there is dedicated to a different thread, right? And so this way, you're maximizing the memory accesses, because you can put all of those together and you can make that you can make that data transfer operation much more efficient when you let an entire warp take care of it. It can do all the values at once, or group them together and make them like way faster, as opposed to going through each individual like Y component, right? So when it goes like thread idx.y, it's actually not as efficient, right? And so we kind of just changed the indexing scheme here with these. So to sort of illustrate the previous point, I wrote a little table for like what's in the brackets here. So this division of thread IDX and block size, then the modulo of, or the modulus of that. So I just kind of wrote out a table here of what these would actually look like in practicality. So if we just assume block size is 4, which, I mean, it's not in this case, but we can just simplify and understand what's going on. That way I don't have to write out like a bunch of numbers. We assume block size is 4. And so because block size, the size of an individual block is 4, that means the thread IDX is going to have 4 indices in it. So it's going to be thread IDX 0, and then 1, 2, and 3. It's going to have 4 inside of it, right? So when we divide, we're going to floor the operation. That's just what's going to happen naturally, is this is going to get floored. It's going to truncate the end of it because we're doing integer division. And we're going to get 0, 0, 0, 0, right? 3 divided by 4 is 0.75. It's going to truncate 7.5, and you're still going to have 0. And then we jump up to when like this advances, then it's going to be, well, the block size is 4, and when the IDX jumps to 1, then it's going to be 1 times 4 is 4, and then plus 0, and it kind of just like resets, right? Except it's plus 1. So we have that going on. And then we have the modulus as well. So modulus is you divide, so 0 divided by 4, like integer, and then what's the remainder of that? So if we do 1 divided by 4, that doesn't actually equal a whole number, so you end up with a remainder of 1. And then you do that for the rest of them. So like 3 divided by 4 is, or 3 mod 4 is 3, and then 4 mod 4, since it just equals 1, there's no remainder left, so it just is 0, right? And you get this thing where it's like 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, and then here it's like 0, 1, 2, 3, 0, 1, 2, 3, right? So when we actually look at this example here inside of the, where is it? No, not this one. Inside of the coalesce kernel, notice how, I'm going to show you a second in our code, how this row does not actually change. And what we're doing is we're just indexing very carefully these values. So when we have different threads that are like, because each thread is going to calculate its own dot product, right? Like this thread and this thread adjacent to each other in the same warp, they're going to access adjacent values. So when they're accessing adjacent values in the same warp, you can actually group all these together. Whereas instead, if you just did this one, if you did this thread and then this thread and then this thread, that means that the first index of all those threads, you cannot actually coalesce that, because you have to do like a stride, and they're not adjacent, right? So that's essentially what we're doing here. And then we end up with this, like instead of a stacking like blocks, we end up with this horizontal layout. So when we go here, we can see that C row. So this is only actually going to change every time we advance, right? So this is going to stay at 0, which means that C row, that's going to stay at 0, and then the plus I part, that's going to advance with the dot product itself. And then here, I is automatically going to advance, so that means it's going to it's going to advance a column each time, while the row is going to stay at the same place because C row is staying at 0, right? And so you can kind of see how this works out. We have C column or current column, and this is actually going to change over the threads. So it's going to go 0, it's going to go 0, 1, 2, 3, 4, and then it's going to jump to the next block IDX, right? And so what you end up with is literally what I just demonstrated. You end up by essentially each thread within that warp is accessing an adjacent value, and so you can group those and coalesce or combine the memory accesses together, and we get more performance efficiency with this. So that's kind of like what this article, this section talked about. And if we bump back to here and actually run this, so kernel number 2, we can see we're actually getting a lot higher gigaflops on this one. And then we can see that we get about 1183 gigaflops here. So that's actually a pretty big increase of performance. I think previously it was about 100 and what was it? Like 180 or something, or like 100 and 160, I can't remember. But it was very low. So this is actually like significantly, it's like almost 10x higher. This is like maybe 5, 8, 10x higher than what we had before on the 4096 square matrix, right? So that's actually a crazy performance improvement. We were previously at like 0.83 seconds per run, and now this is at about 0.12. So if you actually do the math there, it's 83 over 12. That's about a 7x increase in performance and throughput. So that's pretty good. Now we can move on to shared memory cache blocking, which introduces a different concept, still uses what we've currently done, but introduces a whole nother paradigm that's going to really help accelerate and speed things up. So next we jump into something called shared memory, or SRAM. And this is absolutely critical to take care of when we're optimizing algorithms for performance. So let me just kind of explain what the deal is with this. So right now we're using global memory, right? The host is just our little RAM slots going to the CPU, and that's like really slow. That's about 5 gigabytes per second. Still fast, but very slow compared to this 200 gigabytes per second that we get with our VRAM. This is what we're using now. Or you can get even faster and use shared memory, which is around 1.5 terabytes per second of memory bandwidth, or registers, which is about 8 terabytes per second of memory bandwidth. But we're just going to focus on registers right now, or sorry, shared memory right now. Now in this blog post, he had about 700 gigabytes of global memory bandwidth, which is really fast compared to this, and then about 12 terabytes of or 12.1 terabytes of shared memory bandwidth. So, or sorry, not 12 terabytes, 1.2 terabytes of memory bandwidth, terabytes per second. Now, how do we capitalize on that? How do we actually use shared memory? Well, it's actually easy. You use this little keyword called, it's not here, but I have it. It's called shared. So shared memory is literally just how you use that little L1 cache. So when we look up at the actual architecture of this, I could open image in new tab. So you have your global memory, so like the big chunk of memory that you have, that's about 200 gigabytes a second. Then the L2 cache for like a transfer medium, and then in each little SM, or streaming multiprocessor, these have their own little L1 cache, or the shared memory, and this is very small compared to these two, right? But they're extremely fast, and they connect directly with the registers and the cores on your GPU. So when we can utilize these, there's actually far less travel distance you have to go. So instead of like every time you need to access a float, you go all the way through like SMEM or shared, and then to L2, and then to global, you literally just store a bunch of them temporarily in shared memory, have all of the threads use them for essentially do a ton of work with the memory that it has. And then once you're finished with that, you can replace it. You can write new values from global. So instead of writing from global every time you need to access something, you instead preemptively load a bunch into shared memory, and then you use them for a bunch of work, and then you replace them with a new one once you advance, right? And sort of the goal here is just making sure that we do this properly. So if I just go out again, shared memory is located on chip, much lower latency, higher memory bandwidth. He did this on a Volta GPU. So to go over how exactly we'll be using shared memory, it's actually a bit of a different philosophy. Now I'm not gonna write this out and everything because it can get quite intensive when we write stuff out. But this is essentially what we're doing. We're doing a little thing called tiling, which I demonstrated earlier, where you have little tiles that you do matrix multiplies for in a bigger matrix multiply. So instead of doing rows and columns, we actually go and do something a bit different. And instead what that is say we have this chunk in C here. And so what you would do is you would essentially, like, if you have, let me try to use the current VS Code thing as an example. So we have this, we have a C, right? Now going back to this one, I'm gonna try to explain. This is tough to explain, so bear with me. We're essentially going to load in tiles, and we have this little C, like the coordinates here. And all we're going to do is we're just going to multiply these two together, and then multiply these two together, and multiply these two together, and then we just essentially multiply every matrix, and then that like coordinates up to this final thing here. So we go like through this way, and we start at the very the very top of B and the very left of A, and we multiply those together, and then we add it to the next ones. We go in and in and in and in and in until we maybe cross or something, and then that intersection point, right here, that's where C is, right? And so when you have a bunch of these smaller, less intensive matmos that can be actually done on blocks, on thread blocks, then it actually makes the job a lot easier. Because what you can do is you can be smart about it and actually store these blocks in shared memory, right? If you're doing individual rows or columns, I mean, sure, you could do that, but it actually allows us to distribute some of the work more when we're using blocks, when we're using literal tiles of the matrix, right? So let's go ahead and dig into how this actually works under the hood. You're going to understand sort of how tiling works more once I explain it, and how I explain how everything advances as we dig more into detail. But this is the idea here. We tile and we store these blocks temporarily in shared memory and do as much work with them as possible. Okay, so this is the code for a shared memory cache or tiled matmul, you could say. And pretty much a lot of it, well, not a lot of it, but the start is pretty close to, or actually the exact same as the last kernel we wrote. So we have this C row maps to block idx.x, C row maps to block idx.x, and C column is .y, C column is .y. Now we have this thread column maps to the mod operator, and then row maps to division operator, right? So row maps to division and column maps to mod, right? So these are the we essentially use the same idea as before, and then we add this additional piece in, which is going to allocate some space in the shared memory, which is going to be of size block size by block size, right? So it's just giant thing. You could say that each of these little rows just wraps around, and you have this super long thing laid out in memory, but we're going to treat it as an actual block, like a square. And so why we use block size by block size is because if we just say, I mean, we're going to lower what we interpret block size to be in the examples just for intuition purposes, but in practicality, this would be 32, right? Block size would be 32. You have 32 threads that fit in a warp, and maximum 1,024 threads per block. So if you actually divide If you divide 1024 divided by 32, you get 32. So what we end up doing is we have a warp takes care of these, warp takes care of these, warp takes care of these, and we have we're literally taking up the maximum amount everywhere just by using block size or a shared allocation of block size by block size, right? That's the idea there. And so we go down, and I'm just going to pull this up on the side here just for reference. So in A, what we do is we say we're going to advance the pointers to the starting positions, right? So essentially, we're going to multiply C row. So we're going to do C the current row times oh, you can zoom out, the current row times K, right? So K is going to be this dimension here, this long one, the horizontal one. And so if we multiply the current row by K, let's just say we have like a current row of, if we want to do current row of 1, right? So we want to do current row times K, which is this length. So it's going to jump down to this one. And then we want to do times block size, which in this case, since we split it into a bunch of tiles, is going to be 2, right? It's going to be 2 by 2. And so we end up jumping 2 instead of that. So we go, the current row is going to be 1. So we're going to do this one here. So it's going to jump the length of that times the number we want to do, which is essentially 1. So we want to jump down 1, and then that doubles because we have block size equal to 2, right? So it's going to jump 2 rows, and then we end up exactly where we want. We want to start at the first number on the first like essentially tile of this row, right? And then B, we advance that pointer to the current column times block size. So in this case, B, let's say we want B to be like 2, right? So the current column is 2. So we do 2 times 2, which is 4. So we go 0, 1, 2, 3, 4, and we end up there, right? So very intuitive. And then we have C, which essentially combines the two. So in this case, we want to do C. So it's gonna be it's gonna be this row and this column here. So we're gonna end up, it's going to be the first row and then this column. So it's going to be this tile that we want to take care of. So it's going to jump over to this one from the what's it called, from the A matrix. So we're going to jump all the way to, or what was it? No. In B, we're going to jump all the way here, and then in A, we're essentially just going to add the we're going to add the offset, right? So we want to jump down to because this is the n dimension. So instead of multiplying by K, we would do times n. So it ends up being like essentially this. We essentially this plus this, right? Except instead of using K, we use n because that's the length of C, right? So that's the idea there. And then we end up at I believe it was this tile, the 24, 25, 34, 35. So we continue to go down, and this is where we define our accumulator, right? So the temporary accumulator we have, and then stuff really gets interesting once we get inside of this for loop. This is where the magic happens. So we have this term block IDX, and we're going to iterate over K, right? So K is that the row, the columns, number of columns in A, and the number of rows in B, right? So we're going to advance block size each time. We're going to advance block IDX by block size each time. And so inside of here, initially, we want to store the stuff in SRAM, right? Or shared memory. So we want to store it in here. And literally all we do is we look at the index inside of here. So thread row, which row is it? Times the block size. So block size is going to be that stride or that wrapper, and then plus the thread column. So which offset do we want to be at, right? It's going to pick out a certain spot in there. And luckily enough, I picked a block size of 2, so it's going to be 2 by 2. And that actually makes our job a lot more simpler to understand. I mean, you can abstract it up to like 4 or 8 or even 32, but we're going to stick with block size of 2 for now. And this means we're just going to have a thread index, thread idx.x of 0 and 1, right? So very, very basic threads to work with here. And so we're essentially just going to load into this shared memory, which we defined up here. And we're just going to essentially that little spot inside of it, we're going to pick that out from A and B. So in A, it's going to be the thread row times K. So K is going to be that length, right? And then it's going to be plus the thread column offset, right? So just that X, essentially the same idea as what we're doing here. And then we're going to have the same idea for B, which is going to be N. So N is that, again, N is the top one here. And then K is the top one here. So K corresponds to A and N corresponds to B, right? I hope that kind of makes sense. And then afterwards, we just sync up everything. So this part's a little weird because we're doing like sync threads, but this kernel itself, like everything in here up till now is like a thread. So what this means is that in the entire block, it's going to make sure that all the threads catch up to this point. It's going to make sure that it's going to put a barrier and make sure all the threads have like put what they needed to in memory. Or else if we start doing other things, then you might have like a 0 value there where there's nothing that exists at that place in memory. And you're using that to do operations, which is then going to make your answer wrong. So you want to make sure that all of the threads within the block are actually caught up to here. So like these are on the level of threads, but we're essentially telling CUDA that we want all of the different threads that are doing all these parallel operations to catch up within the for loop. That's what we're doing. Then we advance A. Then we advance A by block size. So this is just like advancing it preemptively. We already have all of this stuff stored in shared memory. So we can actually just advance A. We can advance the A pointer, because remember, A is a pointer, right? We can only actually use like the index to get the values, but A itself is a pointer. So we advance that in memory. We advance that in the memory space by block size. So A is like this side one that's like going to point inwards to C, and then B is going to point downwards. So A is going to advance a single block. So if A is like here, for example, A is going to advance block size, so 2. It's going to jump to here, right? And then B is going to do the same, but it's going to jump. So it's going to go. It's gonna jump N, right? So N is like this length. It's gonna do block size times N. It's gonna jump down 2, right? And it's gonna do exactly what we want. So it's going to advance the tiles in the directions that we expected them to. You might have had some confusion about how we're just using like the thread columns. And just a reminder, this A term is already advanced to the correct position, right? So once we're advanced to like this tile, for example, then we can pretty much just use threads. We can use the thread indexing scheme, and that'll give us exactly what we want. So now notice inside of this for loop, we have the same indexing scheme as we did in the global memory coalesced kernel. So when we're just efficient about going through the columns and having the C as like a horizontal layout instead of like a vertical stack of blocks, we're just doing the exact same thing here, right? And so you might be wondering about this temp variable. So this temporary is just going to start off as nothing, and all we're doing is each thread has its own temp variable, right? That's going to be stored in the register. Each thread has its own temp variable, and it's going to accumulate this temp variable for it's going to accumulate a dot product. So what this is going to do is it's not actually going to multiply matrices together. Instead, what it's going to do is it's going to just accumulate as it goes through tiles, right? So as it goes through, it's going to like accumulate each value in the output of C as it goes along, right? So based on the thread, it's going to say one is going to do like the row of this one and then the column of this one, right? And so when they interact together, or when they interact, they're going to end up at like this top left part maybe, and the thread holds the temporary value for that specific part. And what it's going to do is, like, as it goes down through the tiles, it's going to accumulate this dot product, right? So you get the first dot product, and then you add it to the next one from the next tile, right? Because you're essentially just doing the normal naive matrix multiplication, but you're just accumulating through the tiles. And so in the end, you end up with just this accumulated temp. However, this is only for a single dot product operation. This is only for one tile. And the reason why we have this for loop inside of this one, we're being very clever about this, is so that we can actually do this accumulation through the tiles, right? So that way we can kind of we could just be clever about how we go about doing that. And then after we're finished, we can just go ahead and sync up all the threads, make sure that they're all caught up before we actually write this out to C. So I guess just going a little like iterating over this again, the thread row, so that's like which row within the tile do we want, times the block size, so that's going to be our wrapper, and then the dot IDX is going to be how we're iterating through it. So A is rows, so that's the dot IDX, we're going to go through this way. That's going to be the offset on the horizontal part. And then B is going to be dot IDX times block size, and then plus that offset, as we were doing before, right? So we're maintaining that global memory access, that access pattern that we had before, and we're just simply writing out that temporary variable as it accumulates through the tiles, right? So that's the idea here, is we're accumulating through the tiles. So now we can, hopefully that makes sense. Feel free to rewatch some parts of that. Feel free to plug it into something like ChatGPT or Claude Sonnet or something like that and try to visualize what's happening. I have a separate additional like diagram here just of like what this looks like laid out. I decided to add this to the course assets folder inside of the faster matml section. So if you want to check this out, I might add other ones to it, but this is the shared memory blocking CUDA kernel. So now we can actually go in and profile this thing. So pop up into here and just go sgem number 3. We run this for a second. It's going to be really fast. And so if we actually compare this, give it a second, it's doing the last one there. So if I actually compare this to number 2, which wasn't, give it a second. Yeah. So our number 2 with just the coalesced memory access was achieving about, 1200. And this one was achieving about 1600. So we have a decent improvement from that, right? But I probably should have done this earlier, but just to spoil the surprise, cuBLOS is actually a lot faster. If we run the 00, cuBLOS is about 11,400 gigaflops or 11.5 teraflops, which is really fast, especially compared to our previous our previous naive kernel, right? This is extremely fast. Now, just to iterate before we move on, this shared memory kernel, this is not implementing like the full version of tiling. This is just implementing like a partial dot product version of tiling known as blocking. So when we accumulate like dot products, that's not actually like the full, like what you would intuit as tiling, right? Tiling, as I described before, is when you like take the matrices, you multiply them, and then you advance, and then you multiply again, and you like add them every time they multiply, element wise. And this is not what we did here. What we did was a partial dot product. So keep that in mind. The next one is going to be a little bit different though. So 1D block tiling is a bit more advanced, but we'll get through it. So just to help get tiling crystal clear in your head, I'm going to use two matrices as an example, just to show how this intuition works. And I've actually written out, I was testing a little bit, and I did the math wrong by hand, so we're just going to use the computer for that. But I wrote out a matrix A here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And then this one, B, it counts by twos, but it goes backwards. So 2, 4, 6, 8, 10, 12, 14, 16, and then continues up to 32. So I've written these out here in the terminal. And if we just do A multiply B, we notice that we get this output result. And these are pretty easy numbers to work with, right? So what I want to do is work specifically with this upper right tile, the 200, 180, 456, 404. That's exactly what I want to work with. So how we're going to do this is we're going to use an idea from here. To get this top right piece, we essentially want to cross inward, right? So we're going to start off with multiplying A, this A portion, with this B portion. We're going to multiply those together, A times, not B times A times B, and then we're going to add that with the product, the matrix model product of this piece and this piece, right? So if we start off first by doing 1, 2, 5, 6, we can go say A temp torch dot tensor, and then inside of here we're going to have smaller ones. So it's first going to be 1, 2, 5, 6, and then we multiply that with torch dot tensor torch dot tensor 4, 2, 12, 10. Right? And if we print out A temp, we get this result. Now we do B temp torch dot tensor, and I'm just gonna print the actually I'll just print the layout here. We'll do the same idea for A temp, but I'm just going to remove these values and we'll replace this with B temp. So this is going to be 3, 4, 7, 8. Multiply that with 20, 18, 28, 26. All right. Okay, awesome. Now we print out btemp. Oh. And then we do atemp plus btemp. And we get the result that we were expecting. 200, 180, 456, 404. 200, 180, 456, 404. And that's a top mammal. That's really all there is to it. It just helps when you're able to draw this out by hand and understand what the purpose is when we like advance, for example, when we advance pointers by like a greater offset than like 1 or 2 or 3 or 4. It's like when you're skipping entire rows and you're going to like a certain, when we do that stuff, this will help you understand why we're doing it. Yeah, we can go ahead and begin. Awesome. So now let's go ahead and look at the boilerplate code for this, as well as the runner script for this. So in the runner script, we'll actually pop down and you can see each little like function and how we call everything in here. So like the kubloss function, for example, there's like different ones. There's like fp32, brainfloat 16, tensorfloat 32, right? And then we have like the naive, the coalesce, the shared mem caching, which we just recently did. And then we have the 1D block tiling, right? So notice how in the shared memory block, we just have 32s everywhere. We have 32, 32, 32, 32, and 32, right? Everything's 32 because everything is a square. But in this one, we actually mix it up a little bit. So we have these, essentially this block. So M, it's going to be this block on A. So it's going to, like, because it's specific to A and C. Because when we do our matrix multiplication shapes, we're going to cancel out the inner ones, K, and then we're going to be left with M and N, right? So just pay attention to these shapes here. We also have the 8s down below. So just like be aware of this. We use different shapes here to help speed up operations because we introduce a new concept. And that concept is 1D block tiling for calculating multiple results per thread. So if we actually go back into the shared mem blocking, when we write the output, we have this specific index per thread that we write out. It's just one. We write out one output of that block, or sorry, of that tile, and that's it. We just leave it at that. There's no iterations. We're not writing multiple per thread, just one. Now, if we go to here, we notice that we're actually writing multiple. So we go over this res, or this result IDX, that's essentially goes, it iterates through TM, which is this term that we found in here, which is essentially threads per M dimension. You could think of it that way. So in short, we're going to be writing out multiple results per thread, and that's going to speed up everything a lot. So like imagine if you had to do, you had to issue a new thread every time you're going to write an output of this entire matrix. So if you have a 4096 by 4096, that's going to be about 16 different threads that are writing out, right? That is a lot of threads. You have to, there's a lot going on there. So when we iterate over, we can get one thread calculating multiple and make things more efficient. It does make the indexing more complex, and this is probably one of the most intuitively difficult kernels to understand. But once we get there, it should be a breeze. So going up to our boilerplate code, we have this C row is block IDX.y. So we're going to use blocks. Each individual block of threads is going to calculate a specific tile on the output, right? So we have this block, essentially the current row and the current column. So current row is like, it's like vertical, which row are we selecting? And that's Y, right? So that's vertical. And then the column, like we were doing before, it's, you know, horizontal dimension. Now we go to here, which is essentially the thread, the lower level thread column within that. So we have this BN term that's used, and this BN term, if we remember back to here, was 64, right? So let me pop back to this. This BN term, we see it in both the B matrix and the C matrix, right? This is BN, right? It's that length right there. So when we actually, when we do mod BN, what that's going to do is it's like, if BN is 64, it's going to be like thread IDX like 0 divided by that. It's just going to be 0, right? And then it's going to go 1, 2, 3, 4, 5, because we just have this remainder that's like not 64, right? So once we pass 64, then it's going to loop. So it's going to iterate through all the columns, and it's going to go up to like 0 to 63. And then once we actually hit 64, it's going to divide, right? So it's going to floor up, it's going to floor to 0 for each of these indices leading up to 64. And then once we actually hit it, it's going to divide, and it's going to go to 1, right? Because it's going to floor down to 1, and it's going to be like a bunch of zeros and then a 1, right? And we use this to pick out our rows. So the columns, it's like 0, 1, 2, 3, 4, 5, all the way up to 64. And then the rows, it's like every time we stride this many, it's going to bump up 1. So the division is going to go up to like 1 and then 2 and then 3 every time we stride that 64 length. And then it's going to increase the row index. So it's essentially going to be like like I said, a row index. It's going to move us downward, right? In C. And this is kind of why we have this here. So moving further down, we have the A shared and the B shared. So just the normal shared memory that we allocate. So this is going to be M by K and then K by N, right? That's the space we're storing. And then in this specific thread, we advance the we advance the block tile to the beginning of A's row and B's column, right? So we did the same thing in our past one where we advanced everything forward, right? So this is literally this is literally the same idea, right? So we're doing the exact same thing there. We're just using a little bit different terms because it's now rectangular tiles. These assertions here are pretty much in place to say we don't want to go out of the blockdim.x range, right? It's just like essentially like you could think of it as a boundary checker. So when we iterate through BM or BK, we don't want to go out of range. We want to make sure that these kind of add up. We want to make sure that when we have this like 2D structure, that when we flatten it out, it stretches the length of blockdim.x, and that's pretty much what's happening there. We assert both of these. So essentially, when we go back, it's like, n and k are the same, and then m and k are also the same. So that kind of lines up there. And then for these ones, the same idea as what we were doing here. So the thread column, so we do this dot x divided by the x dimension there, which is bn. That's the trailing dimension in C. It's going to be m by n. And so in here, we just do thread idx divided, or for the column index of A, the inner column index of K, or A, sorry, we're going to do thread idx mod bk. So bk is that horizontal dimension in A, right? Because it's m by k. And then the inner row in A is going to be just the division of that. So whenever we stride the length of k, it's going to notch up one, and it's going to tell us which row index we're at, right? That's kind of how we use the threads to decide which index we're at. And then same idea for B here, except we use the trailing dimension in B, which is n instead of k in the A matrix, right? And then we essentially here we allocate memory. This is going to be very important for when we write things out later on. So notice how we iterate over this term tm. We're going to make thread results like an actual thread local cache that has the size tm. Tm is very small, right? So in here tm is actually 8. So that can easily fit in registers. And then we just initialize this with a number, just say 0, and then we're going to populate that later on, right? So we just initialize this beforehand, and then we're going to change it later. Now we actually jump into a little bit more advanced stuff. So this entire loop here is where a lot of the magic actually happens. So when we're in one of these iterations, we are trying to calculate the complete tile for an output in C, right, within a block. That's what we're trying to do. A block in like a certain block IDX within the grid is going to calculate an output tile in C. That's the goal here. So we loop over these block tiles by iterating over K, right? K is the horizontal dimension in A and the vertical dimension in B, right? So we iterate over those and we advance by this much each time. We're not actually going to use block IDX. Like, as you can see, we only actually have it in this one line here. It doesn't show up anywhere else. So this is just for making sure that we don't, if we just like iterate by 1 each time, then it's going to go out of range. And we're going to do this loop way more than we need to. So we just want to do it for as many blocks as we need, right? We then populate the shared memory caches. So this is within a single tile, right? So notice how we use the inner row A times K, right? So that's which row are we at inside of it? And these are like very small ranges of indices, right? And in A, it's gonna loop around K, and then that extra column index is gonna tell us which position we're at, right? Relative to the thread, of course, so we can like parallelize the actual loading part. And then we do the same thing for B, right? So we have this row, and we have like which row are we at, and then we want to essentially stride that number based on n and then end up with that offset column index. So that's what this is here. We sync everything up. So this is again at the block level. So a kernel normally runs at the level of threads, but because we're doing sync threads, it's going to apply to all of them. So all of the threads within this block are actually going to line up. We're going to put a barrier, and they're all going to meet up, and they're going to synchronize at the same spot, right? And then we just advance the block tile for the next step. So when we need to do this load again, this is already ready, and we don't want to like worry about this anymore, right? Okay, so remember A and B are just pointers, right? When we scroll up, we see A and B are pointers to float arrays, right? So when these are laid out in memory, they're not like, it's not like an array of arrays, or like an array of pointers where each pointer inside that array is a new array, like we did in the C and C++ review chapter. It's not like that. It's literally just a pointer, and the pointer is at the start of that thing, that's start of the array that's laid out in memory. So it's not the actual value, it's just the memory address. So if we take that memory address and we +1, it'll go to the next index, next one, right? That's what we're doing here. So we already did this we already did this here, where is it? This part, we just advance further. So A advances essentially plus an entire block size. So we advance we just advance plus whatever this value is to A. So it's just going to increase that much, whatever we set that to. And then this is going to increase, but it's going to have that n stride, right? So the trailing dimension in B is n, so it's like k by n, and so it's going to wrap, right? It's going to wrap, and it's just going to find the sort of the next one in B, right? And that's really all we're doing there. So then we go to this next part. This is where actually a lot of magic happens, and I'll do my best to explain this, but this part's like kind of intuitively hard. So we have multiple for loops in here. We have this .idx that we iterate over bk with. We have this float. We have this specific float. This temporary variable, and then we have an inner loop here. So I'll try to explain this as best as possible. We jump back to here. We notice how, like initially, we have these two matrices that we're trying to multiply together. So this is A and this is B, right? And we have this tile intersection as we did on the whiteboard there. And so really the magic happens is like in these loops, right? We've already taken in this outer one, we've already actually taken the block tiles. We already have these in shared memory, and now we have to do fast operations with them. So we go down to here where we actually have these in shared memory, right? This is a tall and not very wide. This is wide and a little bit taller, right? So it kind of matches up. And then inside of here, what we do is we notice how we iterate over .idx, and then in here we iterate through this tm, right? So we have this .idx and then res idx over tm. So if we actually pop back to here, essentially what's happening is this at the lowest level in the innermost loop, res idx is going through, like we have this jump here, which I'll explain that indexing in a second, like how we actually arrive there. But res idx is going through these. It's advancing vertically downward, and it's multiplying with whatever value this is. So that little top left corner in B, that top left corner value in B is going to stay the same. And res idx is just going to multiply with that value. It's going to go, and it's going to compute a partial dot product along this column. Right now when we iterate over .idx, what's going to happen is .idx is going to go forward this way, and it's going to go down this way, right? So notice how these arrows are colored very similarly. They're actually the same color. So that means we're gonna .idx is going to evolve downwards in B, and .idx is going to evolve to the right in A. So whenever we evolve like one, it's gonna like essentially res idx is gonna take this value, it's gonna go, and then we're going to evolve one forward, and then res IDX is going to reset. And then it's going to do a partial dot product for the next column, right? It's going to do a partial dot product for the next column, and it's going to do this all the way until it is finished inside of this entire section. And then when these evolve inwards, right? So when this is going forwards, and like just not even considering res IDX, just like think about like sure these ones are all filled in, this one too, but when this goes forward and multiplies with this, and they are both inching in one at a time as this is what's happening as .idx is moving up. These are actually acting as little, like essentially little tiles, right? And so you end up computing this specific, you end up computing the full dot product of this. So when this one moves, like here, it's like 1/4 of it is done, right? 1/4 of it is done. And then it moves up, half is done, 75, 75, and then it's fully done. Once that evolves all 4 steps, this entire index right here is computed. And so we notice that when we do res IDX and we go through all of these, we end up completing the entire row. So when we go through this way and this goes forward, we complete one column at a time, right? One column at a time is completed per thread. And so when we have other threads acting, like thread column and the thread row, which is acting as these little blocks that are shifting downwards instead of like little individual 1D columns, you actually end up computing the entire thing. So thread column is laid out this way through it's like essentially all the column indices in the B tile. And then you have the thread rows, which are here. And so this is going to compute all of the columns in C. It's going to cover all of them in the tiling aspect. And then this is also going to cover all of them. So what you actually end up with is you complete the entire tile by giving a thread more operations to do. So when we actually jump into this, we can see, so first of all, we have this temp B, right? So this is coming from the B shared memory. So we just say .idx is 0. This is the first iteration. It hasn't, or the 0th iteration, it hasn't changed yet. So this is 0, and it's going to evolve, across bn 0 number of times, right? So 0 times that is 0, and then plus the thread column. If that is also 0, then it's just going to be here, right? It's literally just going to be there. And when .idx moves up, then it's going to it's not going to move this way. This offset here is from the thread itself, the thread index itself. But we're actually going to traverse downward, right? That's the .idx as I was explaining before. And then you have the this res IDX, the result IDX, and this goes through TM, right? So this is this little block that we have here. And when we actually look at how this is accumulating, remember, this is the size of TM. We're going to iterate through TM with this red IDX or res IDX. That's going to be the amount through TM which we've iterated through. We're setting that index to a place in shared memory, and this exact place is going to be the thread row times TM plus res IDX, right? So thread row in this case is whichever one of these it falls at, right? So that's a specific row that it falls at, considering that we evolve like in TM blocks, right? That's the amount that we evolve. We progress each time, and then this res IDX part. Res IDX is how much are we vertically offset. So we advance like 4 or like 8 or 4 or 8 downwards, and then we have this additional offset res IDX. But we have to make sure that we actually arrive at that specific piece, because it's going to be laid out in memory like this, right? So we have to make sure that we evolve straight downwards and that we get to that certain res IDX position. Now we multiply this by the k dimension, which makes this a lot easier for us, right? That essentially solves that problem. So however many we want to go down, this thread, whichever thread row we're talking about, times TM, which is, that block space, plus res IDX, which is that offset, and then times that, all of that times bk, right? This k dimension here, and that's just going to times, it's going to go right where we need to be. Then we just add the .idx offset, which, as I highlighted before, is literally just going to progress that way. So it's going to iterate all the way to the starting position, and then .idx is going to tell us how much has it gone to the right. And so you have this .idx here that traverses downwards, and here it traverses to the right. Now, if we go back, we're multiplying this by this one. We're multiplying it by the temporary v value. Keep in mind, this is the only thing controlling this is the .idx, which we already highlighted. This is going to make it go downwards, and then the thread column. So thread column, as I mentioned before, again, we're kind of just going like starting with the visual example and then going into the code and then connecting that to our visual example. So thread column is that horizontal offset, and that like each thread is just going to get a different horizontal offset, right? So it depends on which thread we're at. And then we go back to here, and we have this thread row, right? So that's just going to depend on which block we're at. So in this case, we're not at thread row 0, we're at thread row 1. So it's going to traverse TM layers down, which in this case is like maybe 4 or 8 or whatever number we pick, right? And then it's going to end up there. And then the rest of the math is going to ensure that we get to the correct position with respect to res IDX and .idx. Some other things you want to pay attention to here are how these actually are coalesced in memory, right? So in memory, keep in mind when we're loading these columns in, when we're loading these little column bits in memory, we're loading them as if they're like adjacent next to each other, right? So this like thread 0 is going to be adjacent to thread column 1. Thread column 0 is adjacent to thread column 1. They're next to each other. Thread column 2, 3, 4, 5, right? So when we actually load this on the level of threads, that memory access is going to be coalesced. So it's going to be combined. We're not going to have to, consider this stride and then like, oh, we need to get 2 memory accesses to get both of these. It's like, no, you can actually fit like a bunch, like however many as you need into one, right? So technically what you're going to have here is you're going to have, since BN is 64, so this whole length here, it's going to have 2 warps. So it's literally going to be like 2 memory accesses that we need to do, because an entire warp, that can actually make memory accesses really efficient. When we have 2, that's effectively just 2 memory accesses that we have to worry about. So it's really awesome that we have these coalesced, right? I mean, this itself, this other one isn't going to be coalesced, but that's fine. Because we're still using shared memory. What we do care about though is that these are coalesced, right? The column accesses are coalesced, and that's going to make things really, really fast. So to iterate, we essentially iterate over and we let the threads complete the columns like partially, and they advance over, and the dot products are going, or the dot IDXs are going to evolve, and they're going to close inwards, and then they're going to complete that slowly. Right, and these individual threads are going to complete the columns, right? So they're gonna move through the res IDX, and then the dot IDXs are going to evolve this way. So you end up just completing a whole column because these line up and this one lines up, and so you get a bunch of these, and then one of these, right? So then we sync up the threads. We make sure that they're all caught up, so that we can actually write out the results safely, right? This is for a specific block tile. So when we have like a bunch of them in the entire thing, we have a bunch of block tiles we're worrying about. We want to make sure that we've synced them up for this current block tile, just for safety purposes, right? We don't want to mess anything up. So we're going to be safe there. And then when we actually write out the results, it's going to be very similar to what we actually did up here, right? So we iterate through this TM term again. And we're going to have thread row times TM plus res IDX, and then times N, right? So N is in the bigger picture of that whole C matrix, and then plus the actual thread column itself, which is going to be that offset. And that's the actual index that we write out. And we're going to iterate over TM, or 8 indices, every single thread. So each thread is going to write out 8 elements, right? Instead of just one, writing out 8 elements. And then we're just going to keep in mind this, this thread results. We're just essentially, each time we write out, it's just going to populate that index. So it's like a very easy way of just keeping track of like which ones we write out at the lowest level of hardware, like SMEM and registers. So it's just going to make our jobs easier on that level. So we could literally just store them one by one. It's like an array of 8 elements, and then we write out that array of 8 elements. We don't have to worry about strides or any of that stuff, right? We multiply alpha by that for each one, right? For each index. And then we do the same with beta. So beta is another term. And we have C, which, C is just, we're essentially just element, we are point-wise multiplying beta. So it's like whatever beta is, maybe like 0.5 or 3 or whatever it is. We're just multiplying each one. And so we consider the strides and the offset as well for that. Okay, awesome. So now we can actually generate, or we can actually see how this performs. So remember how bad our initial kernel was? I'm going to go ahead and run sgem00 just to show kublas. It's going to iterate up, and we're going to get about 11.4, 11.5 teraflops for performance. And then if we go ahead and run the block tiled one, so kernel number 4, we go ahead and run this. We're going to get like actually quite a bit faster than the previous, which was 0.3. And this one, give it a second. This one gave us about 1600 gigaflops. This one is about a 3x speed up of what we previously had, which is really good. So that pretty much just shows that the memory access patterns we use, so that coalescing of memory access, was really, really useful. And even more useful was using a single thread to do multiple computations to compute 8 elements instead of just 1, right? So that really, really sped up our throughput and performance there. So now, if I actually wrote off camera, I wrote a separate function here, or not function, file, main.cu inside of the kernels folder, so just so we could easily like compile it. What I pretty much did is I just imported this, so essentially the block tiling kernel, the header for that right here. I included the macro which we had in the previous file. I initialized the matrices, so 1024, 1024, 1024, and then our previous like 64, 64, 8, and 8, and then I just populated these. CUDA malloc manage just use like this unified memory, which is like gonna just reduce a bunch of boilerplate and make things a little bit sped up for us. But you're gonna see the main thing that we're looking for in a second. I initialize everything properly, and then I call this kernel, and we're just trying to see like what does the actual code look like under the hood here. So if I go up to this command that I ran recently, nvcc-ptx, that means parallel thread execution. Parallel thread execution is what CUDA compiles down to. It's the assembly language for parallel processors. And then you have just the file that we're compiling, and then we output kernel.ptx, right? Where I have to get out of this, and then go into src/kernels, and then go ahead and run that. This is going to give us this kernel.ptx file, which I'll just open here. We bring this up. We go into kernel.ptx. We notice there are a lot of lines in this. There are 308 lines. And it doesn't tell us anything super specific, right? Like we can see, like for example, like an add operation, or like a fuse multiply add with a floating point 32 number. It's like, I think output and then like multiply these and then add this one. I can't remember the exact order, but like fuse multiply add, right? Like you can find all these instructions in here. Multiply, right? Yeah. We have the load instruction, so LD, so it's going to load a floating point number into shared. into the SRAM. And then we leave this. If I can exit Vim, I have a separate one that I also outputted. This is the shader assembly. So initially, NVCC is going to compile everything down to PTX, and then PTX is going to further compile into shader assembly, which is then actually run on the GPU. Shader assembly is what it executes. So if we compile, CUDA binary, right? It's actually the actual binary that we run, and then we compose this back up into the shader assembly language that is actually executing, and then we output that in the CUDA binary format. We can oh, wrong one. Let me check real quick. We go, yes. So we've compiled it into this, and now we look at it again through the special command. So CUDA object dump shader assembly, and then just essentially open that, and it's going to give us the exact assembly code or what we just compiled, right? That entire script. So if we look very carefully for like load instructions, right? So if we look for LD, which I know is from here. So PTX compiled to shader assembly. The S shared memory loads from B shared are vectorized, right? B shared was the one where we had these individual columns, right? So when that was in shared memory, the SMEM loads from shared are vectorized. Remember when we had the threads that were adjacent to each other? Those are what we're looking for. So if we look for LDS, so we have LDS U128, right? LDS U32, right? We have all these LDSs here. And this is when they're not coalesced. So this LDS, when we have the 32, that means it's not coalesced together, right? These when it's not accessing like 4 in a row. So if you do a 32-bit floating point number, 32 bits times 4 is 128. So when we're accessing 4 in a row, it's going to be a 128-bit load in shader assembly. So this is what it actually looks like when we get those coalesced memory accesses going. And this is what it looks like when we're not, right? So we end up having to, maybe load more. So we have like 2 loads here. But anyways, this is the entire point here. Just to show you what the actual loads look like in binary format, this is what they look like. And we're going to further optimize these kernels to perform better, right? I think this is FFMA is like fuse multiply add, floating point fuse multiply add. I can't remember. We can actually search that up. FFMA in shader assembly. So yeah, fused multiply add. There's probably a manual somewhere, which I'm not going to look through right now. You can do that, but these are the shader assembly instructions that we're working with. Now we move on to 2D block tiling, which builds on what we've already done, but makes it even more efficient and makes it even more performant. Okay, absolutely give yourself a pat on the back if you made it this far. This has been quite challenging, so feel free to take a coffee break or whatever. Get some tea. I have some tea with me right here, so it is a grind. But if we step back to just this blog post here, we go to kernel number 5, so increasing arithmetic intensity with 2D block tiling. Before we were just calculating columns, right? We were just calculating columns, and now this one is going to calculate entire blocks. It's going to calculate like a mini block inside of the big block tile, right? That's the idea. So before we just had this .idx in the B tile, this was going to go downwards, and we just had a single thing that was iterating down and calculating, a column. So you have this, just kind of intersect, and you get this column filled out. But now we have this res idx n component, right? So that's just going to go and make this essentially cover like a square or like a row and a column, right? So they intersect, and it's going to fill up like a square area. So we have this term, which we're going to iterate over. And then we have this new tn term. So tm is literally just this component, and then tm is this component underneath, right? So now, like, stepping into this is kind of just what it looks like under the hood when we sort of visualize how this is being calculated. So we look at our A tile and we look at our B tile, and it's literally just we're storing a column in reg m, so that's like an actual register memory. In this kernel, we're actually using register memory, so we're occupying it a little bit more. We're like, as you can see, we literally populate it. So reg m is going to be of that size, and then reg n is tn size, right? And the total results is going to be the surface area of that total area there. And we essentially just store a column and a row, and those will dot product through this entire thing, and they will intersect, and you'll get this little square right here. And we can see how that evolves at each step, right? So now, where's my marker? Let's actually step into this kernel. So we go back to here, and we see, run sgem 2D block tiling, right? So we have this. We have the same bk term, right? So bk is just going to be 8 in this case, and we have tm, which is also the same, and then we have this new tn term, right? So we're essentially just going to calculate, like, this area that we fill out is going to contain 64 elements. It's going to be 8 by 8. It's going to fill that entire thing up, and we're going to have 64 in there. Now we have this little hacky situation for handling, like, the very, very low, like the smaller matrices that are going to be tested when we do a benchmark. So this is why we have this little else statement here. So in case we, decide to use, like a very small matrix, this is able to deal with that effectively. But normally we're just gonna pay attention to this first if statement for now. So if these are bigger than or equal to 128, right? Yeah. So in here, pay attention to this. We have a grid dim, which is going to have an X component, right, and then a Y component, right. So that's gonna stay the same. And then this block dimension, the number of threads within a block, right? It's like the block itself, the dimension of that, the X component. There's just going to be one value here, and that's going to be essentially the total number of elements in the output tile. So, we have this BN and this BN, and then you sort of just get this filled out area of C, the C tile that is going to be of this size, right? And then we divide that by the total surface area covered by just what a thread calculates. So a thread is going to go through those 64 elements. It's going to be 8 by 8. It's going to go through those, and they're going to calculate a small little mini grid for us, like per thread, right? And so if we divide the total number of output results by the space covered by a thread, we actually get the number of threads, right? Because each little piece here is a thread. And so if we divide this by this, we actually get the total number of threads within that entire C tile. So if we do this math here, we're going to get 128 times 128, and then divide this by 8 by 8. And this simplifies to, 128 is 2 to the 7, right? Because remember, like, if you know, like, int 8 precision, it's like an image, essentially, like a number of like RGB values in a single pixel. So you have like RGB in each of those. It's like 0 to 255. So that's like how you can go down to what, like 128 is 2 to the 7, because it's like int 7 instead of int 8. That's how I made that association. But we have this 2 to the 7 times 2 to the 7 divided by 2 to the 3 times 2 to the 3. And what you end up with is 2 to the 14 divided by 2 to the 6. And we do our exponent laws, and we get 8, right? So 14 minus 6 is 8. So 2 to the 8. That means we have 256 my marker works properly. 256 threads, right? 256 threads. My writing is messy, ignore that. Awesome, so we know the number of threads that we're calculating. Now this is gonna help us when we actually jump into this kernel here. So, we have our BM, or BN, BK, TM, and TN, right? There's a lot happening here. Let's break this down. So to start, we have our row, which is going to be the typical Y component. We've already went over this. The total results in a block tile are, as we already said in the runner file, this is just essentially the whole seed matrix. So you have the M dimension, and then you have the N dimension. You multiply those and you get total area, right? That's the number of results that we're going to calculate. And then we get the number of threads per that entire thing. So how many individual squares are there that a thread is occupying, right? And so the square surface area is this, which we already calculated. And so this number of threads per block tile should equal 256, right? And then we just assert that down here. So we want to make sure that 256 value is equal to what we just calculated, which is going to hold true, of course. And then it'll actually continue with executing, right? Then we go down a little bit further. Don't worry about these right now. We're going to get into those in a second. So we do the classical just allocate shared memory. We advance the block tiles based on where they're supposed to be at in the in the current block, right? Or I guess in the current thread. This is where a lot of the magic happens right here. So this part is crucial to pay attention to. Let's first go over the easy stuff. So thread results is just like how big is that little square that the thread is going to calculate. That's just going to be 8 by 8, right? We have this reg m term, which we saw in the blog post. So reg m is this, and reg n is that. Tm and Tn, right? That's just going to be the iterations of the dot product. So at each iteration of dot idx, it's going to store those in registers, and it's going to calculate them really, really fast, right? It's going to be like 8. That's going to be like 8 by 1, and then a 1 by 8, and it's just going to evolve that way. Now we look up at these. So in a row A, so we just essentially have the thread index, and we divide that by BK, right? In a row, same idea, but we use the mod operator. Then we have this new term called a stride, right? And now we're actually going to do the math out. We're going to do the math for a stride here. So stride A is going to be number of threads per block tile, which is 256. Divided by BK, which in this case is 8. So here, if you divide this out, you end up getting 32. So our stride A is going to be 32, right? My marker is a little weird. Let's pay attention to that term. And then we have this other stride down here, stride B, is the same thing, but instead of dividing by BK, we divide by BN. So BN is actually 128. So if we divide 256, right, by 128, the answer is 2. Now these are going to be important. These are going to be very important as we sort of step through this. So let's jump down to this actual loop here now. So inside of A shared, look at how we index this. It starts here and ends there. We have this first thing in the brackets, which is inner row A. So it's going to be a certain row that we're looking at, plus a load offset, right? So the load offset is going to iterate up to BM, which in this case is 128. So you can think of it as us having this, this is the A tile, right? And so this is going to be, BM. and that's going to be bk, right? So inside of here, we're going to iterate up to bm in strides of stride A. Now, stride A is size 32, right? Stride A is 32. So if we actually look at how many times it's going to stride through this until it reaches the end, it's going to start at 0, and then it's going to go down to 32. If I can. And then it's going to go down to 64. And then it's going to go down to, I believe, 96. And then it's going to stop, right? It's not going to actually hit this. It's going to stop there. So we're going to have this initial offset of 0, and then it's going to bump up to 32 in the next iteration, and it's going to jump to 64 and then 96. So notice the actual area that we have to fill in here, right? Notice the actual area we have to fill in. So this area is 32. And then this bk, we already know is 8, right? And it's going to be the same for this, and same for that, and same for that. So this is actually where some really cool stuff comes in. Now this inner row A here, this inner row A is calculated as the thread IDX divided by bk, right? So this value, if we do the math here, thread IDX is, it maxes out at 256. My marker, I need to get a new marker. 256 divided by bk, which is 8, right? Now this number is going to max out at 32. And that's going to be our row, right? So remember this, if it's 32, this number, this inner row, which is based off of the thread itself, is going to max out at 32. Now this inner column, on the other hand, is going to do mod bk, right? So when we do this, it's essentially going to go like 0, 1, 2, 3, all the way up to 8. And then once it hits 8 again, it's going to jump back to 0 and it's going to reset. So it's going to be like 0 through 8 and then reset, 0 through 8 and reset, right? And then we're going to have these rows, the row index that goes from 0 to 32, right? So every time we hit the next 8, it's going to bump up 1, right? And so this actually makes a lot of sense. So inside of here, we have this load offset, which is going to be strided by this much, this 32 here. And then we add whatever this row offset is. So when we have the row offset plus whatever that number is, we can effectively populate this entire area here. So it's like the 0 or say it's like, I don't know, 64, and then plus whichever row it's at from the thread index itself, which we calculate up here. It's going to be that times the k dimension, so that's why it's going to stride over as many rows as it needs to, and it's going to end up at some certain index. And then once we multiply that, we know where it's at vertically, and then we simply add the inner column index to that. So the inner column index, like I said before, is going to cap out at 8, right? So it's going to cap out at 8, and it's going to land somewhere here. So by doing this, we only actually iterate over this 4 times, and each thread spanning, 32 times 8, because if we actually do 32 times 8, that's like 2 to the 5. 2 to the 5 is 32, and then 2 to the 3 is 8. So 5 plus 3 with our exponent laws, that's 2 to the 8, which is int 8, maps to 256, right? So that's how I kind of make those associations. You don't have to follow along, but 8 times 32 is 256. Look how awesome that is. Each thread is going to occupy an individual spot in here. So we're going to load this chunk in. Each thread is going to take a little spot in there, 32 times 8. And then we load in the next one. Each thread takes its own spot. So it's like one operation for every single iteration, right? So we don't have to go sequentially through it. Each thread is just, boom, done. It's one instruction. Same for this, same for this, same for this. And then we just index accordingly. We just kind of adjust it. So instead of bk being the stride over, we do times k. So it's able to stride over the entire thing when we're actually loading from the GPU VRAM. because it's actually bigger, right? So these matrices are much bigger when they aren't tiles yet. So we have to stride like the whole k distance instead of just the tile k distance. And then same idea applies to BS, right? So the not BS, B share, not that. If I get up for a second and you look at what BS looks like, it's literally this. Let me actually get a different marker. Terrible. Right, it's gonna be like this. It's gonna go down this way, right? That's what BS is gonna look like. Now, if we look at these values inside, we have this load offset, which is going to iterate up to BK, right? And BK is this. Remember, it's not this part anymore. It's the side, and then this part is Bn, right? Because it's K by N as the B matrix. So when we iterate in these strides, it's actually going to end up being well, Bn in this case is 128. So it's going to be this stride value is going to be or stride B, sorry, is going to be 256 divided by 128, which is 2, right? As we calculated down here. So it's actually going to stride. It's going to stride 2, right? And 2 times the length of this is actually a quarter, right? So if you have 8 values, you have 8 different rows. You split it once. Now you're in half, and there's 4 rows here and 4 rows there. Now if you split it in half again, then you have 2 and 2 and 2 and 2. All that adds up to 8. So when we actually stride, we're just going a quarter of the way down. Same thing in here. We go a quarter of the way, quarter, right? Same idea applies here. So whatever this stride value is, it's going to start at 0 and it's going to go up to 6 because it's going to cap out at B, whatever BK is. In this case, it's 8, and it's just going to stop. So it's going to go 0, 0, 2, 4, 6, and it's going to stop, right? Then we have this inner row B, which is from here, and this is just the same idea. So inside of this, we have the thread IDX. In this case, it's just going to max out at 256. And we divide that number. We divide that number by Bn, which in this case is 128. And the column is the same idea. It's going to go 0 all the way up to 128, and then it's going to reset, right? So it's not just going to iterate every time we stride 128. It's going to go up. It's going to essentially 1 mod 128 is 1. 127 mod 28 is 127, right? So that's literally all it's going to do here. In case you haven't noticed already, this is the same idea as here, except we're just dealing with kind of like a more like very stretched out thing instead of like these nice to look at eye candy looking blocks, right? So the idea here is that we just go however much we need to in here, because this total thing is like 128 and 128. That totals up to 256. So it's essentially each thread gets its own little space in there. 1 thread, 2 thread, 3 thread, 4 thread, right? They all get their own little piece in there. And so you're able to load in quarters downwards, right? That's essentially how we're loading into shared memory. So just given this new context, we're just loading, we're just being clever about how we load things. So given that we understand how everything is loaded into shared memory, we can go ahead and jump into the next part here. And this part is like where things get a little funny. It's not actually as intuitive and bad as this part, but it is still a little bit weird with the indexing part. So if we jump into this, we iterate over this .idx, right? And this .idx, going back to this, is literally just it's going to evolve, right? So .idx, index 0, 1, 2, and 3, right? They're going inwards like this, One thread is in charge of this little block at the center, and each thread is responsible for loading in a column and a row, right? One thread takes care of that. Now, if we look inside of here, we load into the registers, right? So the registers are the extremely fast pieces of storage that are literally right next to the core in the GPU. And so we have this reg m, right, which is going to load that column in. So how do we load this? Well, we have to look at this thread row, right? And to understand everything else, let's go look at thread row here. So where is this? Thread row, so it's the thread idx.x. So this could be a maximum of, 256. And then we divide that by bn divided by tn, right? So bn is 128 and tn is 8. So you divide 128 by 8 and that's 16. So we have 256 divided, or 0 to 255, and then whichever one of those it is, divide that by 16, right? So inside of this, we end up having 16 different numbers that we could be through, right? So if we look at this original A top here, there are 16 different there are 16 different rows we could be at, right? And these are just offsets, keep in mind. We're loading in columns that are 8 elements long. So when we have like 16, 16, 16, all the way down, we have this 8 times, and each of these, 16 times. Each little column here, this little like colored in area, you could say, that is going to be 8 long, right? So we essentially are loading in, like, we go 8, that's like a single, that is a single column, and then whichever one comes next, it's like, this is another 8, and we go all the way down 16 times, and that multiplies up to the total length of m, which is 128. So the math is mathing. The same thing applies to thread column, right? I mean, these are square matrices, so it's not actually too bad to deal with this. So same idea here, and we end up with some range between 0 and 15, right? So if we go back down, thread row times tm, so tm is which, tm is essentially 8, right? So it's going to be whichever thread row we're at, so whichever one of these out of 16 are we at, and then times tm plus I, and I is going to be that little iterator here that goes up to tm, right? Tm is like the length of that column, or you could say the height or the length of that column. It's going to iterate up to I, and it's going to put that into the register m, right? We multiply this whole thing by bk so that we get this offset going, because we have to go through this k thing and reset every single time we want to get a new column. You can't just go directly down. You have to stride one entire length over to get to the next one. And then we add .idx to this. So this actually becomes very intuitive when we look at it from a glance. So hopefully this is sort of making sense in your head. But this .idx is just going to evolve us. It's going to be that horizontal offset. And then this is the vertical offset, right? This whole portion here, that's the vertical offset. And then we apply the same concept to loading into register n, right? So register n isn't as bad because we're actually loading horizontally. So it's going to be the .idx, which, by the way, .idx is going downwards now. So .idx times bn. Bn is the length of it, right? So you're going to go down whichever .idx you're at. You're going to go down that many layers, and then you're going to do whichever thread column you're at. So each thread is going to have its own. It's going to have its own little section of that, right? It's going to have its own job, because the thread is like loading a specific square in that tile. So thread here, thread here, thread here, thread here. It's like, yeah. Each thread has its own thing. So we're just worrying about a single thread. Thread is like, thread 1, it's like here, and then thread 255 is, or thread 0 is here, and then thread 255 is here, because it goes to like the very edge, and then the very edge, and then they intersect at 256, right? that's how I'm sort of visualizing this. Now we have this extra I term, which is literally just the horizontal offset. So when you've like looped around whatever amount of dot IDXs you need, then you have that additional I, which is going to be the offset. So you're going to load in the first element in the row, then the second, then the third, and the fourth, and then the same applies for this column up here, which we already did. It's just going to do 1, 2, 3, 4, all the way down to 8, right? And it's going to store this out in like a register memory, like a line, and this allows us to easily dot product that, right? So when we drop down to here, this is the entire loop, yellow to yellow. We start off with the M component, right? So thread M is this part, and then thread N is this part. So this N component is actually inside of it. Now, the thread result is calculated as res IDX M, so however much it is through TM, right? That times TN, which is the horizontal stride that you need to do to get to the next row, right? And then you have this TN as well. So TN is how far along you are. So res IDX is how far along you are. So this is going to be your vertical stride, and then this is going to be the horizontal offset, right? So that's how we're storing it in linear memory, but this is how we're going to index into it, right? And then we do whatever that is. And this, keep in mind, this is an individual grid, right? This is you're looking at a point within that grid. You're doing essentially a dot product across those, so you have to iterate through 8 and then 8 again, so it's 64 iterations you have to go through, filling up that entire tile. And then you just use as you would expect that value, whatever it is. So you're just essentially just crossing them. You're finding where they intersect, and then you're setting whatever this is in that. So and just becoming this entire matrix laid out. It's like, instead of being loaded like this, you just take this row and you attach it to the end, and then this, attach it to there, and then this one, it's even further, right? That's all we're doing there. So it's like literally as you would imagine in your head, this is how it's working. It's just important to actually highlight like what the indexing is actually doing. Instead of just trusting that it works, it's really important to actually dig deep into what this is doing under the hood. So I encourage you, if this doesn't entirely make sense, it's very intuitive. I encourage you to test it with your own examples. So even just like get a piece of paper, write down on a whiteboard, whatever you need to do, and just sort of write this out and try to visualize it through each step, right? So you can even set, for example, TM and TN to 4, right? And you can make it much easier on yourself. You don't have to go to the full extent that we're using with our parameters like 8 and 128 here. You don't have to even go that far. You can be very simple about how you exercise that. But yeah, so this is actually how we calculate the individual thread tiles. So this thread tile, this little 2D thing inside of the bigger block tile, and we calculate one of those per thread, right? So 256 threads are laid out. So it's like 0 to 16, 0 to I think 240. And then over here, it's 256. It might be like shifted based on how you're seeing the picture and my hand waving, but that's the idea, is you go from 0 to 256, right? Let me just make sure everything is synced up. We make sure that all of these are done. As we're iterating through all of these block tiles, right? We have to go like on the bigger matrices A and B. We actually have to take these tiles and we have to move them closer together, right? So this is what this whole loop is doing. We want to make sure everything is synced up, both after the shared memory population. So after we populate those, we want to sync everything, and then once we've written all the results here, we also want to sync everything up, make sure all the threads are caught up before we evolve to the next one and mess with stuff. So then we have this write out, and this isn't actually too bad. This part's pretty good. So inside of here, we iterate over the same things that we did here when we were actually calculating, when we were multiplying those essentially thread rows and columns, those little thread tiles. And if we just step through this is actually going to seem a little bit weird at first, but if we scroll up, remember that we advance everything to the starting position given this thread, right? Or given this block rather. So we have these initial terms, which are the blocks. These are which tiles, which tile we actually care about within C. And this is already stored here. So we already know which tile we actually want to worry about. And the memory address has gone through, it's skipped a bunch of spaces through just like integer operations. It's been multiplied and added up to the point where it's where we want it. And then we just do everything from there. So we can, if we stride like an entire length K, it'll go here and then the remainder of it, and it'll end up back to where it is, but just like one element lower, right? So that's really all we're working with here. Now, if we scroll back down, it's literally just like this n term. That's like the n term. That's the horizontal part, right? So that's the part that we're actually striding over. So if we have, we're looking at the C matrix, we have thread row times thread m, right? Or tm, which is 8, plus the res index. Remember, it's the same idea as what we did up there. And so when we are, it's essentially the same as this, except we're doing I instead. So, I as, you could think of I as like up to, tm. It's like the same idea. We're just iterating through that. That's going to be the offset inside of that tile, right? So like relative to the actual C tile that we're working on, this is going to be like the relative offset, right? So that's going to be downwards times n, right? So that's going to give us our downwards movement. And then to progress sideways, we have the thread column times tn, right? So an individual thread times that tn length of 8, right? So essentially you're going to have a bunch of threads occupying like a square, and those threads are going to or no, not the threads occupying a square, but they're going to occupy the whole thing. And then each thread is going to iterate through that tm and tn, right? And so we have this vertical offset, we have the horizontal offset, and then plus that additional little kick to the right. We're going to iterate. This is how much we need to actually like stride over, like how big steps we take. And then the initial, just like inside of like one of these steps, it's like how much do you actually go forward, right? How much do you add to it? And then we just use what we've already computed. So thread results, same indexing scheme here. This should be fairly intuitive. And we just multiply this element-wise, for each iteration in the loop. And then we have our beta times, element-wise this, which is literally the same indexing scheme that we use here. So hopefully the block tiling kernel made sense. Now we're going to jump into, well, actually, before we actually jump into the vectorized kernel, I want to run this. So if we go sgem, we go sgem 04, right? This is block tiling, normal. This is regular 1D block tiling, right? Then if we step this up to number 5, look at this. 4,800 gigaflops on 4,096, right? That's decent. But if we step it up to 5, we double it. So if we do Python, we go 9162 divided by 4873. We get about 1.9x speed up, right? Which is really good. Now we compare to the results here. So about this times 1.9 roughly it's pretty close to 70, right? So I mean we're essentially getting the same results here. So everything is working out. We just doubled the speed by using 2D block tiling instead of 1D. And now we're already about 2/3 of the way to cuBLAS performance. We're actually really, really high up there. So now let's go ahead and continue with vectorized memory access, which is going to give us an additional little performance boost. Okay, awesome. So now we have this new kernel to worry about, number 6, on vectorizing the shared memory loads. So if we look inside of here, essentially we do this, everything in here remains the same, except we have this new float 4 type, right? So notice how we have this float 4. I'm going to just highlight that and see where it shows up. So it shows up here when we're loading into when we are loading into shared memory, right? So A shared and B shared, right? This is where it comes up, as well as when we're writing out the results. So when we're going in from global VRAM into shared memory, we use float4 loads. And then when we're writing out from registers, we load with float4 as well, right? This is what's happening here. Now, before diving in right into this, I want to go over and review just like what the heck this float4 does. There's a lot of terms like reinterpret, cast, and all this weird symbols and stuff. So let's just like go ahead and clarify what this all means. I wrote a separate file here called float4.cu. You can write the same thing, but I'm just going to go over this kind of step by step. So we have an array, length n, right? 1, 2, 3, 4, all floats. We have a host input, host output. We initialize device input and output. We CUDA malloc those with n times size of float. We CUDA mem copy that from host to device. We launch this with a grid size of 1, so there's a single block, and within that block there's a single thread. So it's just one thread that's actually being used here. Now we run this, and then we copy back, and then we display these based on their indices, right? So 0, 1, 2, 3, and then 0, 1, 2, 3, the inputs and the outputs. And now what actually happens inside of here is what we want to pay attention to. So we pass this device input and the device output in, right? These are pointers to arrays, the output as well. Now we have this IDX, which threaded index in this case is going to be 0, right? It goes from like 0 up to whatever the length is minus 1. And so this is just going to be 0. So when we actually look at this IDX, pay attention, don't worry about this yet. This IDX, this is going to be times 4, so 0 times 4, 0 times 4, 0 times 4, 0 times 4. It's just going to be 0, 1, 2, and 3, right? These are going to be our X, Y, Z, and W components. Now let's actually look at what's happening here. So this new float4 type is part of the CUDA runtime. It's part of the, well, it's not part of the CUDA runtime. If we actually look at this, it's part of x86, right? Vector types. We have this float4. We have a bunch of different other vector types that are device built-ins, so we can't actually, we cannot actually see what these are under the hood. They just kind of work for us. Because if I try to click on these, right, it's just like, that's really all it is. So there's parts in here. A lot of this is built in, handled by the compiler, etc. And so when we break down what's happening here, we notice that we have a few parts. We have this reinterpret cast, and literally all this means is that we're going to reinterpret as this in the actual instructions, right? So this isn't going to manipulate memory or do any data transformations. It's literally just going to reinterpret as a float4. That's what it's going to tell the compiler what to do, right? And this is going to be a pointer to float4, right? So we're transforming this essentially. So this is a memory address. This ampersand is a memory address to whichever index we're looking at. So in this case, it's going to be, IDX times 4. In this case, this is just going to be, like IDX is 0. So it's going to be 0, 0 times 4. That's just the beginning element, right? That's literally all this is just, we're doing input at index 0, and then we're getting the memory address for that. So it's the memory address to the first element in that entire array. And then there's the following memory addresses for the extra ones. And then we reinterpret this as a float4 pointer. So we got the pointer, the memory address here, and we're reinterpreting this as a float4 pointer. So we're just going from pointer as a float to pointer as a float4. And the float4 is just going to contain essentially the starting index plus an additional 3 afterwards, right? And then we just have this stored as index 0 for this specific data type. We don't want to be, redundant and take up extra space. So we're just going to index 0, and then the compiler is going to know what to do with that later on. And it's just literally just going to be the .x component is going to be index 0, .y is going to be index 1, Z is 2, and then W is 3, right? So that's literally how we have it laid out, how we have this thing laid out here. And that's literally all the float4 data type is. So hopefully that kind of makes sense to you. When you read complex when you read kind of like complicated expressions like this, it's good to just break it down step by step, right? So you have this like, you have this thing with its open and its closed, and then you have this thing with its open and its closed, and then this thing with its open and its closed. And you just kind of see like, you do like your order of operations or simplified however you want. But yeah, hopefully that makes sense. And if we can, I'm actually going to sgem cd into source / kernels. And then if we go and compile that into float 4, we notice that we get everything as expected, right? So 1, 2, 3, 4, that is the host input. So that's how we initialized it here. And then the host output, which is exactly how we want everything to be stored. That is all checking out. Now this next kernel is really fun. It plays around with some things that are usually played around with and toyed around with when you write really performance optimal CUDA kernels, right? So the idea here is, like, remember how when I showed you before those, let me go back to here, and I'm gonna step out and go to src / kernels, and then we did this one, and we saw we go up, we saw these like this load, this load instruction, the load.e, and then there was like some load 128, so like load 32s and then load 128s, right? So that's like the whole deal here, is we're going to try to make more of these load 128s. A single floating point number is 32 bits, and so if we make this like a vector type, meaning, you know, we just put multiple numbers with each other in the same type, then we can have more and we can load more things. So let's go ahead and actually jump back to this part here, and let's explain like what the heck we're doing. So in this one, we are essentially taking the A tile, so it's like normally vertical, so it would be like tilted downwards, like the bottom would go here and then this part would go right there. We're just transposing it, right? And this transposing is going to let us cheat a little bit. We still get the same amount of memory in that shared block, except we index it differently. And this will allow us to coalesce memory accesses, right? So normally we would, if we go back up, we would be taking these and we would be advancing to the right here. But notice how, for example, like when we're actually loading this in, our threads are going to be loading in from like top to bottom, right? So we're gonna have like threads essentially organized in different pieces, and we're gonna be iterating downwards to populate this, right? If you remember how we populated it before, these accesses were not coalesced, but the B tile, the B shared tile was coalesced because our threads were loading horizontally. So in our threads, we knew like thread 1, thread 2, thread 3, thread 4, those are all next to each other. So CUDA is going to go ahead and load those in as a, like if you have 4 of them adjacent to each other, it's going to load all those in as a single load operation instead of 4 separate ones. So that's what we're aiming for here. And the idea here is instead of having this vertical tile and then taking this and advancing to the, and like having .idx iterate to the right, it's going to be flipped and we're going to iterate downwards. So our threads are going to be paired like this next to each other, and it's going to iterate downward, right? That's the whole idea there. But what's even more important isn't even how they iterate downward. That's just what the graphic looks like. What it's more so about is how we actually are able to load from global into shared, right? So how do we take the A tile just on its own and then load that into shared and then populate it like this, right? So we pop back to here. We notice a few things. So first of all, this is the same, this is the same, this is the same, but these and these are different, right? So if we pop down here, just pay attention to the inner rows and columns for now. So notice here this is actually very familiar. But notice how we don't actually have that loop. So if we go back to block tiling, for example, this 2D block tiling, we were loading in for loops. So we had BM was 128 long, and then this load offset would increase in increments of 32, and it would do 4 different iterations of the for loop, totaling 8 different iterations per thread. So each thread was doing 8 different instructions, or I guess at the high level, 8 different instructions for moving data around. And that's like kind of a bottleneck a little bit. So we can actually speed that up. And notice here, we don't actually have any loops. It's literally just, we store this temp variable. This is done once per thread, by the way. So this is like once per thread. But we essentially, we go into A, we get this inner row, and we essentially just find where exactly this is at. And we're going to load this into shared memory as if it's transposed, right? So for example, I have this thing written on the board here. This is the A tile, and I drew a little section at the bottom with 1, 2, 3, and 4. These are 4 different values that we're going to count as a float for, all right? So when we actually transpose this, when we do A tile, and then you say T, you might not be able to see all of those, and just don't worry about it. We transpose this, and essentially we're like flipping over this dotted line here. So these are going to flip over. They're going to go from this to this, right? Those are going to flip across that line, and they're going to end up like that. See, what you're going to have is you're going to have, when these flip over, they're going to be ordered 1, 2, or sorry, bottom. 1, 2, 3, 4. Now, don't worry too much about how these are in like a column format. What we do care about is just that we're loading these in a coalesced manner, right? So notice how I've kind of taken like half of this tile here, and I've actually done this for a reason. So if we go ahead and look back at what these inner rows are and all this stuff is saying, it's essentially the same as what we had over here in 2D block tiling, except instead of just BN or BK, it's that and then divide by 4, right? So I mean, it's 4 for a reason. It's literally because we're using the float 4 type. So if we're going to do thread IDX, which in this case is going to max out at 200, and it's going to max out at say 255, and then BK is 8, so it's going to be 8 divided by 4, which is 255 divided by 2, which gives us the indices 0 to 127. Now this one, on the other hand, is going to be same idea, except we're doing the mod, right? So 255 mod 2, that means every 2 times it's going to reset at 0 again. So we're just going to have the 2 numbers 0 and 1. Essentially, this indexing allows us to treat this as a group of 4. So when we divide, that means it's shrinking to 1/4 of its length. And then when we go down here and multiply by 4 again, which you'll kind of see the intuition for in a second, and when we multiply by 4 again, it's just going to stretch that back out to what it normally used to be. So this is just considering this little float 4 indexing scheme we have. Now, if we pop down to this here, we can see that this, I'm actually purposely making this match our A tile here. So notice how we have this inner row A, right? And inner row A is between 0 and 127. So the row for this tile is between 0, let me put this here for now, 0 and 127, right? So you might not be able to see that, but 0, 127, this is very long. This is like the longer side. And then we have 0 to 1. So 2 values for the column, right? Column A. So 0 to 1 or 1 rather. And all this allows us to do is just sort things more easily. So notice how we have we have this thing that's normally of size 128 by 8. And 128 by 8, if we actually do the multiplication for that, that's 1024, right? So 1024, and then reduce this number, we divide this one by 4, right? That actually reduces the whole thing from 1024 to 256. Guess how many threads we have? 256. It works out perfectly. So each thread is essentially taking its own little one of these, right? So this is spanning down 127, 0 to 127, and then this is going 0 to 1, and it's just like split in half, right? So you have like 1, 2, 3, 4, 5, 6, 7, right? 8, and we're just like splitting this in half, and then it's spanning the length, spanning the height downwards, right? And all we have to do is just store this as a float. So this is what we do here. We literally take the inner row. We do that times k. So we need to stride around and get back to the same column again. And then we do plus the inner column A offset. This is all in context of like this A tile being advanced where it needs to be. So we're literally just adding k, considering that we're in this bigger matrix, right? That's all we need k for. Everything else is it just works because we're just dealing relative to this specific tile as a part of the whole bigger matrix. Now, inner column, we're actually going to stretch this out back to 4 again because we previously shrunk it, right? So we just need to expand that back again. And this is just going to index in the old-fashioned style, right? Where we find the vertical offset, meaning here, and then we add that, so a vertical offset, and then we plus to we find which row we want, we multiply by the k term, and then we get where we want to get, and then we plus for the horizontal offset, right? And we have to multiply by 4 to actually span that entire length, right? So if you wanted to go to the very end of the matrix, here, you'd actually have to take this 2 term, whatever that is, times 4, and it would get you all the way to the end, right? That's the whole idea there. But if we go into this, look at the way we store these, right? This isn't actually too bad. So in A shared, we have these 4 different stores, which is each for a different component of the float 4 variable. So we have this x, y, z, and w term. This is the first one, index 0, and then index 1, index 2, etc., right? So all we're doing there is we're looking at the inner column, whichever column that is. Keep in mind we have this new tile of this shape. So we're doing it relative to this because this is how we're storing everything. So we're going to go the inner column, whichever that is. So in this case, the column, we have to keep in context how we stored column for this one. The column in this case is which one of these. But since we transposed it, we have to consider the column in the context of here, right? So it's actually a little bit different. So instead of having row as this, it's actually column because we interpreted column from this originally. That's kind of what's going on there. Hopefully that's easy to understand. And then we have this times 4, which is obviously we're going to stretch it out as we need it to. And then whichever index we need to plus, right? We're storing this as these vertical values, right? So instead of horizontally laying them out, we're storing them vertically. And this is why you have this extra index here, this one. This is going to be like the column offset, you could say. Like which row are you at, rather. And then the BM term, that is just this, and then we move it over here. So it's going to stride across as many times as it needs to, and then we can add the just inner row A part, right? So so the row originally came from this part, and now we're just flipping it over to this side, so we get the actual offset there. And that's literally how we store it. It's like literally that easy. So then we go further, and we look at B. B shouldn't actually be too hard. I'm not even going to explain this. It's literally like B. We're just explicitly adding memory coalescing here. Like if I go back to this, what's it called? Shouldn't the compiler just be able to coalesce the second version and generate the 128-bit loads? And then the reason is that the compiler has no way to verify that the float B pointer is passed to the kernel as 128-bit aligned, right? Which would be a requirement for this. So essentially, we're just saying, like in the previous example where I showed all the shader assembly, there might have been some instances where it did not actually know that it's okay to store as a 128-bit, right? As like a float for like an implicitly 128-bit aligned type. But in this case, we're explicitly passing reinterpret cast, and we're explicitly setting it to float for or 128-bit. And that's promising the compiler that this is aligned, right? This is telling the compiler, you can do what you need to with this. We've set this up properly. Work your magic. And we're just helping out the compiler that way. So that's what's happening here. Same, like it literally this identical indexing scheme. Not really much to talk about here, but after this is all done, keep in mind this is done once per thread, right? So we store, and then we write, and it's just super fast, right? So don't worry about don't worry about how we're writing this. We don't actually have to make the writes coalesce, so then the writes don't have to be adjacent like this. They can be separated like by rows. And then as long as the reads are coalesced, that's fine. So the reads coming from here, and then we're just flipping it over, and it's landing there, which is perfect. And then we move on to actually calculating the results of that little thread block, the essentially the thread mini tile within the bigger one. And we iterate through with normal.idx, right? Similar scheme to what we had before, except the indexing scheme is a little bit different. We remember how we have B as like this rectangle where it's like this is short and this is long, right? A is the same way now. Now that we've transposed it, A is also like this. So instead of A being like this, it's now flipped over like this, right? And so all we have to do is just change up how we index it, and that'll work. So I'm not even going to go over B. B is like very obvious to understand, but going over A, right? How do we iterate through this? So .idx, right? When we look at this, we go, so whichever dot index we're at, we'll just disregard that for now. We'll just say that's 0 maybe. And then this, since this is multiplying by 0, that's going to simplify to 0. So it's going to be 0 plus, and then we'll say maybe whichever thread row it's at, is going to multiply by tm, which is 8. So it's going to stride however much it needs to, right? And then we simply add I to that, right? So thread row, instead of being here, thread row is actually here because it was previously, right? You can see how that translation works. This was thread row, this was long, this is thread row, now this is long, right? So it's the same idea. We're just making the naming a little bit confusing there. That's really all it is. We're just staying consistent with whatever this term means because we have to transpose it, right? And then we just iterate through I as we need to, right? So this should be intuitive. I don't really think I need to explain that too much. It's just like mainly paying attention to the naming convention. So thread row versus thread column, like why are those different? That's because you're transposing. And then you do the typical write outs. So if we go back to this, this is all it's doing, right? So revolving .idx downward, all of these threads are sort of next to each other in memory. That's why we're striding tm, right? Tm is that. This is tm, so whichever thread row we are at, We're going to stride TM because each thread is going to take care of multiple of those values. And yeah, we end up just sort of looking at this a bit differently. And then yeah, just some more visual examples instead of having it as like here and then these like inch forward. It's right, but this is actually switched over. So it's just kind of the transposing spatial reasoning you have to get through, and then this all like is pretty straightforward. But yeah, now we can actually pop over to the write out section. Awesome. So we're actually almost done. We just have to write out the results now, and we have to make sure that these are also in this float for type, so also coalesced into the global VRAM, right? So we have the normal iterate over TM and iterate over TN, except we change the iterators a bit differently. So in TM, the rows, we're iterating up 1 each time. So it's going to go 1, 1, 1, 1, 1, right? And then for TN, we're going +4 each time. So we have 8 values here, and we have 2 values here, right? So when you have this total 8 by 8 thing, you would normally have to do 64 values, but because we're doing float 4, we're storing 4 of those times 16 total, right? So you can kind of do the math. It's like 4 values times 16 different writes. So it's going to do 4 values each write for 16 of them, and we're going to pull that full 64 thing across the TM and TN tile, right? So we set this temporary variable as the current C, the current C value, right? So this whatever the current C is that we care about relative to how we've indexed through these, right? And this is all keeping in mind to where we are actually at in the entire C matrix, right? So the thread row offset times this plus the res IDX M offset, and then all of that times N, which is the stride of that, and then plus our columns times TN, and then our res IDX on N. This should all make sense. This indexing should be like pretty much crystal clear. We've done very similar to this already. And a lot of the syntax is also similar to this float 4 we did here. So if something doesn't make sense, just look back at this and break things down again. That's the easiest way to do it. But in here, we have this temp type, right? And now temp, keep in mind, this is what C originally was. So we can actually store things from the existing TMP or the temp variable inside of it again. So we can actually do more to it and then write back inside of it, because we don't care about the old C result. We just want to calculate the new one, right? So we have this .x part, which is the index 0. So we're not going to add anything. And then index 1, and then 2, and then 3. And these are all x, y, z, w, respectively. So we have this alpha term, the thread results, which is with respect to the thread results variable in the register. So it's going to be the res index m. So which row are you at, right? And then and then tn, which is how that spans. So you're going to stride over and get to whichever row you want. Then you're going to offset by this, and then based on which index you're at within the float 4 array, within that specific the float 4 window, right, you're going to add these to the actual memory addresses or the index themselves, right, stored as like kind of a vector type. So this way we can actually get the value that we want, and then we simply just add that to the beta scaler and then multiply that by the existing C value as we got from up here, right? So that should be very straightforward. Luckily, this is only in register, so the indexing isn't too complicated. And then we simply just write back, right? So using the same idea that we did back here, the same indexing scheme, and we simply write out C on the level of threads. That's vector memory coalescing. Okay, awesome. So now we can actually just print out how well these do, right? So we just finished up the coalesced memory access with vectorization kernel. let's go ahead and print that out. How well does that do? So the last one was 2D block tiling, kernel number 5. We go ahead and print this out, and we get a peak of about 9,000. So about 9,100 gigaflops. And this one, about 10,800 gigaflops, which is quite a big increase from before. So that's about, what, roughly 1,600 more gigaflops than before, which is pretty solid, right? It's like a 15%, 16, whatever percent increase in performance. So now let's actually go ahead and print like some more, right? I know the auto tuning one was good, so we can go print 0.9. This one did about 11,000, so relative to this one, it did, moderately better. And then we can print out the last one, which was cuBLOS. So cuBLOS was supposed to be the fastest. We can actually see that this 11,496 is very close to the auto-tuned kernel, right? So if we actually look back to what we previously did, which was number 6, we are very close to cuBLOS. So 10,000, we'll just do 10,800 divided by 10,800 divided by 11,496. So we get about 94% cuBLOS performance just using the vectorized, like the float 4 loading, right? So that's ridiculously good. And we can still optimize further with these ones, right? So consider that if we were to optimize these further and maybe use some additional tricks that you'd find in like research papers, like this could actually get really, really fast, right? So that's it's pretty cool that we can do that just on our own hardware, and we can actually see it from start to finish and understand it intuitively. The reason I'm not going to go over any more is because it's just more and more complexity to dig through as you go through each one. And I want to save some time for the last final project in the course, which we're going to do shortly. But yeah, I'm not going to cover all of these. I just kind of cover the main ones. So coalesced memory access from global, just like a bump up from naive, and then all the different tiling variants, and then how we can vectorize memory access, right? So given that, let's actually go ahead and print out the assembly instructions for this specific kernel. So if I pop out of here and go into source/kernels, do nvcc ptx, and then we go number 6 out, and we can just go number 6.ptx. Okay, so instead of that, I just remembered that we had this main file here, which we can reference. So if I just go ahead and save this, if I like take the title of this and I replace that in here, and then we go ahead and compile, we're going to get our actual PTX instructions here. So it seems like we got some errors, which is because if I actually go in here, we have to copy this, copy it back. Oh, we're getting Vim. And so pretty much what happened there was I had it imported properly, but we just weren't including the TN at the end here. So I just added that. And now it successfully compiled. So we get kernel.ptx, we open this, and we can go ahead and see, let's see if we can find any, the 128s aren't in here. So I actually have to go in and change this to shader assembly. We can go ahead and do nvcc dash, we'll do arch is sm, arch equals sm underscore 86. And then we'll do q binary main.cu, and then out, and we'll do it main.CUDA binary. And then we'll go ahead and do object dump, and we'll do main.q binary just like that. And we go ahead and move this up, and we can see that if we look for the specific ldg.e instruction, ldg.e 128, 128, 128, 128, 128, 128, 128, and so on and so forth. So how cool is that? We can actually verify that all of these, maybe we can find like a 32 in here somewhere. Oh, that's just going to be in, that's a register. That's a register as well. That's a register. So we actually do not have any 32-bit loads, any 32-bit transfers at all. Everything is perfectly, everything is great. How wonderful. So now, now that kind of makes sense, that we are able to literally see what the instructions are looking like when we provide optimizations. You know, we actually feel a lot more confident in our ability. It's not just like me telling you that this works and trusting it. It's like you can actually see it. This is what is being, this is what's being run on the GPU's controllers, the little microcontrollers inside that issue the instructions, right? And so if we pop back to here, there's one little thing I wanted to cover as an extra optimization, which is using tensor cores. So we go to programming tensor cores. You literally just search, it's on the Nvidia blog, programming tensor cores in CUDA 9. So CUDA 9, I mean, we already actually have, if I go here, Nvidia SMI, we're on CUDA 12.5, so that's fine. We don't have to worry about incompatibility issues. But essentially, this gives the whole instruction set on how to use tensor cores, right? So CUDA 9 provides these new features. These tensor cores will essentially, like for example, on the Volta architecture, you can do this where it's like you multiply these two FP16 matrices and then you add another one, right? The fuse, multiply, and add operation we saw previously, except on the level of 4x4 tensors. And these are supported in the cuBLOS library. So two CUDA libraries that use tensor cores are cuBLOS and cuDNN, right? The ones we covered earlier. cuBLOS uses tensor cores to speed up GEM, matrix multiply operations, and cuDNN uses it to speed up convolutions and RNNs. So that's cool, but what if we want to write our own? What if we want to write our own code that isn't dependent on cuBLOS, right? Because cuBLOS, we could just call like a separate function, but it might not be as slow, or we can't like fuse the actual tensor core instructions with a specific kernel that we want to do. Like for example, flash attention, right? If we wanted to write that, cuBLOS might not let us do that because it's sort of independent. We can't include those calls inside of kernels. So if we wanted to actually look at how to use that, where did it go? Scroll down a little bit. Tensor cores and cuDNN, and then programmatic access to tensor cores. And that's where CUDA 9.0 comes in, so we're good. Essentially, there's this new thing called the complete namespace is NV, and then in C++, it's like the WMMA. This means warp, matrix, multiply, accumulate, which I'm not going to go over like exactly what that means, nor do I entirely know what's happening under the hood there, but that is the tensor core operations that we can call, right? So there's a bunch of examples here. I'm not going to go over this part, but this is just kind of like a nice little doc for understanding how the heck to use tensor core operations. And you might even want to implement those inside of the block tiling kernel, right? So the ones that we just wrote, you might want to say take like a single thread and have like a thread or a piece of it and try to like block these actual tensor core operations, right? And make these really, really fast. So that way it's not iterating through 8 and then iterating through 8 more and having 64 total operations to do, but rather just having one, right? So these are literally going to be organized in a 3D structure inside of the tensor cores on the GPU. And it's literally just like a 3D thing or a 2D thing, depending on how big dimensions you're using. Because you can do like batch by time by channel if you're using transformers, or you can do, yeah, just there is a lot going on in the hardware, but you can capitalize on those. So anyways, I'm not going to ramble on. This is tensor cores. You have permission to have fun with this. I encourage you to do so. I might add some more to this course later on in the GitHub repo that'll, sort of talk more about tensor cores, but this is it. Okay, so we can finally take a breather now. Matrix multiplication is pretty much finished. There's a little bit more that we'll do later on, but for now, you can consider matrix multiplication finished for the next section or two. Now we go into Triton, which essentially takes the previous chapter and says, let's abstract that and make it easier to use. So taking matrix multiplication, or like tiled optimizations, where you're tiling things into blocks and then multiplying them together more efficiently, we can actually take that and do it in Python with much simpler syntax. So this is Triton. Triton is a bit different than CUDA, all right? So before I actually go into the whole design here and what Triton is about, I want you to pay attention to something. So if I go pip install torch, you'll see that we get all this Nvidia stuff, which we've seen before, and then we get this Triton 3.0, right? And Triton is used by PyTorch under the hood for accelerating and making things faster with Python syntax, right? Triton is also fast, just like CUDA. And so there are some differences between them, which I thought I should highlight. So if we pop over to the Triton website, search up Triton docs or Triton website or whatever, this will come up. They also have a GitHub as well. So the GitHub has, a lot of, useful stuff. Yeah, just playing around with it, setting up, configuring Triton, doing custom things. But you can just pip install Triton like that and it'll work the same way. But if you do look at the Triton website, you'll see a bunch of sections. So like, how do you install it? Tutorials on how to use Triton. So there's like a bunch here, which I don't necessarily cover in this course, but you can go over more of these if you want to. And then there's the important ones that we care about. So Triton, what are like the Triton docs? There's like JIT, autotune, heuristics, all that. Just going through functions. And then we get into Triton language, which is the most important part of all. We have a bunch of different operations here with Triton, and I'll go into the whole design of Triton in a second here, but it just like makes it really easy to see that all of the operations are right here. So like the programming model operations to know, creation ops. So if you have an X tensor and you want to make a Y, but you don't want to populate it with anything, or you just want to make it zeros, you can say zeros like, right? That's a creation. Shape manipulation, linear algebra, so dot product, pointer ops, memory pointer ops, bunch of things, math. There's a lot of math ops, reduction ops, so like maximum, where you have an array and you're trying to find the maximum of it and you reduce it to just returning a single value. Scan and sort operations, atomics, like we went on previously, random number generation, and etc. Right? There's a lot here. Even debugging and printing too. So Triton, this is where all of the operations are that you're going to find, which makes this really easy to go through. But if we go through, where is it? Introduction. Yes. So the whole idea here, and if I go to Triton paper. Yes, this one. So I'll look at this in a second here, but this is essentially what Triton was inspired by, is this paper here for tiled neural net computations, like we went on in the previous chapter, right? And this is the whole idea here, is you have CUDA has a scalar program and block threads versus Triton, which has a block program and scalar threads. It's like, okay, well, what does this mean? This is super weird. There's a lot of like geometry happening here. So like, how do we actually break this down? Now, to clarify, the reason why CUDA is a scalar program with block threads is because you write a kernel to operate at the level of threads, or scalars in this case. So that's why it's a scalar program. Each individual kernel runs on a thread. But you need to be aware, you need to be implicitly aware that those kernels also operate on the level of groups too. So when you have, like, for example, shared memory, like that's something you need to worry about, right? CUDA has blocked threads, so scalar program, it's like the actual kernel that you write, and then blocked threads with the idea of when you actually write the kernel itself, which runs on a thread, it has to be aware of all the other threads too. That's kind of what I'm getting at there. And then Triton is abstracted up to thread blocks. So this essentially means compiler takes care of all these thread level operations for us. So when you write something in Triton, instead of having it run on each individual thread and have them communicate and be aware of that, it's going to write on the level of blocks, and all of those like thread level instructions and optimizations are going to be handled by the compiler for you. So you don't have to actually worry about those. And then when we talk about scalar threads, it means you don't have to be as worried about them talking interconnected with each other. You don't have to be aware, because CUDA actually handles that part. So since you're writing on the level of blocks, you don't actually have to worry about inter-thread communications. You just have to worry about what exactly the block is doing, write the operations out clearly for that, and then Triton will actually handle that under the hood. So you saw how there's very little operations in the Triton.language section. This is because the compiler is able to handle a lot of the additional operations that allow for performance increases, right? So that's the whole idea behind Triton, and that whole blocked versus scalar, blocked and scalar threads philosophy. So why can't we just skip CUDA and go straight to Triton? Why can't we do this? Well, Triton is an abstraction on top of CUDA. So you have lower level stuff that offers optimizations and that you can be explicit about to the Nvidia compiler, the NVCC, and Triton takes advantage of those and bumps it up a few layers to something that you can sort of understand easily and write less boilerplate code for. So we still need to understand how CUDA works to ensure that we're applying the right optimizations. You can't naively write Triton code without knowing what's going on a low level. It just helps you prevent boilerplate. You also may want to optimize your own kernels in CUDA, right? So going back to what I said before, you kind of need to know the low-level operations in order to make sure that everything is working as intended, right? And if you want to build on top of Triton, or build things like it, or abstract above CUDA, which is Triton, you need to learn CUDA. You need to understand what is CUDA doing so that you can build on top of it, so that you can leverage what it contains already, right? And so if we go to the Triton paper here, intermediate language and compiler for tiled neural net computations, it's essentially just it does everything that cuBLAS and cuDNN does, but does it roughly as fast and without a ton of boilerplate. So that's like the whole idea, is you have these tiled computations that you have to do in cuBLAS and cuDNN, and it takes care of those. So I'm not going to go through this. This is a separate course going through all of Triton, but we're going to go over like how do the basics work, right? So that you understand how Triton can be applied, and maybe it'll give you some ideas as to what to do later on. Okay, so now we actually go into an example of a vector addition kernel in Triton. All right, so I'm gonna try to break this down as kind of as efficiently as possible. This stuff isn't too hard. It's supposed to be kind of a break from doing things like matrix multiplication. So you'll probably find this ends up being a breeze. So we start off, we import Torch. So Triton is very closely linked with Torch. So we end up using that to handle some other stuff like initialize arrays and matrices and stuff. We import Triton. Triton language, and then shorthand version of that. And then we go down further. We initialize a seed so that the results are reproducible when you randomly initialize stuff, to ensure that we don't get errors or whatever. It's a good practice. And then we have a size of 2 to the 25. So if we go into here, we go, this is 33 million elements long, right? So if we go this, 33.5 million elements long. And then we just initialize our X and Y, the two that we're going to add on device that are randomly initialized. And then we just have some benchmarking stuff down here. Don't worry about this. This is just for testing and seeing how they perform, which we'll see in a second here. But going up, when we're actually adding them together, this is when you're actually adding them, you're going to add X and Y, which are tensors, and then you're going to return a tensor, right? So it's just X plus Y, return output. That's it. Very simple. This is essentially an easier way of doing CUDA malloc. So instead of CUDA malloc in C or CUDA C++, you're going to go torch.empty-like. So it's going to have the same shape as X, but it's going to be populated with zeros. We do an assert, so we make sure all of our tensors are on the device. We set num elements to literally just num elements of the output. So how many, what is like the length of this array? And then we have this weird configuration of like how we actually launch a kernel and how we define like the dim3 and the grid size and all of that stuff. So we have a lambda function here. Don't worry about this too much, by the way. This you care about performance, not like understanding how the syntax works under the hood. But this is just a lambda function, and inside of here, all you have to worry about is that we're doing a ceiling division of n elements. So let's say n elements is like 1024. You have an array, 1024 elements, and you want to add them together in blocks, and your block size is 256. So what you would do is you would partition that 1024 over 4 different blocks of size 256, right? But if you have, say, 1025 elements, then you want to make sure that you give it an extra block so that it doesn't miss that element, right? Or else you're not going to get the right answer. So you have to actually do a ceiling div so that it rounds up to 5 blocks instead of just rounding back down to 4, because then you'll end up missing that extra one, right? So that's all we're doing here. And then just to launch the kernel, I know it's weird. You do like this function, and then you index with this grid term, and then you pass in your variables after. It's like, that's weird. But don't worry about this too much. So we just pass in the grid as like that, those alligator symbols. That's all this is. That's your kernel launch configuration, and then you have the actual parameters themselves. So instead of going, we just go, we just do that. So it's like a syntactical thing, right? Anyways, that shouldn't be too much of a question. I'm not going over this because we care about performance as opposed to like what the heck all these what the heck this syntax is. But yeah, so going up to the actual mechanics of a kernel in Triton and comparing that sort of side by side with CUDA, we have X. We have to actually, I forgot to say, we add this Triton JIT decorator at the top to say that we want it to be JIT compiled by Triton. Just like be aware of that, because if you don't add this, you're going to get errors. But for all the different variables, you have your X and Y, your output, your num elements, and then the block size, which you pass into here, X, Y, output elements, and elements block size. Now we have these as pointers because in memory it's going to be laid out as the first element in that array is going to, or essentially this pointer is going to be the first element in that array. So you want to start from you want to base it off of the start of that entire tensor or array. And you want to continue from there, right? So that's how Triton is going to interpret that. And then you do the same for y, the output pointer, and then we just continue on. So jumping down a little bit, we see PID, and so PID essentially says which block are we at in the grid, right? Now we have to be careful about this. So a good way to think about which block we are in the grid is to actually go down to here and see how does this apply, right? So when we're actually in this array, let's say block size is 64 and we have 256 elements in this array. You don't want to just say 0 or 1 or 2 because those are going to be individual elements, right? When we're looking at the actual data, because remember, this is how we're actually indexing the data, we want to make sure that we're keeping this block length in mind because block size is big, right? So we're going to advance block size times the number of blocks. And then the offsets are actually what's important. So it's like whatever that number is. And then we're going to arrange an additional thing of 0 to block size. So for like, say, 64 to 128, you're going to start, the block start is going to be 64, and then we're going to arrange a bunch of different indices between 64, or it's essentially just going to be an array of 64 up to 128, right? And that's how we're gonna index our data. So we do Triton language.arrange 0 to block size, and that's what that is. And then we just add whatever block start is to that. So hopefully that kind of like makes sense in your head. Now jumping back to PID here, you might want to pay attention to this term. So in here we have access and builder. Don't worry about this. Just worry about access. So access is like block idx dot x, right? Block like x is the same as axis 0. Block idxy is the same as axis 1, and z is equal to 3, right? So we have to keep this in mind when we're writing more like 2D 3D spatial kernels. Then we have to keep in mind this access term. So luckily right now this is very simple, but this is something we're going to want to keep in mind if we do end up writing this is something you're going to want to keep in mind if you end up writing more 2D 3D stuff. Now going down a little bit, we have this mask term. So mask equals offsets. Mask equals whatever the Boolean, I guess the Boolean output of whatever of if offsets is less than num elements. So what this essentially does is we have these offsets, which are the indices in the actual arrays itself. So the input and the output point, the X and Y pointers, whichever indices we're at in those, we want to make sure that those do not surpass. We want to make sure those do not equal to or pass num elements, right? It's going to be 0 up to num elements 1 and -1. So we want to make sure that we mask everything off that is num elements or past that point, right? And that's what this is. So mask is just going to be essentially an array. It's going to do it's essentially going to say, we have all these offsets. We have this giant array in memory, and we're going to see if we have a 64, 65, 67, 122, whatever. We want to make sure that those numbers are less than a num elements, right? So we want to essentially just making sure that we're not accessing something that's outside of our data structure in memory. We have this whole space. We want to keep it masked to this one section, right? That's what this does. And so we get a new array, which is mask, and that's essentially just a bunch of ones and zeros. And this behaves the same way that this if statement does inside of a vector addition kernel in CUDA, right? Same idea. Now going down further, we actually load these efficiently into a shared memory. So don't worry about how Triton handles data, how it transfers data. That's an optimization that's taken care of for you. So just assume that these are going to load in starting from the beginning of X up to up to the end. So it's going to essentially just each point in memory, it's gonna each data point in memory, it's gonna load those in, and it's gonna do a mask. And it's gonna say, do we want to actually compute these values or not? That's what this is doing. So whichever point it starts at, all the way up to all the different offsets. So it's like this point, and then it's copied, and then all the different offsets. And then you have a mask applied to those as well to say which ones do we want to compute. So if these ones are like extra, just like compute this section. That's what this load is going to do, and it's going to efficiently load this into shared memory. So the fast memory on the GPU, the one on the actual streaming multiprocessor. That's what this is taking care of for you. And then we do the exact same thing for Y. Now, Triton implements these block-wise operations very efficiently. So you don't actually need to do any advanced stuff. You literally just have these loaded onto SRAM, and it'll do a element-wise addition. So it'll go through each one and just add together. And notice how this is blue instead of red. That means like it's taken care of by Triton for us. So that's literally how you compute the output. And then we just store this back again with another, with another data transfer operation in Triton. And so that's just going to be the same idea as here. So the starting place in memory plus, the offset of all the offset indices for that block. The output itself. So we're going to store the output, and then have this mask as we did here. And that's how a Triton kernel works. So hopefully this makes sense. Feel free to rewatch some parts that didn't entirely, click in your head. But now we're actually going to jump into the softmax Triton function. Okay, so now we jump into softmax. And instead of just jumping right into code, I'm going to do a manual hand example with this. So let me delete that real quick. Essentially what we're doing here, I have a C file. We're just doing this in C to understand what it's doing intuitively. We have an array of floats, 1 to 3. So it literally just looks like this. X is that. And so we're going to calculate the softmax of X. So how this typically goes is if we search this up on Google, softmax activation function, it looks like this, right? So you have this exponentiate, this input. So you have an input vector, and this symbol is the softmax function, and you go over each one, and then you essentially see how much each exponentiated value contributes to the total sum of all the exponentiated values, right? So if we open here, if I just open IPython, if we import math and go we go math.exp of 1.0, we're going to get 2.71 because that's what E is, right? It's going to be E to the 1. So our first value is going to be 2.71. And then the second one is going to be 2, so 7.39. And then the third one, number 3, is going to be 20.1 roughly. Now we sum these all together. So it's trying to autocomplete for me. 2.71 plus 7.39 plus 20.10, and we get 30.2, right? Now, in order to get the actual softmax output, we see how much each of these exponentiated values contributes to the exponentiated sum of all of them. Well, not the exponentiated sum, but when you exponentiate all of them, you take the sum of those, which is 32.2 or 30.2, and then you see how much each contributes. So 2.71 divided by 30.2. So that's about 9% roughly. So we're going to go 0.09. And then we go 7.39 is 0.24. And then the last one's going to be 0.67 if we go and do it. If you round up, it's 0.67. So you have that, right? And then if we add all these numbers together, 0.09 plus 0.24 plus 0.67, you get 1.0, right? And these are all rounded, of course. But the point here is this is the softmax. Notice how we had this initial distribution here, and then we went to a new one, which kind of just made everything add up to 1 and gave it a bit of extra weight to the 3, right? So notice how like 3 is 3 times that of 1.0. The 6.67 is way more than 3 times 0.09. So you can have that extra weighting for the bigger values, right? And that's what the softmax does. So it's going to like essentially find like the biggest number and put a lot of weight on it or highlight it the most. But there is a flaw with this approach, and I'm going to explain this right now. So essentially the flaw here is if you have, say, if you have X as, say, 1,000, 0, and negative 1,000, right? So some of these, the sum of these is 0, right? You have a problem with that, and that essentially means this is going to contribute a big chunk of this, or at least it's supposed to. It's supposed to contribute all of it, but it's not going to, because you cannot contribute, like it just doesn't make sense. How can you contribute like what percentage does 1,000 contribute to 0? It's like infinity, right? So if you end up doing softmax on this, like even if you try to math.exp of 1,000, you're going to get math out of overflow error, math range error, because it's just too big of a number, right? So what you can actually do is you can subtract by the max of all of these, right? So we can see what is the maximum, what is the maximum number here? So the biggest one is 1,000. And so what we can do is we can subtract each number by that value. So we can say X, we'll just say like X2 equals 0. And then 0 minus 1,000 is negative 1,000. And then 1,000 minus 1,000 is 2,000, right? And so if we go math.exp of 0, notice we get 1. Math.exp of negative 1,000 is going to give us, well, pretty close to 0. It's not quite going to be 0, but it's going to be it's going to be a very small number, right? And then, of course, the same thing with 2,000 is just going to be the same, right? It's going to be very small. And so you notice how if we just did this one normally, using these big numbers would have actually given us errors. So we can subtract by the max. We can pointwise subtract by the max number, and then we get something that makes more sense. So 0 contributes to all of it, because that's what the sum is. And so this is how we actually follow through in the softmax function in C. So we have 3 separate for loops here. The first one finds the max value in the array. So we just set the initial max value to be the first number, and then we iterate through this, starting at the next number. We don't want to start at this first one. We don't want to start at the first one, but we start at the one after it, because we already know what this one is. And we essentially just compare. If the new one is bigger than the max, we set the max to that one. And we end up with this max term, which, same as we did up here. And then we have the accumulation sum. So we iterate through the length of the array, and we do that index minus the maximum, and then we add that total to the sum, right? we add whatever this was to the sum so that we can, accumulate all of it. And then we just write out, the same value. We essentially just take the input and then replace it one by one. And we set it to whatever that exponentiated value is, minus, or sorry, not minus, but we have that exponentiated value. We divide that by the sum. Very simple. I probably could have explained that in a bit shorter time, but I just want you to gain the intuition for that. You've probably already written the softmax in PyTorch and NumPy. I get that. But just to kind of provide that review as to how it works under the hood and this, numerical stability add-on we have. So now I have an example in CUDA as well. So I'm not going to go over this, but the idea here is in CUDA, yes, you could go over, the length of one single array, but in deep learning, you're not actually trying to do that. You're typically going to have a batch size, and this batch size is going to have like a bunch of these. It's going to be a batch of arrays that you're going to softmax, right? And you're going to do the softmax on them row-wise. So you're going to do here, 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 right? Instead of just like to each element. So it's going to go through the rows. And this is where we can actually get a speedup from CUDA, because we can give each of the threads. We know we have batch size many threads, and we give each of them a softmax job, right? So we see in here how we actually give one to each. We give each thread a separate softmax job that's going to go. It's going to span 1024 iterations, or it goes up to the length of n, right? As we can see in these. So like theoretically, it's going to take 3n iterations because it has to go 3 different for loops. That's kind of how that works there. So we want to pay attention to batch sizes, right? But there's an example in CUDA here, which you can look over on your own and get an intuition for the batch softmax, but it's very similar to the one we did in C. Now we jump into the one in Triton. Okay, so now we actually go into the softmax Triton kernel itself. A little bit more advanced in vector addition, but we're going to go through it step by step. So we obviously import at the top. I'm going to go sort of from the bottom here, explain what's happening, and then what we're going as we're calculating the output. So we set our manual seed. We make a random, normally distributed random tensor of floats. So mean 0 and variance 1. So it's a normal distribution, and all of the essentially the shape is batch size by n. So b by n, batch size is 256, n is 1024 elements long. We're just going to softmax those 1024 element rows, and we're going to do this on CUDA. Now, we're going to calculate and make sure that torch and Triton output the same thing. So typically you would do torch.softmax or f.softmax or whatever, and then you would go dim equals 1, right? And then we want to do that same thing for Triton, and then make sure that the max value isn't too ridiculous. We're going to print that out, and then we're going to make sure that this is all close with torch all close, right? So we do the Triton softmax. We go here, and in here we have rows and columns. So when we print out, I'm just going to print out input shape. So we go here. Input shape is as we want, right? Output, we're just going to do a malloc essentially right there. And then instead of doing some weird like meta parameter, like doing like the whole like lambda function calculating, we're just going to do Triton and then next power of 2. So what this says is it returns the smallest power of 2 greater than or equal to n. So similar to what we were doing before, but just a little simpler. And then we're gonna set block size equal to the minimum of 1024 and this, right? So you can kind of see why we would do that. Now we set our grid to n rows because in our grid we want a block for each row, right? When we're processing in parallel, we can't split a single row amongst multiple, or at least naively, we can't split it across multiple threads. So we'd want to do it for each block. So each different row would get its own block essentially, and that's how we launch the grid here. And then you could assume that, you know, why we have this trailing is just that the trailing dimensions you can just assume are 1, right? And so that's how like PyTorch shapes work. If you do like batch size comma, it'll be like b by 1, and so it'll just be like a column vector sort of. You could think of it that way. And then the softmax kernel, we call this the same way as we did vector add, except we add 2 more things in. So we add in this x.stride. This is just an input parameter to what's going to be upstairs here. So we got x.stride, which is essentially the stride of the rows. So when we go across, it's like it's stacked in memory. It's like row 1, row 2, row 3, row 4, right? But the stride is like how far do you have to go to wrap around to a new one. So when we say we want to go to row 4, you actually have to go, okay, well, what is the stride, right? How long do you have to go across to get to the next one? It's like essentially the length. And that's, you know, we could say n columns, but we're just going to use the you know, objective attribute x.stride, pass in n columns, and then block size, right? So we go up and we see that we get the where did it go? Output x stride, n columns, and then block size. Output input stride, and columns, block size. Now we do the same. We do the same like program ID and the start pointers the same way. We calculate this normally. So which block are we at, right? And then we have to advance a number of indices forward in memory. So it's like we essentially take the initial input pointer. So where does it start at? Where does a starting place in memory? And then we add that to we take that and then we plus row IDX. So which row is it times the length of the row, right? So then we can get which row, where is the starting row within that batch, right? So which row do we want to go to? And then this whole thing is actually in the bigger picture, which is the whole memory, right? That's what we're doing there. And then same idea for the output start pointer. So we're essentially just finding the place in memory where we start based on these 3. And then we load in. So you know, we do the typical load. So pointer, and then we want to load in all of the indices. So similar to how we were doing it before. And then our mask is we're just going to make sure that this is smaller than n columns, right? Making sure that we don't go out of bounds. And then this important term other is a bit critical as well. So this other term means that if you have, for example, if you have 1,000 elements in a row and the block size is 1,024, so it's going to be a bit longer, then that means you're going to process some additional elements. It's going to think that there's 24 extra ones at the end. So what you can do, I mean, this is not going to happen in our case because we're very objective about how we define things. But in some cases, this will be important to pay attention to, where you actually want to explicitly set the edge so that it doesn't mess up everything else, right? If that was like 1, for example, then in our whole softmax calculation, that would contribute to it quite significantly because it's, you know, it's not just like massive sparse integers. It's like decimal places that are around 0, right? So it's important to do this when we exponentiate. When you do if we go into Python here, import math, we go we can just say x equals negative float and then inf, right? And then we go math.exp x, we notice that we get 0, right? Whereas if we did math.exp of 1, we would get this number. So we just want to make sure that that is not contributing anything at all. That's all we're doing there. So all the other additional values, if they happen, we don't want those to contribute at all. Just kind of a safety thing. It's good to look out for this. And then we just do the normal softmax calculation, which is actually only takes 4 lines. So we calculate the max across that row, and then we get the numerator, which is, remember, we subtract the max from that. We exponentiate this, so we exponentiate whatever that result is, and then we get the denominator, which is a sum across each individual one. So there's going to be some number, and then we're going to do essentially this array. It's going to be an array of elements, and we're going to divide this by a scalar value. So it's going to just like take this and it's going to divide, right? And that's how we get our softmax output. And then we'll see that we store this similar to how we actually loaded things in initially. So instead of the row starting pointer, it's the out row starting pointer. Same idea. We want to store a value, which is the softmax output, which is what we calculated here. So that's the actual value inside of it. And then our mask is same as we did up here. So we want to make sure that we're not doing reads and writes out of bounds, right? And that's pretty much the entire softmax calculation in Triton. So, I encourage you to, play around with this. You can actually go tl.device print, and then we can go like PID, and then just put like row IDX, or we could do row IDX like this. And we can actually print that out. So, maximum difference between Triton and PyTorch and Triton results is very small. Our results are close is true. And then we can see each individual one of these. So like PID is, 255. This is in the X dimension, right? So if you had this is axis. So if we do axis equals 0, same thing. We'd axis of 1, then, this would be on this spot instead of X, right? So yeah, we print out whatever that value is, and we get we can print stuff out in the terminal. If I do like normal, just like save. Now it might be a good idea to actually dig into PyTorch, or not even dig into it, but rather understand how you can add on top of it, make things a little bit faster for your own custom use cases and whatnot. So we just finished up the Triton chapter. I hope you enjoyed that. But now we're going to go a little bit more into Python and more on the Torch side. So I've written a few files here. I have some descriptions about what's going on with all these like different types and names and stuff in the README, as well as some intuitive examples of what we're going to be looking at. I wrote a setup script for just compiling a separate PyTorch extension, a separate function that we're going to use to do a polynomial. It's a very simple operation. And then a CUDA script that is going to compile and bind into PyTorch so that we can actually use it in Python, and then the Python script itself, which we benchmark against naive PyTorch. So just all we're really doing here is x squared plus x plus 1. That's all we're doing. So going here, we have this include, and this is giving us errors. But don't worry about this. When we set up, it's going to actually handle this properly. So we don't actually need a dedicated include file or any arguments for this. We don't need to specify where the extension .h file is. But going into the actual kernel itself, so just like top to bottom, we have this new thing called a template. I didn't go over this yet, but well, I did. I guess I did in the MATML section. But template is it essentially, if we go down, it'll help if we kind of go down and look at where this applies. So when we call this kernel, we do this and then we provide our arguments, right? we have the kernel configuration here, and then we have this is where the template comes in. So we specify this scalar underscore t type, and that essentially means we're just going to make sure that this the x, the y, or the input, the output are of this type. And so this type is essentially going to be handled by PyTorch, and instead of specifying like a float or a double, or like, I don't know, some other like maybe quantized like FP16 type, it's going to handle that for us, and it's going to just automatically recognize which one it is, and it's going to compile that down and deal with it appropriately. So this is something built into PyTorch, and it's custom type that we have. So this is kind of just like the default to use here, easiest. And then we have this restrict. So restrict, in short, essentially means we're not going to be overlapping memory. We're not going to be overlapping memory accesses. So we have X here, we have an output here. All we're doing is we're doing an operation on this thing, and then we're storing that in here. We're not mixing things over. We're not doing two things on like the same location and then having some output that's stored. We're not doing anything messy like that. So we can just say restrict, and that'll allow the compiler to aggressively optimize essentially what the binary code is. And so in here, we simply just do we do this over the X dimension, the typical CUDA kernel indexing, and then we do, the square, the plus, and then the +1. So that's the kernel is surprisingly simple. There's just some new colors and new keywords to pay attention for. But then we scroll down a bit, and then we got some C++ syntax going on. What the heck does this do? Well, we have this auto, which essentially figures out like which type to set this to. So it's going to recognize that this is going to be some torch type, and it's going to automatically select that. And this is just torch.empty like, so it's going to have the same shape as X, the input, which is a torch tensor type. So auto is going to recognize, it's going to essentially going to, it's going to do this. We'll just leave it as auto for now because it looks nicer. And then we have our threads, which is a typical 10,024 threads per block as per the maximum. And then we have our, num elements plus threads minus 1 divided by number of threads. So this is the typical, we already went over this. This should be very trivial stuff. And then we have essentially just some extra stuff about how the kernel is going to be called. So what things are we feeding into it? We return an output based on that. And then down here, we just have our Python bindings. So don't worry about this too much. Just kind of trust the process. I can kind of read off of like what I was able to find about this exactly. So pybind11 module, this is a macro that defines the entry point for the Python module. Torch extension name. It's a macro defined by PyTorch that expands the name of the extension. So usually defined from the setup.py file over here. And then we have an m and an m.def. So that adds a new function to the module. So the first argument, polynomial activation, is the name of the function in Python. So that's the function we're going to end up calling. We're going to be polynomial activation, open, close parenthesis. The polynomial activation CUDA pointer, or it is a pointer to the C++ function to be called. And then the last argument is a docstring for the function. So it's just like a simple docstring. It's not like entirely required, but we put it there anyways. So anyways, this is the full CUDA script. This is essentially as simple as it gets. You can't really do anything more simple than this. So this is kind of like a template you can work off of. And then in here, we import our compiled polynomial CUDA function, which we'll compile in a second here. We have a class, so we use torch autograd, and by default, when we do an autograd function, we have to include a forward and backward method. These are both going to be static, so we just add this decorator that says this is compiled elsewhere. And then forward, we're going to do just this polynomial activation. So it comes from the binary that we compiled, and then polynomial activation of x, right, as we said before. And then backward, we just don't support it yet, so we could just say not implemented error, backward pass not implemented. And then in here, where we actually do our in and dot module, that PyTorch should be familiar to, of course. This should be super easy to understand from a separate standpoint. But we just do the init, we do the forward. In here, we say, implementation is going to be we just set it to a string, PyTorch, so it's kind of easy to read. And then if the implementation is PyTorch, we do this raw, and if it's not, then we do this. No, if it's CUDA, then we do this other one, which we specified up here. So it's going to do this, and it's going to apply that to x. And then else, we just say, oh, if you did if you missed the t, it would be like, oh, PyTorch is not implemented, right, under an implementation. And then so we go down, and let's just go to the main function first, and then to the benchmark. So in here, random seed, normally distributed random tensor on device, implementation on PyTorch, implementation on CUDA. We move these to the device, so to CUDA. This is just essentially saying that this function is going to be executed on that. You should have probably seen this before. It's not too bad. And then we do, we can actually just print out whatever that input was. And then here we do, here we essentially just benchmark. So we go the actual activation function itself, the input we're doing it on, and then just a string that we're going to print in the name here. So here we just set a time. We go for a number of runs, and then we CUDA synchronize. So we ensure everything is all caught up, and then we end the time, and then we essentially return the name. So whichever of these it was. The delta time, so essentially the, not the delta time, but the difference. And then we divide that by the number of runs, because we're doing an average times 1,000, so that we can get it in milliseconds format. And that just kind of works as we expect it to. Now, to actually compile this, we go to the README, and literally all you have to do is just Python setup.py. Install, give that a second. It's going to use Ninja to build. So we'll give that a moment. But this is going to create, see, a build folder in here. And we'll print out forward and backward in a second. We're going to print both of these. So okay, awesome. It just wrote that out. So now we can go ahead and Python polynomial activation, and it'll do this CUDA activation dot forward of x, and then it'll print whatever that output was. And so we get like a tensor, and it actually formats this properly, which you're like, oh my gosh, we wrote this in CUDA and C, and now it prints so nicely like this. Yeah, that's what PyTorch does for you. And then we see that the PyTorch built-in gets about 10.47 milliseconds over 1,000 runs on average, and then the CUDA extension gets about 0.0243 milliseconds. So if we actually compare these, so if I go this divided by this, we will see the speed up that we get from CUDA. So we get about a 4.31x speed up, which is pretty good if you ask me, especially on bigger tensors, right? This would be awesome. So that's that. And if we actually do a dot backward here, you'll see that it's both, it changed to white. So that's a good sign that it doesn't work. And if we actually run this, it'll say has no attribute backward, right? So essentially raise the attribute error, doesn't work. And then we default back to forward. And it'll pop back to this NN.dot module. Awesome. Okay, so that's PyTorch extensions for you. You can feel free to add whatever you want to this. So if you have your own custom like research that you want to add and make it super easy for others and yourself and your organization to use, totally feel free to go down this route, copy this template code, do whatever you want with it. This is just the easiest example I found to both write and explain. So yeah, that is pretty much the first I don't even know. I'm not going to unify a percent, but that was the majority of the course. Now we actually have a final project to go into. So this final project is super exciting and is going to help you understand neural networks from scratch, how to optimize them for performance, as well as like data loaders. We're going to add a bunch of things, a bunch of optimizations into making a real world training run work. I am so excited for this part. In this last section of the course, we're going to be doing the final project. This final project is awesome. We're going to do an MNIST MLP training run from scratch. It's going to go in the following order. We're going to start in Python, PyTorch, super easy, right? Then we're going to go to NumPy, make it a little harder, but understand what's going on under the hood. And then we're going to go take our NumPy code and port that over to C, right? It's going to run on CPU. It's going to be super easy to read and comprehend and understand, right? And then we're going to push that over to CUDA, and then we're going to make it fast in CUDA. Awesome. So navigate over to this folder. We're going to do a different one. So it's not going to be /CUDA course. It's going to be /MNIST CUDA as like just a separate thing to help organize things better. Maybe you want to show this to a friend or whatever, or present as someone. And this way you can kind of just have things separated out and neatly organized, right? So you can consider this as like kind of a separate part. We're just kind of building on what we did previously. So if we copy this, we're going to go ahead and actually clone this into a new directory, and I'll kind of walk you through how things are going to go. So I'll go ahead and full screen this up. Sure, already saved. Now I'm going to cd into that. I'm going to go uv vnv just like that. I'm going to activate this. Just create like a Python virtual environment. That's all I really did there. And then we're going to go pip uv pip install -r requirements, and it's going to go ahead and install everything that we need. Okay, sweet. Now we're going to pop into the we're actually just going to open this up in VS Code. Go ahead and do that. Now if we pop into the let me full screen this. Perfect. Okay, so if we go into this Python folder, just to like help you navigate the structure of this, so what we're gonna do is we're gonna progress up from Python. So we're gonna go through PyTorch, as seen in here. So that pretty much just like an entire PyTorch training run for a multi-layer perceptron, and then a little Jupyter notebook that's like the same as that, but just in a notebook format instead. And then we have a NumPy script, so just going through and writing everything from scratch in NumPy. This may not look the same by the time you're watching this, but it'll be very similar and very easy to understand, at least for the Python stuff. So I mean, you've probably already written some PyTorch already, or at least you understand like the basic, NN.linear layer, right? You probably understand that already. So all we're actually doing in this one, and this is what I'm going to demo initially, is we're literally just training an MNIST MLP from scratch using basic PyTorch. So I import everything initially. So like time, NumPy, torch, right? The data loader, and the torch vision for the data set itself, which is MNIST. We specify hyperparameters here. So learning rate, batch size, number of epochs. I think there's like an extra one here. I don't know why that's there. Train size for like number of elements in the train set. And then we're going to go and adjust this data directory. Just print this out actually. Take that, inject it into here, and we'll go slash Python. All right. Now, sure, slash data, why not? Now, this is going to make sure that we're using TF32, so that's going to use tensor cores and make things really fast. This is going to initialize the data set properly with like, mean and standard deviation. This is just kind of the best practice for MNIST. So a lot of this here, I'm kind of just following some boilerplate code, template examples, that kind of thing. And now we go down further and it's, we initialize our data sets, we initialize our loaders, we load in all of the data, and we have this exist on the CPU. So notice how we're not doing device equals CUDA or dot CUDA yet. We're not doing that. This just exists on the CPU, right? System RAM. So we load all of our training data in, right? Load all of our test data in. We're just printing some stuff at each step here. Iters per epoch. So per epoch, we're going to do train size, which is 10,000, divided by batch size, which in this case is 4. So it's going to be about 2,500 iterations per epoch. And we're going to do 3 different epochs. So 7,500 steps total. Now we go down further and we have the actual architecture for this itself, right? So we take in an X, which is our input. We reshape this to batch size by 784. We do our first layer, second layer, third, right? So it's just like matmul 1, activation, matmul 2, and this is organized as such. In features, hidden features, hidden features, and then the output dimension or num classes. We have our in feature set to 784. So this way it's going to be like a batch size by batch size is the X, and then weight is going to be 784 by 256, right? So that's the shape of this. It's going to multiply by this linear layer. And then we have the ReLU, which is going to take that and it's going to do the ReLU activation on it. You can search that up if you don't know what that is already. It's very, very basic to understand. It's literally just a graph. NN.linear, same idea. We're going to take that previous batch size by hidden features. We're going to multiply that by hidden features by num classes, and we're going to end up with B by num classes, right? Or B by output dimension, whatever you want to say, right? And that's the whole idea, is we just want to keep forward and back propagating through that and making the network smarter. We're going to go ahead and transfer the model to CUDA. We're going to we can do torch.compile for a faster version, but we're not going to do that just because it like takes a little bit of extra time to do that. We're going to use cross entropy loss for the entire project here. Cross entropy loss is critical to understand. I'm going to go over some of this as well. Like, don't worry if this doesn't make sense yet. We're going to like literally write this in C. So don't worry if this doesn't entirely make sense. I'm just kind of giving you the rundown as to like what everything is based off of. We're going to use stochastic gradient descent. So that's just literally your optimizer. So it's going to just nudge the, when you calculate like a gradient or the error for a given weight, it's going to just literally do learning rate times that, and then subtract that result from the actual weight itself. So stochastic gradient descent sounds complicated, but it's not. It's not that bad. And then we just have our training loop here. And I'll go through sort of more intimately what this means in the NumPy script in a second here. But all that matters is that we kind of understand this boilerplate. This is designed to be like quite minimalistic, just kind of match what we're doing everywhere else. And yeah, I'm not going to highlight this too much, but we'll go ahead and run this just for fun, you know. CD into there. We'll do Python torch reference. And literally what this is going to do, it's just going to install our MNIST data. So notice how we got it in the Python data directory. Awesome. So now it's initializing everything. It's loading all the data. So we can see this. This is learning over 3 epochs, total of 2,500 each. And we end up with an average batch accuracy of 90%, which is really good. So when it's classifying those digits, it's getting about 9 out of 10 of those guesses correct, which is really good. And we can see that by the loss here, right? The loss is, if I move this up, the loss, we start from, you know, loading everything in. Start from a loss of about 2.38, which if we pop into Chrome here, go to Wolfram Alpha, just to like provide a reference. EXP of negative 2.38. That's about 0.92. If it's like, if we round down and say negative 2.3, it's about 0.1, which if you convert that to a percentage is about 10% accuracy, which is exactly what we want. Their images arranged or the labels are between 0 and 9. So 0, like literally there's 10 values there. So there should be at initialization a 10% chance of getting one correct because it's randomly initialized, right? And so that's exactly what we want. Everything is initialized properly there. Now, before I actually go into the NumPy implementation, like NumPy is like taking PyTorch and seeing like what the heck that's doing under the hood. Just like kind of a from scratch approach. I would recommend that you pause the video right now and watch Andrej Karpathy's microguide video. So he made this microguide video about 2 years ago. It's done really, really well. And it literally just explains the concept of backpropagation on the level of scalar values. So in this one, we're using backpropagation on the level of tensors, but understanding this is crucial for moving up to tensors. So after you're done this, and it's like still a little bit confusing about how we're going to bring this up to like bigger matrices, I would recommend that you also take a peek at my backpropagation video. This is just on my YouTube channel here, Elliot Codes. About right now, 5.7 thousand subscribers. You should be able to find me. And I just kind of made like a funny title because backpropagation is annoying to understand sometimes. And so I tried to do my best job to break down what the heck that means on the level of tensors on the whiteboard. This does have 1440p quality, so you can see stuff. But yeah, and then there's just like a ton of like content that you can watch, right? I don't encourage you to just like consume all the content out there, but these are the 3 that I thought were the easiest to like build an intuition on what backpropagation is. We're going to be going over backpropagation as well, but this is like where you want to start from if this is like a completely foreign concept to you. So Andrej Karpathy does really good. I go above Andrej Karpathy's lecture and go up to tensors, and then 3 Blue 1 Brown, which you've probably heard of already, does a quick little lecture on backpropagation intuitively. So let's go ahead and jump into NumPy. Okay, awesome. So now let's go ahead and take a look at what exactly this diagram is supposed to be. I could walk through and sort of just like explain what's going down, like essentially what is happening step by step in here. But first I want to make this obvious how our neural net architecture is structured and how the neurons actually work, right? What is a neuron? That type of thing. So I drew this little diagram to help us understand what's happening, and I'm going to lay this out here. So we essentially take an image. This is the handwritten digit. It's 28 by 28, and we're going to have this in a batch, right? So it's going to be 28 by 28, and then depth be our batch size, you could say. So it's just a bunch of panes essentially layered on top of each other. We flatten these, so 28 times 28, it's gonna have this whole image, and we're gonna take a row and we're just gonna add it to the end, until it stretches out to the full length. It's going to be 28 of these rows that are added to the edge, right? And then we plug this into the first weight. So x1 times w1, that's going to be b by 784. So b by 784, and then times 784 by 256. So a column, the size of a column in the weight matrix is 784, and then the length of a row in X is also the 784. So it's going to layer on top of those, right? And we're going to end up with b by 256. Then we go to the next one, and we get this. We essentially just feed this through the ReLU, so it's going to do the ReLU function on each value. Pretty simple. Then we do x2 times w2, and that's going to do b by 256, which was output from the ReLU. It's going to matrix multiply that with 256 by 10. 10 is our output size, right? So we have this b by hidden size, which is 256. That's each neuron output. That's essentially how many neurons we have is 256 in our hidden layer there. And then we just have to ensure that broadcasting is done correctly. So I mean, you could pop over to like PyTorch broadcast rules, broadcasting semantics here. So this is pretty much just how you're allowed to like multiply things and do operations with tensors when they're certain sizes, right? So, if you haven't gone through this already, it probably is a good idea. It's not too hard to learn. PyTorch handles this stuff pretty well, so it's just a little short read to do, just kind of understand like what's happening there. But essentially, you just want to make sure those inner values are the same, and then the outer ones are going to be your output shape, right? So we have this b by 256, and then the 256 here is going to it's going to dot product. It's going to take each column and dot product there, and you're going to end up with a total of 10 values for each batch element, right? And this is essentially this 10 here is a distribution of probabilities. So probability distribution in batches and in a batch, and those are going to be our predictions, the probability of which digit it is. So if the screen says like a 0, then what's going to happen after our network is really smart is if we go to say any batch element, so any essentially row, and we go to the 0th index in that, that's most likely going to be the highest number in the entire distribution, right? That's kind of what's going there. And then we just do a loss function on this called cross entropy loss, which I'll explain in a second. Cross entropy loss isn't too bad. It's different than MSE loss, but it's better for batches and kind of what we're doing here. So we get our loss, which initially is going to be around 2.3, based on the Wolfram alpha calculation you can do, right? Where you go exp like exponentiate negative x, so exponentiate negative 2.3, you get about 0.1 for that, which is 10% accuracy. And then you do the derivative of the loss, which is just going to essentially element-wise subtract the softmax probabilities by the true one-hot probabilities. And I'll explain those as well, what one-hot means. And then we just backpropagate, right? So this is kind of the forward pass here, where we go matmul1, activation, matmul2, calculate the loss, and then we backwards this way. So we do derivative of the loss, and then we do our chain rule backpropagation. So we calculate dw2, and that's just going to be, keep in mind, the gradient of the weight is supposed to match the shape of the weight itself. So notice how W2 here was 256 by 10. Here we do 256 by B, matmul that with B by 10. And so we end up with the outer dimensions, 256 by 10, and that matches up. Then we do dx2, which is needed for, continually backpropagating through the ReLU out layer. And so here it's literally just taking the dx2 and then doing an element-wise multiplication with the derivative of the ReLU function of x. So whatever the input was into that, and then we end up with the same shape that we got here. We simply plug this ReLU out into both of these. We don't actually need to do it for dx1, but it's just kind of here just in case you have like a deeper network and you want to modify things. But but DW1, it's going to be, so x1.t, right? So we're transposing x1. X1 is over here, so just flipping those dimensions. Instead of being b by 784, it's now going to be 784 by b. So you have each column is an image, right? Instead of each row being an image. We mapmul that with b by 256, which was the ReLU output. So that's like the last output gradient. And then we get our weight value, right? So, and then from here, we pretty much just modify the weights value. We get the same shape there. So that kind of checks out. And then dx1. I mean, we don't actually need dx1 here, but I include it just in case. Kind of the point there is, dx1 relies on w1. So we don't actually need to like update anything for this. It's just if there was like a dw0, if there was like a layer before that. Because notice how this ReLU layer relies on this, right? So if you had if we had a ReLU layer like before this, if we had a ReLU layer somewhere in here, then you would actually need to, like dx0 for example, and dw0, you'd actually need to use this. But since we're not, we can kind of just understand that it's something you would have if it was a deeper network, but you don't actually need it to make the network improve in performance, right? It's just like an extra calculation that's redundant. So you can just kind of exclude it unless you want to modify it. But I'm not going to ramble on about that for too long. Let's actually get to what the heck these neurons are doing, all right? So I got this little like editor open here. It's like my first time using it, but essentially how a neuron works is, we're going to like zoom in. How a neuron works is we're going to take a bunch of x values, all right? So x1, x2, x3, and these are going to go, see, these are going forward into a neuron, right? What's going to happen here is these are going to go, maybe I should draw these a little better. So this is our neuron here. We're just going to put a plus there, and you'll understand why in a second. This neuron is going to have a bunch of different weights, okay? This neuron is going to have one weight for each of these x values. So W1, W2, and W3. And all this is going to do is it's going to dot product these. So it's going to go W1, X1, plus W2, X2, plus W3, X3. And that's going to give us output, right? So this times this times this, and this times this, right? That's a single neuron. And what we're going to end up with is, when we sum these together, we're going to end up with a single value. We're going to end up with a single value one value here. Now, when we jump up to a bunch of neurons, so if we had, say, like x1, x2, and we have, say, 1, 2, 3 neurons, this one is going to have, each of these are going to have 2 neurons, right? So it's going to have 1, 2, 1, 2, and 1, 2. This looks very familiar to something you've seen before, which is the MLP that I previously showed you, right? The images. You've probably seen, like, you know, clickbait thumbnails with these before, and this is exactly what it is, right? So you're going to have 2 weights in here, 2 weights in here, and 2 weights in here. And so it's going to dot product with each of these. You're going to have this, which is going to be, you know, like a W1, x1 plus a w2 x2. And then the same for these as well, right? It's going to do all of these, and you're going to end up with 3 total values. So you're going to end up with 1, 2, 3 values in the output. Now, if we actually go to linear algebra and try to understand this concept, things are going to actually make a lot more sense, okay? So we go to linear algebra. Say we have something of size 1 by, say, 784, all right? And then we matmul this with something of size 784 by 256, okay? Ignore my handwriting, it's terrible. But this is going to be each x value, right? x1, and then x 784. And we're going to have 256 neurons, okay? So this is number 1, and this is 256, okay? Now, all we're going to do is literally take the, this is going to be like essentially it's going to have, this is the number of rows it has, right? This is the height of the matrix. So it's going to essentially just look like a vector. It's going to be this, and it's just going to be a line. And this one is going to be quite tall. So it's actually going to look like this. It's going to be 784 by 256, like that. Now this column right here is going to be a single neuron, right? This is going to be, say, 1 neuron. This is going to be a set of weights that's going to map. Each of those weight values is going to multiply with a single x value, right? So W1 is going to multiply with this one. W2 is going to multiply with x2 down here, and then all the way down to whatever n is, or sorry, down to 784, which is the length of it, or the length of the column, I guess, the height of the column, whatever you want to interpret that as. And this acts as a single neuron, right? As long as that's clear, we're good. Now we have a bunch of these neurons. As a matter of fact, we have 256 different neurons, right? I don't know how to write with my hand yet. I'm still getting used to it. But we have 256 different neurons, right? And they're each dot producting with the input itself. And we end up with a final output. So notice these, cancel out, and we end up with 1 by 256. So for one example, we're going to get 256 neuron outputs. Now, if you envision this as, say, batch by 784, so instead of one image flattened, it's a bunch of flattened images, right? Each flattened image is a row. Then essentially all you end up with is this B just replaces the 1. So you get rid of that. And you end up with this B here. And this is just a batch of neuron outputs, right? So it's like imagine thinking about this architecture here, where you have each X value plugging into like a different neuron. Just imagine this, but you like layer them on top of each other. So you have say you have this like as it's looking at you at the screen, and then you plop it down like this, then you put another one on top. Batch element 1, batch element 2, batch element 3, batch element 4, and each of these is going to give you something. So all these outputs is going to give you like, say, this is going to give you, what's it called? 256 different outputs. And you're going to have these in a batch size, right? So there are 256 outputs are all layered out here. And then each one stacked on top is just another set of 256, right? That's how I like to reason through this in my head. You might want to reason through it differently, but I find that to be a pretty cool trick to understanding how these are working. Now, there's another term that I did sort of leave out, and this is the bias, right? So the bias, each little one of these neurons is going to have its own bias, right? So, x1, xn, and now each of these little neurons is going to have its own bias. So we're going to do, a dot product operation as we normally would. We're going to do like x2 or x1 times x1 times w1 plus x2 times w2, all the way through all the different weights inside of a neuron. And then once we get that, we're going to add a bias to that. And the bias is just going to be a single number because of course it's a scalar value, right? So it's going to be, essentially it's going to look like this. W times x, we're going to do all of these that we need to, dot product, essentially a vector multiplication. And we're going to add a single bias value to that, right? So the vector x is going to look like this. And the vector w is going to look like this. It's going to be a column. So we take this column and we do essentially a matrix multiplication, but they're vectors. So it's like literally what it looks like is, and you just take this element and you multiply it with this one, right? So you kind of like put like a stick through it. You go, and it's like cut up into a bunch of little multiplications, and you sum them together, and you do your bias. And we can back propagate through that as well. So that hopefully that just clears up some of the intuition as to how we're actually structuring this part here. So that rule that I just showed you also applies for the x2 and w2, right? The point is, we're just trying to understand what the whole design of the neuron is and how we can abstract that up to linear algebra and then write really, really fast C and C++ and CUDA code to make this like run fast. Instead of just considering each little neuron operation independently, we can put a layer of abstraction up and say, we've proven that this is how this works in linear algebra. And now we can step forward and try to really optimize that based on our knowledge about matrix multiplication, right? This is one of the reasons why I emphasize the MATLAB so much, is because it's an extremely important algorithm in all of this deep learning stuff, right? But yeah, now we can, now let's look at how we can cross entropy loss and back propagating through all of this. All right, awesome. So now we next have to do the loss function. And the loss function isn't actually too bad. So if we pop over to here, notice how we have this cross entropy loss, right? This is our loss function. Once we get we do model.forward from our x batch and we get the y predicted and then a cache, right? Don't worry about the cache, just worry about this y pred and the batch y, right? So we go over to our cross entropy loss, and inside here, we're going to dissect this thing, by the way. Don't worry too much. Inside of this thing, we have batch size. So we essentially just take an element from the shape, do our probabilities from the softmax function, which we did go over before. We have this piece of work here, and then we just finish it up by calculating the loss, right? So assuming that we understand how our softmax function works, we can actually go ahead and dig into this. So I'm going to open up a Jupyter notebook here. So I'm going to go ahead and import NumPy. Then we're going to define the cross entropy loss function itself and softmax. So let's go ahead and take these and pop these into here. Then we're going to set our batch size as 2, and then we're going to set num classes to 5. All right. Then we're going to go ahead and make a shape. We're going to go ahead and make both of our inputs to cross entropy loss here, the y pred and the y true. All right. So y pred, we're going to set this equal to this NumPy rand batch size by num classes, right? So that's going to be our predictions. We have a bunch of we have a bunch of batch elements, each with a probability distribution about which output it thinks should be. Those are the predictions, right? And then we have a y true, which is going to be random integers. And I'm going to print these out so you can see. So ypred looks like this. We have batch size of 2, so 1, 2, and then we have a bunch of these elements, right? This is our probability. Actually, these are not our probability distribution yet. These are actually called logits. So I skipped a step there, but logits are the step before the softmax, right? Softmax is going to make sure that everything is above 0, right? It's going to make sure everything is like 0, between 0 and 1, right? That's the whole idea there. And it's going to express with confidence which numbers should be high, right? Because it's exponentiating. These are logits because it's like the log its, I guess you could say. It's like the log probabilities. So because you have to exponentiate up to get to softmax, it's like log because you go down. It's going to do ln, not actually log with base 2, or log base 10. It's going to be ln, so base 2, base e, or 2.71. And we can go ahead and print out our y true. So this is an array. It's very, yeah. You're going to see this. You're going to see why this is important in a second here. But if we actually pop to our next step, we can go probabilities equals softmax of ypred. So we're going to see these values get exponentiated. We can print out our probabilities. So we can see that as a part of this, which values were the biggest, right? So this one was the biggest, like, closer to positive infinity. And this is like negative, 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 right? So this is like the biggest, this is the second biggest, right? So we can see this is the biggest number, this is the second biggest, and this is like, these numbers are like smaller, right? And same for this one. We notice how, this 1.95 is really big, and then we have a 1.2, so it's like, this is the biggest, second biggest, right? That's kind of how that plays out. Then we're going to go and do correct log probs is going to be, or correct probs. We're going to do this part. We're going to do this part here. So probabilities, and then we're going to stick these two inside of it. All right. So when we do this, we notice that what this does is it gives us the indices of the correct probs inside of the prediction matrix, right? So inside of here, if we actually print out, np.arrange, right? And then we have our y true. We can essentially think of this 4 and 1 as our correct labels. So in this first batch element, the correct index, the correct answer is number 4, right? So it goes 0, 1, 2, 3, 4. This is supposed to be close to 1. If this is close to 1, we're doing a good job. That means the loss is going to be low, right? This is the correct answer. So if everything is like favoring this index here, if this was the correct, say, class to pick, that's what we want to optimize for. And then this 1 is picking out the same thing, but for the second element, right? So that's why we do, when we go up to y true here, we're doing, that's why we do this batch size here. So it's going to span the elements, the total number of elements in batch size. And it's going to just select the indices, right? So we kind of just do a random number here because it's between 0 and num classes. So, it goes from 0 to essentially 4. So 1, 2, 3, 4, 5, or 0, 1, 2, 3, 4. And so that's what's happening there. We just initialize things randomly. But we see that we did number 4. So it's going to pluck out number 4 of the first one. So 0.165. And then same thing for the second, right? We have index 1. So it's going to go to 0.227. Now, we have this correct probs, which I just explained here. And if we go down, or sorry, if we pop up a little bit further, we see that we just did this part, right? So now if I wrap np.log around that term, np.log, we'll just say correct log probs. We'll just do np.log of that. And then if we do correct log probs, we notice that we're just doing the log of each of these number, right? So if we go import math and then we go math.log of 0.165, we get this number, right? So negative 1.8. We're just doing this for each of these elements, right? And then we continue further and we go loss is the sum of sum of all of those. So the correct log prob is going to sum these all up together. So it's going to be like negative 1.8 and then negative, well, around 1.5. So they're going to add and we're going to get about negative 3.3, negative 3.47 or 3.27. And then we divide all of this by batch size to kind of, normalize across batch. We don't want it to get too massive. Like if you increase your batch size to like 1,000, then your loss is going to be insanely high and you're going to get numerical instability from that. You just don't want it. So you want to normalize over the amount of samples that you actually have in the batch, and that's going to help stabilize things for us later. During the training process, we don't want things to like step up and get worse every single training step. So if we go ahead and print out the loss, we notice how we get this 1.64, right? So going back up here, this was quite off. This was a little bit less off, but it's still fairly high. Like these are still like, this is like 16%, 17% chance, and this is 23% chance. And so that's not very good. So our loss is going to be higher. But if our correct probs array, our correct probs array was numpy.array, and we go say 0.9 and 0.8, and then we continue to go through this. So correct log probs equals, and then we do our loss, right? And we print out our loss again. Loss is going to be significantly lower because these values, the difference between our prediction accuracy and the actual label was very close, right? So we thought there was a 90% chance that this index was going to be it, right? And we were correct, right? So that's a very high confidence that we were correct, and that's a good thing. This is also quite high confidence that we were correct. So we want to reward ourselves for that or minimize the loss, right? So if we have values like 10% chance or 5% chance, our loss is going to be stupid high. But if we get closer and closer to what we sort of minimizing the difference between what the model thinks it is and what the actual thing is, that is a good thing. That's what we're trying to optimize for here. Now, there's another little step that comes along with this, and that's the derivative of the loss, right? So if you go over to Grok here and say, what is the derivative of cross entropy loss? So it's defined as this, which we just went over. So yi is the true label, either 0 or 1. And this is the predicted. So yi without a hat is the true label, and y hat I is the predicted probability. And we run through this. We do some differentiation. We go a few steps later. I'm not going to really cover the math behind this differentiation part. This part is, you can do that on your own if you really feel it's necessary. But really what we care about is just the answer. So the actual derivative, so putting it all together, look at the gradient. What we actually care about is y hat minus y. And notice y hat was the predicted probability. So that softmaxed the softmax logits, right? The probability distribution, and then just normal y is the true label. So if we go back to our code here, and we look at how that's calculated, we pop down and we see it is the softmax probability distribution minus the true labels, right? So that's exactly what we want it to be. And a lot of this, what we're doing here, this is mainly just converting things to the actual one hot vector. Yeah, that's pretty much how you do softmax and then derivative, or sorry, cross entropy loss and derivative of it, right? Now going back, what's next? So now we actually have to go through and calculate the gradient of our W2, our X2, even maybe possibly forward ones, and the bias, right? So let's go and look at that. I'm going to do an example where we pretty much do, we calculate DW1 and then we kind of just bring the intuition from that into everything else and then go ahead and apply it, right? So in DW1, I'm actually going to go to this in a second here. But I'll bring my whiteboard a little closer. So I don't know if you can see this, but I pretty much did, based on, the micrograd tutorial, I did like an output. This is a neuron output, right? So x1 times w1 plus x2 times w2, where it's like each of the x values go in, and then the neuron will like two x values go in, and there's a single neuron that has two weights in it, w1 and w2, and then it outputs those by doing a dot product between, so it does x1 times w1 and then plus that to x2 times w2. And I just wrote this in the context of micrograd. So there's a data and a grad attribute for this. There is a data and a grad attribute for this. So notice how I did this is a plus sign. I know you can't see it because it's very small, but I essentially did a plus sign. So those two added together, and the gradients are going to, this grad right here of 2, that's going to flow to both of these nodes, this x1 times w1 and x2 times w2. That's going to flow to these the same. So when you like, for example, when you're trying to differentiate a constant, it ends up just becoming 1, right? So there's actually no change. When you have like a graph, which you add like a bias to it and just shift that curve upwards, it still has the same slope, right? So that's essentially what's happening here. And then we continue forward, and this now becomes just a multiplication. So W2, x1 times W1, and then we have a data and a grad attribute for those. So that's just like kind of how a neuron is going to be structured in the context of micrograd. Now, if we pop over to this example, which is over here, so this DW1 output, what I pretty much did is we go 784 times by B. So let's just draw that out really quick. So $784 by B, and then we have B by 256, right? This is an @ symbol. It's really bad drawing. B by 256. All right. So how do we actually matrix multiply here? Well, we take a column of this and we dot product with a row of this, right? And notice how this is batches, right? So this is going to be a batch element. This is a batch element. This is a batch element. So we're essentially doing, we're taking the first pixel across the first batch element. So if we were to just go here, that would be an entire image, right? That would be the first batch element. It would be an entire image, but we're doing the first pixel across the entire batch, right? So across all the different batch elements, we're dot producting the pixel values. So like, for example, x dot data at index 0, right? And then in this context, this is B by 256, which is the same as the output layer. So if we did, like, for example, the classical input of, you go back to this, it's like B by 784 times 784 by 256, you end up with B by 256, and that's our output gradient, right? So we're essentially just taking this and we're shifting it around. So we're taking this B by 256, that stays the same, but we're transposing the input. So it's like x dot data transpose, matrix multiply that with the output gradient, and we're getting the gradient for the weights, right? The DW1 value. So if we go back to here, 256, remember, 784 is how many weights are in a single neuron, but 256 is the amount of neurons we actually have in that hidden layer. So 256 is going to be like these are all the neurons laid out, right? But what we're going to do is, instead of taking like a single set of all the neurons from a single batch element, we're going to take all of the index 0 gradients across essentially batch element, no, sorry, not batch element 0, across, we're going to take the first neurons across the entire batch. That's what we're doing. So this ends up being, we'll just say y.grad, y.grad at index 0. We're doing it across the entire batch, so it's just a single neuron, right? It's just a single neuron, but we're generalizing that across the entire batch. So when we have this X component generalizing across the whole batch and this Y component generalizing across the whole batch, we use the same intuition that we got from the micrograd lecture, and we just apply it here, except we get that generalization ability from using batch processing. That's where the big thing comes in here, because we're essentially doing columns here, dot product with rows, and notice the shapes are oriented in a certain way. Yeah, it is a lot to take in, but in the end, we end up with so this is like 784 by B and then B by 256, so the B's cancel out, and we're left with I know these shapes are out of proportion. 784 by 256, right? So this 784, that's the first pixel value. So each of these, or sorry, each of these elements, that's a pixel, right? That's a pixel in the whole flattened image. And these are all the neurons. So we end up calculating these in a way that we can actually update all of the weights properly, right? So when all these are laid out, you have the gradient for each neuron across the first pixel value, and that is the same way that our initial weight matrix is organized, right? So in our weight matrix, it's taking these columns of like a single neuron of weights and dot producting that with a single with a single image, right? And it's doing that, and that's very intuitive and it makes sense. But in this example, we end up getting the same ones that we would want to update those with. So you can kind of translate and see, like, what is this column here? What does that consist of? And what does this row here consist of? And we can plug that in, and we can see that our weight updates are actually going to make sense here. So in this one, we essentially end up with this thing of 256 values, and that is just going to be essentially the gradient of all of the neurons with respect to a single pixel, right? Because this is a single pixel across an entire batch. We're just using the batch generalization idea here. We're just like generalizing across the whole batch instead of using one specific sample. That way it's like better for stabilizing training. And we're taking that and we're just laying everything out for all of the neurons across a single pixel, right? That's how we're calculating these. So this it's gonna be like this row. This is our pixel across all the pixels for all the first pixel for all the batches, and then we have our our single, we have our first neuron, and it's going to go first neuron, boom, it's going to put the first value there, and then second neuron, boom, all the way to 256 neurons, and it's going to spit this out in a column, right? That's all of the neurons for the entire first pixel. And then if we look at how it goes down column-wise, then we get all the neurons for the second pixel and the third pixel and the fourth one, right? And so we can sort of see that this ties back again into the original forward pass example that we were doing. If this doesn't make sense, I know my explanations might be bad. You might want to go back and I mean, you could draw this out yourself. That does work, and just sort of visualizing it in your head. That's a good idea to do. That is a good idea to try to understand how this is working. Alternatively, you can watch my tensor level backprop video. I think I did a good job on that. It's about 30 minutes long. So, anyways, well, if this doesn't entirely make sense, we're going to use this intuition of we have this 784 by 256, and this is the same as just our W dot data, right? So our W dot grad and our W dot data have the same shape. So what we can essentially do is we can take say in the gradient, for example, we can take this value, multiply it by a learning rate of, say, LR equals 0.1, and we can then subtract this from the original one, right? So if the gradient is really high, that means there's a lot of error, and if the gradient is really low, that means that there's going to be less error, right? This is why it's called stochastic gradient descent, because you're descending the gradient. So it's going to be essentially W dot data equals LR times, just do X for times, learning rate times the grad element, right? And then we do minus equals, so that if the gradient value is really high and learning rate is 0.1, then it's going to be positive times negative. And then this is going to get adjusted in the negative direction if the gradient is really high. And if the gradient is really, if it's really negative, gradient's really negative, then this is going to multiply with this. It's going to give a negative value, and then since we're subtracting a negative, it's going to go up, and the way it's going to go up. So that's literally all we're doing in gradient descent. And we're doing that for each element. Now we can sort of take that intuition and branch it off to, DW2, right? And we can apply that to DX2. This isn't really a course on backprop, so don't worry too much if that doesn't completely make sense. It is important, but if it doesn't completely make sense, you're still going to be okay. Because we're going to implement this, and you're going to actually be able to see the network learning, and you can actually print out things to understand what's happening under the hood. And of course, we do need these X values for calculating these intermediate layers, right, with the activation functions. And the activation functions, like literally, if you want me to like draw out how that would work, ReLU, it goes like this, right? It's like a line, and then it goes up, just like that. So what you can do for this is you can say, if my value is 0 or less, I'm going to set the gradient to 0 because there's no slope. The slope is 0. And if it's greater than that, if it's greater than 0, then we're going to set that to 1, right? Because if it's really is going to make it remain the same if it's above 0. Okay, awesome. Now let's pop into sort of this Python script that we have running here and just dissect everything that's happening. So we can just tie it back to this image that I wrote in Excalidraw, just so that everything kind of makes sense on the code, on a conceptual and a code level. All right, so just kind of going through this NumPy script now. We import NumPy normally. I mean, I actually already went through this part. I'm not going to review this again. But if we go down, you can see a bunch of functions here, right? And these are all super useful functions that we're going to use to essentially train a single hidden layer, multi-layer perceptron from scratch, using the intuition we previously built on that from, micrograd, etc. Right? So we scroll down, and in this main function, we declare some variables here. So like hidden size, which I'll just set to like 256 in this case. Output size is 10, right? So 10 different digits, 0 through 9. Then our input size is 28 by 28 pixels flattened out. And then we're going to put our batch size. I'll just put 8 here so we can get speed. Learning rate of 0.001 or alternatively 1 times 10 to the negative 3. And then epochs, we're going to do 5. So epochs is how many times you go through the entire training set, right? So you go through it once. That's like a certain number of iterations, a certain number of like forward and backward passes. It's like one iteration, and then you do multiple epochs, which is, times that you go over the training data. So inside of here, we declare this model, neural network, right? Input, hidden, and output size. And then we just have this train function, which is going to actually do that for us. So inside of here, we have a number of epochs that we're going to do. And inside of each epoch, we're going to train in batches, right? So we have this batch size, a batch of images that are all flattened. So it's like B by 784. And we're just going to step through, kind of going through one by one here. So in the model.forward, we're in this one, we're just taking, the X train is just input images. And then this is the output labels, right? It's the batch Y. So in the model forward, we input a batch, and we get an output cache, and we get Y-pred, right? The Y predictions, the probability distribution in a batch, or in batches, right? After we do this model forward, we're going to take the loss function of Y-pred and batch Y, which we got from here. And then we're going to, so cross entropy loss calculates the loss, and then separately, we're going to take that output again, which keep in mind, this is logits, so not actual probability distribution. It's cross entropy loss is going to softmax those. And then it's going to return a loss, right? So it does softmax inside of here. So when we're actually getting the derivative of the cross entropy loss, we have to go and do that separately, right? We have to get our probability distribution, and then we have to essentially just, like I walked through before, how we actually do the cross entropy loss derivative. I walked through that with Grok previously, and this is literally all we do. So, feel free to like print this out, but this should be fairly intuitive if you worked with Python and PyTorch before. And then we just, do the minus for our grad output, and then we backpropagate from there, right? So we take our grad output and we use the cache. So keep in mind, when we do model.forward, we have YPred, which is the logits, and then we have the cache, which is literally just the inputs, right? So all the different pieces of the layer that we're going to need, like for example, our dx2, the derivative of the second x value, or for example, the ReLU output, right? So just stuff like this that we're going to need to back propagate through all the layers, and not just like a single weight here. We're going to need that whole cache of like through the forward pass, right? So that's all that is. It's just a tuple of those. And then of course the output, the logits, right? So just to clear up like what the heck cache means there, I know that can be like sometimes misleading. So we do model.backward, and then we just do model.update weights, and we pass in, weights, bias, weights, and bias again. So let's walk through what's happening in forward. This part, I assume, kind of just makes sense. We'll walk through model.backward and then update weights. So in forward, model.forward over here. So inside of here, we have the batch size as x.shape at position 0. So it's gonna list the shape. It's gonna be B by 784, or sorry, it's gonna be the batch that we get. So when we take this part, we're getting an actual batch. So I, and then to I plus batch size. So it gets a little segment of like eight images. On the side of here, we're going to take the first, the leading dimension of that, which is batch size, and we set batch size here. And then we do reshape. We go batch size by, and then essentially just the last one. So it's going to be reshape to batch size by, this is just a short way of doing 28 times 28. So 784, that's what this is going to reshape to. And then we go ahead and do our linear forwards. And these should be very sensical, right? So in our linear forwards, we take in a weight, we take in an X, a weight, and a bias, right? So we do X at W plus B, right? Instead of WX plus B, it's XW plus B. So it's B by 784. We go back to this. So we go in here, B by 784 times 784 by 256, and we end up with B by 256, right? Should be fairly intuitive. And then we add the bias as well, which is another term I actually did not include in this, but we can kind of just think of the bias as like an extra thing that it adds on. Now scroll down to ReLU, right? So ReLU, I mean, this is self-explanatory. It's just going to do a point ras ReLU. It's going to be numpy.maximum. It's going to apply that to every single value in there, doing a, if it's if the value is like -1, then 0 is going to be the maximum. It's like which one is higher, 0 or -1, then it's going to pick 0. And if it's like 1, then it's going to be like, oh, 1 is higher than 0, right? So it's just kind of the ReLU. And then ReLU derivative is, as we explained before, how you have like the chart, and then it goes like this, derivative of 0, then it's going to go gradient 1 after the 0, right? So that's what this is doing here, because we want a ReLU derivative, right? Now, going back, another linear forward, we take the ReLU output, so that's the new input to the next linear forward layer, the weights too, and then the bias too, right? So that should also make sense, and then we just return that. So forward pass isn't actually too complicated. We can sort of just walk through and understand how the shapes are changing. This is more a template example of how to understand this from scratch. Now we move down to backward, which is a little harder. Go to backward here. We have the W1, B1, W2, B2, right? So we put in the grad output. So wherever we start from in backpropagation and go backward through the layers, and then cache as well, which is the forward pass, like intermediate cache stored values, right? So we go into backward here, and we see we get in this grad output and the cache as we'd expect. And then we just lay out that tuple. So FC1 input. So we just FC1 input, FC1 output, ReLU output, right? So just kind of just unpacking this again. Now we go to here and it's linear backward. So if we step back to this, linear backward 1 is going to, it's going to calculate both of these, right? So linear backward is a bit bigger actually. We go here, taking a grad output. So like the output thing, the input, and then the weights, right? So we can calculate both the grad attribute for both the X and the W value, right? So in here we do grad weights is X transpose times the grad output. And so if we go to here, we can see X transpose and then times the grad output, which in this case, in the first layer is derivative of the loss. And then in this dx2, for example, we see the grad output times the transpose weight 2, right? So grad output times transpose weight 2. And then the bias, I'll break that down more so in the C section, but this is the grad bias, right? So I can actually just like print that out. Let's pop into here really quick and just exit that. So how did this go again? We do np.sum. So I'll just do np, we'll just do ipython import numpy as np. Then we go x equals we'll just do torch.randn. We'll do 3 by, we'll say 2 by 4, right? We print out, import torch, and go back up, print out x, and we get this, right? So if we do, we print out torch.sum of x, we do axis equals 0, and we go keep dims. I think it's keep, is it keep dims? How does it go? Keep dims equals true. We can see that literally all this does is it mushes these together. So it's going to go 2 plus 1, and then this is like 21 plus that, so it's 3.23, and then so essentially like mushing these, right? And it's going to do this across across like this, the horizontal, right? So it's going to mush cross or vertical, sorry, because that is the 0 axis, right? The leading dimension here. So that's this vertical part. So it's going to mush vertically. And so that's really all that is. So we're just combining things across the entire batch, right? But you'll see this more intuitively in the C version. Now we do the, this as I mentioned before, and we just essentially return those, right, for the linear backward layer. We return all of our gradients, and then we perform a optimization step. So we do the model.backward, and we do model.update weights, and we pass 1, 2, 3, 4, as well as the learning rate in. And inside of update weights, we'll see right here, we literally just do self.weights, self.bias, weights, and bias. And we do minus equals the learning rate times the gradient, right? So as I was talking about before, you're trying to reduce, you're trying to essentially do gradient descent. That's what this is, just the stochastic gradient descent, because it's doing it constantly every single time. And yeah, that's how we update the network. So, if the gradient gradient's really high, that means there's a lot of error, right? So if we do learning rate times something really high, so a positive times a positive, and then subtract that from here, that's going to mean it's contributing a lot, and then it's going to be it's initially contributing a lot of error, and we want to reduce that. We want to change it significantly, and then if it's like say lower, we don't want to adjust that as much, right? So it's kind of just going to balance between in the middle, whichever one gives us the most error, right? And we do the same idea for all of these, and we just do this essentially this scalar value multiplied by each thing in the entire weights and the bias matrix. We do that everywhere, and that's pretty much it. We do that for every single iteration. We get whatever inputs and output predictions we need. We do a forward pass. We do loss function, derivative of the loss, model.backward, so backward pass, update weights, and then if we need to, we just like print out the progress over time, right? So if we go ahead and run this, Python C friendly, we can go ahead and see this is actually training quite well. So this is training quite fast as well. NumPy is binded to C, which C is really fast, and we can see that over the first 7,500 iterations, we get 93% accuracy. So just to iterate a little more about this whole linear backward np.sum across axis 0, where you take each column and you squash it together. The reason why we do that is because each of those is like across the entire batch, right? So this would be like a single single layer, right? A bunch of biases for like all the neurons or whatever you want to say. And what we're doing here is we're taking a single neuron and we're squashing everything together. Because like imagine if you have a really big, like a really sparse, a really big reward signal for a single example, and then like you do 20 other ones and they have the complete opposite, right? The idea is to like kind of average all of them together. You're not like dividing, you're not adding them all together and then dividing, but you're just like accumulating all of them together, so you end up with something that's like close and pushes in the direction of like where generalization should be. So I know that sounds like really conceptually advanced, but it's not. You're just trying to push in whatever way the average favors. So that's why you do it across the actual batch itself. Because if you had just this vector laid out, I mean, you could do that, but training might not go as smoothly. Whereas if you were to just accumulate everything, so you get like on average, what is the best way to move? What is the best way to move that bias value? Then it helps a little bit more. So that's why we do that. But now let's get into C. This is pretty much a port of just the last script that we ran. So this v1.c, you'll find this in the naive CPU, because this is a naive algorithms. These aren't like really, really fast. These are just like the easiest way to write them. Very like intuitive to understand, but gives us a basis for how we can modify this and turn it to CUDA, right? So inside of here, we do the same idea. We have a little neural network thing at the top. I mean, I should probably go from like top to bottom, but yeah, so inside of here, learning rate, same learning rate. We have 10 epochs, which is a bit different. I changed batch size to 4 because having it as 8 or 16 or 32 just took a ridiculous amount of time to compute through each layer. So I set this a little lower to 4. Input size remains the same. It has to. Hidden size 256. Output size is 10. Train size 10,000. Test size, we're not going to really need this, but 1,000 for that. And then we have this neural network struct, right? So we can't actually do a class. We can't do a class in C, but we can do structs. We don't have like the class and object oriented aspect that we do in C++, right? This is a functional language, so we're only allowed to use structs. And inside of here, we just store a bunch of arrays. So all the weights and biases, and then the gradients for those, right? Just to kind of mark everything down easily and use this very simple struct, right? Now we have some functions for actually loading the data. Now I don't want you to worry too much about the loading data aspect. This part, it kind of just depends on like which use case you have. But in this case, I run the downloader script. So this downloader script just saves everything to a binary file. And then inside of C, we just write those back again. So, or sorry, we read them. We read from the binary. So notice how we do like file open and then the file name and then a read binary. And then it just turns that into a useful format, right? So yeah, it's not entirely too crazy. We essentially just like directly read this into bytes. And then we modify that as needed later on. We do the same thing for labels. So very simple data loading functions, not too crazy compared to the MNIST one, but this is in C, right? So it's obviously going to be a bit different. Now, we have this interesting thing here called initialize weight, which I probably should have shown you back here in our, where did it go? In our C-friendly script. So notice in here, how we have multiple functions, right? We have ReLU, ReLU derivative, initialize weights, initialize bias, and then these other ones, which I already went over. Initializing weights and biases are kind of simple, all right? They just follow a specific guide. So if we start off with initialize bias, it's literally just going to be just a bunch of zeros, right? That's all it's going to be. Just need the biases a bunch of zeros. That's okay. We can start and we can move up and down from there. But the weights, so bias is flowing from the previous layer. So having it as a 0 doesn't actually matter. It doesn't affect anything. The bias, the bias gradient are just flowing directly from the previous layer. Those unmodified, the same gradients. But the weights themselves are a little different. So how we initialize weights is, I'm actually going to go over to here. We're going to search up PyTorch chiming initialization. And this is how you actually initialize. I'll just do torch.nn.linear. We'll go to linear. So in PyTorch, we do this. Where is it? Yes. So the biases are initialized in this distribution, which we can do. We don't entirely have to worry about that. It's not a big deal. But then the weights themselves, these are initialized on this basis, right? So we have of shape output features by input features, and we make this from negative square root of k to positive square root of k, where k is 1 over the input features. So if we pop back to this, we're doing a random normal distribution, right? And with each of these numbers, we have to clump them to this range, right? So these values are in some normally distributed range, and all we have to do there is we initialize to this, right? So k in this case. Okay, so if we actually go to the Hay initialization paper, Hay init paper, I think this is it. Chiming Hay, so chiming and Hay are chiming init, Hay init are the same thing. But if we go into here, we go 2 divided by, no, maybe it's not there. Formula is somewhere in here. Where did it go? I search up ReLU. Initialization, maybe that's a better term to look for. Yes. This right here. So this leads to a zero mean Gaussian distribution whose standard deviation is square root of 2 over this term. And this term is the, I can't remember exactly what this is, but I think this is length. So we have an input size here, which you could say is the length. I don't know if that's specifically what L ties to, but we'll just hold that assumption for now. That's the idea there, is you would have standard deviation is this. And if we continue to go forward, maybe we might find something else here too. If we continue. Yeah, so some layers, another solution is to small factor on the weights, right? Anyways, yeah, this is pretty much the inspiration from it. So just looking at like kind of the purpose of this, this specific initialization as compared to the PyTorch one, which I probably should have looked into beforehand. The PyTorch one is a little different, but the Hay initialization is designed to work well with ReLU. So it uses square root of 2 divided by input size as a standard deviation for the distribution that it's generated on, right? It essentially counts out for the ReLU's activation to zero out negative values. So you might have these so-called dead neurons that come up when you have like the ReLU that just zeroes something out. And then when you try to like multiply that by something, it ends up just like zeroing it out. And you might like end up through the training process with like a row of zeros that just don't do anything and they're like useless. And so you're not actually compressing information down into those because they're just zero. So this helps deal with that. Now, jumping back to our C script, this is what we're doing here. So we essentially have this. We just have to use like what we're defaulted to with C. So we get this weights with the size that it's in. We make this scale, so square root function, you know, like we were doing before, square root of 2 divided by size in this case, which size would be, you know, size may not be appropriate. I just kind of found this to work, and training did exceptionally well with this, so we're going to stick with that. But the size, we're going to iterate through this, and essentially for each weight value, we're going to generate a value between rand. So rand is going to be anywhere between 0 and rand max. So 2, 1, whatever this is. So essentially this in here is going to be 0 between that max number. This is going to simplify to between a value between 0 and 1. Decimal, floating point 32 number between 0 and 1. We're going to multiply this by the scale, which is going to be that. and then we're going to subtract it by the scale divided by 2. And this is just going to give us a nice normal distribution for our weights, right? This is going to do essentially the same job as we were doing before. Bias, initialize all these to 0 as we were doing before. ReLU is also very simple. The softmax, I think I showed you the softmax in the Triton section. So this is, this should be fairly intuitive. We get this, we get this max value, right? And then when we're actually doing the exponentiation, we subtract the max value, so we still remain with numerical stability. Not having that would just like give these crazy, e to the whatever stupid crazy numbers when we have ridiculous arrays with like 1,000, negative 1,000, negative 10. It just gets out of hand, right? So we want max to normalize that and just get rid of any of those instability. And then we just compute the softmax, right? This isn't too bad. Same function we looked at before. We have a matmul. So I specifically worded these so that it would make the most sense. So it's a matmul, but this treats it as like you're taking in an array A and you matrix multiply that with B, right? So say for example, a 2x4 is A and a 4x3. And so you'd end up with a 2x3 and it would organize that in row measure order, right? Made these as simple as possible. You can dissect these, but we already did a ton of stuff on matmul, so I'm not going to go over this for the like 20th time. Then we have a times B transposed. So it's going to take in B as like, say it's like A is 2x4, and then B is a 3x4. And so it's going to do this operation as if it's transposing B to a 4x3. So you end up with a 2x3, right? And then same idea for this one. If you end up with a 4x2 and then a 4x2 as A, and then a 4x3 as B, it's going to transpose A and it's going to make it a 2x4, and they're going to match up. You're going to get 2 and 3, right? So that's just kind of the idea there. And then we do the ReLU forward. I probably wrote an additional, might have wrote. Yeah, so this is like designed to work in batches. I might have probably written an additional one just like accidentally, which I'll probably remove. Oh, ReLU there. Yeah, so I should probably remove this actually, but well, I'll worry about that later, and this will be updated by the time you're working on it. And then we just have the bias forwarded, which is going to, add the bias. So literally what this is doing is it's iterating through, it's going through batch size, right? And then we iterate through the actual size itself, which is the actual, like the row length. So it's going to go skip over as many number of batch elements as it needs to. So it's going to skip, it's going to stride over. Then it's going to add this I offset to it, and it's just going to plus equals bias at that value, right? So we essentially just have this row of biases, and it's going to just essentially add each of those. For like a given batch element, for like batch element 1, it's going to just add, say it's like 10 values here. It's going to add all 10 of the bias values, and it's going to go down. It's going to add those same values again. It's just applying the same bias to each row, right? That's what this is doing. Scrolling down further, I'm not going to go into these quite yet because there's like more happening, but scroll down to the actual train function and the, where is this? The int main function. So in here, we have a pseudo random number generator. These are pseudo random. They're not, you can't actually have completely random numbers. That's like a very hard, cryptographic problem and everything. That's something I'm not going to go into. In this case, we're using srand to generate random numbers, but in CUDA, you can use qrand. So it's going to generate random numbers in parallel really fast. So you don't have to like wait for the CPU to do this one and this one and this one, right? It's kind of faster. We initialize this neural network class with struct. Got to use the politically correct terms. We initialize the neural net. So we go here and we just have this NN and then the weight attribute, right? equals, and then we do malloc, it's just a regular C malloc. So weights 1 is going to be hidden size by input size, right? So that's the 256 by 784. And then the weights 2, which is output size by hidden size. So this is going to be, what's it called? 256 by 10. So it's going to take the B by 256 and then 256 by 10, and it's going to multiply those, and it's going to get a B by 10 output, right? For the after the weights. Bias 1 is hidden size. Just adding again to that output of all of those neurons, each bias value for each neuron. Bias 2, same idea. The grad weight, so just this, but it's just a different variable, right? So we're storing the gradients of those, the error, and they're just going to be the same shape, right? And then we initialize, so we have initialize weights and initialize bias. Now this is going back to the chiming init that we did, the hey initialization and the initialize bias that we did before. Now that we've initialized those with random values, we go into here. So our X train is going to be the train size. So train size in this case is 10,000. Let me go down a little bit more. Train size times input size. So an image is 784, flattened, and then we have the train size, which in this case is 10,000. The Y train is just going to be a bunch of integers that are that span this. So we don't actually need 784. There's only one integer value per sample, which is the label, and then we have the same for an F for the test set, right? We load these in using the previous loading scripts that I showed you before. We can print the first image in the terminal. So this is just gonna print things out using the X thing, right? So if I'm gonna compile this later and you'll kind of see what I mean, but it just kind of shows us like how good our actual predictions are gonna be. So we can actually like look at an image in the terminal and see, okay, what did it think this was? What was the actual label, right? So we can kind of like look and sort of match things up in our own head. I don't want to use like OpenCV or a custom extension to put a window because that's just a bunch of extra work. It's easier to do it in the terminal. And then just the training labels for those as well, right? And then we go through and we do the train function, which is comprehensive, and then we free everything up. We don't do CUDA free, this is just C, so we just do free, and it gets rid of the weights, biases, all the gradients for those, the train set and the test set, right? Now we go into train. Inside of here, there's a bunch of things happening, all right? So if I click this and see where the end is, we have this hidden right here. So that's going to be, the B by 256 as we looked at in the B by, where was it? Batch size by hidden size. So that's like going to be the actual hidden layer output, right? So here we get a B by 256. That's the hidden layer. That's the first, MATML output essentially. And then we get the output, which is batch size by output size, which in this case is B by 10. And then we do num batches. So the number of batches we're actually going to do is train size divided by batch size. And the reason we do this is because we don't want to just like offset each time. We don't want to give it the same data each sample. So if we take that total 60,000 and divide that by batch size, meaning like 4, train size is 10,000 and then batch size is 4, we're going to get 2,500 total batches, each with 4 images in them. So we're going to do 4 and then 4 and then 4 and then 4. This way we don't like overlap, right? Containing the same images in adjacent batches. We just kind of give it new data every time. And we do epochs over that, right? So we do all of the batches and then we do another epoch over that. So what's going to happen? It's going to do like up to 50% in the first epoch or some number like that, 50%. And then it's going to start the next epoch and it's going to learn from all the examples that it had previously. And it's going to be like, oh, we saw those again. We know exactly what to do there. So it's going to get, the accuracy is going to like, the loss is going to look like this. It's going to start figuring everything out, tuning whatever it can get its hands on, and it's going to drop because it figures out what to optimize. And then it's going to plateau through that epoch. It's going to sort of plateau out, and then the next epoch starts, and it's going to It's going to drop again because it's seen those again, and it can optimize for more. It can compress more features into that because it's seen that already. So it's going to continue dropping again, and then it's going to sort of plateau, and then it's going to drop again, and then we're just going to end up at some place whenever all the epochs are done, right? So we iterate through epochs. Now this is, if I look at this actually, this finishes here. So inside of a single epoch, this is where most of the work is done, right? We just do like free, hidden, and output. So most of the work is actually done in the epochs loop. Inside of here, we do total loss, which we initialize to 0. The number of correct answers, so we also set that to 0. This is just for tracking the accuracy, so we can see the loss dropping versus what the percent accuracy is over the training samples, right? So each training step, we can see every 1,000, every 1,000, or every 100 training steps, we can see what the accuracy is over the batches. Then inside of here, we iterate over num batches, increasing by this each time, right? Batch plus plus. And then we do start IDX. It's going to be batch times batch size. We do our forward, so we get essentially inside of here, we pass in our neural net. We pass in our neural net struct pointer, an input. So that's going to be train, and it's going to be the start IDX. So whichever this is, whichever actual batch it is, times the batch size. So it's going to skip in increments of batch size, right? So it's going to instead of skipping, like this isn't going to actually like plus equals like batch itself. This is going to add 1 each time. So this is just going to act as like an increment. So we're jumping, right? That's what that's doing, is it's going to jump 4 at a time instead of just 1, where it's just plus plus. And then we pass in the hidden layer, we pass in the output, and then the batch size as well, right? So all of the inputs, hidden, output size, right? And this is just going to do our forward pass all the way from, taking this flattened image, which we've done already, just because it's just laid out in binary. It just like exists as that. You can reformat it and interpret it as whatever you want, but in C, in memory, it's actually laid out as literally 1 through 0, 0 through 784 or whatever. So it's like not that hard to actually like mess around with. We do the forward pass. We calculate our cross entropy loss, right? Using the same cross entropy loss idea that we did in the C friendly script. So we're just porting that over to C, which if there's like if this doesn't like make sense, then you can actually go in and you can see, okay, well, what are we doing here versus here, right? You have tools like language models and the internet, which you can investigate these things through, and you can kind of see what's happening. But yeah, so we calculate our loss. We add that loss to the total loss. So inside of that actual epoch, we see, okay, well, what was the average loss, right? In here we do total loss divided by num batches. So we kind of average that out. We do that every single epoch. And then inside of here, we simply this just acts as a little incrementer for the correct counter. So this is just going to see, okay, well, were we close or not? So this should be self-explanatory. This is also just like not necessarily part of the training run, but just like an extra feature that you can use to print out what the accuracy was over time. Not the loss, but the actual percent accuracy. The backward function, so this takes in, NN, and it takes a pointer to the input, right? So this is a memory address to this at this index, which is going to be starting index times input size, right? And then inside of here, we pass in a few things, meaning hidden, this neural net is going to contain all of our weights and stuff. So this is like all contained within that. The input itself, hidden, output, labels, and batch size. So very similar structure to the forward pass, except we also include labels, right? Update weights. Everything is now updated after that. And then we can print out some useful stuff, okay? And that's pretty much all that happens in this training loop. A lot of it is just like printing and keeping track of stuff. But yeah, so going up, if we actually look at our, let me jump up to the forward pass. Where did this go? Okay, awesome. So inside the forward, it's very simple, right? 1, 2, 3, 4, 5, 6. Not too bad. Now inside of here, I added the extra softmax just because I didn't want to be redundant and included in the whole like training loop thing. There was a lot happening in there. It was quite complicated to sort through everything. But yeah, it's really helpful when you break things up into smaller chunks. This is super manageable. I wanted to make the forward and backward pass as modular as possible so that you guys could like really performance optimize it if you wanted to, like on the side. But this is like literally identical to what we did or almost identical to what we did in the C-friendly function or the C-friendly script, right? So in there we had this like linear forward method, which would do the matmul and the bias. And then the linear backward, which would do, 2 matmuls and a bias backward. But in this one, we kind of just split it into easier, more manageable chunks. So a matmul specifically is like an operation that you can optimize on its own. And so like optimizing a linear forward or even more generally linear backward, it's like kind of hard to do that, right? You have multiple things in there. You have to like fuse kernels together. It's more complicated. So I decided to keep this like as manageable as possible, super hackable, modular. But in the matmul, the AB, this is literally the same as C-friendly. So if I pop this over here, actually, maybe I'll bring it actually downward. But in here, linear forward, right? We just do X times W. This is X times W. We're X times W, A and B, same thing. We're not transposing anything. And inside of there, I already went over this function, but you kind of get the idea. We just do a matmul between A and B. That goes. We do a bias forward. So that's also going to, if we pop over to there. Yeah, I already reviewed that too. No need to go over that again. ReLU forward, it's just going to apply that to each element. Very simple. Matmul A and B, so same thing again, except it's the hidden. It's actually the hidden to output instead of the output to hidden. So next one, and then we do the bias forward again, and then softmax, right? So obviously, like this is very, very simple to follow. It's more of the complexity happens within the actual function. So like this is a lot more to handle than just the forward pass function calls itself, right? So I X out of that. And then go down to, say, the backward function, which is a little worse. I have to be honest. Go down to here, backward function. So inside of here, we're going to zero grad everything. So what this means is previously our gradients were accumulating items, right? So our grad bias and our grad weights are actually accumulating stuff. So we want to just zero those out, right? This is the equivalent of zero grad in PyTorch. When we go here, we do optimizer.step. So that's like the actual update weight. So you do the forward, and then you calculate the loss, and then you do backward, and then you update the weights with gradient descent, and then you zero grad. So you're just zeroing out every single gradient in the entire network. And then you're going to recalculate those when you do the next optimizer.step, right? Or sorry, no, loss.backward rather. When you calculate the gradients again, they're not going to accumulate further. They're just going to set them initially, and then you're going to update based on those gradients, and then put them down to zero again. So that's all we do here. We zero grad, and there's actually a function for this. So memset, literally just a C function, um, set n bytes of s to C. So set n, set, so bytes of s, which is the first one, so grad, and then C is the value we want to set it to, so 0, and then the n, the length of it, is just the size of grad, right? So size is the number of numbers, and then a float is like the number of bytes, essentially. So the number of bytes that grad occupies in memory, we're going to start from the beginning of that, and we're going to initialize all of those values at those sequential memory addresses. We're going to set those to 0. That's what zero grad does on a very low level. So we do that with our weights and our biases. Now we do a grad output. So this is just going to malloc batch size times output size. So B times 10, right? B by 10. The compute output gradients. So we go to this. Really all this is doing is it's taking this grad output, which we initialize, just everything is like 0. And we have this output, which is the, which remember from the forward pass is the output of the softmax, which is actually a probability distribution. It is not logits. It's not before the exponentiation. It is actually a probability distribution with each value between 0 and 1. Then we have the labels, and literally all we do here is we just element wise we set the grad output to the actual output value. So which floating point number is it, right? And then we subtract 1 based on the actual label of it. So notice how before in C friendly we did grad output equals softmax probs minus y true. We're doing the same thing here, except we can't just do a simple numpy element wise operations. We can't just be dumb and say this, right? We have to be explicit, and we can be a little clever by just doing the minus equals 1 there. So it's literally doing the same thing. We're just using a different trick. So we just continue going through. We just did compute output gradients. Now we can actually use those gradients and start using like matrix multiple highs and bias backwards and ReLU backwards and all this stuff, right? So the first one here is matmul. We go through, we calculate w2.grad. Now w2.grad is right here. So x2.t times the derivative of the loss, which is grad output. So here we do hidden, which is x2 here in this case. Or sorry. Yeah, x2. So the essentially the input going into that. And then times, so this is times b, right? So b is in this case is the grad output. So we're transposing this with this AT here, and then times this, and then that's going to equal C, or the grad weights 2, right? So grad weights number W2, right? Yeah, so that should be fairly intuitive. Now we go further, we go to bias backward. Bias backward isn't actually too bad. So bias backward is literally just we're going to iterate through the size. I mean, keep in mind we have batch size, right? So we're going to iterate through the entire size of it, iterating at incrementing I each time. We're going to store a bias value, a gradient, bias gradient at this index as 0. And we're going to iterate through the entire batch size. And we're literally just going to set that specific value. We're going to iterate, remember, we're iterating through the entire batch size. So like we were doing before, how we were like smushing the numbers, we're going to go through that. And we're going to just essentially do b times size. So the entire length of that, the entire length of like a row, and then plus I, and we're just going to set because this is going to increase each time, so we're essentially just going down one row at a time, right? And we're smushing it together because we're plus equal accumulating that value here. So our grad biases are this is the equivalent of np.sum across axis 0, keeping dims true, right? And then we go back to, where is it? we pop back to the backward function. Awesome. So now we get bias backward. We pass in the grad bias, right? So we're calculating the gradient bias, and we pass in the grad. So that would, in this case, would be the grad output, and then batch size and size, right? So that should be fairly intuitive. It's just the gradients are directly flowing, and we just do an accumulate operation across the batch because we want to generalize over a batch, right? It's more useful to do that. And then we just do, since we're done the W2, now we actually move on to the dx2, right? So dx2 is right here. We malloc this, because remember, this is just temporary. We don't actually need to store this. This doesn't need to be updated anywhere. We're just calculating this because it's a prerequisite for calculating W1. So we can free it after. We don't need to store this in memory. Just be like efficient. And inside of here, we literally just go grad output times W2 transpose, right? So we go grad output A times W2 transpose T, and we store that in dx2, right? Going down further, drelu out, which is this part here, drelu out is dx2 times drelu of x. We allocate memory for this. We go through the entire batch. We literally just do dx2. So dx2 times drelu of whatever that value is. Just going through it, right? And this is going to be if this is going to evaluate to a true, so, or essentially a 1 if this value is essentially just ReLU derivative, right? ReLU derivative. That's all this is. We might not actually even need the ReLU derivative backwards in this whole thing, but we're going to keep it anyways. This does work though. So this stores the DRELU out. That's what we want, right? DRELU out is good. Then we update using the what's it called? We calculate DRELU out from dx2, which we used up here, right? We stored that. We stored the gradient for that, the temporary gradient there. We don't need it for later. We just need it for now. Calculate DRELU out based on that. And then we use DRELU out later. And we essentially go to calculate W1, we go x1.t times DRELU out, right? So transpose, so AT underscore B, that's what this is going to be. AT underscore B, we go input, so input x1, transpose that, times DRELU out, and store that in weights 1. Awesome. Bias backward, as per usual. So we just have the bias itself, and then the one that it's flowing from, right? So whatever the previous layer gradient was, that's just going to flow directly into bias, right? Because adding does not change the gradient of something. It just changes the position, the offset of it, but the slope remains the same. But yeah, that's literally the backward pass. Not too bad. That might have been a little hard to keep up with. My DRELU outs constantly might have confused you. But yeah, that's pretty much it. And then inside of yeah, so that's backward. And then after this, we do update weights, then we print some stuff out. So let's just pay attention to update weights here. Don't worry about the rest of this. You can parse this on your own. What we really care about is the actual learning mechanics of it, right? You can print anything out any day you want. It's very easy. But we care about what the actual mechanism is here. So if I go to update weights, we pass in the neural net struct, right? The pointer to that. We go through each one in here, and we literally just do the same thing. So hidden size times input size, so that's going to be 784 by 256. That's the weight 1. We iterate through each index. Remember, this is laid out sequentially in memory. So this is going to evaluate to whatever 784 by 256 is. That's a large value. Just going to iterate through that in memory. It's going to go through the lines or this straight thing, and it's just going to do learning rate times whatever the grad was, and then it's going to minus equals accumulate that into weights 1. It's going to do the same thing for weights 2. Remember, weights 2 is output size times hidden size. So hidden size 256, output size is 10. Bias, hidden size, bias 2, output size. Very straightforward. And that's pretty much it. Let's go ahead and train this thing. So going back up, let me just make sure these are all set correctly. So we'll do 256, sure. We'll do batch size of 4, that's fine. Learning rate 0.001, that's okay as well. We'll set epochs to 5, just to be less redundant. Or we'll set it to, we'll actually set it to 30, why not? So now we go into here, gcc-o, v1, and then v1.c, which is the file we're going to compile, and we do lm for link math, right? So inside of here, we do the math.h file. We need to link math for this to work. Because if we don't, right, and unidentified reference to this, these are all the math functions, right? But if we do lm, it'll work. You can go ahead and run this. So we get the first, this is a 5 printed out. First trend training labels is 5, as we see here, and then 0, 4, 1, 9, 2, 1, 3, 1, 4. And we can see the accuracy starts off at about, well, the loss is about 2.3, which is random as we'd expect it to. So 2.3 evaluates to about 10% accuracy. And we can see that through the first epoch, it goes through 2,500 iters. And we can see that the accuracy goes up to about 60%, which is solid, right? Losses going down. And then in the next one, it sees, oh my gosh, wait, we've seen these samples before. And it's going to drop even further. It's going to go down to 0.88. And accuracy is going to fly up, 15% because it's already seen these samples before. And then it's going to do that again. It's going to go up to 86%. And we end up with about 88.6% here. Yeah, I mean, you could always print out the ending samples if you really wanted to. You could always print out like some extra samples and just like how it matches those up. But we're going to notice that in our CUDA file. So anyways, that was a lot to unpack there, but that is the C file. That's how we transfer from NumPy to C. It's not actually that crazy of a jump. It's mainly just writing the algorithm, the hard way, and just kind of being more aware about things, right? It's very easy to run into issues, but as long as we're careful about things, it shouldn't be too bad. Let's go ahead and jump into CUDA now. Okay, everyone. So this is one of the last parts of the course, actually, and this part is intended to be a little shorter. So this is designed to give you sort of a template for continuing on. This is the final project, right? So I'm not going to give you all the answers right away. A part of your job is to figure this out on your own and use what we've developed beforehand to continue and optimize performance further, right? So I have this naive GPU file right here, folder inside of CUDA. So we go to the CUDA directory, and then we cd into naive GPU. And inside of here, you're going to find this file, this v1, right? I just have this as like versions, so I'll like update more versions later on if something breaks in future CUDA releases or whatever. But yeah, so this is essentially just a direct port from our C file. So literally all we do here is we load in the same things. We initialize weights the same. All these are done on CPU, as you can see. The only things that we actually change are the matmul kernels, right? So we can see well, there's more than just matmul kernels, but you can see, so we have this matmul A and B. So this is not transposed, and then this is B transposed, and then this is A transposed, right? So when we're doing our backward pass and we need to transpose certain values, that's what we'll use that for, right? So we have certain kernels that are dedicated for that. And we can actually see based on the indexing scheme in here, like notice how we iterate over n every single time, except this one is a little different. This one is m, but if we go in here, we can see A, this is just the normal one, right? So row times n plus I, and then if we go to this one, B, it's I times K plus column, right? And this is different. So notice how this A stays the same, But because we're changing B and making it transpose, this indexing changes, right? And then same idea here is we just transpose A. So this part, I, K, and then column, I, K, and then column, and this part is going to be different, right? So instead of row n I, it's I n row. And yeah, those are pretty much the major changes. The reason why we do this for A is because A is transposed. And the M is a little different, but these are naive kernels. I expect you to be able to dissect these. But if we continue further, we have the ReLU, we have our bias, we have a softmax kernel. So this is going to do a single softmax output. So a distribution for every single batch element. So it's going to go vertically downwards. Each thread is going to do a row. We zero our gradients with this simple kernel. So it's just going to go, it's going to go through every single value and just set that to 0. Probably faster than memset. I'm not sure, but and then we have our DReLU kernel. So this is just the derivative of ReLU, multiply gradients. So element-wise multiplication of gradients, which we can see is used down here in multiply gradients. And this function is used right here. So when we're doing our ReLU, when we're doing our actual we're going through DReLU and we need to multiply those values. It kind of makes sense why we would put that there. Going back up, we just have our forward. So the typical A times B. I don't know why this is dot T. Okay. Vim is not working. All right. And we just do a matmul, add the bias, ReLU, matmul, add a bias, and then softmax, right? Very simple. Cross entropy loss is going to be done on the host. We're going to compute our output gradients on the GPU because there is actually going to be a lot of, you have to consider when you're actually writing kernels, you're like, what is how useful is it, right? To actually go and write your own, So like, for example, this one, we could probably turn this into CPU and it might be faster, but who knows? The idea here is like, if you have a big one, if you have a big update to do, like update to gradients, and you have these big giant, W matrices that you're trying to change and modify, then having a thread to do each little like point-wise update will help speed that up. But if you're doing just like a B by 10, for example, which is what this is, you could probably get away with just doing this really fast on CPU and you'd be fine. Because there is like kernel launch overhead when you have to like literally launch this. It has to tell the GPU what to do, and then it has to trigger a bunch of threads to go and execute that, right? And then in our backward pass, we zero out the gradients to make sure that they're not accumulating and giving us, mixed signals. We have our compute output gradient. So that's going to be essentially the output probabilities minus the true labels, right? And then we have our A transpose times B. So if we go back to here, this DW2, right? We update gradients for bias 2. So there's a specific kernel for that. Now remember, when we're launching these, it seems like there's a lot to sort through, but really all this is looking at that previous technique we did where it's like you have to launch, say if you have 1,025 elements and you would normally only do like 1,024 threads, right? So what you do is you add on an additional block, right, with a single thread inside of it, or another block in general, you could say. And since you have those bounds, those like that little if statement that checks if everything is where it's not like out of the matrices that you're working with, outside of that memory, then you can, that's essentially what this is, right? So we're just being careful about how we launch this stuff. And yeah, this goes back to the chapter number 5 on kernels, right? So these launch configurations can like really mess you up and make things look more complicated than they are. But if you can just like look through this one bit at a time, you have the like the grid size and the grid dim and the block dim, right? And that's all you're really working with. And then of course the arguments for the kernel launch itself. More matmls, right? Going back to here, this times, so it's A times B transpose, A times B transpose. And then inside here, we just go backward through our ReLU function. All of this is like very close to our C file. It's just run in parallel, right? Same idea here. I'm just gonna go further downwards, updating our weights. It's kind of, oh. I guess I have two of these. Are we using this? Let me see. Yes, we are. We're using that one, but this one, update gradients. Yeah, that's also, okay, so these are different things, right? Yeah, so the update gradients, that's for the bias, and the update weights, that is for, that is actually where gradient descent itself takes place. And then inside of this loop, we go through initializing our device training sets. So when you have this D prefix, remember that's for device. Y is labels, train is the train set. We CUDA malloc all of those. We mem copy them over to device because they're initialized as pointers on the host. And we have to copy those over with respect to their memory addresses over to device. And then inside of here, we just iterate over all the epochs we need to do, which in this case is defined at the top, and then number of batches, right? And then we set a starting index. We make sure to like stride a little bit. So we have whichever batch we're at here. So number of batches in the total thing, which we actually calculate by doing train size divide by batch size. So if you have 10,000 training examples and a batch size of 4, you're going to have 2,500 batches, right? And so when you do whichever batch you're at, which is going to go through, it's going to essentially going to go 0, 3, 0, 3, 7, 11. It's going to skip by 4, right? We do our forward pass. So keeping this simple, this nice little concise NN struct, right? With all of our gradients and our weights, right? We calculate the, essentially what this part is doing is we're calculating the loss. We're adding it to the total running loss of, where is it? On this level, we initialize the total loss inside of the epoch loop, right? So this is for the entire epoch. That's what we're kind of doing there, is when we add the loss, we're just like appending it, and then we're dividing it accordingly. So we're just taking like the average loss over the entire epoch. In this case, we are essentially just like we were doing in the C file. We're just adding to the correct counter. So however many samples we got correct, that's the % accuracy. Go into backward pass. I already walked through this. You can kind of sort through all these different arguments. We do an update weights for each of our individual weight matrices. So it's just going to essentially element-wise multiply the gradient times the learning rate, and it's going to accumulate that into the weight, right, on device. And then in here, we just print some useful stuff, right? Go down here, make sure that we free the training sets, the hidden, and the D output that we initialized before. And we have our initialization of the entire neural net. So just essentially doing our malloc, initializing those. So each of these are going to be set to like random values, or in this case, biases are going to be set to 0. And then we do our CUDA malloc. So we allocate on CPU. We initialize everything on CPU. We allocate on device. We move everything to device, and then we're ready to run, right? And then in this case, all we would do is initialize this neural net. We initialize it with random data values. Then we load in our entire training set into the host memory. We go and train everything, and when we're done, we can free whatever we need to on CPU and free whatever we need to on device. So if I go ahead and give this a run here, v1, I'm not going to run with CUDA. So variable I was used member reference. Don't worry about that, so warning. And then we go ahead and run this. We can see this trains insanely fast. We go from epoch 1. We have 3 epochs in here total, each one doing 2,500 iters. And we get a loss of about 2.3, which is as we'd expect. And then we see the accuracy increase up to 60%. And then it gets even, it jumps, right? It goes up to about 87%, and then jumps even higher. And we end up at around 90%, right? So that's pretty good. And we can actually run this with bigger hype parameters. So I can go ahead and plug in 10,024 there and use a bigger batch size, maybe 8, and then epochs is 5. We pop into here, compile that, we go and run it. You can see that we get a lot better accuracy, right? So even up to 92% now. So it's kind of what this part is it's called grokking. So you get the first part where it's like just starting on its training steps, and it's sort of figuring out which weights to push in the right direction, and then it figures that out, and then it plummets. The loss drops like really fast, which is what we're seeing right here. With the loss is like 2.3, and then it's 1.72, and then boom, 0.5, and then all the way down to like 2.9, 0.3-ish. And then what's happening here is it now can no longer use the easy patterns that it recognized, and now it has to search for more difficult attributes. There might be certain images that it has a really hard time recognizing, and it has to learn additional stuff, which takes more training steps to do. In that process of deeply understanding the data set or generalizing over it, that's called grokking, right? Hence the grok language model I was using before. But yeah, so if we step out of this and go over to this vroom file, I named it vroom because it's supposed to be fast, and it's the one that you're supposed to edit later. Go to vroom, and I was doing some comparisons here, but I'm going to remove those. Compare and compare. And we have this other comparing file, which was experimental, but I'll probably remove that soon. And then we go into this other one, v1.cu, inside of the vroom file. And this one is pretty close to what we had before. Now, the only thing we actually change here is instead of having, we actually make this easier for you. So in the past one, we kind of simplified it and had all of the, and did like the matmos a bit differently, where we transposed inside of the kernel. But in this example, we want to make it easier for you to just plug your own code into here and have it work. So using like the SGEM, the SGEM CUDA optimizations we did before in the faster matmul chapter, like that's what you would plug into here, right? Where you'd have your own kernel and you would launch it from here. And then inside of, if I go down, we can see a transpose kernel up there, but if we go into backward pass, there's nothing modified in the forward because there's no transposing there. But in the backward pass, we can see that there's just transpose matrix function, right? Transpose, 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 because we have to do this 3 times. We have to calculate this one, and this one. There's no dx1, right? We don't have to, that's redundant because we don't have a layer before it. So we do three of those, 3 transpose mammal operations. And so in here, this literally just switches it from column major to row major. That's all it does. It's just a cool little trick. There is a custom kernel for it that you can review if you want to. Where did it go? Right here. So there's this transpose matrix function that we call. We pass in these device inputs into it, and then inside of here, we actually do the transpose launch, and we make sure that no errors happen, and we synchronize all of the threads on the GPU, right? This is where the actual transposing happens, which isn't too conceptually bad, but don't worry about this too much. It's more so worrying about how do you speed this thing up. So I can go ahead and run this actually, and like all we change here is literally just the transpose. Oh, I had some CUDA stuff at the top. Let me remove that. Oh, CUDA. Oh, I'll just add that in temporarily. It'll just compile. I was messing around with CUDA. Like, this is a totally experimental file, so don't, like, I'm just kind of like screwing around with this one. But we could just do link CUDA like that, and go and run this, and we can see it's also pretty quick too. But yeah, so it trains the same on 250 on hidden size 256, which is what we have, or this is 1024 actually. So 1024. We give it a batch size of 8, only 3 epochs to learn though. It takes, it gets up to about 90% accuracy, which is still good. But yeah, on a reduced number of training samples, so we do batch size 8 instead of 4. So it gets more, like, it gets twice the amount of generalization because it has double the batch size, but the amount of training samples is cut in half, right? So it's actually like not that bad when you think about it. So we could like bump this epochs number up to 6. And you would see how much of a difference that actually makes. So we can see that it's kind of going up to 92, which is, this last phase here was grokking is what it was doing there. But yeah, so we got up to about 92%, close to 93 in some cases. But yeah, that's decent. That's, I know most humans are better than that, but for 10 seconds of training, I think that's pretty good. From having no knowledge about the world at all, this neural network did fine. Now, over time, I am going to add optimizations to this, but since you're watching this right now, this does not exist in the current repo. The version of this course you're watching right now, whether that be 5 years from when it was posted, whether that be 2 months, 1 day, this is the current version that you're seeing right now. And so this might be different by the time I've updated the GitHub repo in the future. I do plan to maintain this and add in, additional, like maybe a V2 with like, I'll make sure to name everything, of course, but just to go in and like add some extra features. For example, like I might add in like a really fast like custom row major kernel where we do like tensor core operations. So the warped matrix multiply accumulate, the WMMA with TF32 precision, that stuff is really fast. And then as well, another optimization you could take over is using CUDA streams. So remember in the concurrency chapter in chapter number 5, where we went more deeper into kernels and the whole CUDA architecture, you can use streams to make things run concurrently, right? So you could be loading in some data and then doing, say, like a forward. You could do like a forward and a backward pass, and then while that's happening, you could be loading in the next piece of data, right? So, I mean, obviously this is just like a digit classification, and you're not going to be super performance limited here. There's not a need for like having super high throughput, because you can get this thing up to like 99% accuracy if you make, deeper layers and you increase the hidden size and adjust all these things. It's pretty easy to get this thing to perform well, but this is the type of thing you want to practice so that when you write more complex kernels, it's not as difficult to start with, right? So, there are lots of optimizations you can do. You can add in this, where is it? In this matrix multiply kernel in here, you can switch this out with stuff. I'm not going to switch it out right now because that's something that you kind of want to do as a part of the final project, something you want to do self-guided and sort of go into it on your own. So, I mean, you can use this as is, but if you want to have some fun, this is just simple mammal kernel here. There's no transposing or anything. This is row major, and you can have fun with it. So that's that. Feel free to change this kernel, maybe experiment with tensor core operations, WMMA stuff, and then, you know, CUDA streams or something like that. Feel free to use the NCU profiler. And yeah, hopefully this gave you a better insight on how to kind of build up projects and how while they might look complex on the outside, you can sort of dig in and figure out what's going on. Now, just really quick to run all these again, just so everything is crystal clear that these are performing the same. We'll go ahead and edit each of them back to, you know, 256. So we'll do 256 there. Epochs, we'll do like 3. We'll do batch size 4. Learning rate is 1 times 10 to the negative 3. And then in here, we'll do 256 as well. Batch size, we'll lower that down to 4. Inside of our CPU, we will turn this up to 256. Batch size is 4, epochs 3, that's good. Then we pop into our Python here, set the torch reference script to, this is 256 already, 1 times 10 to the negative 3, batch size 4, we're looking good. And then we go to the C-friendly script. Oh, scrolled a little too far. 256, good, batch size 4, awesome. So now we'll go into Python. I'll run Python torch reference. Give this a second. The data loading takes a little while in Python. It's not the most optimized thing ever. So, awesome. So we end up with about 90% accuracy in the end. You know, 89. Here we have 87 in this case. So we end up with about 90 in the end. Let's memorize that number, 90. And then we go to Python C friendly. And we get 87%, 89%, about 90%. I had 5 epochs in there. Yeah, about 90% as well, 91%. And then we navigate over to the CD into naive CPU. We go GCC, compile with math. We'll go and run this. In the, this is gonna take a second. It's not used to going this fast. I know NumPy probably has more specialized mammal routines, so a lot of this is just, yeah, NumPy probably has more specialized routines here. So just doing it in raw C, like naively, is gonna take a while. But yeah, so we can see this. We end up at about, give it a second, pretty close to 90% as well. So 88.5, slightly worse, but that's almost negligible. Now, we have to, what am I doing? CD into CUDA / naive GPU. And then we'll do NVCC, compile without cuBLOS. Run that. Look how much faster that is, right? New total of 3 epochs, and we end up with, boom, 90%. Oh, how convenient is that, hey? And then we'll head out, and we'll go to the vroom file, vroom burr, and compile with cuBLOS. I just added the cuBLOS thing because you can add your own cuBLOS SGEM or like the LT matmul in and just play with that. We run this about the same speed, and we end up with about 90% as well. So everything's getting about 90%, which is good. It shows results are kind of consistent, just to like make sure that's all cleared up. Give yourself a pat on the back if you made it this far. It's pretty much the end of the course. You made it. Good job. I'm just going to go over some quick little tips, points in the right direction if you want to continue with this stuff. You know, it probably was hard to grasp everything, so I understand if you don't. But if you do, I have some extra resources for you. So inside of the README file here, I have a section on, you know, like what is unified memory and memory architectures, which I thought would be, you know, kind of useful and you might be interested in. But mainly what I want to cover right now is I'm going to add to this README file as well in the future. But there's a section on dive deeper. And this is like if you want to take that extra step and really figure out how you can apply deep optimizations and advancements and whatever you want to call it in CUDA and GPU programming, especially in deep learning. This is what you can do. So there's this thing called quantization, which I'm going to start with. Quantization is where you go from say FP32 and you go down to say FP16 or int8. You can actually go from FP32 to int8 and you can still have really good performance and quality of the precision on models, right? So there are specific ways you can do tricks around this, but a lot of it has to do with you know, if your range is limited. So if you can hit like a maximum of say like, I don't know, 10 and a minimum of -10, then you don't actually have to worry about a lot of those exponent values, right? If your weights are initialized and your training is stable and nothing's going to go like above or below 10, you don't have to worry about it. You could literally just cap that as your precision, right? And that'll be the maximum it can go. Those will be like the more sparse values, right? So quantization is pretty much just the art of doing that, which is like taking numbers that are really high precision and then moving them down to lower precision, doing really fast operations with those. Because I can tell you for a fact, int8 is a lot faster than FP32, like not just by 4 times, it's by quite a lot. And we saw that in the cuBLOS versus cuBLOS LT section, where we compared 32-bit versus 16-bit, and the performance was pretty substantial. So you can imagine what int8 would be, because it's just integers. There's no floating point, just numbers to worry about. There's no decimal places, right? It's just int8. So quantization is pretty cool. It's used a lot in current models like, you know, say GPT-4 or like Llama 405B, if you've heard of that one. Like a lot of these actually use quantization, right? So most likely like BF16 or like FP8 or something like that. Some of them even use float 4, which is cool. Then there's tensor cores, which I talked about already, but I can't leave it out. Tensor cores are great. I'm just not covering it in this because this is kind of like an intro. It's kind of an intro course. So I tried to like pack as much as possible into a certain amount of hours that you could, you know, digest. And then if you want to continue with that, there's obviously tensor cores too. Sparsity is a cool one. So sparsity is, you can think of sparsity as if I have like an array, say like it would be like 0 0 0 0 like -7 0 0 0 0 0, and then say over here we'd have like a 6, right? This is what sparse means. So there's a bunch of zeros and there's an occasional like very big number that represents a lot, right? Based on its position, maybe based on its position relative to other numbers. But the idea here is that you can actually store these in much smaller memory. So it's more of a memory and compute thing more than just like, why is this, like what quality do you get from this? It's really performance. So what we can actually do is we can say, you know, we're gonna have 2 matrices, one with the values and one with the coordinates. So we go -7 and 6, and then this other matrix would be, you know, 0 1 2 3 4. So this would be 4, and then 5 6 7 8 9 10 11 12 13 14 15 16, right? And so you would end up storing only 4 integers instead of instead of 16 integers, and you reduce everything by a lot. Now imagine this when you scale up to 2D or 3D structures. You're saving like orders of magnitude of memory, and it can be really, really efficient, right? So this is something to consider when you're designing highly performant neural networks. Is can we capitalize on things like sparsity, right? That might be encouraged by the the people who are writing the neural net outside. So when they're just writing like the PyTorch architecture, if it favors sparsity, if it does really well with that, and that's what it runs on, then this is really good for you. This makes your job easy. But sparsity is just a performance hack. You take it when you can, right? Then there's this book, CUDA by Example. So this it's literally just a book, Intro to General Purpose GPU Programming. I found this off of a Google search. So it's just like one of those edu websites. And yeah, it has a bunch of things in it. So like CPUs, rise of GPU computing, right? A lot of what I covered. It's like, what is the CUDA architecture? Pretty much a lot of what I said, or a lot of the important parts in here are compressed down into the course, right? So obviously not all of it is, and I haven't read this book either. 300 pages. So I haven't read this book, but a lot of what you're going to find in here is going to be compressed down into this course. Now, there's this other article by Simon, the guy who works at Anthropic, on data parallel distributed training of deep learning models. So that other chapter where we were talking about getting big algorithms to train across multiple instances, this is a good example of it. So distributed training is a big problem right now, is getting like data centers into one compact place. There is research around it and helping reduce that distributed aspect. But when you have a massive data center of a bunch of models, and you have to get them to talk to, or a bunch of GPUs, sorry, and you have to get the model to talk to each other a certain way, it's hard, right? So this kind of goes into that. I'm not going to go through this entire thing, but this does go through more performance optimizations, things like all reduce, which are used for the actual optimization process. So you'll see like an Atom W all reduce or something. There's a, yeah, there's a lot to consider here, but I don't even have a cluster to train this on, so I can't really teach this part. We go back. There's a few projects that I found that were really cool. One of them was MNIST CUDA, or CUDANN, sorry. I did MNIST CUDA, which was this. And then this is the actual CUDANN and cuBLAS for training on the MNIST dataset. This uses, I believe, convolutions. So if we were to go into, yeah, see, it's like a Visual Studio Code project or whatever. So this might be easier if you're on Windows, but like if you go into, for example, the network C++ file, yeah, I'm not going to dig through this, but this is a cool little project that I found. Feel free to do whatever you want with it, but it came up in the GitHub search results when I searched for MNIST CUDA. So do what you will with that. I'm not going to go CUDA mode right now. I'm going to save the best for last. Micrograd CUDA is very similar to Micrograd by Karpathy. So this is something I touched on earlier, and this is something you should review heavily for understanding how things like backpropagation work. So it's pretty much like a PyTorch autograd, but very, very small. So if we actually go into the files for it, go into the Micrograd files itself, there's an engine for it. So the values, there's like a value thing for it. So with operations you can do, like a power. So when you go double asterisk, it's going to call this __ power as a method, right? And then the add is this same thing. You have the plus, and that's going to call the add method. And then outside of engine, you have the actual neural net.py, which is brings up all the abstraction of going from neurons to layers. So you have a single neuron with a set of weights in it that take in, all the different X values, and then dot product, and then output one. That's a neuron, right? So, it does a dot product there. We can see that very clearly. And then there's, a layer where it does a bunch of neurons. and then it'll it's just like a layer of neurons, just like that, right? A bunch of neurons stacked on top of each other. And then the MLP, which is like that layer, but there's multiple of those. And then microgrid CUDA is just that, but implemented in CUDA, right? There had to be one. So yeah, feel free to like have fun with this and everything. It's supposed to be faster, so you can kind of just understand things on a level of compute unified device architecture. There's like operations, all the CUDA operations. So move to GPU is like malloc and memcopy. It's a very simple interface. You can imagine PyTorch being similar to this. Probably more performance optimal, but you don't want to do like a CUDA memcopy and a malloc every time you want to move something or use a piece of data. You have the naive matmul kernel, of course, the tanh kernel, right? All of this. But yeah, so a bunch of cool projects people are doing. And then there's this other interesting one I found, second best one, GPU puzzles. So you can use the QPy library. So if we go QPy Python. So QPy, open source, GPU accelerated computing with Python. So it's essentially CUDA, but you get to use it through a Python interface, which is awesome. We go to the GitHub for this, QPy, right? There's a bunch of cool stuff on this. You would just import it, and then you can make like shapes and stuff and do stuff with that. Similar to something like PyTorch or NumPy, right? But yeah, so these GPU puzzles are just like going through, solving like essentially the logic problems where we had a kernel solve an issue for us, but doing that for a bunch of different examples, right? So instead of just matrix multiplication, there's like a lot of other things in here, which you might find fun to practice. And then the last one, which I decided to save for last, is CUDA mode. So they have a GitHub, they have a YouTube channel, they have a Discord server, and pretty much a bunch of this like actually contains a lot of material and beyond what I covered in my course. This one was more to be like video assistive, but the community behind CUDA mode is amazing. They have really, really good engineers and researchers here. Just like building cool stuff constantly, people being super active in the community. It's a great place. So this is something I'd absolutely recommend you check out. Yeah, there's a lot of chapters, like see like flash attention, right? They have everything: Cutlass, Triton, fused kernels, data processing, tensor cores, right? So a bunch of cool things. I'd recommend that you join their Discord server. You can find that. Where's their Discord server? Here. Yeah, bunch of cool groups and everything. It's like beginner section, right? Super active. Like today, the last message was like not even like a few hours ago, and that's just one channel, right? So if you go down here, the last message was like 1 hour ago. So if you enjoyed this course, you can totally find me on other platforms. You can find me on YouTube. You can find me on X/Twitter. You can find me on Discord. I have a Discord server full of a lot of people. There's CUDA mode as well, but I also have a server with a bunch of people, and we, like to learn stuff and collaborate and all that. Yeah, find me on YouTube, find me on LinkedIn, find me on X, find me on Discord. Those are all going to be either links in the description, or if they're not in the description, they'll be in the GitHub repo in the description below. Thank you for watching.